Part 5 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 5. Compass Systems. The Earth is a huge magnet, spinning in space, surrounded by a magnetic field made up of invisible lines of flux. These lines leave the surface at the magnetic North Pole and re-enter at the magnetic South Pole. Lines of magnetic flux have two important characteristics. Any magnet that is free to rotate will align with them, and an electrical current is induced into any conductor that cuts across them. Most direction indicators installed in aircraft make use of one of these two characteristics. Magnetic compass. One of the oldest and simplest instruments for indicating direction is the magnetic compass. It is also one of the basic instruments required by Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, for both VFR and IFR flight. A magnet is a piece of material, usually a metal containing iron, which attracts and holds lines of magnetic flux. Regardless of size, every magnet has two poles, north and south. When one magnet is placed in the field of another, the unlike poles attract each other, and like poles repel. An aircraft magnetic compass, such as the one in Figure 7-31, has two small magnets attached to a metal float sealed inside a bowl of clear compass fluid similar to kerosene. A graduated scale, called a card, is wrapped around the float and viewed through a glass window with a lubber line across it. The card is marked with letters representing the cardinal directions, north, east, south, and west, and a number for each 30 degrees between these letters. The final 0 is omitted from these directions. For example, 3 equals 30 degrees, 6 equals 60 degrees, and 33 equals 330 degrees. There are long and short graduation marks between the letters and numbers, each long mark representing 10 degrees and each short mark representing 5 degrees. The float and card assembly has a hardened steel pivot in its center that rides inside a special, spring-loaded, hard glass jewel cup. The buoyancy of the float takes most of the weight off the pivot, and the fluid damps the oscillation of the float and card. This jewel and pivot type mounting allows the float freedom to rotate and tilt up to approximately 18 degrees angle of bank. At steeper bank angles, the compass indications are erratic and unpredictable. The compass housing is entirely full of compass fluid. To prevent damage or leakage when the fluid expands and contracts with temperature changes, the rear of the compass case is sealed with a flexible diaphragm, or with a metal bellows in some compasses. The magnets align with the Earth's magnetic field, and the pilot reads the direction on the scale opposite the lubber line. Note that in Figure 7-31, the pilot sees the compass card from its backside. When the pilot is flying north, as the compass shows, east is to the pilot's right. On the card, 33, which represents 330 degrees, west of north, is to the right of north. The reason for this apparent backward graduation is that the card remains stationary, and the compass housing and the pilot turn around it, always viewing the card from its backside. A compensator assembly mounted on the top or bottom of the compass allows an aviation maintenance technician, AMT, to create a magnetic field inside the compass housing that cancels the influence of local outside magnetic fields. This is done to correct for deviation error. The compensator assembly has two shafts, whose ends have screwdriver slots accessible from the front of the compass. Each shaft rotates one or two small compensating magnets. The end of one shaft is marked E-W, and its magnets affect the compass when the aircraft is pointed east or west. The other shaft is marked N-S, and its magnets affect the compass when the aircraft is pointed north or south. Magnetic compass-induced errors. The magnetic compass is the simplest instrument in the panel, but it is subject to a number of errors that must be considered. Variation. The Earth rotates about its geographic axis. Maps and charts are drawn using meridians of longitude that pass through the geographic poles. Directions measured from the geographic poles are called true directions. The magnetic North Pole, to which the magnetic compass points, is not co-located with the geographic North Pole, but is some 1,300 miles away. Directions measured from the magnetic poles are called magnetic directions. In aerial navigation, the difference between true and magnetic directions is called variation. This same angular difference in surveying and land navigation is called declination. Figure 7-32 shows the isogonic lines that identify the number of degrees of variation in their area. The line that passes near Chicago is called the agonic line. Anywhere along this line, the two poles are aligned, and there is no variation. East of this line, the magnetic North Pole is to the west of the geographic North Pole, and a correction must be applied to a compass indication to get a true direction. Flying in the Washington, D.C. area, for example, the variation is 10 degrees west. If a pilot wants to fly a true course of south, 180 degrees, the variation must be added to this, resulting in a magnetic course of 190 degrees to fly. Flying in the Los Angeles, California area, the variation is 14 degrees east. To fly a true course of 180 degrees there, the pilot would have to subtract the variation and fly a magnetic course of 166 degrees. The variation error does not change with the heading of the aircraft. It is the same anywhere along the isogonic line. Deviation. The magnets in a compass align with any magnetic field. Local magnetic fields in an aircraft caused by electrical current flowing in the structure, in nearby wiring, or any magnetized part of the structure conflict with the Earth's magnetic field and cause a compass error called deviation. Deviation, unlike variation, is different on each heading, but it is not affected by the geographic location. Variation error cannot be reduced or changed, but deviation error can be minimized when an AMT performs the maintenance task known as swinging the compass. Most airports have a compass rose, which is a series of lines marked out on a ramp or maintenance run-up area where there is no magnetic interference. Lines, oriented to magnetic north, are painted every 30 degrees, as shown in Figure 7-33. The AMT aligns the aircraft on each magnetic heading and adjusts the compensating magnets to minimize the difference between the compass indication and the actual magnetic heading of the aircraft. Any error that cannot be removed is recorded on a compass correction card, like the one in Figure 7-34, and placed in a card holder near the compass. The pilot can taxi the aircraft to the compass rose and maneuver the aircraft to the headings prescribed by the AMT. And if authorized to do so, the AMT can also taxi and maneuver the aircraft. However, only the AMT can adjust the compass or complete the compass correction card. If the pilot wants to fly a magnetic heading of 120 degrees, and the aircraft is operating with the radios on, the pilot should fly a compass heading of 123 degrees. The corrections for variation and deviation must be applied in the correct sequence and is shown below, starting from the true course desired. Step 1. Determine the magnetic course. True course, 180 degrees, plus or minus variation, plus 10 degrees, equals magnetic course, 190 degrees. The magnetic course, 190 degrees, is steered if there is no deviation error to be applied. The compass card must now be considered for the compass course of 190 degrees. Step 2. Determine the compass course. Magnetic course, 190 degrees from step 1, plus or minus deviation, minus 2 degrees from correction card, equals compass course, 188 degrees. Note: intermediate magnetic courses between those listed on the compass card need to be interpreted. Therefore, to steer a true course of 180 degrees, the pilot would follow a compass course of 188 degrees. To find the true course that is being flown when the compass course is known, compass course plus or minus deviation equals magnetic course plus or minus variation equals true course. Dip errors. The lines of magnetic flux are considered to leave the Earth at the magnetic North Pole and enter at the magnetic South Pole. At both locations, the lines are perpendicular to the Earth's surface. At the magnetic equator, which is halfway between the poles, the lines are parallel with the surface. The magnets in a compass align with this field, and near the poles they dip or tilt the float end card. This dip causes two very noticeable errors: northerly turning error and acceleration error. The pull of the vertical component of the Earth's magnetic field causes northerly turning error, which is apparent on a heading of north or south. When an aircraft flying on a heading of north makes a turn toward east, the aircraft banks to the right, and the compass card tilts to the right. The vertical component of the Earth's magnetic field pulls the north-seeking end of the magnet to the right, and the float rotates, causing the card to rotate toward west, the direction opposite the direction the turn is being made. Figure 7-35. If the turn is made from north to west, the aircraft banks to the left, and the compass card tilts down on the left side. The magnetic field pulls on the end of the magnet that causes the card to rotate toward east. This indication is, again, opposite to the direction the turn is being made. The rule for this error is, when starting a turn from a northerly heading, the compass indication lags behind the turn. When an aircraft is flying on a heading of south and begins a turn toward east, the Earth's magnetic field pulls on the end of the magnet that rotates the card toward east, the same direction the turn is being made. If the turn is made from south toward west, the magnetic pull starts the card rotating toward west, again, in the same direction the turn is being made. The rule for this error is, when starting a turn from a southerly heading, the compass indication leads the turn. In acceleration error, the dip correction weight causes the end of the float and card marked N, the south-seeking end, to be heavier than the opposite end. When the aircraft is flying at a constant speed on a heading of east or west, the float and card is level. The effects of magnetic dip and the weight are approximately equal. If the aircraft accelerates on a heading of east, Figure 7-36, the inertia of the weight holds its end of the float back, and the card rotates toward north. As soon as the speed of the aircraft stabilizes, the card swings back to its east indication. If, while flying on this easterly heading, the aircraft decelerates, the inertia causes the weight to move ahead, and the card rotates towards south until the speed again stabilizes. When flying on a heading of west, the same things happen. Inertia from acceleration causes the weight to lag, and the card rotates toward north. When the aircraft decelerates on a heading of west, inertia causes the weight to move ahead, and the card rotates toward south. A mnemonic or memory jogger for the effect of acceleration error is the word ANDS. Acceleration, north. Deceleration, south. Acceleration causes an indication toward north. Deceleration causes an indication toward south. Oscillation error. Oscillation is a combination of all of the other errors, and it results in the compass card swinging back and forth around the heading being flown. When setting the gyroscopic heading indicator to agree with the magnetic compass, use the average indication between the swings. The vertical card magnetic compass. The floating magnet type of compass not only has all the errors just described, but also lends itself to confused reading. It is easy to begin a turn in the wrong direction because its card appears backward. East is on what the pilot would expect to be the west side. The vertical card magnetic compass eliminates some of the errors and confusion. The dial of this compass is graduated with letters representing the cardinal directions, numbers every 30 degrees, and tick marks every 5 degrees. The dial is rotated by a set of gears from the shaft-mounted magnet, and the nose of the symbolic aircraft on the instrument glass represents the lubber line for reading the heading of the aircraft from the dial. Eddy currents induced into an aluminum damping cup damp, or decrease, oscillation of the magnet. Figure 7-37. Lags or leads. When starting a turn from a northerly heading, the compass lags behind the turn. When starting a turn from a southerly heading, the compass leads the turn. Eddy current damping. In the case of a vertical card magnetic compass, flux from the oscillating permanent magnet produces eddy currents in a damping disc or cup. The magnetic flux produced by the eddy currents opposes the flux from the permanent magnet and decreases the oscillations. Outside air temperature, OAT, gauge. The outside air temperature, OAT, gauge, is a simple and effective device mounted so that the sensing element is exposed to the outside air. The sensing element consists of a bimetallic type thermometer in which two dissimilar materials are welded together in a single strip and twisted into a helix. One end is anchored into a protective tube, and the other end is affixed to the pointer, which reads against the calibration on a circular face. OAT gauges are calibrated in degrees Celsius, degrees Fahrenheit, or both. An accurate air temperature provides the pilot with useful information about temperature lapse rate with altitude change. Figure 7-38. Chapter Summary. Flight instruments enable an aircraft to be operated with maximum performance and enhanced safety, especially when flying long distances. Manufacturers provide the necessary flight instruments, but to use them effectively, pilots need to understand how they operate. As a pilot, it is important to become very familiar with the operational aspects of the pitot-static system and associated instruments, the vacuum system and associated instruments, the gyroscopic instruments, and the magnetic compass. End of Chapter 7, Part 5.
Part 1 of Chapter 8 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 1 of Chapter 8, Flight Manuals and Other Documents. Introduction. Each aircraft comes with documentation and a set of manuals with which a pilot must be familiar in order to fly that aircraft. This chapter covers airplane flight manuals, AFM, the pilot's operating handbook, POH, and aircraft documents pertaining to ownership, airworthiness, maintenance, and operations with inoperative equipment. Knowledge of these required documents and manuals is essential for a pilot to conduct a safe flight. Airplane Flight Manuals, AFM. Flight manuals and operating handbooks are concise reference books that provide specific information about a particular aircraft or subject. They contain basic facts, information, and/or instructions for the pilot about the operation of an aircraft, flying techniques, etc., and are intended to be kept at hand for ready reference. The Aircraft Owner/Information Manual is a document developed by the manufacturer and contains general information about the make and model of aircraft. The manual is not approved by the Federal Aviation Administration, FAA, and is not specific to an individual aircraft. The manual provides general information about the operation of an aircraft, is not kept current, and cannot be substituted for the AFM/POH. An AFM is a document developed by the manufacturer and approved by the FAA. This book contains the information and instructions required to operate an aircraft safely. A pilot must comply with this information, which is specific to a particular make and model aircraft, usually by serial number. An AFM contains the operating procedures and limitations of that aircraft. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 requires that pilots comply with the operating limitations specified in the approved flight manuals, markings, and placards. Originally, flight manuals followed whatever format and content the manufacturer felt was appropriate, but this changed with the acceptance of Specification Number 1, prepared by the General Aviation Manufacturers Association, GAMA. Specification Number 1 established a standardized format for all general aviation airplane and helicopter flight manuals. The POH is a document developed by the aircraft manufacturer and contains FAA-approved AFM information. If POH is used in the main title, a statement must be included on the title page indicating that sections of the document are FAA-approved as the AFM. The POH for most light aircraft built after 1975 is also designated as the FAA-approved flight manual. The typical AFM/POH contains the following 9 sections: General, Limitations, Emergency Procedures, Normal Procedures, Performance, Weight and Balance/Equipment List, Systems Description, Handling, Service, and Maintenance, and supplements. Manufacturers also have the option of including additional sections, such as one on safety and operational tips, or an alphabetical index at the end of the POH. Preliminary pages. While the AFM/POH may appear similar for the same make and model of aircraft, each manual is unique and contains specific information about a particular aircraft, such as the equipment installed and the weight and balance information. Manufacturers are required to include the serial number and registration on the title page to identify the aircraft to which the manual belongs. If a manual does not indicate a specific aircraft registration and serial number, it is limited to general study purposes only. Most manufacturers include a table of contents which identifies the order of the entire manual by section number and title. Usually, each section also contains a table of contents for that section. Page numbers reflect the section and page within that section: 1-1, 1-2, 2-1, 3-1, etc. If the manual is published in loose-leaf form, each section is usually marked with a divider tab indicating the section number or title or both. The Emergency Procedures section may have a red tab for quick identification and reference. General, Section 1. The General section provides the basic descriptive information on the airframe and the power plant or power plants. Some manuals include a three-dimensional drawing of the aircraft that provide dimensions of various components. Included are such items as wingspan, maximum height, overall length, wheelbase length, main landing gear track width, diameter of the rotor system, maximum propeller diameter, propeller ground clearance, minimum turning radius, and wing area. This section serves as a quick reference and helps a pilot become familiar with the aircraft. The last segment of the General section contains definitions, abbreviations, explanations of symbology, and some of the terminology used in the POH. At the option of the manufacturer, metric and other conversion tables may also be included. Limitations, Section 2. The Limitations section contains only those limitations required by regulation or that are necessary for the safe operation of the aircraft, power plant, systems, and equipment. It includes operating limitations, instrument markings, color coding, and basic placards. Some of the limitation areas are airspeed, power plant, weight and loading distribution, and flight. Airspeed. Airspeed limitations are shown on the Airspeed Indicator, ASI, by color coding and on placards or graphs in the aircraft. Refer to Figure 8-1. A red line on the ASI shows the airspeed limit beyond which structural damage could occur. This is called the Never Exceed Speed, VNE. A yellow arc indicates the speed range between maximum structural cruising speed, VNO, and VNE. Operation of an airplane in the yellow airspeed arc is for smooth air only, and then only with caution. A green arc depicts the normal operating speed range, with the upper end at VNO and the lower end at stalling speed at maximum weight with the landing gear and flaps retracted, VS1. For airplanes, the flap operating range is depicted by the white arc, with the upper end at the maximum flap extended speed, VFE, and the lower end at the stalling speed with the landing gear and flaps in the landing configuration, VSO. In addition to the markings listed above, small multi-engine airplanes will have a red radial line to indicate single-engine minimum controllable airspeed, VMC. A blue radial line is used to indicate single-engine best rate of climb speed at maximum weight at sea level, VYSE. Refer to Figure 8-2. Power plant. The power plant limitations portion describes operating limitations on an aircraft's reciprocating or turbine engine or engines. These include limitations for takeoff power, maximum continuous power, and maximum normal operating power, which is the maximum power the engine can produce without any restrictions and is depicted by a green arc. Other items that can be included in this area are the minimum and maximum oil and fuel pressures, oil and fuel grades, and propeller operating limits. Refer to Figure 8-3. All reciprocating engine-powered aircraft must have a revolutions per minute RPM indicator for each engine. Aircraft equipped with a constant speed propeller or rotor system use a manifold pressure gauge to monitor power output and a tachometer to monitor propeller or rotor speed. Both instruments depict the maximum operating limit with a red radial line and the normal operating range with a green arc. Refer to Figure 8-4. Some instruments may have a yellow arc to indicate a caution area. Weight and loading distribution. Weight and loading distribution contains the maximum certificated weights as well as the center of gravity, CG range. The location of the reference datum used in balance computations is included in this section. Weight and balance computations are not provided in this area, but rather in the weight and balance section of the AFM/POH. Flight limits. Flight limits list authorized maneuvers with appropriate entry speeds, flight load factor limits, and kinds of operation limits. It also indicates those maneuvers that are prohibited, such as spins or acrobatic flight, as well as operational limitations such as flight into known icing conditions. Placards. Most aircraft display one or more placards that contain information having a direct bearing on the safe operation of the aircraft. These placards are located in conspicuous places and are reproduced in the Limitations section or as directed by an Airworthiness Directive, AD. Refer to Figure 8-5. Emergency Procedures, Section 3. Checklists describing the recommended procedures and airspeeds for coping with various types of emergencies or critical situations are located in the Emergency Procedures section. Some of the emergencies covered include engine failure, fire, and system failure. The procedures for in-flight engine restarting and ditching may also be included. Manufacturers may first show an emergency checklist in an abbreviated form with the order of items reflecting the sequence of action. Amplified checklists that provide additional information on the procedures follow the abbreviated checklist. To be prepared for emergency situations, memorize the immediate action items and, after completion, refer to the appropriate checklist. Manufacturers may include an optional subsection titled Abnormal Procedures. This subsection describes recommended procedures for handling malfunctions that are not considered emergencies. Normal Procedures, Section 4. This section begins with a list of the airspeeds for normal operations. The next area consists of several checklists that may include pre-flight inspection, before starting procedures, starting engine, before taxiing, before takeoff, climb, cruise, descent, before landing, balked landing, after landing, and post-flight procedures. An amplified procedures area follows the checklist to provide more detailed information about the various previously mentioned procedures. To avoid missing important steps, always use the appropriate checklists when available. Consistent adherence to approved checklists is a sign of a disciplined and competent pilot. Performance, Section 5. The Performance section contains all the information required by the aircraft certification regulations and any additional performance information the manufacturer deems important to pilot ability to safely operate the aircraft. Performance charts, tables, and graphs vary in style, but all contain the same basic information. Examples of the performance information found in most flight manuals include a graph or table for converting calibrated airspeed to true airspeed, stall speeds in various configurations, and data for determining takeoff and climb performance, cruise performance, and landing performance. Figure 8-6 is an example of a typical performance graph. For more information on the use of charts, graphs, and tables, refer to Chapter 10, Aircraft Performance. Weight and Balance Slant Equipment List, Section 6. The Weight and Balance Slant Equipment List section contains all the information required by the FAA to calculate the weight and balance of an aircraft. Manufacturers include sample weight and balance problems. Weight and balance is discussed in greater detail in Chapter 9, Weight and Balance. Systems Description, Section 7. This section describes the aircraft systems in a manner appropriate to the pilot most likely to operate the aircraft. For example, a manufacturer might assume an experienced pilot will be reading the information for an advanced aircraft. For more information on aircraft systems, refer to Chapter 6, Aircraft Systems. Handling, Service, and Maintenance, Section 8. The Handling, Service, and Maintenance section describes the maintenance and inspections recommended by the manufacturer and the regulations. Additional maintenance or inspections may be required by the issuance of AD applicable to the airframe, engine, propeller, or components. This section also describes preventive maintenance that may be accomplished by certificated pilots as well as the manufacturer's recommended ground handling procedures. It includes considerations for hangaring, tie-down, and general storage procedures for the aircraft. Supplements, Section 9. The Supplements section contains information necessary to safely and efficiently operate the aircraft when equipped with optional systems and equipment not provided with the standard aircraft. Some of this information may be supplied by the aircraft manufacturer or by the manufacturer of the optional equipment. The appropriate information is inserted into the flight manual at the time the equipment is installed. Autopilots, navigation systems, and air conditioning systems are examples of equipment described in this section. Refer to Figure 8-7. Safety Tips, Section 10. The Safety Tips section is an optional section containing a review of information that enhances the safe operation of the aircraft. For example, physiological factors, general weather information, fuel conservation procedures, high-altitude operations, or cold weather operations might be discussed. Aircraft Documents. Certificate of Aircraft Registration. Before an aircraft can be flown legally, it must be registered with the FAA Aircraft Registry. The Certificate of Aircraft Registration, which is issued to the owner as evidence of the registration, must be carried in the aircraft at all times. Refer to Figure 8-8. The Certificate of Aircraft Registration cannot be used for operations when the aircraft is registered under the laws of a foreign country, the aircraft's registration is canceled upon written request of the certificate holder, the aircraft is totally destroyed or scrapped, the ownership of the aircraft is transferred, or the certificate holder loses United States citizenship. For additional information, see 14 CFR Section 47.41. When one of the events listed in 14 CFR Section 47.41 occurs, the previous owner must notify the FAA by filling in the back of the Certificate of Aircraft Registration and mailing it to FAA Aircraft Registration Branch, AFS-750, P.O. Box 25504, Oklahoma City, Oklahoma, 73125-0504. A dealer's aircraft registration certificate is another form of registration certificate, but is valid only for required flight tests by the manufacturer or in flights that are necessary for the sale of the aircraft by the manufacturer or a dealer. The dealer must remove the certificate when the aircraft is sold. Upon complying with 14 CFR Section 47.31, the pink copy of the application for an aircraft registration application, Aeronautical Center AC Form 8050-1, provides authorization to operate an unregistered aircraft for a period not to exceed 90 days. Since the aircraft is unregistered, it cannot be operated outside of the United States until a permanent certificate of aircraft registration is received and placed in the aircraft. The FAA does not issue any certificate of ownership or endorse any information with respect to ownership on a certificate of aircraft registration. Note: for additional information concerning the aircraft registration application or the aircraft bill of sale, contact the nearest FAA Flight Standards District Office, FSDO. Light Sport Aircraft, LSA. The FAA recently added a new category called Light Sport Aircraft, LSA. Requirements for registration of these aircraft differ from those of other aircraft. The following guidelines are provided for LSA registration, but a more detailed explanation can be found on the FAA website at http://www.faa.gov. An existing LSA that has not been issued a United States or a foreign airworthiness certificate and does not meet the provisions of 14 CFR Section 103.1 must meet specific criteria in order to be certificated as an experimental LSA under 14 CFR Section 21.191, paragraph I-1, before January 31, 2008. The following items must be provided: evidence of ownership of the parts or the manufacturer's kit, aircraft registration application, AC Form 8050-1, and a $5 registration fee. If evidence of ownership cannot be supplied, An affidavit stating why it is not available must be submitted on the AC Form 8050-88A. If an owner wants to register a newly manufactured LSA that will be certificated as an experimental light sport aircraft under 14 CFR Section 21.191, paragraph I-2, the following items must be provided: AC Form 8050-88A or its equivalent, completed by the LSA manufacturer, unless previously submitted to the registry by the manufacturer; evidence from the manufacturer of ownership of an aircraft, kit built or flyaway; AC Form 8050-1, and a $5 registration fee. Airworthiness Certificate. An airworthiness certificate is issued by a representative of the FAA after the aircraft has been inspected, is found to meet the requirements of 14 CFR Part 21, and is in condition for safe operation. The airworthiness certificate must be displayed in the aircraft so it is legible to the passengers and crew whenever it is operated. The airworthiness certificate is transferred with the aircraft except when it is sold to a foreign purchaser. A standard airworthiness certificate is issued for aircraft type certificated in the normal, utility, acrobatic, commuter, transport categories, and manned free balloons. Figure 8-9 illustrates a standard airworthiness certificate, and an explanation of each item in the certificate follows. 1. National and registration marks. The N indicates the aircraft is registered in the United States. Registration marks consist of a series of up to 5 numbers or numbers and letters. In this case, N2631A is the registration number assigned to this airplane. 2. Manufacturer and model indicates the manufacturer, make, and model of the aircraft. 3. Aircraft serial number indicates the manufacturer's serial number assigned to the aircraft as noted on the aircraft data plate. 4. Category indicates the category in which the aircraft must be operated. In this case, it must be operated in accordance with the limitations specified for the normal category. 5. Authority and basis for issuance indicates the aircraft conforms to its type certificate and is considered in condition for safe operation at the time of inspection and issuance of the certificate. Any exemptions from the applicable airworthiness standards are briefly noted here, and the exemption number given. The word none is entered if no exemptions exist. 6. Terms and conditions indicates the airworthiness certificate is in effect indefinitely if the aircraft is maintained in accordance with 14 CFR Parts 21, 43, and 91, and the aircraft is registered in the United States. Also included are the date the certificate was issued and the signature and office identification of the FAA representative. A standard airworthiness certificate remains in effect if the aircraft receives the required maintenance and is properly registered in the United States. Flight safety relies in part on the condition of the aircraft, which is determined by inspections performed by mechanics, approved repair stations, or manufacturers that meet specific requirements of 14 CFR Part 43. A special airworthiness certificate is issued for all aircraft certificated in other than the standard classifications, such as experimental, restricted, limited, provisional, and LSA. LSA receive a pink special airworthiness certificate. There are exceptions. For example, the Piper Cub is in the new LSA category, but it was certificated as a normal aircraft during its manufacture. When purchasing an aircraft classified as other than standard, it is recommended that the local FSDO be contacted for an explanation of the pertinent airworthiness requirements and the limitations of such a certificate. Aircraft maintenance. Maintenance is defined as the preservation, inspection, overhaul, and repair of an aircraft, including the replacement of parts. Regular and proper maintenance ensures that an aircraft meets an acceptable standard of airworthiness throughout its operational life. Although maintenance requirements vary for different types of aircraft, experience shows that aircraft need some type of preventative maintenance every 25 hours of flying time or less, and minor maintenance at least every 100 hours. This is influenced by the kind of operation, climatic conditions, storage facilities, age, and construction of the aircraft. Manufacturers supply maintenance manuals, parts, catalogs, and other service information that should be used in maintaining the aircraft. End of Part 1 of Chapter 8. Part 2 of Chapter 8 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 2 of Chapter 8, Flight Manuals and Other Documents. Aircraft Inspections. 14 CFR Part 91 places primary responsibility on the owner or operator for maintaining an aircraft in an airworthy condition. Certain inspections must be performed on the aircraft, and the owner must maintain the airworthiness of the aircraft during the time between required inspections by having any defects corrected. 14 CFR Part 91, Subpart E, requires the inspection of all civil aircraft at specific intervals to determine the overall condition. The interval depends upon the type of operations in which the aircraft is engaged. All aircraft need to be inspected at least once each 12 calendar months, while inspection is required for others after each 100 hours of operation. Some aircraft are inspected in accordance with an inspection system set up to provide for total inspection of the aircraft on the basis of calendar time, time in service, number of system operations, or any combination of these. All inspections should follow the current manufacturer's maintenance manual, including the instruction for continued airworthiness concerning inspections intervals, parts replacement, and life-limited items as applicable to the aircraft. Annual inspection. Any reciprocating engine or single-engine turbojet slant turbo propeller-powered small aircraft, 12,500 pounds and under, flown for business or pleasure and not flown for compensation or hire, is required to be inspected at least annually. The inspection shall be performed by a certificated airframe and power plant A&P mechanic who holds an inspection authorization, IA, by the manufacturer of the aircraft or by a certificated and appropriately rated repair station. The aircraft may not be operated unless the annual inspection has been performed within the preceding 12 calendar months. A period of 12 calendar months extends from any day of the month to the last day of the same month the following year. An aircraft overdue for an annual inspection may be operated under a special flight permit issued by the FAA for the purpose of flying the aircraft to a location where the annual inspection can be performed. However, all applicable ADs that are due must be complied with before the flight. 100-hour inspection. All aircraft under 12,500 pounds, except turbojet slant turbo propeller-powered multi-engine airplanes and turbine-powered rotorcraft, used to carry passengers for hire, must have received a 100-hour inspection within the preceding 100 hours of time in service, and have been approved for return to service. Additionally, an aircraft used for flight instruction for hire, when provided by the person giving the flight instruction, must also have received a 100-hour inspection. This inspection must be performed by an FAA-certificated A&P mechanic, an appropriately rated FAA-certificated repair station, or by the aircraft manufacturer. An annual inspection, or an inspection for the issuance of an airworthiness certificate, may be substituted for a required 100-hour inspection. The 100-hour limitation may be exceeded by not more than 10 hours while en route to reach a place where the inspection can be done. The excess time used to reach a place where the inspection can be done must be included in computing the next 100 hours of time in service. Other inspection programs. The annual and 100-hour inspection requirements do not apply to large, over 12,500 pounds, airplanes, turbojets, or turbopropeller-powered multi-engine airplanes, or to aircraft for which the owner complies with a progressive inspection program. Details of these requirements may be determined by reference to 14 CFR Section 43.11 and 14 CFR Part 91, Subpart E, and by inquiring at a local FSDO. Altimeter System Inspection. 14 CFR Section 91.411 requires that the altimeter, encoding altimeter, and related system be tested and inspected in the preceding 24 months before operated in controlled airspace under Instrument Flight Rules, IFR. Transponder Inspection. 14 CFR Section 91.413 requires that before a transponder can be used under 14 CFR Section 91.215A, it shall be tested and inspected within the preceding 24 months. Emergency Locator Transmitter. An emergency locator transmitter, ELT, is required by 14 CFR Section 91.207 and must be inspected within 12 calendar months after the last inspection for the following: proper installation, battery corrosion, operation of the controls and crash sensor, the presence of a sufficient signal radiated from its antenna. The ELT must be attached to the airplane in such a manner that the probability of damage to the transmitter in the event of crash impact is minimized. Fixed and deployable automatic type transmitters must be attached to the airplane as far aft as practicable. Batteries used in the ELTs must be replaced or recharged if the batteries are rechargeable when the transmitter has been in use for more than 1 cumulative hour, or when 50% of the battery useful life, or for rechargeable batteries, 50% of useful life of the charge has expired. An expiration date for replacing or recharging the battery must be legibly marked on the outside of the transmitter and entered in the aircraft maintenance record. This does not apply to batteries that are essentially unaffected during storage intervals, such as water-activated batteries. Pre-flight inspections. The pre-flight inspection is a thorough and systematic means by which a pilot determines if the aircraft is airworthy and in condition for safe operation. POHs and owner slant information manuals contain a section devoted to a systematic method of performing a pre-flight inspection. Minimum Equipment Lists, MEL, and Operations with Inoperative Equipment. 14 CFR requires that all aircraft instruments and installed equipment be operative prior to each departure. When the FAA adopted the Minimum Equipment List, MEL concept for 14 CFR Part 91 operations, this allowed operations with inoperative equipment determined to be non-essential for safe flight. At the same time, it allowed Part 91 operators without an MEL to defer repairs on non-essential equipment within the guidelines of Part 91. The FAA has two acceptable methods of deferring maintenance on small rotorcraft, non-turbine-powered airplanes, gliders, or lighter-than-air aircraft operated under Part 91. They are the deferral provision of 14 CFR Section 91.213D and an FAA-approved MEL. The deferral provision of 14 CFR Section 91.213D is widely used by most pilot slant operators. Its popularity is due to simplicity and minimal paperwork. When inoperative equipment is found during pre-flight or prior to departure, the decision should be made to cancel the flight, obtain maintenance prior to flight, or to defer the item or equipment. Maintenance deferrals are not used for in-flight discrepancies. The manufacturer's AFM/POH procedures are to be used in those situations. The discussion that follows assumes that the pilot wishes to defer maintenance that would ordinarily be required prior to flight. Using the deferral provision of 14 CFR Section 91.213D, the pilot determines whether the inoperative equipment is required by type design, 14 CFR, or ADs. If the inoperative item is not required and the aircraft can be safely operated without it, the deferral may be made. The inoperative item shall be deactivated or removed, and an inoperative placard placed near the appropriate switch, control, or indicator. If deactivation or removal involves maintenance, removal always will, it must be accomplished by certificated maintenance personnel and recorded in accordance with 14 CFR Part 43. For example, if the position lights, installed equipment, were discovered to be inoperative prior to a daytime flight, the pilot would follow the requirements of 14 CFR Section 91.213D. The deactivation may be a process as simple as the pilot positioning a circuit breaker to the off position, or as complex as rendering instruments or equipment totally inoperable. Complex maintenance tasks require a certificated and appropriately rated maintenance person to perform the deactivation. In all cases, the item or equipment must be placarded inoperative. All small rotorcraft, non-turbine-powered airplanes, gliders, or lighter-than-air aircraft operated under 14 CFR Part 91 are eligible to use the maintenance deferral provisions of 14 CFR Section 91.213D. However, once an operator requests an MEL and a letter of authorization, LOA, is issued by the FAA, then the use of the MEL becomes mandatory for that aircraft. All maintenance deferrals must be accomplished in accordance with the terms and conditions of the MEL and the operator-generated procedures document. The use of an MEL for an aircraft operated under 14 CFR Part 91 also allows for the deferral of inoperative items or equipment. The primary guidance becomes the FAA-approved MEL issued to that specific operator and N-numbered aircraft. The FAA has developed Master Minimum Equipment Lists, MMELs, for aircraft in current use. Upon written request by an operator, the local FSDO may issue the appropriate make and model MMEL, along with an LOA and the preamble. The operator then develops operations and maintenance O&M procedures from the MMEL. This MMEL with O&M procedures now becomes the operator's MEL. The MEL, LOA, preamble, and the procedures document developed by the operator must be on board the aircraft when it is operated. The FAA considers an approved MEL to be a supplemental type certificate, STC, issued to an aircraft by serial number and registration number. It therefore becomes the authority to operate that aircraft in a condition other than originally type certificated. With an approved MEL, if the position lights were discovered inoperative prior to a daytime flight, the pilot would make an entry in the maintenance record or discrepancy record provided for that purpose. The item is then either repaired or deferred in accordance with the MEL. Upon confirming the daytime flight with inoperative position lights is acceptable in accordance with the provisions of the MEL, the pilot would leave the position lights switched off, open the circuit breaker, or whatever action is called for in the procedures document, and placard the position light switch as inoperative. There are exceptions to the use of the MEL for deferral. For example, should a component fail that is not listed in the MEL as deferrable, the tachometer, flaps, or stall warning device, for example, then repairs are required to be performed prior to departure. If maintenance or parts are not readily available at that location, a special flight permit can be obtained from the nearest FSDO. This permit allows the aircraft to be flown to another location for maintenance. This allows an aircraft that may not currently meet applicable airworthiness requirements, but is capable of safe flight, to be operated under the restrictive special terms and conditions attached to the special flight permit. Deferral of maintenance is not to be taken lightly, and due consideration should be given to the effect an inoperative component may have on the operation of an aircraft, particularly if other items are inoperative. Further information regarding MELs and operations with inoperative equipment can be found in AC 91-67, Minimum Equipment Requirements for General Aviation Operations under CFR Part 91. Preventive maintenance. Preventive maintenance is considered to be simple or minor preservation operations and the replacement of small standard parts, not involving complex assembly operations. Allowed items of preventative maintenance are listed and limited to the items of 14 CFR Part 43, Appendix A, C. Maintenance entries. All pilots who maintain or perform preventive maintenance must make an entry in the maintenance record of the aircraft. This entry must include 1. A description of the work, such as changed oil, shell aero-50 at 2,345 hours. 2. The date of completion of the work performed. 3. The entry of the pilot's name, signature, certificate number, and type of certificate held. Examples of preventive maintenance. The following examples of preventive maintenance are taken from 14 CFR Part 43, Maintenance, Preventative Maintenance, Rebuilding, and Alteration, which should be consulted for a more in-depth look at preventive maintenance a pilot can perform on an aircraft. Remember, preventive maintenance is limited to work that does not involve complex assembly operations and includes removal, installation, and repair of landing gear tires and shock cords, servicing landing gear shock struts by adding oil, air, or both, servicing gear wheel bearings, replacing defective safety wiring or cotter keys, lubrication not requiring disassembly other than removal of non-structural items such as cover plates, cowlings, and fairings, making simple fabric patches not requiring rib stitching or the removal of structural parts or control surfaces. In the case of balloons, the making of small fabric repairs to envelopes, as defined in and in accordance with the balloon manufacturer's instructions, not requiring load tape repair or replacement. Replenishing hydraulic fluid in the hydraulic reservoir. Refinishing decorative coating of fuselage, balloon baskets, wings, tail group surfaces, excluding balanced control surfaces. Fairings, cowlings, landing gear, cabin or flight deck interior when removal or disassembly of any primary structure or operating system is not required. Applying preservative or protective material to components where no disassembly of any primary structure or operating system is involved, and where such coating is not prohibited or is not contrary to good practices. Repairing upholstery and decorative furnishings of the cabin, flight deck, or balloon basket interior when a repair does not require disassembly of any primary structure or operating system or interfere with an operating system or affect the primary structure of the aircraft. Making small, simple repairs to fairings, non-structural cover plates, cowlings, and small patches and reinforcements, not changing the contour to interfere with proper airflow, replacing side windows where that work does not interfere with the structure or any operating system such as controls, electrical equipment, etc. Replacing safety belts, seats, or seat parts with replacement parts approved for the aircraft, not involving disassembly of any primary structure or operating system. Bulbs, reflectors, and lenses of position and landing lights. Replacing wheels and skis where no weight and balance computation is involved. Replacing any cowling not requiring removal of the propeller or disconnection of flight controls. Replacing or cleaning spark plugs and setting of spark plug gap clearance. Replacing any hose connection, except hydraulic connections. However, prefabricated fuel lines may be replaced. Cleaning or replacing fuel and oil strainers or filter elements. Servicing batteries, cleaning of balloon burner pilot and main nozzles in accordance with the balloon manufacturer's instructions. The interchange of balloon baskets and burners on envelopes when the basket or burner is designated as interchangeable in the balloon type certificate data, and the baskets and burners are specifically designed for quick removal and installation. Adjustment of non-structural standard fasteners incidental to operations. The installations of anti-misfueling devices to reduce the diameter of fuel tank filler openings only if the specific device has been made a part of the aircraft type certificate data by the aircraft manufacturer. The aircraft manufacturer has provided FAA-approved instructions for installation of the specific device, and installation does not involve the disassembly of the existing tank filler opening. Troubleshooting and repairing broken circuits and landing light wiring circuits. Removing and replacing self-contained, front instrument panel-mounted navigation and communication devices employing tray-mounted connectors that connect the unit when the unit is installed into the instrument panel. Excluding automatic flight control systems, transponders, and microwave frequency distance measuring equipment, DME. The approved unit must be designed to be readily and repeatedly removed and replaced, and pertinent instructions must be provided. Prior to the unit's intended use, an operational check must be performed in accordance with the applicable sections of 14 CFR Part 91 on checking, removing, and replacing magnetic chip detectors. Inspection and maintenance tasks prescribed and specifically identified as preventative maintenance in a primary category aircraft type certificate or a supplemental type certificate holder's approved special inspection and preventative maintenance program when accomplished on a primary category aircraft. Updating self-contained front instrument panel mounted air traffic control ATC navigational software databases, excluding those of automatic flight control systems, transponders, and microwave frequency DME, only if no disassembly of the unit is required and pertinent instructions are provided. Prior to the unit's intended use, an operational check must be performed in accordance with applicable sections of 14 CFR Part 91. Certificated pilots, excluding student pilots, sport pilots, and recreational pilots, may perform preventative maintenance on any aircraft that is owned or operated by them, provided that aircraft is not used in air carrier service or 14 CFR Part 121, 129, or 135. A pilot holding a sport pilot certificate may perform preventive maintenance on an aircraft owned or operated by that pilot if that aircraft is issued a special airworthiness certificate in the LSA category. Sport pilots operating LSA should refer to 14 CFR Part 65 for maintenance privileges. 14 CFR Part 43, Appendix A, contains a list of the operations that are considered to be preventive maintenance. Repairs and alterations. Repairs and alterations are classified as either major or minor. 14 CFR Part 43, Appendix A, describes the alterations and repairs considered major. Major repairs or alterations shall be approved for return to service on FAA Form 337, Major Repair and Alteration, by an appropriately rated certificated repair station, an FAA certificated A&P mechanic holding an IA, or a representative of the administrator. Minor repairs and minor alterations may be approved for return to service with a proper entry in the maintenance records by an FAA certificated A&P mechanic or an appropriately certificated repair station. For modifications of experimental aircraft, refer to the operating limitations issued to that aircraft. Modifications in accordance with FAA Order 8130.2, Airworthiness Certification of Aircraft and Related Products, may require the notification of the issuing authority. Special Flight Permits. A special flight permit is a special airworthiness certificate authorizing operation of an aircraft that does not currently meet applicable airworthiness requirements, but is safe for a specific flight. Before the permit is issued, an FAA inspector may personally inspect the aircraft, or require it to be inspected by an FAA certificated A&P mechanic, or an appropriately certificated repair station to determine its safety for the intended flight. The inspection shall be recorded in the aircraft records. The special flight permit is issued to allow the aircraft to be flown to a base where repairs, alterations, or maintenance can be performed, for delivering or exporting the aircraft, or for evacuating an aircraft from an area of impending danger. A special flight permit may be issued to allow the operation of an overweight aircraft for flight beyond its normal range over water or land areas where adequate landing facilities or fuel is not available. If a special flight permit is needed, assistance and the necessary forms may be obtained from the local FSDO or designated airworthiness representative, DAR. Refer to Figure 8-10. Airworthiness Directives, ADs. A primary safety function of the FAA is to require correction of unsafe conditions found in an aircraft, aircraft engine, propeller, or appliance when such conditions exist and are likely to exist or develop in other products of the same design. The unsafe condition may exist because of a design defect, maintenance, or other causes. 14 CFR Part 39 and Airworthiness Directives, ADs, define the authority and responsibility of the administrator for requiring the necessary corrective action. ADs are used to notify aircraft owners and other interested persons of unsafe conditions and to specify the conditions under which the product may continue to be operated. ADs are divided into two categories. 1. Those of an emergency nature requiring immediate compliance prior to further flight. 2. Those of a less urgent nature requiring compliance within a specified period of time. ADs are regulatory and shall be complied with unless a specific exemption is granted. It is the responsibility of the aircraft owner or operator to ensure compliance with all pertinent ADs, including those ADs that require recurrent or continuing action. For example, an AD may require a repetitive inspection each 50 hours of operation, meaning the particular inspection shall be accomplished and recorded every 50 hours of time in service. Owners/operators are reminded there is no provision to overfly the maximum hour requirement of an AD unless it is specifically written into the AD. To help determine if an AD applies to an amateur-built aircraft, contact the local FSDO. 14 CFR Section 91.417 requires a record to be maintained that shows the current status of applicable ADs, including the method of compliance, the AD number and revision date, if recurring, next due date and time, the signature, kind of certificate, and the certificate number of the repair station or mechanic who performed the work. For ready reference, many aircraft owners have a chronological listing of the pertinent ADs in the back of their aircraft engine and propeller maintenance records. All ADs and the AD bi-weekly are free on the Internet at http://rgl.faa.gov. In July of 2007, the FAA made ADs available through email. Individuals can enroll for the email service at the link above. Mailing paper copies of ADs will be discontinued when the email system is proven to be effective. Paper copies of the Summary of Airworthiness Directives and the AD Bi-Weekly may be purchased from the Superintendent of Documents. The summary contains all the valid ADs previously published and is divided into two areas. The small aircraft and helicopter books contain all ADs applicable to small aircraft, 12,500 pounds or less maximum certificated takeoff weight, and ADs applicable to all helicopters. The large aircraft books contain all ADs applicable to large aircraft. For current information on how to order paper copies of AD books and the AD Bi-Weekly, visit the FAA Online Regulatory and Guidance Library at http://rgl.faa.gov. Aircraft owner/operator responsibilities. The registered owner/operator of an aircraft is responsible for having a current airworthiness certificate and a certificate of aircraft registration in the aircraft, maintaining the aircraft in an airworthy condition, including compliance with all applicable ADs and assuring that maintenance is properly recorded, keeping abreast of current regulations concerning the operation and maintenance of the aircraft, notifying the FAA Aircraft Registry immediately of any change of permanent mailing address or of the sale or export of the aircraft or of the loss of the eligibility to register an aircraft. Refer to 14 CFR Section 47.41. Having a current Federal Communications Commission FCC radio station license if equipped with radios, including Emergency Locator Transmitter, ELT, if operated outside of the United States. Chapter Summary. Knowledge of an aircraft's AFM/POH and documents such as ADs help a pilot to have ready access to pertinent information needed to safely fly a particular aircraft. By understanding the operations, limitations, and performance characteristics of the aircraft, the pilot can make good flight decisions. By learning what preventative maintenance is allowed on the aircraft, a pilot can maintain his or her aircraft in an airworthy condition. The goal of every pilot is a safe flight. Flight manuals and aircraft documentation are essential tools used to reach that goal. End of Part 2 of Chapter 8. Part 1 of Chapter 9 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 1 of Chapter 9, Weight and Balance. Introduction. Compliance with the weight and balance limits of any aircraft is critical to flight safety. Operating above the maximum weight limitation compromises the structural integrity of an aircraft and adversely affects its performance. Operation with the center of gravity, CG, outside the approved limits results in control difficulty. Weight control. As discussed in Chapter 4, Aerodynamics of Flight, weight is the force with which gravity attracts a body toward the center of the Earth. It is a product of the mass of a body and the acceleration acting on the body. Weight is a major factor in aircraft construction and operation and demands respect from all pilots. The force of gravity continuously attempts to pull an aircraft down toward Earth. The force of lift is the only force that counteracts weight and sustains an aircraft in flight. The amount of lift produced by an airfoil is limited by the airfoil design, angle of attack, AOA, airspeed, and air density. To assure that the lift generated is sufficient to counteract weight, loading an aircraft beyond the manufacturer's recommended weight must be avoided. If the weight is greater than the lift generated, the aircraft may be incapable of flight. Effects of weight. Any item aboard the aircraft that increases the total weight is undesirable for performance. Manufacturers attempt to make an aircraft as light as possible without sacrificing strength or safety. The pilot should always be aware of the consequences of overloading. An overloaded aircraft may not be able to leave the ground, or if it does become airborne, it may exhibit unexpected and unusually poor flight characteristics. If not properly loaded, the initial indication of poor performance usually takes place during takeoff. Excessive weight reduces the flight performance in almost every respect. For example, the most important performance deficiencies of an overloaded aircraft are high takeoff speed, longer takeoff run, reduced rate and angle of climb, lower maximum altitude, shorter range, reduced cruising speed, reduced maneuverability, higher stalling speed, higher approach and landing speed, longer landing roll, excessive weight on the nose wheel or tail wheel. The pilot must be knowledgeable about the effect of weight on the performance of the particular aircraft being flown. Pre-flight planning should include a check of performance charts to determine if the aircraft's weight may contribute to hazardous flight conditions. Excessive weight in itself reduces the safety margins available to the pilot, and becomes even more hazardous when other performance-reducing factors are combined with excess weight. The pilot must also consider the consequences of an overweight aircraft if an emergency condition arises. If an engine fails on takeoff, or airframe ice forms at low altitude, it is usually too late to reduce an aircraft's weight to keep it in the air. Weight changes. The operating weight of an aircraft can be changed by simply altering the fuel load. Gasoline has considerable weight, 6 pounds per gallon. 30 gallons of fuel may weigh more than one passenger. If a pilot lowers airplane weight by reducing fuel, the resulting decrease in the range of the airplane must be taken into consideration during flight planning. During flight, fuel burn is normally the only weight change that takes place. As fuel is used, an aircraft becomes lighter and performance is improved. Changes of fixed equipment have a major effect upon the weight of an aircraft. The installation of extra radios or instruments, as well as repairs or modifications, may also affect the weight of an aircraft. Balance, stability, and center of gravity. Balance refers to the location of the CG of an aircraft and is important to stability and safety in flight. The CG is a point at which the aircraft would balance if it were suspended at that point. The primary concern in balancing an aircraft is the fore and aft location of the CG along the longitudinal axis. The CG is not necessarily a fixed point. Its location depends on the distribution of weight in the aircraft. As variable load items are shifted or expended, there is a resultant shift in CG location. The distance between the forward and back limits for the position for the center of gravity or CG range is certified for an aircraft by the manufacturer. The pilot should realize that if the CG is displaced too far forward on the longitudinal axis, a nose-heavy condition will result. Conversely, if the CG is displaced too far aft on the longitudinal axis, a tail-heavy condition results. It is possible that the pilot could not control the aircraft if the CG location produced an unstable condition. Refer to Figure 9-1. Location of the CG with reference to the lateral axis is also important. For each item of weight existing to the left of the fuselage centerline, there is an equal weight existing at a corresponding location on the right. This may be upset by unbalanced lateral loading. The position of the lateral CG is not computed in all aircraft, but the pilot must be aware that adverse effects arise as a result of a laterally unbalanced condition. In an airplane, lateral unbalance occurs if the fuel load is mismanaged by supplying the engine or engines unevenly from tanks on one side of the airplane. The pilot can compensate for the resulting wing-heavy condition by adjusting the trim or by holding a constant control pressure. This action places the aircraft controls in an out-of-streamline condition, increases drag, and results in decreased operating efficiency. Since lateral balance is addressed when needed in the Aircraft Flight Manual, AFM, and longitudinal balance is more critical, further reference to balance in this handbook means longitudinal location of the CG. A single pilot operating a small rotorcraft may require additional weight to keep the aircraft laterally balanced. Flying an aircraft that is out of balance can produce increased pilot fatigue with obvious effects on the safety and efficiency of flight. The pilot's natural correction for longitudinal unbalance is a change of trim to remove the excessive control pressure. Excessive trim, however, has the effect of reducing not only aerodynamic efficiency, but also the primary control travel distance in the direction the trim is applied. Effects of adverse balance. Adverse balance conditions affect flight characteristics in much the same manner as those mentioned for an excess weight condition. It is vital to comply with weight and balance limits established for all aircraft, especially rotorcraft. Operating above the maximum weight limitation compromises the structural integrity of the rotorcraft and adversely affects performance. Balance is also critical because on some fully loaded rotorcraft, CG deviations as small as 3 inches can dramatically change handling characteristics. Stability and control are also affected by improper balance. Stability. Loading in a nose-heavy condition causes problems in controlling and raising the nose, especially during takeoff and landing. Loading in a tail-heavy condition has a serious effect upon longitudinal stability and reduces the capability to recover from stalls and spins. Tail-heavy loading also produces very light control forces, another undesirable characteristic. This makes it easy for the pilot to inadvertently overstress an aircraft. It is important to reevaluate the balance in a rotorcraft whenever loading changes. In most aircraft, offloading a passenger is unlikely to adversely affect the CG, but offloading a passenger from a rotorcraft can create an unsafe flight condition. An out-of-balance loading condition also decreases maneuverability, since cyclic control is less effective in the direction opposite to the CG location. Limits for the location of the CG are established by the manufacturer. There are the fore and aft limitations beyond which the CG should not be located for flight. These limits are published for each aircraft in the Type Certificate Data Sheet, TCDS, or Aircraft Specification, and the AFM, or Pilot's Operating Handbook, POH. If the CG is not within the allowable limits after loading, it will be necessary to relocate some items before flight is attempted. The forward CG limit is often established at a location that is determined by the landing characteristics of an aircraft. During landing, one of the most critical phases of flight, exceeding the forward CG limit may result in excessive loads on the nose wheel, a tendency to nose over on tailwheel type airplanes, decreased performance, higher stalling speeds, and higher control forces. Control. In extreme cases, a CG location that is beyond the forward limit may result in nose heaviness, making it difficult or impossible to flare for landing. Manufacturers purposefully place the forward CG limit as far rearward as possible to aid pilots in avoiding damage when landing. In addition to decreased static and dynamic longitudinal stability, other undesirable effects caused by a CG location after the allowable range may include extreme control difficulty, violent stall characteristics, and very light control forces which make it easy to overstress an aircraft inadvertently. A restricted forward CG limit is also specified to assure that sufficient elevator control deflection is available at minimum airspeed. When structural limitations do not limit the forward CG position, it is located at the position where full-up elevator control deflection is required to obtain a high AOA for landing. The aft CG limit is the most rearward position at which the CG can be located for the most critical maneuver or operation. As the CG moves aft, a less stable condition occurs, which decreases the ability of the aircraft to right itself after maneuvering or turbulence. For some aircraft, both fore and aft CG limits may be specified to vary as gross weight changes. They may also be changed for certain operations, such as acrobatic flight, retraction of the landing gear, or the installation of special loads and devices that change the flight characteristics. The actual location of the CG can be altered by many variable factors and is usually controlled by the pilot. Placement of baggage and cargo items determines the CG location. The assignment of seats to passengers can also be used as a means of obtaining a favorable balance. If an aircraft is tail-heavy, it is only logical to place heavy passengers in forward seats. Fuel burn can also affect the CG based on the location of the fuel tanks. For example, most small aircraft carry fuel in the wings very near the CG, and burning off fuel has little effect on the loaded CG. On rotorcraft, the fuel tanks are often located behind the CG, and fuel consumption from a tank after the rotor mast causes the loaded CG to move forward. A rotorcraft in this condition has a nose-low attitude when coming to a hover following a vertical takeoff. Excessive rearward displacement of the cyclic control is needed to maintain a hover in a no-wind condition. Flight should not be continued since rearward cyclic control fades as fuel is consumed. Deceleration to a stop may also be impossible. In the event of engine failure and auto-rotation, there may not be enough cyclic control to flare properly for a landing. Management of weight and balance control. Title 14 of the Code of Federal Regulations, 14 CFR, Section 23.23, requires establishment of the ranges of weights and CGs within which an aircraft may be operated safely. The manufacturer provides this information, which is included in the approved AFM, TCDS, or aircraft specifications. While there are no specified requirements for a pilot operating under 14 CFR Part 91 to conduct weight and balance calculations prior to each flight, 14 CFR Section 91.9 requires the pilot in command, PIC, to comply with the operating limits in the approved AFM. These limits include the weight and balance of the aircraft. To enable pilots to make weight and balance computations, charts and graphs are provided in the approved AFM. Weight and balance control should be a matter of concern to all pilots. The pilot controls loading and fuel management, the two variable factors that can change both total weight and CG location of a particular aircraft. The aircraft owner or operator should make certain that up-to-date information is available for pilot use and should ensure that appropriate entries are made in the records when repairs or modifications have been accomplished. The removal or addition of equipment results in changes to the CG. Weight changes must be accounted for, and the proper notations made in weight and balance records. The equipment list must be updated if appropriate. Without such information, the pilot has no foundation upon which to base the necessary calculations and decisions. Standard parts with negligible weight or the addition of minor items of equipment such as nuts, bolts, washers, rivets, and similar standard parts of negligible weight on fixed-wing aircraft do not require a weight and balance check. Rotorcraft are, in general, more critical with respect to control with changes in CG position. The following criteria for negligible weight change is outlined in Advisory Circular AC 43.13-1 as revised. Methods, Techniques, and Practices. Aircraft Inspection and Repair. 1 pound or less for an aircraft whose weight empty is less than 5,000 pounds. 2 pounds or less for an aircraft with an empty weight of more than 5,000 pounds to 50,000 pounds. And 5 pounds or less for aircraft with an empty weight of more than 50,000 pounds. Negligible CG change is any change of less than 0.05% mean aerodynamic chord, MAC, for fixed-wing aircraft, 0.2% of the maximum allowable CG range for rotorcraft. Exceeding these limits would require a weight and balance check. Before any flight, the pilot should determine the weight and balance condition of the aircraft. Simple and orderly procedures based on sound principles have been devised by the manufacturer for the determination of loading conditions. The pilot uses these procedures and exercises good judgment when determining weight and balance. In many modern aircraft, it is not possible to fill all seats, baggage compartments, and fuel tanks and still remain within the approved weight and balance limits. If the maximum passenger load is carried, the pilot must often reduce the fuel load or reduce the amount of baggage. 14 CFR Part 125 requires aircraft with 20 or more seats or weighing 6,000 pounds or more to be weighed every 36 calendar months. Multi-engine aircraft operated under a 14 CFR Part 135 are also required to be weighed every 36 months. Aircraft operated under 14 CFR Part 135 are exempt from the 36-month requirement if operated under a weight and balance system approved in the operation specifications of the certificate holder. AC 43.13-1, Acceptable Methods, Techniques, and Practices, Aircraft Inspection and Repair, also requires that the aircraft mechanic must ensure the weight and balance data in the aircraft records is current and accurate after a 100-hour or annual inspection. Terms and definitions. The pilot should be familiar with terms used in working problems related to weight and balance. The following list of terms and their definitions is standardized, and knowledge of these terms aids the pilot to better understand weight and balance calculations of any aircraft. Terms defined by the General Aviation Manufacturers Association, GAMA, as industry standard are marked in the titles with GAMA. Arm, moment arm. The horizontal distance in inches from the reference datum line to the CG of an item. The algebraic sign is plus if measured after the datum, and minus if measured forward of the datum. Basic empty weight, GAMA. The standard empty weight plus the weight of optional and special equipment that have been installed. Center of gravity, CG. The point about which an aircraft would balance if it were possible to suspend it at that point. It is the mass center of the aircraft, or the theoretical point at which the entire weight of the aircraft is assumed to be concentrated. It may be expressed in inches from the reference datum or in percent of MAC. The CG is a three-dimensional point with longitudinal, lateral, and vertical positioning in the aircraft. CG limits. The specified forward and aft points within which the CG must be located during flight. These limits are indicated on pertinent aircraft specifications. CG range. The distance between the forward and aft CG limits indicated on pertinent aircraft specifications. Datum. Reference datum. An imaginary vertical plane or line from which all measurements of arm are taken. The datum is established by the manufacturer. Once the datum has been selected, all moment arms and the location of CG range are measured from this point. Delta. A Greek letter expressed by the symbol delta to indicate a change of values. As an example, delta CG indicates a change or movement of the CG. Floor load limit. The maximum weight the floor can sustain per square inch or foot as provided by the manufacturer. Fuel load. The expendable part of the load of the aircraft. It includes only usable fuel, not fuel required to fill the lines or that which remains trapped in the tank's sumps. Licensed empty weight. The empty weight that consists of the airframe, engine or engines, unusable fuel, and undrainable oil, plus standard and optional equipment as specified in the equipment list. Some manufacturers use this term prior to GAMA standardization. Maximum landing weight. The greatest weight that an aircraft normally is allowed to have at landing. Maximum ramp weight. The total weight of a loaded aircraft and includes all fuel. It is greater than the takeoff weight due to the fuel that will be burned during the taxi and run-up operations. Ramp weight may also be referred to as taxi weight. Maximum takeoff weight. The maximum allowable weight for takeoff. Maximum weight. The maximum authorized weight of the aircraft and all of its equipment as specified in the TCDS for the aircraft. Maximum zero fuel weight, GAMA. The maximum weight exclusive of usable fuel. Mean aerodynamic chord, MAC. The average distance from the leading edge to the trailing edge of the wing. Moment. The product of the weight of an item multiplied by its arm. Moments are expressed in pound-inches, or inch-pounds. Total moment is the weight of the airplane multiplied by the distance between the datum and the CG. Moment index, or index. A moment divided by a constant such as 100, 1,000, or 10,000. The purpose of using a moment index is to simplify weight and balance computations of aircraft where heavy items and long arms result in large, unmanageable numbers. Payload, GAMA. The weight of occupants, cargo, and baggage. Standard empty weight, GAMA. Aircraft weight that consists of the airframe, engines, and all items of operating equipment that have fixed locations and are permanently installed in the aircraft, including fixed ballast, hydraulic fluid, unusable fuel, and full engine oil. Standard weights. Established weights for numerous items involved in weight and balance computations. These weights should not be used if actual weights are available. Some of the standard weights are gasoline, 6 pounds per U.S. gallon. Jet A, Jet A1, 6.8 pounds per U.S. gallon. Jet B, 6.5 pounds per U.S. gallon. Oil, 7.5 pounds per U.S. gallon. And water, 8.35 pounds per U.S. gallon. Station. A location in the aircraft that is identified by a number designating its distance in inches from the datum. The datum is therefore identified as station 0. An item located at station plus 50 would have an arm of 50 inches. Useful load. The weight of the pilot, co-pilot, passengers, baggage, usable fuel, and drainable oil. It is the basic empty weight subtracted from the maximum allowable gross weight. This term applies to general aviation, GA aircraft only. End of Part 1 of Chapter 9. Part 2 of Chapter 9 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 9, Weight and Balance. Principles of Weight and Balance Computations. It might be advantageous at this point to review and discuss some of the basic principles of weight and balance determination. The following method of computation can be applied to any object or vehicle for which weight and balance information is essential. By determining the weight of the empty aircraft and adding the weight of everything loaded on the aircraft, a total weight can be determined. A simple concept. A greater problem, particularly if the basic principles of weight and balance are not understood, is distributing this weight in such a manner that the entire mass of the loaded aircraft is balanced around a point, CG, that must be located within specified limits. The point at which an aircraft balances can be determined by locating the CG, which is, as stated in the definition of terms, the imaginary point at which all the weight is concentrated. To provide the necessary balance between longitudinal stability and elevator control, the CG is usually located slightly forward of the center of lift. This loading condition causes a nose-down tendency in flight, which is desirable during flight at high AOA and slow speeds. As mentioned earlier, a safe zone within which the balance point, CG, must fall is called the CG range. The extremities of the range are called the forward CG limits and aft CG limits. These limits are usually specified in inches along the longitudinal axis of the airplane, measured from a reference point called a datum reference. The datum is an arbitrary point established by aircraft designers, which may vary in location between different aircraft. Refer to Figure 9-2. The distance from the datum to any component part or any object loaded on the aircraft is called the arm. When the object or component is located after the datum, it is measured in positive inches. If located forward of the datum, it is measured as negative inches or minus inches. The location of the object or part is often referred to as the station. If the weight of any object or component is multiplied by the distance from the datum, arm, the product is the moment. The moment is the measurement of the gravitational force that causes a tendency of the weight to rotate about a point or axis and is expressed in inch-pounds. To illustrate, assume a weight of 50 pounds is placed on the board at a station or point 100 inches from the datum. The downward force of the weight can be determined by multiplying 50 pounds by 100 inches, which produces a moment of 5,000 inch-pounds. Refer to Figure 9-3. To establish a balance, a total of 5,000 inch-pounds must be applied to the other end of the board. Any combination of weight and distance which, when multiplied, produces a 5,000 inch-pound moment will balance the board. For example, illustrated in Figure 9-4, if a 100-pound weight is placed at a point or station 25 inches from the datum, and another 50-pound weight is placed at a point or station 50 inches from the datum, the sum of the product of the two weights and their distances will total a moment of 5,000 inch-pounds, which will balance the board. Weight and balance restrictions. An aircraft's weight and balance restrictions should be closely followed. The loading conditions and empty weight of a particular aircraft may differ from that found in the AFM/POH, because modifications or equipment changes may have been made. Sample loading problems in the AFM/POH are intended for guidance only. Therefore, each aircraft must be treated separately. Although an aircraft is certified for a specified maximum gross takeoff weight, it will not safely take off with this load under all conditions. Conditions that affect takeoff and climb performance, such as high elevations, high temperatures, and high humidity, high-density altitudes, may require a reduction in weight before flight is attempted. Other factors to consider prior to takeoff are runway length, runway surface, runway slope, surface wind, and the presence of obstacles. These factors may require a reduction in weight prior to flight. Some aircraft are designed so that it is difficult to load them in a manner that will place the CG out of limits. These are usually small aircraft with the seats, fuel, and baggage areas located near the CG limit. Pilots must be aware that while within CG limits, these aircraft can be overloaded in weight. Other aircraft can be loaded in such a manner that they will be out of CG limits, even though the useful load has not been exceeded. Because of the effects of an out-of-balance or overweight condition, a pilot should always be sure that an aircraft is properly loaded. Determining loaded weight in CG. There are various methods for determining the loaded weight in CG of an aircraft. There is the computational method, as well as methods that utilize graphs and tables provided by the aircraft manufacturer. Computational method. The following is an example of the computational method involving the application of basic math functions. Aircraft allowances. Maximum gross weight, 3,400 pounds. CG range, 78 to 86 inches. Given: weight of the front seat occupants, 340 pounds. Weight of rear seat occupants, 350 pounds. Fuel, 75 gallons. Weight of baggage in Area 1, 80 pounds. 1. List the weight of the aircraft, occupants, fuel, and baggage. Remember that aviation gas, avgas, weighs 6 pounds per gallon and is used in this example. 2. Enter the moment for each item listed. Remember, weight times arm equals moment. 3. Find the total weight and total moment. 4. To determine the CG, divide the total moment by the total weight. Note: the weight and balance records for a particular aircraft will provide the empty weight and moment, as well as the information on the arm distance. Refer to Figure 9-5. The total loaded weight of 3,320 pounds does not exceed the maximum gross weight of 3,400 pounds, and the CG of 84.8 is within the 78 to 86 inch range. Therefore, the aircraft is loaded within limits. Graph method. Another method for determining the loaded weight in CG is the use of graphs provided by the manufacturers. To simplify calculations, the moment may sometimes be divided by 100, 1,000, or 10,000. Refer to Figures 9-6, 9-7, and 9-8. Front seat occupants, 340 pounds. Rear seat occupants, 300 pounds. Fuel, 40 gallons. Baggage area 1, 20 pounds. The same steps should be followed as in the computational method, except the graphs provided will calculate the moments and allow the pilot to determine if the aircraft is loaded within limits. To determine the moment using the loading graph, find the weight and draw a line straight across until it intercepts the item for which the moment is to be calculated. Then draw a line straight down to determine the moment. The red line on the loading graph represents the moment for the pilot and front passenger. All other moments were determined in the same way. Once this has been done for each item, total the weight and moments and draw a line for both weight and moment on the CG envelope graph. If the lines intersect within the envelope, the aircraft is loaded within limits. In this sample loading problem, the aircraft is loaded within limits. Table method. The table method applies the same principles as the computational and graph methods. The information and limitations are contained in tables provided by the manufacturer. Figure 9-9 is an example of a table and a weight and balance calculation based on that table. In this problem, the total weight of 2,799 pounds and moment of 2,278 divided by 100 are within limits of the table. Computations with a negative arm. Figure 9-10 is a sample of weight and balance computation using an airplane with a negative arm. It is important to remember that a positive times a negative equals a negative, and a negative would be subtracted from the total moments. Computations with zero fuel weight. Figure 9-11 is a sample of weight and balance computation using an aircraft with a zero fuel weight. In this example, the total weight of the aircraft less fuel is 4,240 pounds, which is under the zero fuel weight of 4,400 pounds. If the total weight of the aircraft without fuel had exceeded 4,400 pounds, passengers or cargo would have needed to be reduced to bring the weight at or below the max zero fuel weight. Shifting, adding, and removing weight. A pilot must be able to solve any problems accurately that involve the shift, addition, or removal of weight. For example, the pilot may load the aircraft within the allowable takeoff weight limit, then find a CG limit has been exceeded. The most satisfactory solution to this problem is to shift baggage, passengers, or both. The pilot should be able to determine the minimum load shift needed to make the aircraft safe for flight. Pilots should be able to determine if shifting a load to a new location will correct an out-of-limit condition. There are some standardized calculations that can help make these determinations. Weight shifting. When weight is shifted from one location to another, the total weight of the aircraft is unchanged. The total moments, however, do change in relation and proportion to the direction and distance the weight is moved. When weight is moved forward, the total moments decrease. When weight is moved aft, total moments increase. The moment change is proportional to the amount of weight moved. Since many aircraft have forward and aft baggage compartments, weight may be shifted from one to the other to change the CG. If starting with a known aircraft weight, CG, and total moments, calculate the new CG after the weight shift by dividing the new total moments by the total aircraft weight. To determine the new total moments, find out how many moments are gained or lost when the weight is shifted. Assume that 100 pounds has been shifted from station 30 to station 150. This movement increases the total moments of the aircraft by 12,000 inch-pounds. Moment when at station 150 equals 100 pounds times 150 inches equals 15,000 inch-pounds. Moment when at station 30 equals 100 pounds times 30 inches equals 3,000 inch-pounds. The moment change is equal to 15,000 minus 3,000 equals 12,000 inch-pounds. By adding the moment change to the original moment, or subtracting if the weight had been moved forward instead of aft, the new total moments are obtained. Then determine the new CG by dividing the new moments by the total weight. Total moment equals 616,000 inch-pounds plus 12,000 inch-pounds equals 628,000 inch-pounds. CG is equal to 628,000 inch-pounds divided by 8,000 pounds equals 78.5 inches. The shift has caused the CG to shift to station 78.5. A simpler solution may be obtained by using a computer or a calculator and a proportional formula. This can be done because the CG will shift a distance that is proportional to the distance the weight is shifted. Example: weight shifted divided by total weight equals delta CG, or change of CG, divided by the distance weight is shifted. 100 divided by 8,000 equals delta CG divided by 120. The delta CG is equal to 1.5 inches. The change of CG is added or subtracted from, when appropriate, the original CG to determine the new CG. 77 plus 1.5 equals 78.5 inches aft of datum. The shifting weight proportion formula can also be used to determine how much weight must be shifted to achieve a particular shift of the CG. The following problem illustrates a solution of this type. Example. Given aircraft total weight 7,800 pounds, CG station 81.5 inches, aft CG limit 80.5 inches. Determine how much cargo must be shifted from the aft cargo compartment at station 150 to the forward cargo compartment at station 30 to move the CG to exactly the aft limit. The solution, the weight to be shifted divided by the total weight equals delta CG divided by the distance weight is shifted. So, weight to be shifted divided by 7,800 pounds equals 1.0 inches divided by 120 inches. The weight to be shifted equals 65 pounds. Weight addition or removal. In many instances, the weight and balance of the aircraft will be changed by the addition or removal of weight. When this happens, a new CG must be calculated and checked against the limitations to see if the location is acceptable. This type of weight and balance problem is commonly encountered when the aircraft burns fuel in flight, thereby reducing the weight located at the fuel tanks. Most small aircraft are designed with the fuel tanks positioned close to the CG. Therefore, the consumption of fuel does not affect the CG to any great extent. The addition or removal of cargo presents a CG change problem that must be calculated before flight. The problem may always be solved by calculations involving total moments. A typical problem may involve the calculation of a new CG for an aircraft which, when loaded and ready for flight, receives some additional cargo or passengers just before departure time. Example. Given an aircraft total weight of 6,860 pounds, CG station 80.0 inches. Determine the location of the CG if 140 pounds of baggage is added to station 150. Solution. Added weight divided by the new total weight is equal to the delta CG divided by the distance between the weight and old CG. 140 pounds divided by 6,860 pounds plus 140 pounds is equal to delta CG divided by 150 inches minus 80 inches. 140 pounds divided by 7,000 pounds equals delta CG divided by 70 inches. The CG is equal to 1.4 inches aft. Add the delta CG to the old CG. The new CG is equal to 80 inches plus 1.4 inches, which is equal to 81.4 inches. Example. Given an aircraft total weight of 6,100 pounds, CG station of 80.0 inches. Determine the location of the CG if 100 pounds is removed from station 150. Solution. Weight removed divided by the new total weight equals delta CG divided by the distance between the weight and the old CG. So 100 pounds divided by 6,100 pounds minus 100 pounds equals delta CG divided by 150 inches minus 80 inches. 100 pounds divided by 6,000 pounds is equal to delta CG over 70 inches. And the CG is equal to 1.2 inches forward. Subtract delta CG from the old CG. The new CG is equal to 80 inches minus 1.2 inches equals 78.8 inches. In the previous examples, the delta CG is either added or subtracted from the old CG. Deciding which to accomplish is best handled by mentally calculating which way the CG will shift for the particular weight change. If the CG is shifting aft, the delta CG is added to the old CG. If the CG is shifting forward, the delta CG is subtracted from the old CG. Chapter Summary. Operating an aircraft within the weight and balance limits is critical to flight safety. Pilots must ensure that the CG is and remains within approved limits for all phases of a flight. Additional information on weight, balance, CG, and aircraft stability can be found in FAA-H-8083-1, Aircraft Weight and Balance Handbook. Those pilots flying helicopters or gyroplanes should consult the Rotorcraft Flying Handbook, FAA-H-8083-21, for specific information relating to aircraft type. End of Part 2 of Chapter 9. Part 1 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 1 of Chapter 10, Aircraft Performance. Introduction. This chapter discusses the factors that affect aircraft performance, which include the aircraft weight, atmospheric conditions, runway environment, and the fundamental physical laws governing the forces acting on an aircraft. Importance of performance data. The Performance or Operational Information section of the Aircraft Flight Manual / Pilot's Operating Handbook, AFM / POH, contains the operating data for the aircraft. That is, the data pertaining to takeoff, climb, range, endurance, descent, and landing. The use of this data in flying operations is mandatory for safe and efficient operation. Considerable knowledge and familiarity of the aircraft can be gained through study of this material. It must be emphasized that the manufacturer's information and data furnished in the AFM / POH is not standardized. Some provide the data in tabular form, while others use graphs. In addition, the performance data may be presented on the basis of standard atmospheric conditions, pressure altitude, or density altitude. The performance information in the AFM / POH has little or no value unless the user recognizes those variations and makes the necessary adjustments. To be able to make practical use of the aircraft's capabilities and limitations, it is essential to understand the significance of the operational data. The pilot must be cognizant of the basis for the performance data, as well as the meanings of the various terms used in expressing performance capabilities and limitations. Since the characteristics of the atmosphere have a major effect on performance, it is necessary to review the two dominant factors, pressure and temperature. Structure of the atmosphere. The atmosphere is an envelope of air that surrounds the Earth and rests upon its surface. It is as much a part of the Earth as its land and water. However, air differs from land and water inasmuch as it is a mixture of gases. It has mass, weight, and indefinite shape. Air, like any other fluid, is able to flow and change its shape when subjected to even minute pressures because of the lack of strong molecular cohesion. For example, gas will completely fill any container into which it is placed, expanding or contracting to adjust its shape to the limits of the container. The atmosphere is composed of 78% nitrogen, 21% oxygen, and 1% other gases, such as argon or helium. Most of the oxygen is contained below 35,000 feet altitude. Atmospheric pressure. Though there are various kinds of pressure, pilots are mainly concerned with atmospheric pressure. It is one of the basic factors in weather changes, helps to lift the aircraft, and actuates some of the most important flight instruments in the aircraft. These instruments often include the altimeter, the airspeed indicator, ASI, the vertical speed indicator, and the manifold pressure gauge. Though air is very light, it has mass and is affected by the attraction of gravity. Therefore, like any other substance, it has weight. Because it has weight, it has force. Since it is a fluid substance, this force is exerted equally in all directions, and its effect on bodies within the air is called pressure. Under standard conditions at sea level, the average pressure exerted by the weight of the atmosphere is approximately 14.7 pounds per square inch, psi. The density of air has significant effects on the aircraft's performance. As air becomes less dense, it reduces power because the engine takes in less air, thrust because the propeller is less efficient in thin air, lift because the thin air exerts less force on the airfoils. The pressure of the atmosphere varies with time and altitude. Due to the changing atmospheric pressure, a standard reference was developed. The standard atmosphere at sea level is a surface temperature of 59 degrees Fahrenheit, degrees F, or 15 degrees Celsius, degrees C, and a surface pressure of 29.92 inches of mercury, inches Hg, or 1013.2 millibars, MB. Refer to Figure 10-1. A standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet up to 36,000 feet. Above this point, the temperature is considered constant up to 80,000 feet. A standard pressure lapse rate is one in which pressure decreases at a rate of approximately 1 inch mercury per 1,000 feet of altitude gain to 10,000 feet. Refer to Figure 10-2. The International Civil Aviation Organization, ICAO, has established this as a worldwide standard, and it is often referred to as International Standard Atmosphere, ISA, or ICAO Standard Atmosphere. Any temperature or pressure that differs from the standard lapse rates is considered non-standard temperature and pressure. Adjustments for non-standard temperatures and pressures are provided on the manufacturer's performance charts. Since all aircraft performance is compared and evaluated with respect to the standard atmosphere, all aircraft instruments are calibrated for the standard atmosphere. Thus, certain corrections must apply to the instrumentation as well as aircraft performance if the actual operating conditions do not fit the standard atmosphere. In order to account properly for the non-standard atmosphere, certain related terms must be defined. Pressure altitude. Pressure altitude is the height above the standard datum plane, SDP. The aircraft altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 inches of mercury SDP, the altitude indicated is the pressure altitude, the altitude in the standard atmosphere corresponding to the sensed pressure. The SDP is a theoretical level where the pressure of the atmosphere is 29.92 inches of mercury and the weight of air is 14.7 psi. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis for determining aircraft performance, as well as for assigning flight levels to aircraft operating at above 18,000 feet. The pressure altitude can be determined by any of three methods. 1. By setting the barometric scale of the altimeter to 29.92 inches of mercury and reading the indicated altitude. Or 2. By applying a correction factor to the indicated altitude according to the reported altimeter setting. See Figure 10-3. Or 3. By using a flight computer. Density altitude. The more appropriate term for correlating aerodynamic performance in the non-standard atmosphere is density altitude, the altitude in the standard atmosphere corresponding to a particular value of air density. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude. An increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance. Under standard atmospheric condition, air at each level in the atmosphere has a specific density. Under standard conditions, pressure altitude and density altitude identify the same level. Density altitude, then, is the vertical distance above sea level in the standard atmosphere at which a given density is to be found. The computation of density altitude must involve consideration of pressure altitude, and temperature. Since aircraft performance data at any level is based upon air density under standard day conditions, such performance data apply to air density levels that may not be identical to altimeter indications. Under conditions higher or lower than standard, these levels cannot be determined directly from the altimeter. Density altitude is determined by first finding pressure altitude and then correcting this altitude for non-standard temperature variations. Since density varies directly with pressure and inversely with temperature, a given pressure altitude may exist for a wide range of temperature by allowing the density to vary. However, a known density occurs for any one temperature and pressure altitude. The density of the air, of course, has a pronounced effect on aircraft and engine performance. Regardless of the actual altitude at which the aircraft is operating, it will perform as though it were operating at an altitude equal to the existing density altitude. For example, when set at 29.92 inches of mercury, the altimeter may indicate a pressure altitude of 5,000 feet. According to the AFM/POH, the ground run on takeoff may require a distance of 790 feet under standard temperature conditions. However, if the temperature is 20 degrees Celsius above standard, the expansion of air raises the density level. Using temperature correction data from tables or graphs or by deriving the density altitude with a computer, it may be found that the density level is above 7,000 feet, and the ground run may be closer to 1,000 feet. Air density is affected by changes in altitude, temperature, and humidity. High-density altitude refers to thin air, while low-density altitude refers to dense air. The conditions that result in high-density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low-density altitude. Using a flight computer, density altitude can be computed by inputting the pressure altitude and outside air temperature at flight level. Density altitude can also be determined by referring to the table and chart in figures 10-3 and 10-4. Effects of pressure on density. Since air is a gas, it can be compressed or expanded. When air is compressed, a greater amount of air can occupy a given volume. Conversely, when pressure on a given volume of air is decreased, the air expands and occupies a greater space. That is, the original column of air at a lower pressure contains a smaller mass of air. In other words, the density is decreased. In fact, density is directly proportional to pressure. If the pressure is doubled, the density is doubled, and if the pressure is lowered, so is the density. This statement is true only at a constant temperature. Effects of temperature on density. Increasing the temperature of a substance decreases its density. Conversely, decreasing the temperature increases the density. Thus, the density of air varies inversely with temperature. This statement is true only at a constant pressure. In the atmosphere, both temperature and pressure decrease with altitude and have conflicting effects upon density. However, the fairly rapid drop in pressure as altitude is increased usually has the dominant effect. Hence, pilots can expect the density to decrease with altitude. Effects of humidity, moisture, on density. The preceding paragraphs are based on the presupposition of perfectly dry air. In reality, it is never completely dry. The small amount of water vapor suspended in the atmosphere may be negligible under certain conditions, but in other conditions humidity may become an important factor in the performance of an aircraft. water vapor is lighter than air. Consequently, moist air is lighter than dry air. Therefore, as the water content of the air increases, the air becomes less dense, increasing density altitude and decreasing performance. It is lightest or least dense when, in a given set of conditions, it contains the maximum amount of water vapor. Humidity, also called relative humidity, refers to the amount of water vapor contained in the atmosphere and is expressed as a percentage of the maximum amount of water vapor the air can hold. This amount varies with the temperature. Warm air can hold more water vapor, while colder air can hold less. Perfectly dry air that contains no water vapor has a relative humidity of 0%, while saturated air that cannot hold any more water vapor has a relative humidity of 100%. Humidity alone is usually not considered an essential factor in calculating density altitude and aircraft performance. However, it does contribute. The higher the temperature, the greater amount of water vapor the air can hold. When comparing two separate air masses, the first warm and moist, both qualities making air lighter, and the second cold and dry, both qualities making it heavier, the first must be less dense than the second. Pressure, temperature, and humidity have a great influence on aircraft performance because of their effect upon density. There is no rule of thumb or chart used to compute the effects of humidity on density altitude, but it must be taken into consideration. Expect a decrease in overall performance in high humidity conditions. End of Part 1 of Chapter 10. Part 2 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 10. Aircraft Performance. Performance. Performance is a term used to describe the ability of an aircraft to accomplish certain things that make it useful for certain purposes. For example, the ability of an aircraft to land and take off in a very short distance is an important factor to the pilot who operates in and out of short, unimproved airfields. The ability to carry heavy loads, fly at high altitudes at fast speeds, or travel long distances is essential performance for operators of airline and executive-type aircraft. The primary factors most affected by performance are the takeoff and landing distance, rate of climb, ceiling, payload, range, speed, maneuverability, stability, and fuel economy. Some of these factors are often directly opposed, for example, high speed versus short landing distance, long range versus great payload, and high rate of climb versus fuel economy. It is the preeminence of one or more of these factors that dictates differences between aircraft and explains the high degree of specialization found in modern aircraft. The various items of aircraft performance result from the combination of aircraft and power plant characteristics. The aerodynamic characteristics of the aircraft generally define the power and thrust requirements at various conditions of flight, while power plant characteristics generally define the power and thrust available at various conditions of flight. The matching of the aerodynamic configuration with the power plant is accomplished by the manufacturer to provide maximum performance at the specific design condition, e.g. range, endurance, and climb. Straight and level flight. All of the principal components of flight performance involve steady-state flight conditions and equilibrium of the aircraft. For the aircraft to remain in steady level flight, equilibrium must be obtained by a lift equal to the aircraft weight and a power plant thrust equal to the aircraft drag. Thus, the aircraft drag defines the thrust required to maintain steady level flight. As presented in Chapter 4, Aerodynamics of Flight, all parts of an aircraft contribute to the drag, either induced from lifting surfaces or parasite drag. While the parasite drag predominates at high speed, induced drag predominates at low speed. Refer to Figure 10-5. For example, If an aircraft in a steady flight condition at 100 knots is then accelerated to 200 knots, the parasite drag becomes 4 times as great, but the power required to overcome that drag is 8 times the original value. Conversely, when the aircraft is operated in steady level flight at twice as great a speed, the induced drag is 1/4 the original value, and the power required to overcome that drag is only 1/2 the original value. When an aircraft is in steady level flight, the condition of equilibrium must prevail. The unaccelerated condition of flight is achieved with the aircraft trimmed for lift equal to weight and the power plant set for a thrust equal to the aircraft drag. The maximum level flight speed for the aircraft will be obtained when the power or thrust required equals the maximum power or thrust available from the power plant. Refer to Figure 10-6. The minimum level flight airspeed is not usually defined by thrust or power requirements, since conditions of stall or stability and control problems generally predominate. Climb performance. Climb performance is a result of using the aircraft's potential energy provided by one or a combination of 2 factors. The first is the use of excess power above that required for level flight. An aircraft equipped with an engine capable of 200 horsepower at a given altitude, but using 130 horsepower to sustain level flight at a given airspeed, has 70 excess horsepower available for climbing. A second factor is that the aircraft can trade off its kinetic energy and increase its potential energy by reducing its airspeed. The reduction in airspeed will increase the aircraft's potential energy, thereby also making the aircraft climb. Both terms, power and thrust, are often used in aircraft performance. However, they should not be confused. Although the terms power and thrust are sometimes used interchangeably, erroneously implying that they are synonymous, it is important to distinguish between the two when discussing climb performance. Work is the product of a force moving through a distance, and is usually independent of time. Work is measured by several standards. The most common unit is called a foot-pound. If 1 pound mass is raised 1 foot, a work unit of 1 foot-pound has been performed. The common unit of mechanical power is horsepower. 1 horsepower is work equivalent to lifting 33,000 pounds a vertical distance of 1 foot in 1 minute. The term power implies work rate, or units of work per unit of time, and as such is a function of the speed at which the force is developed. Thrust, also a function of work, means the force that imparts a change in the velocity of a mass. This force is measured in pounds but has no element of time or rate. It can be said, then, that during steady climb, the rate of climb is a function of excess thrust. This relationship means that, for a given weight of an aircraft, the angle of climb depends on the difference between the thrust and drag, or the excess power. Refer to Figure 10-7. Of course, when the excess thrust is 0, the inclination of the flight path is 0, and the aircraft will be in steady level flight. When thrust is greater than the drag, the excess thrust will allow a climb angle depending on the value of excess thrust. On the other hand, when the thrust is less than the drag, the deficiency of thrust will allow an angle of descent. The most immediate interest in the climb angle performance involves obstacle clearance. The most obvious purpose for which it might be used is to clear obstacles when climbing out of short or confined airports. The maximum angle of climb would occur where there exists the greatest difference between thrust available and thrust required, i.e., for the propeller-powered airplane, the maximum excess thrust and angle of climb will occur at some speed just above the stall speed. Thus, if it is necessary to clear an obstacle after takeoff, the propeller-powered airplane will attain maximum angle of climb at an airspeed close to, if not at, the takeoff speed. Of greater interest in climb performance are the factors that affect the rate of climb. The vertical velocity of an aircraft depends on the flight speed and the inclination of the flight path. In fact, the rate of climb is the vertical component of the flight path velocity. For rate of climb, the maximum rate would occur where there exists the greatest difference between power available and power required. Refer to Figure 10-8. The above relationship means that for a given weight of an aircraft, the rate of climb depends on the difference between the power available and the power required, or the excess power. Of course, when the excess power is zero, the rate of climb is zero and the aircraft is in steady level flight. When power available is greater than the power required, the excess power will allow a rate of climb specific to the magnitude of excess power. During a steady climb, the rate of climb will depend on excess power, while the angle of climb is a function of excess thrust. The climb performance of an aircraft is affected by certain variables. The conditions of the aircraft's maximum climb angle or maximum climb rate occur at specific speeds, and variations in speed will produce variations in climb performance. There is sufficient latitude in most aircraft that small variations in speed from the optimum do not produce large changes in climb performance, and certain operational considerations may require speeds slightly different from the optimum. Of course, climb performance would be most critical with high gross weight, at high altitude, in obstructed takeoff areas, or during malfunction of a power plant. Then optimum climb speeds are necessary. Weight has a very pronounced effect on aircraft performance. If weight is added to an aircraft, it must fly at a higher angle of attack, AOA, to maintain a given altitude and speed. This increases the induced drag of the wings as well as the parasite drag of the aircraft. Increased drag means that additional thrust is needed to overcome it, which in turn means that less reserve thrust is available for climbing. Aircraft designers go to great effort to minimize the weight since it has such a marked effect on the factors pertaining to performance. A change in an aircraft's weight produces a twofold effect on climb performance. First, a change in weight will change the drag and the power required. This alters the reserve power available, which in turn affects both the climb angle and the climb rate. Secondly, an increase in weight will reduce the maximum rate of climb, but the aircraft must be operated at a higher climb speed to achieve the smaller peak climb rate. An increase in altitude also will increase the power required and decrease the power available. Therefore, the climb performance of an aircraft diminishes with altitude. The speeds for maximum rate of climb, maximum angle of climb, and maximum and minimum level flight airspeeds vary with altitude. As altitude is increased, these various speeds finally converge at the absolute ceiling of the aircraft. At the absolute ceiling, there is no excess of power, and only one speed will allow steady level flight. Consequently, the absolute ceiling of an aircraft produces zero rate of climb. The service ceiling is the altitude at which an aircraft is unable to climb at a rate greater than 100 feet per minute, FPM. Usually, these specific performance reference points are provided for the aircraft at a specific design consideration. Refer to Figure 10-9. In discussing performance, it frequently is convenient to use the terms power loading, wing loading, blade loading, and disc loading. Power loading is expressed in pounds per horsepower and is obtained by dividing the total weight of the aircraft by the rated horsepower of the engine. It is a significant factor in an aircraft's takeoff and climb capabilities. Wing loading is expressed in pounds per square foot and is obtained by dividing the total weight of an airplane in pounds by the wing area, including ailerons, in square feet. It is the airplane's wing loading that determines the landing speed. Blade loading is expressed in pounds per square foot and is obtained by dividing the total weight of a helicopter by the area of the rotor blades. Blade loading is not to be confused with disc loading, which is the total weight of a helicopter divided by the area of the disc swept by the rotor blades. Range performance. The ability of an aircraft to convert fuel energy into flying distance is one of the most important items of aircraft performance. In flying operations, the problem of efficient range operation of an aircraft appears in two general forms. 1. To extract the maximum flying distance from a given fuel load, 2. To fly a specified distance with a minimum expenditure of fuel. A common element for each of those operating problems is the specific range, that is, nautical miles, NM, of flying distance versus the amount of fuel consumed. Range must be clearly distinguished from the item of endurance. Range involves consideration of flying distance, while endurance involves consideration of flying time. Thus, it is appropriate to define a separate term, specific endurance. Specific endurance equals flight hours divided by pounds of fuel, or specific endurance equals flight hours per hour divided by pounds of fuel per hour, or specific endurance equals 1 divided by the fuel flow. Fuel flow can be defined in either pounds or gallons. If maximum endurance is desired, the flight condition must provide a minimal fuel flow. In Figure 10-10, at point A, the airspeed is low and the fuel flow is high. This would occur during ground operations or when taking off and climbing. As airspeed is increased, power requirements decrease due to aerodynamic factors, and fuel flow decreases to point B. This is the point of maximum endurance. Beyond this point, increases in airspeed come at a cost. Airspeed increases require additional power, and fuel flow increases with additional power. Cruise flight operations for maximum range should be conducted so that the aircraft obtains maximum specific range throughout the flight. The specific range can be defined by the following relationship. Specific range equals nautical miles divided by pounds of fuel, or specific range equals nautical miles per hour divided by pounds of fuel per hour, or specific range equals knots divided by fuel flow. If maximum specific range is desired, the flight condition must provide a maximum of speed per fuel flow. While the peak value of specific range would provide maximum range operation, long-range cruise operation is generally recommended at some slightly higher airspeed. Most long-range cruise operations are conducted at flight condition that provides 99% of the absolute maximum specific range. The advantage of such operation is that 1% of range is traded for 3 to 5% higher cruise speed. Since the higher cruise speed has a great number of advantages, the small sacrifice of range is a fair bargain. The values of specific range versus speed are affected by 3 principal variables. 1. Aircraft gross weight. 2. Altitude. 3. The external aerodynamic configuration of the aircraft. These are the source of range and endurance operating data included in the performance section of the AFM/POH. Cruise control of an aircraft implies that the aircraft is operated to maintain the recommended long-range cruise condition throughout the flight. Since fuel is consumed during cruise, the gross weight of the aircraft will vary, and optimum airspeed, altitude, and power setting can also vary. Cruise control means the control of the optimum airspeed, altitude, and power setting to maintain the 99% maximum specific range condition. At the beginning of cruise flight, the relatively high initial weight of the aircraft will require specific values of airspeed, altitude, and power setting to produce the recommended cruise condition. As fuel is consumed and the aircraft's gross weight decreases, the optimum airspeed and the power setting may decrease, or the optimum altitude may increase. In addition, the optimum specific range will increase. Therefore, the pilot must provide the proper cruise control procedure to ensure that optimum conditions are maintained. Total range is dependent on both fuel available and specific range. When range and economy of operation are the principal goals, the pilot must ensure that the aircraft is operated at the recommended long-range cruise condition. By this procedure, the aircraft will be capable of its maximum design operating radius, or can achieve flight distances less than the maximum with a maximum of fuel reserve at the destination. A propeller-driven aircraft combines the propeller with the reciprocating engine for propulsive power. Fuel flow is determined mainly by the shaft power put into the propeller rather than thrust. Thus, the fuel flow can be related directly to the power required to maintain the aircraft in steady level flight, and on performance charts, power can be substituted for fuel flow. This fact allows for the determination of range through analysis of power required versus speed. The maximum endurance condition would be obtained at the point of minimum power required, since this would require the lowest fuel flow to keep the airplane in steady level flight. Maximum range condition would occur where the ratio of speed to power required is greatest. Refer to Figure 10-10. The maximum range condition is obtained at maximum lift to drag ratio, L/D max, and it is important to note that for a given aircraft configuration, the L/D max occurs at a particular AOA and lift coefficient, and is unaffected by weight or altitude. A variation in weight will alter the values of airspeed and power required to obtain the L/D max. Refer to Figure 10-11. The variations of speed and power required must be monitored by the pilot as part of the cruise control procedure to maintain the L/D max. When the aircraft's fuel weight is a small part of the gross weight and the aircraft's range is small, the cruise control procedure can be simplified to essentially maintaining a constant speed and power setting throughout the time of cruise flight. However, a long-range aircraft has a fuel weight that is a considerable part of the gross weight, and cruise control procedures must employ scheduled airspeed and power changes to maintain optimum range conditions. The effective altitude on the range of a propeller-driven aircraft is illustrated in Figure 10-12. A flight conducted at high altitude has a greater true airspeed, TAS, and the power required is proportionally greater than when conducted at sea level. The drag of the aircraft at altitude is the same as the drag at sea level, but the higher TAS causes a proportionately greater power required. Note, the straight line that is tangent to the sea level power curve is also tangent to the altitude power curve. The effect of altitude on specific range also can be appreciated from the previous relationships. If a change in altitude causes identical changes in speed and power required, the proportion of speed to power required would be unchanged. The fact implies that the specific range of a propeller-driven aircraft would be unaffected by altitude. Actually, this is true to the extent that specific fuel consumption and propeller efficiency are the principal factors that could cause a variation of specific range with altitude. If compressibility effects are negligible, any variation of specific range with altitude is strictly a function of engine/propeller performance. An aircraft equipped with a reciprocating engine will experience very little, if any, variation of specific range up to its absolute altitude. There is negligible variation of brake-specific fuel consumption for values of brake horsepower below the maximum cruise power rating of the engine that is the lean range of engine operation. Thus, an increase in altitude will produce a decrease in specific range only when the increased power requirement exceeds the maximum cruise power rating of the engine. One advantage of supercharging is that cruise power may be maintained at higher altitude, and the aircraft may achieve the range at high altitude with the corresponding increase in TAS. The principal differences in the high-altitude cruise and low-altitude cruise are the TAS and climb fuel requirements. Region of reversed command. The aerodynamic properties of an aircraft generally determine the power requirements at various conditions of flight, while the power plant capabilities generally determine the power available at various conditions of flight. When an aircraft is in steady level flight, a condition of equilibrium must prevail. An unaccelerated condition of flight is achieved when lift equals weight and the power plant is set for thrust equal to drag. The power required to achieve equilibrium in constant altitude flight at various airspeeds is depicted on a power required curve. The power required curve illustrates the fact that at low airspeeds near the stall or minimum controllable airspeed, the power setting required for steady level flight is quite high. Flight in the region of normal command means that while holding a constant altitude, A higher airspeed requires a higher power setting, and a lower airspeed requires a lower power setting. The majority of aircraft flying, climb, cruise, and maneuvers, is conducted in the region of normal command. Flight in the region of reversed command means flight in which a higher airspeed requires a lower power setting, and a lower airspeed requires a higher power setting to hold altitude. It does not imply that a decrease in power will produce lower airspeed. The region of reversed command is encountered in the low-speed phases of flight. Flight speeds below the speed for maximum endurance, lowest point on the power curve, require higher power settings with a decrease in airspeed. Since the need to increase the required power setting with decreased speed is contrary to the normal command of flight, the regime of flight speeds between the speed for minimum required power setting and the stall speed, or minimum control speed, is termed the region of reversed command. In the region of reversed command, a decrease in airspeed must be accompanied by an increased power setting in order to maintain steady flight. Figure 10-13 shows the maximum power available as a curved line. Lower power settings such as cruise power would also appear in a similar curve. The lowest point on the power required curve represents the speed at which the lowest brake horsepower will sustain level flight. This is termed the best endurance airspeed. An airplane performing a low airspeed, high pitch attitude power approach for a short field landing is an example of operating in the region of reversed command. If an unacceptably high sink rate should develop, it may be possible for the pilot to reduce or stop the descent by applying power. But without further use of power, the airplane would probably stall or be incapable of flaring for the landing. Merely lowering the nose of the airplane to regain flying speed in this situation without the use of power would result in a rapid sink rate and corresponding loss of altitude. If during a soft field takeoff and climb, for example, the pilot attempts to climb out of ground effect without first attaining normal climb pitch attitude and airspeed, the airplane may inadvertently enter the region of reversed command at a dangerously low altitude. Even with full power, the airplane may be incapable of climbing or even maintaining altitude. The pilot's only recourse in this situation is to lower the pitch attitude in order to increase airspeed, which will inevitably result in a loss of altitude. Airplane pilots must give particular attention to precise control of airspeed when operating in the low flight speeds of the region of reversed command. End of Part 2 of Chapter 10. Part 3 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 3 of Chapter 10, Aircraft Performance. Takeoff and Landing Performance. The majority of pilot-caused aircraft accidents occur during the takeoff and landing phase of flight. Because of this fact, the pilot must be familiar with all the variables that influence the takeoff and landing performance of an aircraft, and must strive for exacting professional procedures of operation during these phases of flight. Takeoff and landing performance is a condition of accelerated and decelerated motion. For instance, during takeoff, an aircraft starts at 0 speed and accelerates to the takeoff speed to become airborne. During landing, the aircraft touches down at the landing speed and decelerates to 0 speed. The important factors of takeoff or landing performance are: the takeoff or landing speed is generally a function of the stall speed or minimum flying speed. The rate of acceleration/deceleration during the takeoff or landing roll. The speed, acceleration, and deceleration experienced by any object varies directly with the imbalance of force and inversely with the mass of the object. An airplane on the runway moving at 75 knots has 4 times the energy it has traveling at 37 knots. Thus, an airplane requires 4 times as much distance to stop as required at half the speed. The takeoff or landing roll distance is a function of both acceleration, slant deceleration, and speed. Runway surface and gradient. Runway conditions affect takeoff and landing performance. Typically, performance chart information assumes paved, level, smooth, and dry runway surfaces. Since no two runways are alike, the runway surface differs from one runway to another, as does the runway gradient or slope. Refer to Figure 10-14. Runway surfaces vary widely from one airport to another. The runway surface encountered may be concrete, asphalt, gravel, dirt, or grass. The runway surface for a specific airport is noted in the Airport Slant Facility Directory, A/FD. Any surface that is not hard and smooth will increase the ground roll during takeoff. This is due to the inability of the tires to roll smoothly along the runway. Tires can sink into soft, grassy, or muddy runways. Potholes or other ruts in the pavement can be the cause of poor tire movement along the runway. Obstructions such as mud, snow, or standing water reduce the airplane's acceleration down the runway. Although muddy and wet surface conditions can reduce friction between the runway and the tires, they can also act as obstructions and reduce the landing distance. Refer to Figure 10-15. Braking effectiveness is another consideration when dealing with various runway types. The condition of the surface affects the braking ability of the airplane. The amount of power that is applied to the brakes without skidding the tires is referred to as braking effectiveness. Ensure that runways are adequate in length for takeoff acceleration and landing deceleration when less than ideal surface conditions are being reported. The gradient or slope of the runway is the amount of change in runway height over the length of the runway. The gradient is expressed as a percentage, such as a 3% gradient. This means that for every 100 feet of runway length, the runway height changes by 3 feet. A positive gradient indicates the runway height increases, and a negative gradient indicates the runway decreases in height. An upsloping runway impedes acceleration and results in a longer ground run during takeoff. However, landing on an upsloping runway typically reduces the landing roll. A downsloping runway aids in acceleration on takeoff, resulting in shorter takeoff distances. The opposite is true when landing, as landing on a downsloping runway increases landing distances. Runway slope information is contained in the A/FD. Refer to Figure 10-16. Water on the runway and dynamic hydroplaning. Water on the runways reduces the friction between the tires and the ground, and can reduce braking effectiveness. The ability to brake can be completely lost when the tires are hydroplaning because a layer of water separates the tires from the runway surface. This is also true of braking effectiveness when runways are covered in ice. When the runway is wet, the pilot may be confronted with dynamic hydroplaning. Dynamic hydroplaning is a condition in which the aircraft tire rides on a thin sheet of water rather than on the runway's surface. Because hydroplaning wheels are not touching the runway, braking and directional control are almost nil. To help minimize dynamic hydroplaning, some runways are grooved to help water run off. Most runways are not. Tire pressure is a factor in dynamic hydroplaning. Using the simple formula in Figure 10-17, a pilot can calculate the minimum speed in knots at which hydroplaning will begin. In plain language, the minimum hydroplaning speed is determined by multiplying the square root of the main gear tire pressure in PSI by 9. For example, if the main gear tire pressure is at 36 PSI, the aircraft would begin hydroplaning at 54 knots. Landing at higher than recommended touchdown speeds will expose the aircraft to a greater potential for hydroplaning. And once hydroplaning starts, it can continue well below the minimum initial hydroplaning speed. On wet runways, directional control can be maximized by landing into the wind. Abrupt control input should be avoided. When the runway is wet, anticipate braking problems well before landing and be prepared for hydroplaning. Opt for a suitable runway most aligned with the wind. Mechanical braking may be ineffective, so aerodynamic braking should be used to its fullest advantage. Takeoff performance. The minimum takeoff distance is of primary interest in the operation of any aircraft because it defines the runway requirements. The minimum takeoff distance is obtained by taking off at some minimum safe speed that allows sufficient margin above stall and provides satisfactory control and initial rate of climb. Generally, the liftoff speed is some fixed percentage of the stall speed or minimum control speed for the aircraft in the takeoff configuration. As such, the liftoff will be accomplished at some particular value of lift coefficient and AOA. Depending on the aircraft characteristics, the liftoff speed will be anywhere from 1.05 to 1.25 times the stall speed or minimum control speed. To obtain minimum takeoff distance at the specific liftoff speed, the forces that act on the aircraft must provide the maximum acceleration during the takeoff roll. The various forces acting on the aircraft may or may not be under the control of the pilot, and various procedures may be necessary in certain aircraft to maintain takeoff acceleration at the highest value. The power plant thrust is the principal force to provide the acceleration, and for minimum takeoff distance, the output thrust should be at maximum. Lift and drag are produced as soon as the aircraft has speed, and the values of lift and drag depend upon the AOA and dynamic pressure. In addition to the important factors of proper procedures, many other variables affect the takeoff performance of an aircraft. Any item that alters the takeoff speed or acceleration rate during the takeoff roll will affect the takeoff distance. For example, the effect of gross weight on takeoff distance is significant, and proper consideration of this item must be made in predicting the aircraft's takeoff distance. Increased gross weight can be considered to produce a threefold effect on takeoff performance. 1. Higher liftoff speed. 2. Greater mass to accelerate. 3. Increased retarding force, drag and ground friction. If the gross weight increases, a greater speed is necessary to produce the greater lift necessary to get the aircraft airborne at the takeoff lift coefficient. As an example of the effect of a change in gross weight, a 21% increase in takeoff weight will require a 10% increase in liftoff speed to support the greater weight. A change in gross weight will change the net accelerating force and change the mass that is being accelerated. If the aircraft has a relatively high thrust-to-weight ratio, the change in the net accelerating force is slight, and the principal effect on acceleration is due to the change in mass. For example, a 10% increase in takeoff gross weight would cause a 5% increase in takeoff velocity, at least a 9% decrease in the rate of acceleration, and at least a 21% increase in takeoff distance. With ISA conditions, increasing the takeoff weight of the average Cessna 182 from 2,400 pounds to 2,700 pounds, 11% increase, results in an increased takeoff distance from 440 feet to 575 feet, 23% increase. For the aircraft with a high thrust-to-weight ratio, the increase in takeoff distance might be approximately 21 to 22%, but for the aircraft with a relatively low thrust-to-weight ratio, the increase in takeoff distance would be approximately 25 to 30%. Such a powerful effect requires proper consideration of gross weight in predicting takeoff distance. The effect of wind on takeoff distance is large, and proper consideration also must be provided when predicting takeoff distance. The effect of a headwind is to allow the aircraft to reach the liftoff speed at a lower ground speed, while the effect of a tailwind is to require the aircraft to achieve a greater ground speed to attain the liftoff speed. A headwind that is 10% of the takeoff airspeed will reduce the takeoff distance approximately 19%. However, a tailwind that is 10% of the takeoff speed will increase the takeoff distance approximately 21%. In the case where the headwind speed is 50% of the takeoff speed, the takeoff distance would be approximately 25% of the zero-wind takeoff distance, 75% reduction. The effective wind on landing distance is identical to its effect on takeoff distance. Figure 10-18 illustrates the general effect of wind by the percent change in takeoff or landing distance as a function of the ratio of wind velocity to takeoff or landing speed. The effect of proper takeoff speed is especially important when runway lengths and takeoff distances are critical. The takeoff speed specified in the AFM/POH are generally the minimum safe speeds at which the aircraft can become airborne. Any attempt to take off below the recommended speed means that the aircraft could stall, be difficult to control, or have a very low initial rate of climb. In some cases, an excessive AOA may not allow the aircraft to climb out of ground effect. On the other hand, an excessive airspeed at takeoff may improve the initial rate of climb and feel of the aircraft, but will produce an undesirable increase in takeoff distance. Assuming that the acceleration is essentially unaffected, the takeoff distance varies with the square of the takeoff velocity. Thus, 10% excess airspeed would increase the takeoff distance 21%. In most critical takeoff conditions, such an increase in takeoff distance would be prohibitive, and the pilot must adhere to the recommended takeoff speeds. The effect of pressure altitude and ambient temperature is to define the density altitude and its effect on takeoff performance. While subsequent corrections are appropriate for the effect of temperature on certain items of power plant performance, density altitude defines specific effects on takeoff performance. An increase in density altitude can produce a twofold effect on takeoff performance. 1. Greater takeoff speed. 2. Decreased thrust and reduced net accelerating force. If an aircraft of given weight and configuration is operated at greater heights above standard sea level, the aircraft requires the same dynamic pressure to become airborne at the takeoff lift coefficient. Thus, the aircraft at altitude will take off at the same indicated airspeed as at sea level, but because of the reduced air density, the true airspeed will be greater. The effect of density altitude on power plant thrust depends much on the type of power plant. An increase in altitude above standard sea level will bring an immediate decrease in power output for the unsupercharged reciprocating engine. However, an increase in altitude above standard sea level will not cause a decrease in power output for the supercharged reciprocating engine until the altitude exceeds the critical operating altitude. For those power plants that experience a decay in thrust with an increase in altitude, the effect on the net accelerating force and acceleration rate can be approximated by assuming a direct variation with density. Actually, this assumed variation would closely approximate the effect on aircraft with high thrust-to-weight ratios. Proper accounting of pressure, altitude, and temperature is mandatory for accurate prediction of takeoff roll distance. The most critical conditions of takeoff performance are the result of some combination of high gross weight, altitude, temperature, and unfavorable wind. In all cases, the pilot must make an accurate prediction of takeoff distance from the performance data of the AFM/POH, regardless of the runway available, and strive for a polished, professional takeoff procedure. In the prediction of takeoff distances from the AFM/POH data, the following primary considerations must be given. Pressure, altitude, and temperature, to define the effect of density altitude on distance. Gross weight, a large effect on distance. Wind, a large effect due to the wind or wind component along the runway. Runway slope and condition, the effect of an incline and retarding effect of factors such as snow or ice. Landing performance. In many cases, the landing distance of an aircraft will define the runway requirements for flight operations. The minimum landing distance is obtained by landing at some minimum safe speed, which allows sufficient margin above stall and provides satisfactory control and capability for a go-around. Generally, the landing speed is some fixed percentage of the stall speed or minimum control speed for the aircraft in the landing configuration. As such, the landing will be accomplished at some particular value of lift coefficient and AOA. The exact values will depend on the aircraft characteristics, but once defined, The values are independent of weight, altitude, and wind. To obtain minimum landing distance at the specified landing speed, the forces that act on the aircraft must provide maximum deceleration during the landing roll. The forces acting on the aircraft during the landing roll may require various procedures to maintain landing deceleration at the peak value. A distinction should be made between the procedures for minimum landing distance and an ordinary landing roll with considerable excess runway available. Minimum landing distance will be obtained by creating a continuous peak deceleration of the aircraft, that is, extensive use of the brakes for maximum deceleration. On the other hand, an ordinary landing roll with considerable excess runway may allow extensive use of aerodynamic drag to minimize wear and tear on the tires and brakes. If aerodynamic drag is sufficient to cause deceleration, it can be used in deference to the brakes in the early stages of the landing roll, i.e. brakes and tires suffer from continuous hard use, but aircraft aerodynamic drag is free and does not wear out with use. The use of aerodynamic drag is applicable only for deceleration to 60 or 70% of the touchdown speed. At speeds less than 60 to 70% of the touchdown speed, aerodynamic drag is so slight as to be of little use, and braking must be utilized to produce continued deceleration. Since the objective during the landing roll is to decelerate, the power plant thrust should be the smallest possible positive value, or largest possible negative value in the case of thrust reversers. In addition to the important factors of proper procedures, many other variables affect the landing performance. Any item that alters the landing roll or deceleration rate during the landing roll will affect the landing distance. The effect of gross weight on landing distance is one of the principal items determining the landing distance. One effect of an increased gross weight is that a greater speed will be required to support the aircraft at the landing AOA and lift coefficient. For an example of the effect of a change in gross weight, a 21% increase in landing weight will require a 10% increase in landing speed to support the greater weight. When minimum landing distances are considered, braking friction forces predominate during the landing roll, and for the majority of aircraft configurations, braking friction is the main source of deceleration. The minimum landing distance will vary in direct proportion to the gross weight. For example, a 10% increase in gross weight at landing would cause a 5% increase in landing velocity, 10% increase in landing distance. A contingency of this is the relationship between weight and braking friction force. The effect of wind on landing distance is large and deserves proper consideration when predicting landing distance. Since the aircraft will land at a particular airspeed independent of the wind, the principal effect of wind on landing distance is the change in the ground speed at which the aircraft touches down. The effect of wind on deceleration during the landing is identical to the effect on acceleration during takeoff. The effect of pressure altitude and ambient temperature is to define density altitude and its effect on landing performance. An increase in density altitude increases the landing speed, but does not alter the net retarding force. Thus, the aircraft at altitude lands at the same IAS as at sea level, but because of the reduced density, the TAS is greater. Since the aircraft lands at altitude with the same weight and dynamic pressure, the drag and braking friction throughout the landing roll have the same values as at sea level. As long as the condition is within the capability of the brakes, the net retarding force is unchanged, and the deceleration is the same as with the landing at sea level. Since an increase in altitude does not alter deceleration, the effect of density altitude on landing distance is due to the greater TAS. The minimum landing distance at 5,000 feet is 16% greater than the minimum landing distance at sea level. The approximate increase in landing distance with altitude is approximately 3.5% for each 1,000 feet of altitude. Proper accounting of density altitude is necessary to accurately predict landing distance. The effect of proper landing speed is important when runway lengths and landing distances are critical. The landing speed specified in the AFM/POH are generally the minimum safe speeds at which the aircraft can be landed. Any attempt to land at below the specified speed may mean that the aircraft may stall, be difficult to control, or develop high rates of descent. On the other hand, an excessive speed at landing may improve the controllability slightly, especially in crosswinds, but causes an undesirable increase in landing distance. A 10% excess landing speed causes at least a 21% increase in landing distance. The excess speed places a greater working load on the brakes because of the additional kinetic energy to be dissipated. Also, the additional speed causes increased drag and lift in the normal ground attitude, and the increased lift reduces the normal force on the braking surfaces. The deceleration during this range of speed immediately after touchdown may suffer, and it is more probable for a tire to be blown out from braking at this point. The most critical conditions of landing performance are combinations of high gross weight, high density altitude, and unfavorable wind. These conditions produce the greatest required landing distances and critical levels of energy dissipation required of the brakes. In all cases, it is necessary to make an accurate prediction of minimum landing distance to compare with the available runway. A polished professional landing procedure is necessary because the landing phase of flight accounts for more pilot-caused aircraft accidents than any other single phase of flight. In the prediction of minimum landing distance from the AFM/POH data, the following considerations must be given. Pressure, altitude, and temperature to define the effect of density altitude. Gross weight, which defines the CAS for landing. Wind, a large effect due to wind or wind component along the runway. Runway slope and condition, relatively small correction for ordinary values of runway slope, but a significant effect of snow, ice, or soft ground. A tailwind of 10 knots increases the landing distance by about 21%. An increase of landing speed by 10% increases the landing distance by 20%. Hydroplaning makes braking ineffective until a decrease of speed to that determined using Figure 10-17. For instance, a pilot is downwind for runway 18, and the tower asks if runway 27 could be accepted. There is a light rain, and the winds are out of the east at 10 knots. The pilot accepts because he or she is approaching the extended center line of runway 27. The turn is tight, and the pilot must dive, to get to runway 27. After becoming aligned with the runway and at 50 feet AGL, the pilot is already 1,000 feet down the 3,500-foot runway. The airspeed is still high by about 10%, should be at 70 knots, and is at about 80 knots. The wind of 10 knots is blowing from behind. First, the airspeed being high by about 10%, 80 knots versus 70 knots, as presented in the performance chapter, results in a 20% increase in the landing distance. In performance planning, the pilot determined that at 70 knots the distance would be 1,600 feet. However, now it is increased by 20% and the required distance is now 1,920 feet. The newly revised landing distance of 1,920 feet is also affected by the wind. In looking at Figure 10-18, the effect of the wind is an additional 20% for every 10 miles per hour mph in wind. This is computed not on the original estimate, but on the estimate based upon the increased airspeed. Now the distance is increased another 320 feet for a total requirement of 2,240 feet to land the airplane after reaching 50 feet AGL. That is the original estimate of 1,600 under planned conditions, plus the additional 640 feet for excess speed and the tailwind. Given the pilot overshot the threshold by 1,000 feet, the total length required is 3,240 on a 3,500-foot runway, 260 feet to spare. But this is in a perfect environment. Most pilots become fearful as the end of the runway is facing them just ahead. A typical pilot reaction is to brake, and brake hard. Because the aircraft does not have anti-lock braking features like a car, the brakes lock and the aircraft hydroplanes on the wet surface of the runway until decreasing to a speed of about 54 knots, the square root of the tire pressure, square root of 36 times 9. Braking is ineffective when hydroplaning. The 260 feet that a pilot might feel is left over has long since evaporated as the aircraft hydroplaned the first 300 to 500 feet when the brakes locked. This is an example of a true story, but one which only changes from year to year because of new participants and aircraft with different end numbers. In this example, the pilot actually made many bad decisions. Bad decisions, when combined, have a synergy greater than the individual errors. Therefore, the corrective actions become larger and larger until correction is almost impossible. Aeronautical decision-making will be discussed more fully in Chapter 17, Aeronautical Decision-Making, ADM. End of Part 3 of Chapter 10. Part 4 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 4 of Chapter 10, Aircraft Performance. Performance Speeds. True Airspeed, TAS. The speed of the aircraft in relation to the air mass in which it is flying. Indicated Airspeed, IAS. The speed of the aircraft as observed on the ASI. It is the airspeed without correction for indicator, position, or installation, or compressibility errors. Calibrated Airspeed, CAS. The ASI reading corrected for position or installation and instrument errors. CAS is equal to TAS at sea level in standard atmosphere. The color coding for various design speeds marked on ASIs may be IAS or CAS. Equivalent Airspeed, EAS. The ASI reading corrected for position or installation, for instrument error, and for adiabatic compressible flow for the particular altitude. EAS is equal to CAS at sea level in standard atmosphere. VSO. The calibrated power-off stalling speed, or the minimum steady flight speed at which the aircraft is controllable in the landing configuration. VS1. The calibrated power-off stalling speed, or the minimum steady flight speed at which the aircraft is controllable in a specified configuration. VY. The speed at which the aircraft will obtain the maximum increase in altitude per unit of time. The best rate of climb speed normally decreases slightly with altitude. Vx. The speed at which the aircraft will obtain the highest altitude in a given horizontal distance. This best angle of climb speed normally increases slightly with altitude. VLE. The maximum speed at which the aircraft can be safely flown with the landing gear extended. This is a problem involving stability and controllability. VLO. The maximum speed at which the landing gear can be safely extended or retracted. This is a problem involving the air loads imposed on the operating mechanism during extension or retraction of the gear. VFE. The highest speed permissible with the wing flaps in a prescribed extended position. This is because of the air loads imposed on the structure of the flaps. VA. The calibrated design maneuvering airspeed. This is the maximum speed at which the limit load can be imposed, either by gusts or by full deflection of the controlled surfaces, without causing structural damage. Operating at or below maneuvering speed does not provide structural protection against multiple full control inputs in one axis or full control inputs in more than one axis at the same time. VNO. The maximum speed for normal operation, or the maximum structural cruising speed. This is the speed at which exceeding the limit load factor may cause permanent deformation of the aircraft structure. VNE. The speed which should never be exceeded. If flight is attempted above this speed, structural damage or structural failure may result. Performance charts. Performance charts allow a pilot to predict the takeoff, climb, cruise, and landing performance of an aircraft. These charts, provided by the manufacturer, are included in the AFM/POH. Information the manufacturer provides on these charts has been gathered from test flights conducted in a new aircraft under normal operating conditions while using average piloting skills and with the aircraft and engine in good working order. Engineers record the flight data and create performance charts based on the behavior of the aircraft during the test flights. By using these performance charts, a pilot can determine the runway length needed to take off and land, the amount of fuel to be used during flight, and the time required to arrive at the destination. It is important to remember that the data from the charts will not be accurate if the aircraft is not in good working order or when operating under adverse conditions. Always consider the necessity to compensate for the performance numbers if the aircraft is not in good working order or piloting skills are below average. Each aircraft performs differently and therefore has different performance numbers. Compute the performance of the aircraft prior to every flight, as every flight is different. See Appendix for examples of performance charts for a Cessna Model 172R and Challenger 605. Every chart is based on certain conditions and contains notes on how to adapt the information for flight conditions. It is important to read every chart and understand how to use it. Read the instructions provided by the manufacturer. For an explanation on how to use the charts, refer to the example provided by the manufacturer for that specific chart. Refer to Figure 10-19. The information manufacturers furnish is not standardized. Information may be contained in a table format, and other information may be contained in a graph format. Sometimes combined graphs incorporate two or more graphs into one chart to compensate for multiple conditions of flight. Combined graphs allow the pilot to predict aircraft performance for variations in density, altitude, weight, and winds all on one chart. Because of the vast amount of information that can be extracted from this type of chart, it is important to be very accurate in reading the chart. A small error in the beginning can lead to a large error at the end. The remainder of this section covers performance information for aircraft in general and discusses what information the charts contain and how to extract information from the charts by direct reading and interpolation methods. Every chart contains a wealth of information that should be used when flight planning. Examples of the table, graph, and combined graph formats for all aspects of flight will be discussed. Interpolation. Not all of the information on the charts is easily extracted. Some charts require interpolation to find the information for specific flight conditions. Interpolating information means that by taking the known information, a pilot can compute intermediate information. However, pilots sometimes round off values from charts to a more conservative figure. Using values that reflect slightly more adverse conditions provides a reasonable estimate of performance information and gives a slight margin of safety. The following illustration is an example of interpolating information from a takeoff distance chart. Refer to Figure 10-20. Density altitude charts. Use a density altitude chart to figure the density altitude at the departing airport. Using Figure 10-21, determine the density altitude based on the given information. Sample Problem 1. Airport elevation, 5,883 feet. Outside air temperature, 70 degrees Fahrenheit. Altimeter, 30.10 inches of mercury. First, compute the pressure-altitude conversion. Find 30.10 under the altimeter heading. Read across to the second column. It reads minus 165. Therefore, it is necessary to subtract 165 from the airport elevation, giving a pressure altitude of 5,718 feet. Next, locate the outside air temperature on the scale along the bottom of the graph. From 70 degrees, draw a line up to the 5,718 feet pressure altitude line, which is about 2/3 of the way up between the 5,000 and 6,000 foot lines. Draw a line straight across to the far left side of the graph and read the approximate density altitude. The approximate density altitude in thousands of feet is 7,700 feet. Takeoff charts. Takeoff charts are typically provided in several forms and allow a pilot to compute the takeoff distance of the aircraft with no flaps or with a specific flap configuration. A pilot can also compute distances for no flap takeoff over a 50-foot obstacle scenario, as well as with flaps over a 50-foot obstacle. The takeoff distance chart provides for various aircraft weights, altitudes, temperatures, winds, and obstacle heights. Sample problem 2. Pressure altitude, 2,000 feet. Outside air temperature, 22 degrees Celsius. Takeoff weight, 2,600 pounds. Headwind, 6 knots. Obstacle height, 50-foot obstacle. Refer to Figure 10-22. This chart is an example of a combined takeoff distance graph. It takes into consideration pressure altitude, temperature, weight, wind, and obstacles all on one chart. First, find the correct temperature on the bottom left-hand side of the graph. Follow the line from 22 degrees Celsius straight up until it intersects the 2,000-foot altitude line. From that point, draw a line straight across to the first dark reference line. Continue to draw the line from the reference point in a diagonal direction following the surrounding lines until it intersects the corresponding weight line. From the intersection of 2,600 pounds, draw a line straight across until it reaches the second reference line. Once again, follow the lines in a diagonal manner until it reaches the 6-knot headwind mark. Follow straight across to the third reference line, and from here, draw a line in 2 directions. First, draw a line straight across to figure the ground roll distance. Next, follow the diagonal lines until it reaches the corresponding obstacle height. In this case, it is a 50-foot obstacle. Therefore, draw the diagonal line to the far edge of the chart. This results in a 700-foot ground roll distance and a total distance of 1,400 feet over a 50-foot obstacle. To find the corresponding takeoff speeds at liftoff and over the 50-foot obstacle, refer to the table on the top of the chart. In this case, the liftoff speed at 2,600 pounds would be 63 knots, and over the 50-foot obstacle would be 68 knots. Sample problem 3. Pressure altitude, 3,000 feet. Outside air temperature, 30 degrees Celsius. Takeoff weight, 2,400 pounds. Headwind, 18 knots. Refer to Figure 10-23. This chart is an example of a takeoff distance table for short field takeoffs. For this table, first find the takeoff weight. Once at 2,400 pounds, begin reading left to right across the table. The takeoff speed is in the second column, and in the third column under pressure altitude, find the pressure altitude of 3,000 feet. Carefully follow that line to the right until it is under the correct temperature column of 30 degrees Celsius. The ground roll total reads 1,325 feet, and the total required to clear a 50-foot obstacle is 2,480 feet. At this point, there is an 18-knot headwind. According to the notes section under point number 2, decrease the distances by 10% for each 9 knots of headwind. With an 18-knot headwind, it is necessary to decrease the distance by 20%. Multiply 1,325 feet by 20%. 1,325 times 0.20 equals 265. Subtract the product from the total distance, 1,325 minus 265 equals 1,060. Repeat this process for the total distance over a 50-foot obstacle. The ground roll distance is 1,060 feet, and the total distance over a 50-foot obstacle is 1,984 feet. Climb and cruise charts. Climb and cruise chart information is based on actual flight tests conducted in an aircraft of the same type. This information is extremely useful when planning across country to predict the performance and fuel consumption of the aircraft. Manufacturers produce several different charts for climb and cruise performance. These charts include everything from fuel, time, and distance to climb, to best power setting during cruise, to cruise range performance. The first chart to check for climb performance is a fuel, time, and distance to climb chart. This chart will give the fuel amount used during the climb, the time it will take to accomplish the climb, and the ground distance that will be covered during the climb. To use this chart, obtain the information for the departing airport and for the cruise altitude. Using Figure 10-24, calculate the fuel, time, and distance to climb based on the information provided. Sample Problem 4. Departing airport pressure altitude, 6,000 feet. Departing airport outside air temperature, 25 degrees Celsius. Cruise pressure altitude, 10,000 feet. Cruise outside air temperature, 10 degrees Celsius. First, find the information for the departing airport. Find the outside air temperature for the departing airport along the bottom left-hand side of the graph. Follow the line from 25 degrees Celsius straight up until it intersects the line corresponding to the pressure altitude of 6,000 feet. Continue this line straight across until it intersects all three lines for fuel, time, and distance. Draw a line straight down from the intersection of altitude and fuel, altitude and time, and a third line at altitude and distance. It should read 3½ gallons of fuel, 6.5 minutes of time, and 9 nautical miles. Next, repeat the steps to find the information for the cruise altitude. It should read 6½ gallons of fuel, 11.5 minutes of time, and 15 nautical miles. Take each set of numbers for fuel, time, and distance and subtract them from one another. 6.5 minus 3.5 equals 3 gallons of fuel. It will take 3 gallons of fuel and 5 minutes of time to climb to 10,000 feet. During that climb, the distance covered is 6 nautical miles. Remember, according to the notes at the top of the chart, these numbers do not take into account wind, and it is assumed maximum continuous power is being used. The next example is a fuel, time, and distance to climb table. For this table, use the same basic criteria as for the previous chart. However, it is necessary to figure the information in a different manner. Refer to Figure 10-25 to work the following sample problem. Sample Problem 5. Departing airport pressure altitude, sea level. Departing airport outside air temperature, 22 degrees Celsius. Cruise pressure altitude, 8,000 feet. Takeoff weight, 3,400 pounds. To begin, find the given weight of 3,400 in the first column of the chart. Move across to the pressure altitude column to find the sea level altitude numbers. At sea level, the numbers read 0. Next, read the line that corresponds with the cruising altitude of 8,000 feet. Normally, a pilot would subtract these two sets of numbers from one another, but given the fact that the number reads 0 at sea level, it is known that the time to climb from sea level to 8,000 feet is 10 minutes. It is also known that 21 pounds of fuel will be used and 20 nautical miles will be covered during the climb. However, the temperature is 22 degrees Celsius, which is 7 degrees above the standard temperature of 15 degrees Celsius. The notes section of this chart indicate that the findings must be increased by 10% for each 7 degrees above standard. Multiply the findings by 10%, or 0.10. 10 times 0.10 equals 1. 1 plus 10 equals 11 minutes. After accounting for the additional 10%, the findings should read 11 minutes, 23.1 pounds of fuel, and 22 nautical miles. Notice that the fuel is reported in pounds of fuel, not gallons. Aviation fuel weighs 6 pounds per gallon, so 23.1 pounds of fuel is equal to 3.85 gallons of fuel. 23.1 divided by 6 equals 3.85. The next example is a cruise and range performance chart. This type of table is designed to give TAS, fuel consumption, endurance in hours, and range in miles at specific cruise configurations. Use Figure 10-26 to determine the cruise and range performance under the given conditions. Sample Problem 6. Pressure altitude, 5,000 feet. RPM, 2,400 RPM. Fuel carrying capacity, 38 gallons, no reserve. Find 5,000 feet pressure altitude in the first column on the left-hand side of the table. Next, find the correct RPM of 2,400 in the second column. Follow that line straight across and read the TAS of 116 miles per hour and a fuel burn rate of 6.9 gallons per hour. As per the example, the aircraft is equipped with a fuel carrying capacity of 38 gallons. Under this column, read that the endurance in hours is 5.5 hours and the range in miles is 635 miles. Cruise power setting tables are useful when planning cross-country flights. The table gives the correct cruise power settings as well as the fuel flow and airspeed performance numbers at that altitude and airspeed. Sample Problem 7. Pressure altitude at cruise, 6,000 feet. Outside air temperature, 36 degrees Fahrenheit above standard. Refer to Figure 10-27 for this sample problem. First, locate the pressure altitude of 6,000 feet on the far left side of the table. Follow that line across to the far right side of the table under the 20 degrees Celsius or 36 degrees Fahrenheit column. At 6,000 feet, the RPM setting of 2,450 will maintain 65% continuous power at 21 inches of mercury with a fuel flow rate of 11.5 gallons per hour and airspeed of 161 knots. Another type of cruise chart is a best power mixture range graph. This graph gives the best range based on power setting and altitude. Using Figure 10-28, find the range at 65% power with and without a reserve based on the provided conditions. Sample Problem 8. Outside air temperature, standard. Pressure altitude, 5,000 feet. First, move up the left side of the graph to 5,000 feet and standard temperature. Follow the line straight across the graph until it intersects the 65% line under both the reserve and no reserve categories. Draw a line straight down from both intersections to the bottom of the graph. At 65% power, with a reserve, the range is approximately 522 miles. At 65% power with no reserve, the range should be 581 miles. The last cruise chart referenced is a cruise performance graph. This graph is designed to tell the TAS performance of the airplane depending on the altitude, temperature, and power setting. Using Figure 10-29, find the TAS performance based on the given information. Sample Problem 9. Outside air temperature, 16 degrees Celsius. Pressure altitude, 6,000 feet. Power setting, 65%, best power. Wheel fairings not installed. Begin by finding the correct OAT on the bottom left side of the graph. Move up that line until it intersects the pressure altitude of 6,000 feet. Draw a line straight across to the 65% best power line. This is the solid line, which represents best economy. Draw a line straight down from this intersection to the bottom of the graph. The TAS at 65% best power is 140 knots. However, it is necessary to subtract 8 knots from the speed since there are no wheel fairings. This note is listed under the title and conditions. The TAS will be 132 knots. Crosswind and headwind component chart. Every aircraft is tested according to Federal Aviation Administration, FAA, regulations prior to certification. The aircraft is tested by a pilot with average piloting skills in 90-degree crosswinds with a velocity up to 0.2 VSO or 2/10 of the aircraft's stalling speed with power off, gear down, and flaps down. This means that if the stalling speed of the aircraft is 45 knots, it must be capable of landing in a 9-knot, 90-degree crosswind. The maximum demonstrated crosswind component is published in the AFM/POH. The crosswind and headwind component chart allows for figuring the headwind and crosswind component for any given wind direction and velocity. Sample problem 10. Runway 17. Wind 140 degrees at 25 knots. Refer to Figure 10-30 to solve this problem. First, determine how many degrees difference there is between the runway and the wind direction. It is known that runway 17 means a direction of 170 degrees. From that, subtract the wind direction of 140 degrees. This gives a 30-degree angular difference or wind angle. Next, locate the 30-degree mark and draw a line from there until it intersects the correct wind velocity of 25 knots. From there, draw a line straight down and a line straight across. The headwind component is 22 knots and the crosswind component is 13 knots. This information is important when taking off and landing, so first of all, the appropriate runway can be picked if more than one exists at a particular airport, but also so that the aircraft is not pushed beyond its tested limits. Landing charts. Landing performance is affected by variables similar to those affecting takeoff performance. It is necessary to compensate for differences in density altitude, weight of the airplane, and headwinds. Like takeoff performance charts, landing distance information is available as normal landing information, as well as landing distance over a 50-foot obstacle. As usual, read the associated conditions and notes in order to ascertain the basis of the chart information. Remember, when calculating landing distance, that the landing weight will not be the same as the takeoff weight. The weight must be recalculated to compensate for the fuel that was used during the flight. Sample problem 11. Pressure altitude 1,250 feet. Temperature standard. Refer to Figure 10-31. This example makes use of a landing distance table. Notice that the altitude of 1,250 feet is not on this table. It is therefore necessary to interpolate to find the correct landing distance. The pressure altitude of 1,250 is halfway between the sea level and 2,500 feet. First, find the column for sea level and the column for 2,500 feet. Take the total distance of 1,075 for sea level and the total distance of 1,135 for 2,500 and add them together. Divide the total by 2 to obtain the distance for 1,250 feet. The distance is 1,105 feet total landing distance to clear a 50-foot obstacle. Repeat this process to obtain the ground roll distance for the pressure altitude. The ground roll should be 457.5 feet. Sample problem 12. Outside air temperature, 57 degrees Fahrenheit. Pressure altitude, 4,000 feet. Landing weight, 2,400 pounds. Headwind, 6 knots. Obstacle height, 50 feet. Using the given conditions and Figure 10-32, determine the landing distance for the aircraft. This graph is an example of a combined landing distance graph and allows compensation for temperature, weight, headwinds, tailwinds, and varying obstacle height. Begin by finding the correct OAT on the scale on the left side of the chart. Move up in a straight line to the correct pressure altitude of 4,000 feet. From this intersection, move straight across to the first dark reference line. Follow the lines in the same diagonal fashion until the correct landing weight is reached. At 2,400 pounds, continue in a straight line across to the second dark reference line. Once again, draw a line in a diagonal manner to the correct wind component and then straight across to the third dark reference line. From this point, draw a line in 2 separate directions. One straight across to figure the ground roll, and one in a diagonal manner to the correct obstacle height. This should be 975 feet for the total ground roll, and 1,500 feet for the total distance over a 50-foot obstacle. Stall speed performance charts. Stall speed performance charts are designed to give an understanding of the speed at which the aircraft will stall in a given configuration. This type of chart will typically take into account the angle of bank, the position of the gear and flaps, and the throttle position. Use Figure 10-33 and the accompanying conditions to find the speed at which the airplane will stall. Sample Problem 13. Power off. Flaps down. Gear down. Angle of bank 45 degrees. First, locate the correct flap and gear configuration. The bottom half of the chart should be used since the gear and flaps are down. Next, choose the row corresponding to a power-off situation. Now find the correct angle of bank column, which is 45 degrees. The stall speed is 78 miles per hour, and the stall speed in knots would be 68 knots. Performance charts provide valuable information to the pilot. Take advantage of these charts. A pilot can predict the performance of the aircraft under most flying conditions, and this enables a better plan for every flight. The Code of Federal Regulations, CFR, requires that a pilot be familiar with all information available prior to any flight. Pilots should use the information to their advantage, as it can only contribute to safety in flight. End of Part 4 of Chapter 10. Part 5 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 5 of Chapter 10, Aircraft Performance. Transport Category Airplane Performance. Transport Category aircraft are certificated under Title 14 of the CFR, 14 CFR, Parts 25 and 29. The airworthiness certification standards of Part 25 and 29 require proven levels of performance and guarantee safety margins for these aircraft, regardless of the specific operating regulations under which they are employed. Major differences in transport category versus non-transport category performance requirements. Full temperature accountability. All of the performance charts for the transport category aircraft require that takeoff and climb performance be computed with the full effects of temperature considered. Climb performance expressed as % gradient of climb. The transport category aircraft's climb performance is expressed as a % gradient of climb rather than a figure calculated in FPM of climb. This % gradient of climb is a much more practical expression of performance since it is the aircraft's angle of climb that is critical in an obstacle clearance situation. Change in liftoff technique. Liftoff technique in transport category aircraft allows the reaching of V2, takeoff safety speed, after the aircraft is airborne. This is possible because of the excellent acceleration and reliability characteristics of the engines on these aircraft and due to the larger surplus of power. Performance requirements applicable to all segments of aviation. All aircraft certified by the FAA in the transport category, whatever the size, must be operated in accordance with the same performance criteria. This applies to both commercial and non-commercial operations. Performance requirements. The performance requirements that the transport category aircraft must meet are takeoff, takeoff speeds, takeoff runway required, takeoff climb required, obstacle clearance requirements. Landing, landing speeds, landing runway required, landing climb required. Takeoff planning. Listed below are the speeds that affect the transport category aircraft's takeoff performance. The flight crew must be thoroughly familiar with each of these speeds and how they are used in takeoff planning. VS, stalling speed or the minimum steady flight speed at which the aircraft is controllable. VMCG, minimum control speed on the ground with one engine inoperative, critical engine on two engine airplanes, takeoff power on other engine or engines, using aerodynamic controls only for directional control, must be less than V1. VMCA, minimum control speed in the air with one engine inoperative, critical engine on two engine aircraft, operating engine or engines at takeoff power, maximum of 5 degrees bank into the good engine or engines. V1, critical engine failure speed or decision speed. Engine failure below this speed shall result in an aborted takeoff. Above this speed, the takeoff run should be continued. VR, speed at which the rotation of the aircraft is initiated to takeoff attitude. The speed cannot be less than V1 or less than 1.05 times VMC. With an engine failure, it must allow for the acceleration to V2 at the 35-foot height at the end of the runway. VLOF, liftoff speed, the speed at which the aircraft first becomes airborne. V2, the takeoff safety speed which must be attained at the 35-foot height at the end of the required runway distance. This is essentially the best one-engine operative angle of climb speed for the aircraft and should be held until clearing obstacles after takeoff or until at least 400 feet above the ground. VFS, final segment climb speed, which is based upon one-engine inoperative climb, clean configuration, and maximum continuous power setting. All of the V speeds should be considered during every takeoff. The V1, VR, V2, and VFS speeds should be visibly posted in the flight deck for reference during the takeoff. Takeoff speeds vary with aircraft weight. Before takeoff speeds can be computed, the pilot must first determine the maximum allowable takeoff weight. The three items that can limit takeoff weight are runway requirements, takeoff climb requirements, and obstacle clearance requirements. Runway requirements. The runway requirements for takeoff are affected by pressure altitude, temperature, headwind component, runway gradient or slope, aircraft weight. The runway required for takeoff must be based upon the possible loss of an engine at the most critical point, which is at V1, decision speed. By regulation, the aircraft's takeoff weight has to accommodate the longest of three distances. 1. Accelerate go distance. The distance required to accelerate to V1 with all engines at takeoff power, experience an engine failure at V1, and continue the takeoff on the remaining engine or engines. The runway required includes the distance required to climb to 35 feet, by which time V2 speed must be attained. 2. Accelerate stop distance. The distance required to accelerate to V1 with all engines at takeoff power, experience an engine failure at V1, and abort the takeoff and bring the aircraft to a stop using braking action only. Use of thrust reversing is not considered. 3. Takeoff distance. The distance required to complete an all-engines operative takeoff to the 35-foot height. It must be at least 15% less than the distance required for a one-engine inoperative engine takeoff. This distance is not normally a limiting factor, as it is usually less than the one-engine inoperative takeoff distance. These three required takeoff runway considerations are shown in Figure 10-34. Balanced field length. In most cases, the pilot will be working with a performance chart for takeoff runway required, which will give balanced field length information. This means that the distance shown for the takeoff will include both the accelerate go and accelerate stop distances. One effective means of presenting the normal takeoff data is shown in the tabulated chart in Figure 10-35. The chart in Figure 10-35 shows the runway distance required under normal conditions and is useful as a quick reference chart for the standard takeoff. The V-speeds for the various weights and conditions are also shown. For other than normal takeoff conditions, such as with engine anti-ice, anti-skid brakes inoperative, or extremes in temperature or runway slope, the pilot should consult the appropriate takeoff performance charts in the performance section of the AFM. There are other occasions of very high weight and temperature where the runway requirement may be dictated by the maximum brake kinetic energy limits that affect the aircraft's ability to stop. Under these conditions, the accelerate stop distance may be greater than the accelerate go. The procedure to bring performance back to a balanced field takeoff condition is to limit the V1 speed so that it does not exceed the maximum brake kinetic energy speed, sometimes called VBE. This procedure also results in a reduction in allowable takeoff weight. Climb requirements. After the aircraft has reached the 35-foot height with one engine inoperative, there is a requirement that it be able to climb at a specified climb gradient. This is known as the takeoff flight path requirement. The aircraft's performance must be considered based upon a one-engine inoperative climb up to 1,500 feet above the ground. The takeoff flight path profile, with required gradients of climb for the various segments and configurations, is shown in Figure 10-36. Note: climb gradient can best be described as being a specific gain of vertical height for a given distance covered horizontally. For instance, a 2.4% gradient means that 24 feet of altitude would be gained for each 1,000 feet of distance covered horizontally across the ground. The following brief explanation of the one-engine inoperative climb profile may be helpful in understanding the chart in Figure 10-36. First segment. This segment is included in the takeoff runway required charts and is measured from the point at which the aircraft becomes airborne until it reaches the 35-foot height at the end of the runway distance required. Speed initially is VLO and must be V2 at the 35-foot height. Second segment. This is the most critical segment of the profile. The second segment is the climb from the 35-foot height to 400 feet above the ground. The climb is done at full takeoff power on the operating engine or engines at V2 speed and with the flaps in the takeoff configuration. The required climb gradient in this segment is 2.4% for two-engine aircraft, 2.7% for three-engine aircraft, and 3.0% for four-engine aircraft. Third, or acceleration segment. During this segment, the airplane is considered to be maintaining the 400 feet above the ground and accelerating from the V2 speed to the VFS speed before the climb profile is continued. The flaps are raised at the beginning of the acceleration segment, and power is maintained at the takeoff setting as long as possible, 5 minutes maximum. Fourth, or final segment. This segment is from 400 to 1,500 foot AGL altitude with power set at maximum continuous. The required climb in this segment is a gradient of 1.2% for two-engine airplanes, 1.55% for three-engine airplanes, and 1.7% for four-engine airplanes. Second segment climb limitations. The second segment climb requirements from 35 to 400 feet are the most restrictive, or hardest to meet, of the climb segments. The pilot must determine that the second segment climb is met for each takeoff. In order to achieve this performance at the higher density altitude conditions, it may be necessary to limit the takeoff weight of the aircraft. It must be realized that, regardless of the actual available length of the takeoff runway, takeoff weight must be adjusted so that the second segment climb requirements can be met. The aircraft may well be capable of lifting off with one engine inoperative, but it must then be able to climb and clear obstacles. Although second segment climb may not present much of a problem at the lower altitudes, at the higher altitude airports and higher temperatures, the second segment climb chart should be consulted to determine the effects on maximum takeoff weights before figuring takeoff runway distance required. Air carrier obstacle clearance requirements. Regulations require that large transport category turbine-powered aircraft certificated after September 30, 1958, be taken off at a weight that allows a net takeoff flight path, one engine inoperative, that clears all obstacles either by height of at least 35 feet vertically or by at least 200 feet horizontally within the airport boundaries, and by at least 300 feet horizontally after passing the boundaries. The takeoff flight path is considered to begin 35 feet above the takeoff surface at the end of the takeoff distance, and extends to a point in the takeoff at which the aircraft is 1,500 feet above the takeoff surface, or at which the transition from the takeoff to the en route configuration is completed. The net takeoff flight path is the actual takeoff flight path reduced at each point by 0.8% for 2-engine aircraft, 0.9% for 3-engine aircraft, and 1.0% for 4-engine aircraft. Air carrier pilots, therefore, are responsible not only for determining that there is enough runway available for an engine-inoperative takeoff, balanced field length, and the ability to meet required climb gradients, but they must also assure that the aircraft will safely be able to clear any obstacles that may be in the takeoff flight path. The net takeoff flight path and obstacle clearance required are shown in Figure 10-37. The usual method of computing net takeoff flight path performance is to add up the total ground distances required for each of the climb segments and/or use obstacle clearance performance charts in the AFM. Although this obstacle clearance requirement is seldom a limitation at the normally used airports, it is quite often an important consideration under critical conditions such as high takeoff weight and/or high density altitude. Consider that at a 2.4% climb gradient, 2.4 feet up for every 100 feet forward, a 1,500-foot altitude gain would take a horizontal distance of 10.4 nautical miles to achieve. Summary of takeoff requirements. In order to establish the allowable takeoff weight for a transport category aircraft at any airfield, the following must be considered: airfield pressure altitude, temperature, headwind component, runway length, runway gradient or slope, obstacles in the flight path. Once the above details are known and applied to the appropriate performance charts, it is possible to determine the maximum allowable takeoff weight. This weight would be the lower of the maximum weights as allowed by balanced field length required, engine inoperative climb ability, second segment limited, obstacle clearance requirement. In practice, restrictions to takeoff weight at low altitude airports are usually due to runway length limitations. Engine inoperative climb limitations are most common at the higher altitude airports. All limitations to weight must be observed. Since the combined weight of fuel and payload in the aircraft may amount to nearly half the maximum takeoff weight, it is usually possible to reduce fuel weight to meet takeoff limitations. If this is done, however, flight planning must be recalculated in light of reduced fuel and range. Landing performance. As in the takeoff planning, certain speeds must be considered during landing. These speeds are shown below. VSO. Stalling speed, or the minimum steady state flight speed in the landing configuration. VREF. 1.3 times the stalling speed in the landing configuration. This is the required speed at the 50-foot height above the threshold end of the runway. Approach climb. The speed which gives the best climb performance in the approach configuration with one engine inoperative and with maximum takeoff power on the operating engine or engines. The required gradient of climb in this configuration is 2.1% for 2-engine aircraft, 2.4% for 3-engine aircraft, and 2.7% for 4-engine aircraft. Landing climb. The speed giving the best performance in the full landing configuration with maximum takeoff power on all engines. The gradient of climb required in this configuration is 3.2%. Planning the landing. As in the takeoff, the landing speed shown above should be pre-computed and visible to both pilots prior to the landing. The VREF speed or threshold speed is used as a reference speed throughout the traffic pattern or instrument approach as in the following example. VREF plus 30 knots, downwind or procedure turn. VREF plus 20 knots, base leg or final course inbound to final fix. VREF plus 10 knots. Final or final course inbound from fix. ILS final. VREF, speed at the 50-foot height above the threshold. Landing requirements. The maximum landing weight of an aircraft can be restricted by either the approach climb requirements or by the landing runway available. Approach climb requirements. The approach climb is usually more limiting or more difficult to meet than the landing climb, primarily because it is based upon the ability to execute a missed approach with one engine inoperative. The required climb gradient can be affected by pressure, altitude, and temperature, and as in the second segment climb in the takeoff, aircraft weight must be limited as needed in order to comply with this climb requirement. Landing runway required. The runway distance needed for landing can be affected by the following: pressure, altitude, temperature, headwind component, runway gradient or slope, aircraft weight. In computing the landing distance required, some manufacturers do not include all of the above items in their charts, since the regulations state that only pressure, altitude, wind, and aircraft weight must be considered. Charts are provided for anti-skid on and anti-skid off conditions, but the use of reverse thrust is not used in computing required landing distances. The landing distance, as required by the regulations, is that distance needed to land and come to a complete stop from a point 50 feet above the threshold end of the runway. It includes the air distance required to travel from the 50-foot height to touchdown, which can consume 1,000 feet of runway distance, plus the stopping distance with no margin left over. This is all that is required for 14 CFR Part 91 operators, non-air carrier, and all that is shown on some landing distance required charts. For air carriers and other commercial operators subject to 14 CFR Part 121, a different set of rules applies, stating that the required landing distance from the 50-foot height cannot exceed 60% of the actual runway length available. In all cases, the minimum airspeed allowed at the 50-foot height must be no less than 1.3 times the aircraft's stalling speed in the landing configuration. This speed is commonly called the aircraft's VREF speed and varies with landing weight. Figure 10-38 is a diagram of these landing runway requirements. Summary of landing requirements. In order to establish the allowable landing weight for a transport category aircraft, the following details must be considered: airfield pressure, altitude, temperature, headwind component, runway length, runway gradient or slope, runway surface condition. With these details, it is possible to establish the maximum allowable landing weight, which will be the lower of the weights as dictated by landing runway requirements, approach climb requirements. In practice, the approach climb limitations, ability to climb an approach configuration with one engine inoperative, are seldom encountered because the landing weights upon arrival at the destination airport are usually low. However, as in the second segment climb requirement for takeoff, this approach climb gradient must be met and landing weights must be restricted if necessary. The most likely conditions that would make the approach climb critical would be the landings at high weights and high pressure altitudes and temperatures, which might be encountered if a landing were required shortly after takeoff. Landing field requirements can more frequently limit an aircraft's allowable landing weight than the approach climb limitations. Again, however, unless the runway is particularly short, this is seldom problematical, as the average landing weight at the destination rarely approaches the maximum design landing weight due to fuel burn-off. Chapter Summary. Performance characteristics and capabilities vary greatly among aircraft. Moreover, aircraft weight, atmospheric conditions, and external environmental factors can significantly affect aircraft performance. It is essential that a pilot become intimately familiar with the performance characteristics and capabilities of the aircraft being flown. The primary source of this information is the AFM/POH. End of Part 5 of Chapter 10.
Part 1 of Chapter 11 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA, Chapter 11, Part 1, Weather Theory. Introduction. Weather is an important factor that influences aircraft performance and flying safety. It is the state of the atmosphere at a given time and place, with respect to variables such as temperature, heat or cold, moisture, wetness or dryness, wind velocity, calm or storm, visibility, clearness or cloudiness, and barometric pressure, high or low. The term weather can also apply to adverse or destructive atmospheric conditions such as high winds. This chapter explains basic weather theory and offers pilots background knowledge of weather principles. It is designed to help them gain a good understanding of how weather affects daily flying activities. Understanding the theories behind weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station, FSS, weather specialist, and other aviation weather services. Be it a local flight or a long cross-country flight, decisions based on weather can dramatically affect the safety of the flight. Atmosphere. The atmosphere is a blanket of air made up of a mixture of gases that surrounds the Earth and reaches almost 350 miles from the surface of the Earth. This mixture is in constant motion. If the atmosphere were visible, it might look like an ocean with swirls and eddies, rising and falling air, and waves that travel for great distances. Life on Earth is supported by the atmosphere, solar energy, and the planet's magnetic fields. The atmosphere absorbs energy from the sun, recycles water and other chemicals, and works with the electrical and magnetic forces to provide a moderate climate. The atmosphere also protects life on Earth from high-energy radiation and the frigid vacuum of space. Composition of the atmosphere. In any given volume of air, nitrogen accounts for 78% of the gases that comprise the atmosphere, while oxygen makes up 21%. Argon, carbon dioxide, and traces of other gases make up the remaining 1%. This cubic foot also contains some water vapor, varying from 0 to about 5% by volume. This small amount of water vapor is responsible for major changes in the weather. See Figure 11-1. The envelope of gases surrounding the Earth changes from the ground up. 4 distinct layers or spheres of the atmosphere have been identified using thermal characteristics, temperature changes, chemical composition, movement, and density. See Figure 11-2. The first layer, known as the troposphere, extends from sea level up to 20,000 feet, 8 kilometers, over the northern and southern poles, and up to 48,000 feet, or 14.5 kilometers, over the equatorial regions. The vast majority of weather, clouds, storms, and temperature variances occur within this first layer of the atmosphere. Inside the troposphere, the temperature decreases at a rate of about 2 degrees Celsius every 1,000 feet of altitude gain, and the pressure decreases at a rate of about 1 inch per 1,000 feet of altitude gain. At the top of the troposphere is a boundary known as the tropopause, which traps moisture and the associated weather in the troposphere. The altitude of the tropopause varies with latitude and with the season of the year. Therefore, it takes on an elliptical shape as opposed to round. Location of the tropopause is important because it is commonly associated with the location of the jet stream and possible clear air turbulence. Above the tropopause are 3 more atmospheric layers. The first is the stratosphere, which extends from the tropopause to a height of about 160,000 feet, or 50 kilometers. Little weather exists in this layer, and the air remains stable, although certain types of clouds occasionally extend in it. Above the stratosphere are the mesosphere and thermosphere, which have little influence over weather. Atmospheric circulation. As noted earlier, the atmosphere is in constant motion. Certain factors combine to set the atmosphere in motion, but a major factor is the uneven heating of the Earth's surface. This heating upsets the equilibrium of the atmosphere, creating changes in air movement and atmospheric pressure. The movement of air around the surface of the Earth is called atmospheric circulation. Heating of the Earth's surface is accomplished by several processes, but in the simple convection-only model used for this discussion, the Earth is warmed by energy radiating from the sun. The process causes a circular motion that results when warm air rises and is replaced by cooler air. Warm air rises because heat causes air molecules to spread apart. As the air expands, it becomes less dense and lighter than the surrounding air. As air cools, the molecules pack together more closely, becoming denser and heavier than warm air. As a result, cool, heavy air tends to sink and replace warmer, rising air. Because the Earth has a curved surface that rotates on a tilted axis while orbiting the sun, the equatorial regions of the Earth receive a greater amount of heat from the sun than the polar regions. The amount of sun that heats the Earth depends on the time of year and the latitude of the specific region. All of these factors affect the length of time and the angle at which sunlight strikes the surface. Solar heating causes higher temperatures in equatorial areas, which causes the air to be less dense and rise. As the warm air flows toward the poles, it cools, becoming denser, and sinks back toward the surface. See Figure 11-3. Atmospheric pressure. The unequal heating of the Earth's surface not only modifies air density and creates circulation patterns, it also causes changes in air pressure, or the force exerted by the weight of air molecules. Although air molecules are invisible, they still have weight and take up space. Imagine a sealed column of air that has a footprint of 1 square inch and is 350 miles high. It would take 14.7 pounds of effort to lift that column. This represents the air's weight. If the column is shortened, the pressure exerted at the bottom and its weight would be less. The weight of the shortened column of air at 18,000 feet is approximately 7.4 pounds, almost 50% that of sea level. For instance, if a bathroom scale calibrated for sea level were raised to 18,000 feet, the column of air weighing 14.7 pounds at sea level would be 18,000 feet shorter and would weigh approximately 7.3 pounds, 50% less than at sea level. See Figure 11-4. The actual pressure at a given place in time differs with altitude, temperature, and density of the air. These conditions also affect aircraft performance, especially with regard to takeoff, rate of climb, and landings. Coriolis force. In general atmospheric circulation theory, areas of low pressure exist over the equatorial regions and areas of high pressure exist over the polar regions due to a difference in temperature. The resulting low pressure allows the high pressure air at the poles to flow along the planet's surface toward the equator. While this pattern of air circulation is correct in theory, the circulation of air is modified by several forces, the most important of which is the rotation of the Earth. The force created by the rotation of the Earth is known as the Coriolis force. This force is not perceptible to humans as they walk around because humans move slowly and travel relatively short distances compared to the size and rotation rate of the Earth. However, the Coriolis force significantly affects bodies that move over great distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is greatest at the poles and diminishes to 0 at the equator. The magnitude of the Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. In the northern hemisphere, the rotation of the Earth deflects moving air to the right and changes the general circulation pattern of the air. The speed of the Earth's rotation causes the general flow to break up into 3 distinct cells in each hemisphere. See Figure 11-5. In the northern hemisphere, the warm air at the equator rises upward from the surface, travels northward, and is deflected eastward by the rotation of the Earth. By the time it has traveled 1/3 of the distance from the equator to the North Pole, it is no longer moving northward but eastward. This air cools and sinks in a belt-like area at about 30 degrees latitude, creating an area of high pressure as it sinks toward the surface. Then it flows southward along the surface back toward the equator. Coriolis force bends the flow to the right, thus creating the northeasterly trade winds that prevail from 30 degrees latitude to the equator. Similar forces create circulation cells that encircle the Earth between 30 and 60 degrees latitude and between 60 degrees and the poles. This circulation pattern results in the prevailing westerly winds in the conterminous United States. Circulation patterns are further complicated by seasonal changes, differences between surfaces of continents and oceans, and other factors such as frictional forces caused by the topography of the Earth's surface, which modify the movement of the air in the atmosphere. For example, within 2,000 feet of the ground, the friction between the surface and the atmosphere slows the moving air. The wind is diverted from its path because the frictional force reduces the Coriolis force. Thus, the wind direction at the surface varies somewhat from the wind direction just a few thousand feet above the Earth. Measurement of atmosphere pressure. Atmospheric pressure is typically measured in inches of mercury, Hg, by a mercurial barometer. See Figure 11-6. The barometer measures the height of a column of mercury inside a glass tube. A section of the mercury is exposed to the pressure of the atmosphere, which exerts a force on the mercury. An increase in pressure forces the mercury to rise inside the tube. When the pressure drops, mercury drains out of the tube, decreasing the height of the column. This type of barometer is typically used in a laboratory or weather observation station. It's not easily transported and difficult to read. An aneroid barometer is an alternative to a mercurial barometer. It is easier to read and transport. See Figure 11-7. The aneroid barometer contains a closed vessel, called an aneroid cell, that contracts or expands with changes in pressure. The aneroid cell attaches to a pressure indicator with mechanical linkage to provide pressure readings. The pressure sensing part of an aircraft altimeter is essentially an aneroid barometer. It is important to note that due to the linkage mechanism of an aneroid barometer, it is not as accurate as a mercurial barometer. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for certain flight instruments and most aircraft performance data. Standard sea level pressure is defined as 29.92 inches mercury and a standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius. Atmospheric pressure is also reported in millibars, MB, with 1 inch mercury equal to approximately 34 millibars. Standard sea level pressure is 1,013.2 millibars. Typical millibar pressure readings range from 950 to 1,040 millibars. Constant pressure charts and hurricane pressure reports are written using millibars. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 inch mercury for every 1,000 feet of elevation. For example, a station at 5,000 feet above sea level with a reading of 24.92 inches mercury reports a sea level pressure reading of 29.92 inches mercury. See Figure 11-8. Using common sea level pressure readings helps ensure aircraft altimeters are set correctly, based on the current pressure readings. By tracking barometric pressure trends across a large area, weather forecasters can more accurately predict movement of pressure systems and the associated weather. For example, tracking a pattern of rising pressure at a single weather station generally indicates the approach of fair weather. Conversely, decreasing or rapidly falling pressure usually indicates approaching bad weather and possibly severe storms. Altitude and atmospheric pressure. As altitude increases, atmospheric pressure decreases. On average, with every 1,000 feet of increase in altitude, the atmospheric pressure decreases 1 inch mercury. As pressure decreases, the air becomes less dense or thinner. This is the equivalent of being at a higher altitude and is referred to as density altitude, dA. As pressure decreases, dA increases and has a pronounced effect on aircraft performance. Differences in air density caused by changes in temperature result in a change in pressure. This in turn creates motion in the atmosphere, both vertically and horizontally, in the form of currents and wind. The atmosphere is almost constantly in motion as it strives to reach equilibrium. These never-ending air movements set up chain reactions which cause a continuing variety in the weather. Altitude and flight. Altitude affects every aspect of flight, from aircraft performance to human performance. At higher altitudes, with a decreased atmospheric pressure, takeoff and landing distances are increased, as are climb rates. When an aircraft takes off, lift must be developed by the flow of air around the wings. If the air is thin, more speed is required to obtain enough lift for takeoff. Therefore, the ground run is longer. An aircraft that requires 745 feet of ground run at sea level requires more than double that at a pressure altitude of 8,000 feet. See Figure 11-9. It is also true that at higher altitudes, due to the decreased density of the air, aircraft engines and propellers are less efficient. This leads to reduced rates of climb and greater ground run for obstacle clearance. Altitude and the human body. As discussed earlier, nitrogen and other trace gases make up 79% of the atmosphere, while the remaining 21% is life-sustaining atmospheric oxygen. At sea level, atmospheric pressure is great enough to support normal growth, activity, and life. By 18,000 feet, the partial pressure of oxygen is reduced and adversely affects the normal activities and functions of the human body. The reactions of the average person become impaired at an altitude of about 10,000 feet, but for some people, impairment can occur at an altitude as low as 5,000 feet. The physiological reactions to hypoxia, or oxygen deprivation, are insidious and affect people in different ways. These symptoms range from mild disorientation to total incapacitation, depending on body tolerance and altitude. Supplemental oxygen or cabin pressurization systems help pilots fly at higher altitudes and overcome the effects of oxygen deprivation. End of Part 1 of Chapter 11. Recording by April Walters. Part 2 of Chapter 11 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA, Chapter 11, Part 2. Wind and currents. Air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. Air pressure, temperature changes, and the Coriolis force work in combination to create two kinds of motion in the atmosphere: vertical movement of ascending and descending currents, and horizontal movement in the form of wind. Currents and wind are important as they affect takeoff, landing, and cruise flight operations. Most importantly, currents and winds, or atmospheric circulation, cause weather changes. Wind patterns. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. This is known as anticyclonic circulation. The opposite is true of low-pressure areas. The air flows toward a low and is deflected to create a counterclockwise or cyclonic circulation. See Figure 11-10. High-pressure systems are generally areas of dry, stable, descending air. Good weather is typically associated with high-pressure systems for this reason. Conversely, air flows into a low-pressure area to replace rising air. This air tends to be unstable and usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A good understanding of high and low pressure wind patterns can be of great help when planning a flight, because a pilot can take advantage of beneficial tailwinds. See Figure 11-11. When planning a flight from west to east, favorable winds would be encountered along the northern side of a high-pressure system or the southern side of a low-pressure system. On the return flight, the most favorable winds would be along the southern side of the same high-pressure system or the northern side of a low-pressure system. An added advantage is a better understanding of what type of weather to expect in a given area along a route of flight based on the prevailing areas of highs and lows. While the theory of circulation and wind patterns is accurate for large-scale atmospheric circulation, it does not take into account changes to the circulation on a local scale. Local conditions, geological features, and other anomalies can change the wind direction and speed close to Earth's surface. Convective currents. Different surfaces radiate heat in varying amounts. Plowed ground, rocks, sand, and barren land give off large amounts of heat. Water, trees, and other areas of vegetation tend to absorb and retain heat. The resulting uneven heating of the air creates small areas of local circulation called convective currents. Convective currents cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. On a low-altitude flight over varying surfaces, updrafts are likely to occur over pavement or barren places, and downdrafts often occur over water or expansive areas of vegetation like a group of trees. Typically, these turbulent conditions can be avoided by flying at higher altitudes, even above cumulus cloud layers. See Figure 11-12. Convective currents are particularly noticeable in areas with a landmass directly adjacent to a large body of water, such as an ocean, large lake, or other appreciable area of water. During the day, land heats faster than water, so the air over the land becomes warmer and less dense. It rises and is replaced by cooler, denser air flowing in from over the water. This causes an onshore wind called a sea breeze. Conversely, at night, land cools faster than water, as does the corresponding air. In this case, the warmer air over the water rises and is replaced by the cooler, denser air from the land, creating an offshore wind called a land breeze. This reverses the local wind circulation pattern. Convective currents can occur anywhere there is an uneven heating of the Earth's surface. See Figure 11-13. Convective currents close to the ground can affect a pilot's ability to control the aircraft. For example, on final approach, the rising air from terrain devoid of vegetation sometimes produces a ballooning effect that can cause a pilot to overshoot the intended landing spot. On the other hand, an approach over a large body of water or an area of thick vegetation tends to create a sinking effect that can cause an unwary pilot to land short of the intended landing spot. See Figure 11-14. Effect of obstructions on wind. Another atmospheric hazard exists that can create problems for pilots. Obstructions on the ground can affect the flow of wind and can be an unseen danger. Ground topography and large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures like hangars to large natural obstructions, such as mountains, bluffs, or canyons. It is especially important to be vigilant when flying in or out of airports that have large buildings or natural obstructions located near the runway. See Figure 11-15. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the takeoff and landing performance of any aircraft and can present a very serious hazard. During the landing phase of flight, an aircraft may drop in due to the turbulent air and be too low to clear obstacles during the approach. This same condition is even more noticeable when flying in mountainous regions. See Figure 11-16. While the wind flows smoothly up the windward side of the mountain and the upward currents help carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of the mountain. The stronger the wind, the greater the downward pressure and turbulence become. Due to the effect terrain has on the wind in valleys or canyons, downdrafts can be severe. Before conducting a flight in or near mountainous terrain, it is helpful for a pilot unfamiliar with a mountainous area to get a checkout with a mountain-qualified flight instructor. Low-level wind shear. Wind shear is a sudden, drastic change in wind speed and/or direction over a very small area. Wind shear can subject an aircraft to violent updrafts and downdrafts, as well as abrupt changes to the horizontal movement of the aircraft. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the proximity of an aircraft to the ground. Directional wind changes of 180 degrees and speed changes of 50 knots or more are associated with low-level wind shear. Low-level wind shear is commonly associated with passing frontal systems, thunderstorms, and temperature inversions with strong upper-level winds greater than 25 knots. Wind shear is dangerous to an aircraft for several reasons. The rapid changes in wind direction and velocity change the wind's relation to the aircraft, disrupting the normal flight attitude and performance of the aircraft. During a wind shear situation, the effects can be subtle or very dramatic, depending on wind speed and direction of change. For example, a tailwind that quickly changes to a headwind causes an increase in airspeed and performance. Conversely, when a headwind changes to a tailwind, the airspeed rapidly decreases, and there's a corresponding decrease in performance. In either case, a pilot must be prepared to react immediately to the changes to maintain control of the aircraft. In general, the most severe type of low-level wind shear is associated with convective precipitation, or rain from thunderstorms. One critical type of shear associated with convective precipitation is known as a microburst. A typical microburst occurs in a space of less than 1 mile horizontally and within 1,000 feet vertically. The lifespan of a microburst is about 15 minutes, during which it can produce downdrafts of up to 6,000 feet per minute, or FPM. It can also produce a hazardous wind direction change of 45 degrees or more in a matter of seconds. When encountered close to the ground, these excessive downdrafts and rapid changes in wind direction can produce a situation in which it is difficult to control the aircraft. See Figure 11-17. During an inadvertent takeoff into a microburst, the plane first experiences a performance-increasing headwind, followed by a performance-decreasing downdrafts. Then, the wind rapidly shears to a tailwind and can result in terrain impact or flight dangerously close to the ground. Microbursts are often difficult to detect because they occur in relatively confined areas. In an effort to warn pilots of low-level wind shear, alert systems have been installed at several airports around the country. A series of anemometers placed around the airport form a net to detect changes in wind speeds. When wind speeds differ by more than 15 knots, a warning for wind shear is given to pilots. This system is known as the Low-Level Wind Shear Alert System, LLWAS. It is important to remember that wind shear can affect any flight and any pilot at any altitude. While wind shear may be reported, it often remains undetected and is a silent danger to aviation. Always be alert to the possibility of wind shear, especially when flying in and around thunderstorms and frontal systems. Wind and pressure representation on surface weather maps. Surface weather maps provide information about fronts, areas of high and low pressure, and surface winds and pressures for each station. This type of weather map allows pilots to see the locations of fronts and pressure systems, but more importantly, it depicts the wind and pressure at the surface for each location. For more information on surface analysis and weather depiction charts, see Chapter 12, Weather Aviation Services. Wind conditions are reported by an arrow attached to the station location circle. See Figure 11-18. The station circle represents the head of the arrow, with the arrow pointing in the direction from which the wind is blowing. Winds are described by the direction from which they blow. Thus, a northwest wind means that the wind is blowing from the northwest toward the southeast. The speed of the wind is depicted by barbs or pennants placed on the wind line. Each barb represents a speed of 10 knots, while a half barb is equal to 5 knots, and a pennant is equal to 50 knots. The pressure for each station is recorded on the weather chart and is shown in millibars. Isobars are lines drawn on the chart to depict areas of equal pressure. These lines result in a pattern that reveals the pressure gradient or change in pressure over distance. See Figure 11-19. Isobars are similar to contour lines on a topographic map that indicate terrain altitudes and slope steepness. For example, isobars that are closely spaced indicate a steep wind gradient and strong winds prevail. Shallow gradients, on the other hand, are represented by isobars that are spaced far apart and are indicative of light winds. Isobars help identify low and high pressure systems, as well as the locations of ridges, troughs, and cutoff lows, COLs. A high is an area of high pressure surrounded by lower pressure. A low is an area of low pressure surrounded by higher pressure. A ridge is an elongated area of high pressure, and a trough is an elongated area of low pressure. A col is the intersection between a ridge and a trough, or an area of neutrality between two highs and two lows. Isobars furnish valuable information about winds in the first few thousand feet above the surface. Close to the ground, wind direction is modified by the surface and wind speed decreases due to friction with the surface. At levels 2,000 to 3,000 feet above the surface, however, the speed is greater and the direction becomes more parallel to the isobars. Therefore, the surface winds are shown on the weather map, as well as the winds at a slightly higher altitude. Generally, the wind 2,000 feet above ground level, AGL, is 20 degrees to 40 degrees to the right of the surface winds, and the wind speed is greater. The change of wind direction is greatest over rough terrain and least over flat surfaces, such as open water. In the absence of winds aloft information, this rule of thumb allows for a rough estimate of the wind conditions a few thousand feet above the surface. End of Part 2 of Chapter 11. Recording by April Walters. Part 3 of Chapter 11 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 11, Part 3. Atmospheric Stability. The stability of the atmosphere depends on its ability to resist vertical motion. A stable atmosphere makes vertical movement difficult, and small vertical disturbances dampen out and disappear. In an unstable atmosphere, small vertical air movements tend to become larger, resulting in turbulent airflow and convective activity. Instability can lead to significant turbulence, extensive vertical clouds, and severe weather. Rising air expands and cools due to the decrease in air pressure as altitude increases. The opposite is true of descending air. As atmospheric pressure increases, the temperature of descending air increases as it is compressed. Adiabatic heating and adiabatic cooling are terms used to describe this temperature change. The adiabatic process takes place in all upward and downward moving air. When air rises into an area of lower pressure, it expands to a larger volume. As the molecules of air expand, the temperature of the air lowers. As a result, when a parcel of air rises, pressure decreases, volume increases, and temperature decreases. When air descends, the opposite is true. The rate at which temperature decreases with an increase in altitude is referred to as its lapse rate. As air ascends through the atmosphere, the average rate of temperature change is 2 degrees Celsius, or 3.5 degrees Fahrenheit per 1,000 feet. Since water vapor is lighter than air, moisture decreases air density, causing it to rise. Conversely, as moisture decreases, air becomes denser and tends to sink. Since moist air cools at a slower rate, it is generally less stable than dry air, since the moist air must rise higher before its temperature cools to that of the surrounding air. The dry adiabatic lapse rate, unsaturated air, is 3 degrees Celsius, or 5.4 degrees Fahrenheit, per 1,000 feet. The moist adiabatic lapse rate varies from 1.1 degrees Celsius to 2.8 degrees Celsius, or 2 degrees Fahrenheit to 5 degrees Fahrenheit, per 1,000 feet. The combination of moisture and temperature determine the stability of the air and the resulting weather. Cool, dry air is very stable and resists vertical movement, which leads to good and generally clear weather. The greatest instability occurs when the air is moist and warm, as it is in the tropical regions in the summer. Typically, thunderstorms appear on a daily basis in these regions due to the instability of the surrounding air. Inversion. As air rises and expands in the atmosphere, the temperature decreases. There is an atmospheric anomaly that can occur, however, that changes this typical pattern of atmospheric behavior. When the temperature of the air rises with altitude, a temperature inversion exists. Inversion layers are commonly shallow layers of smooth, stable air close to the ground. The temperature of the air increases with altitude to a certain point, which is the top of the inversion. The air at the top of the layer acts as a lid, keeping weather and pollutants trapped below. If the relative humidity of the air is high, it can contribute to the formation of clouds, fog, haze, or smoke, resulting in diminished visibility in the inversion layer. Surface-based temperature inversions occur on clear, cool nights when the air close to the ground is cooled by the lowering temperature of the ground. The air within a few hundred feet of the surface becomes cooler than the air above it. Frontal inversions occur when warm air spreads over a layer of cooler air, or cooler air is forced under a layer of warmer air. Moisture and temperature. The atmosphere, by nature, contains moisture in the form of water vapor. The amount of moisture present in the atmosphere is dependent upon the temperature of the air. Every 20 degrees Fahrenheit increase in temperature doubles the amount of moisture the air can hold. Conversely, a decrease of 20 degrees Fahrenheit cuts the capacity in half. Water is present in the atmosphere in 3 states: liquid, solid, and gaseous. All 3 forms can readily change to another, and all are present within the temperature ranges of the atmosphere. As water changes from one state to another, an exchange of heat takes place. These changes occur through the processes of evaporation, sublimation, condensation, deposition, melting, or freezing. However, water vapor is added into the atmosphere only by the processes of evaporation and sublimation. Evaporation is the changing of liquid water to water vapor. As water vapor forms, it absorbs heat from the nearest available source. This heat exchange is known as the latent heat of evaporation. A good example is the evaporation of human perspiration. The net effect is a cooling sensation as heat is subtracted from the body. Similarly, sublimation is the changing of ice directly to water vapor, completely bypassing the liquid stage. Though dry ice is not made of water, but rather carbon dioxide, it demonstrates the principle of sublimation when a solid turns directly into vapor. Relative humidity. Humidity refers to the amount of water vapor present in the atmosphere at a given time. Relative humidity is the actual amount of moisture in the air compared to the total amount of moisture the air could hold at that temperature. For example, if the current relative humidity is 65%, the air is holding 65% of the total amount of moisture that it is capable of holding at that temperature and pressure. While much of the western United States rarely sees days of high humidity, relative humidity readings of 75 to 90% are not uncommon in the southern United States during warmer months. See Figure 11-20. Temperature-dew point relationship. The relationship between dew points and temperature defines the concept of relative humidity. The dew point, given in degrees, is the temperature at which the air can hold no more moisture. When the temperature of the air is reduced to the dew point, the air is completely saturated, and moisture begins to condense out of the air in the form of fog, dew, frost, clouds, rain, hail, or snow. As moist, unstable air rises, clouds often form at the altitude where temperature and dew point reach the same value. When lifted, unsaturated air cools at a rate of 5.4 degrees Fahrenheit per 1,000 feet, and the dew point temperature decreases at a rate of 1 degree Fahrenheit per 1,000 feet. This results in a convergence of temperature and dew point at a rate of 4.4 degrees Fahrenheit. Apply the convergence rate to the reported temperature and dew point to determine the height of the cloud base. Given temperature T equals 85 degrees Fahrenheit, dew point dP equals 71 degrees Fahrenheit, convergence rate CR equals 4.4 degrees, T minus dP equals temperature dew point spread, TDS. TDS divided by CR equals X. X times 1,000 feet equals height of cloud base AGL. Example: 85 degrees Fahrenheit minus 71 degrees Fahrenheit equals 14 degrees Fahrenheit. 14 degrees Fahrenheit divided by 4.4 degrees Fahrenheit equals 3.18. 3.18 times 1,000 equals 3,180 feet AGL. The height of the cloud base is 3,180 feet AGL. Explanation: with an outside air temperature, OAT, of 85 degrees Fahrenheit at the surface and dew point at the surface of 71 degrees Fahrenheit, the spread is 14 degrees. Divide the temperature dew point spread by the convergence rate of 4.4 degrees Fahrenheit and multiply by 1,000 to determine the approximate height of the cloud base. Methods by which air reaches the saturation point. If air reaches the saturation point while temperature and dew point are close together, it is highly likely that fog, low clouds, and precipitation will form. There are 4 methods by which air can reach the complete saturation point. First, when warm air moves over a cold surface, the air temperature drops and reaches the saturation point. Second, the saturation point may be reached when cold air and warm air mix. Third, when air cools at night through contact with the cooler ground, air reaches its saturation point. The fourth method occurs when air is lifted or is forced upward into the atmosphere. As air rises, it uses heat energy to expand. As a result, the rising air loses heat rapidly. Unsaturated air loses heat at a rate of 3.0 degrees Celsius, 5.4 degrees Fahrenheit, for every 1,000 feet of altitude gain. No matter what causes the air to reach its saturation point, saturated air brings clouds, rain, and other critical weather situations. Dew and frost. On cool, calm nights, the temperature of the ground and objects on the surface can cause temperatures of the surrounding air to drop below the dew point. When this occurs, the moisture in the air condenses and deposits itself on the ground, buildings, and other objects like cars and aircraft. This moisture is known as dew, and sometimes can be seen on grass in the morning. If the temperature is below freezing, the moisture is deposited in the form of frost. While dew poses no threat to an aircraft, frost poses a definite flight safety hazard. Frost disrupts the flow of air over the wing and can drastically reduce the production of lift. It also increases drag, which, when combined with lowered lift production, can adversely affect the ability to take off. An aircraft must be thoroughly cleaned and free of frost prior to beginning a flight. Fog. Fog is a cloud that begins within 50 feet of the surface. It typically occurs when the temperature of air near the ground is cooled to the air's dew point. At this point, water vapor in the air condenses and becomes visible in the form of fog. Fog is classified according to the manner in which it forms and is dependent upon the current temperature and the amount of water vapor in the air. On clear nights, with relatively little to no wind present, radiation fog may develop. See Figure 11-21. Usually, it forms in low-lying areas like mountain valleys. This type of fog occurs when the ground cools rapidly due to terrestrial radiation and the surrounding air temperature reaches its dew point. As the sun rises and the temperature increases, radiation fog lifts and eventually burns off. Any increase in wind also speeds the dissipation of radiation fog. If radiation fog is less than 20 feet thick, then it is known as ground fog. When a layer of warm, moist air moves over a cold surface, advection fog is likely to occur. Unlike radiation fog, wind is required to form advection fog. Winds of up to 15 knots allow the fog to form and intensify. Above a speed of 15 knots, the fog usually lifts and forms low stratus clouds. Advection fog is common in coastal areas where sea breezes can blow the air over cooler land masses. Upslope fog occurs when moist, stable air is forced up sloping land features, like a mountain range. This type of fog also requires wind for formation and continued existence. Upslope and advection fog, unlike radiation fog, may not burn off with the morning sun, but instead can persist for days. They can also extend to greater heights than radiation fog. Steam fog, or sea smoke, forms when cold, dry air moves over warm water. As the water evaporates, it rises and resembles smoke. This type of fog is common over bodies of water during the coldest times of the year. Low-level turbulence and icing are commonly associated with steam fog. Ice fog occurs in cold weather when the temperature is much below freezing and water vapor forms directly into ice crystals. Conditions favorable for its formation are the same as for radiation fog, except for cold temperature, usually minus 25 degrees Fahrenheit or colder. It occurs mostly in the Arctic regions, but is not unknown in middle latitudes during the cold season. Clouds. Clouds are visible indicators and are often indicative of future weather. For clouds to form, there must be adequate weather vapor and condensation nuclei, as well as a method by which the air can be cooled. When the air cools and reaches its saturation point, the invisible water vapor changes into a visible state. Through the process of deposition, also referred to as sublimation, and condensation, moisture condenses or sublimates onto minuscule particles of matter, like dust, salt, and smoke, known as condensation nuclei. The nuclei are important because they provide a means for the moisture to change from one state to another. Cloud type is determined by its height, shape, and behavior. They are classified according to the height of their bases as low, middle, or high clouds, as well as clouds with vertical development. See Figure 11-22. Low clouds are those that form near the Earth's surface and extend up to 6,500 feet AGL. They are made primarily of water droplets, but can include supercooled water droplets that induce hazardous icecraft icing. Typical low clouds are stratus, stratocumulus, and nimbostratus. Fog is also classified as a type of low cloud formation. Clouds in this family create low ceilings, hamper visibility, and can change rapidly. Because of this, they influence flight planning and can make visual flight rules VFR flight impossible. Middle clouds form around 6,500 feet AGL and extend up to 20,000 feet AGL. They are composed of water, ice crystals, and supercooled water droplets. Typical middle-level clouds include altostratus and altocumulus. These types of clouds may be encountered on cross-country flights at higher altitudes. Altostratus clouds can produce turbulence and may contain moderate icing. Altocumulus clouds, which usually form when altostratus clouds are breaking apart, also may contain light turbulence and icing. High clouds form above 20,000 feet AGL and usually form only in stable air. They are made up of ice crystals and pose no real threat of turbulence or aircraft icing. Typical high-level clouds are cirrus, cirrostratus, and cirrocumulus. Clouds with extensive vertical development are cumulus clouds that build vertically into towering cumulus or cumulonimbus clouds. The bases of these clouds form in the low to middle cloud base region, but can extend into high-altitude cloud levels. Towering cumulus clouds indicate areas of instability in the atmosphere, and the air around and inside them is turbulent. These types of clouds often develop into cumulonimbus clouds, or thunderstorms. Cumulonimbus clouds contain large amounts of moisture and unstable air, and usually produce hazardous weather phenomena, such as lightning, hail, tornadoes, gusty winds, and wind shear. These extensive vertical clouds can be obscured by other cloud formations and are not always visible from ground or while in flight. When this happens, these clouds are said to be embedded, hence the term embedded thunderstorms. To pilots, the cumulonimbus cloud is perhaps the most dangerous cloud type. It appears individually or in groups and is known as either an air mass or orographic thunderstorm. Heating of the air near the Earth's surface creates an air mass thunderstorm. The upslope motion of air in the mountainous regions causes orographic thunderstorms. Cumulonimbus clouds that form in a continuous line are non-frontal bands of thunderstorms, or squall lines. Since rising air currents cause cumulonimbus clouds, they are extremely turbulent and pose a significant hazard to flight safety. For example, if an aircraft enters a thunderstorm, the aircraft could experience updrafts and downdrafts that exceed 3,000 ppm. In addition, thunderstorms can produce large hailstones, damaging lightning, tornadoes, and large quantities of water, all of which are potentially hazardous to aircraft. A thunderstorm makes its way through 3 distinct stages before dissipating. It begins with the cumulus stage, in which lifting action of air begins. If sufficient moisture and instability are present, the clouds continue to increase in vertical height. Continuous strong updrafts prohibit moisture from falling. The updraft region grows larger than the individual thermals feeding the storm. Within approximately 15 minutes, the thunderstorm reaches the mature stage, which is the most violent time period of the thunderstorm's life cycle. At this point, drops of moisture, whether rain or ice, are too heavy for the cloud to support and begin falling in the form of rain or hail. This creates a downward motion of the air. Warm rising air, cool precipitation-induced descending air, and violent turbulence all exist within and near the cloud. Below the cloud, the downrushing air increases surface winds and decreases the temperature. Once the vertical motion near the top of the cloud slows down, the top of the cloud spreads out and takes on an anvil-like shape. At this point, the storm enters the dissipating stage. This is when the downdrafts spread out and replace the updrafts needed to sustain the storm. See Figure 11-23. It is impossible to fly over thunderstorms in light aircraft. Severe thunderstorms can punch through the tropopause and reach staggering heights of 50,000 to 60,000 feet, depending on latitude. Flying under thunderstorms can subject aircraft to rain, hail, damaging lightning, and violent turbulence. A good rule of thumb is to circumnavigate thunderstorms identified as severe or giving an intense radar echo by at least 20 nautical miles, (nm), since hail may fall from miles outside of the clouds. If flying around a thunderstorm is not an option, stay on the ground until it passes. Cloud classification can be further broken into specific cloud types according to outward appearance and cloud composition. Knowing these terms can help a pilot identify visible clouds. The following is a list of cloud classifications. Cumulus, heaped or piled clouds. Stratus, formed in layers. Cirrus, ringlets, fibrous clouds, also high cloud levels above 20,000 feet. Castellanus, common base but separate vertical development, castle-like. Lenticularis, lens-shaped, formed over mountains in strong winds. Nimbus, rain-bearing clouds. Fracto, ragged or broken. Alto, meaning high, also middle-level clouds existing at 5,000 to 20,000 feet. Ceiling. For aviation purposes, a ceiling is the lowest layer of clouds reported as being broken or overcast, or the vertical visibility into an obscuration like fog or haze. Clouds are reported as broken when 5/8 to 7/8 of the sky is covered with clouds. Overcast means the entire sky is covered with clouds. Current ceiling information is reported by the Aviation Routine Weather Report, METAR, and automated weather stations of various types. Visibility. Closely related to cloud cover and reported ceiling is visibility information. Visibility refers to the greatest horizontal distance at which prominent objects can be viewed with the naked eye. Current visibility is also reported in METAR and other aviation weather reports, as well as by automated weather systems. Visibility information, as predicted by meteorologists, is available for a pilot during a pre-flight weather briefing. Precipitation. Precipitation refers to any type of water particles that form in the atmosphere and fall to the ground. It has a profound impact on flight safety. Depending on the form of precipitation, it can reduce visibility, create icing situations, and affect landing and takeoff performance of an aircraft. Precipitation occurs because water or ice particles in clouds grow in size until the atmosphere can no longer support them. It can occur in several forms as it falls toward the earth, including drizzle, rain, ice pellets, hail, snow, and ice. Drizzle is classified as very small water droplets, smaller than 0.02 inches in diameter. Drizzle usually accompanies fog or low stratus clouds. Water droplets of larger size are referred to as rain. Rain that falls through the atmosphere but evaporates prior to striking the ground is known as virga. Freezing rain and freezing drizzle occur when the temperature of the surface is below freezing, and the rain freezes on contact with the cooler surface. If rain falls through a temperature inversion, it may freeze as it passes through the underlying cold and fall to the ground in the form of ice pellets. Ice pellets are an indication of a temperature inversion and that freezing rain exists at a higher altitude. In the case of hail, freezing water droplets are carried up and down by drafts inside clouds, growing larger in size as they come in contact with more moisture. Once the updrafts can no longer hold the freezing water, it falls to the earth in the form of hail. Hail can be pea-sized or can grow as large as 5 inches in diameter, larger than a softball. Snow is precipitation in the form of ice crystals that falls at a steady state or in snow showers that begin, change in intensity, and end rapidly. Falling snow also varies in size, being very small grains or large flakes. Snow grains are the equivalent of drizzle in size. Precipitation in any form poses a threat to the safety of flight. Often, precipitation is accompanied by low ceilings and reduced visibility. Aircraft that have ice, snow, or frost on their surfaces must be carefully cleaned prior to beginning a flight because of the possible airflow disruption and loss of lift. Rain can contribute to water in the fuel tanks. Precipitation can create hazards on the runway surface itself, making takeoffs and landings difficult, if not impossible, due to the snow, ice, or pooling water and very slick surfaces. End of Part 3 of Chapter 11. Read by April Walters. Part 4 of Chapter 11 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 11, Part 4. Air Masses. Air masses are classified according to the regions where they originate. They are large bodies of air that take on characteristics of the surrounding area or source region. A source region is typically an area in which the air remains relatively stagnant for a period of days or longer. During this time of stagnation, the air mass takes on the temperature and moisture characteristics of the source region. Areas of stagnation can be found in polar regions, tropical oceans, and dry deserts. Air masses are generally identified as polar or tropical, based on temperature characteristics, and maritime or continental, based on moisture content. A continental polar air mass forms over a polar region and brings cool, dry air with it. Maritime tropical air masses form over warm tropical waters, like the Caribbean Sea, and bring a warm, moist air. As the air mass moves from its source region and passes over land or water, the air mass is subjected to the varying conditions of the land or water, and these modify the nature of the air mass. See Figure 11-24. Note standard air mass abbreviations: Arctic, A, Continental Polar, CP, Maritime Polar, MP, Continental Tropical, CT, and Maritime Tropical, MT. An air mass passing over a warmer surface is warmed from below, and convective currents form, causing the air to rise. This creates an unstable air mass with good surface visibility. Moist, unstable air causes cumulus clouds, showers, and turbulence to form. Conversely, an air mass passing over a colder surface does not form convective currents, but instead creates a stable air mass with poor surface visibility. The poor surface visibility is due to the fact that smoke, dust, and other particles cannot rise out of the air mass and are instead trapped near the surface. A stable air mass can produce low stratus clouds and fog. Fronts. As an air mass moves over bodies of water and land, it eventually comes in contact with another air mass with different characteristics. The boundary layer between two types of air masses is known as a front. An approaching front of any type always means changes to the weather are imminent. There are 4 types of fronts, which are named according to the temperature of the advancing air relative to the temperature of the air it is replacing. See Figure 11-25. Warm, cold, stationary, occluded. Symbols for surface fronts and other significant lines shown on surface analysis charts. Warm front, red. Cold front, blue. Stationary front, red-blue. Occluded front, purple. Note, fronts may be black and white or color, depending on their source. Also, fronts shown in color code will not necessarily show frontal symbols. Any discussion of frontal systems must be tempered with the knowledge that no 2 fronts are the same. However, generalized weather conditions are associated with a specific type of front that helps identify the front. Warm front. A warm front occurs when a warm mass of air advances and replaces a body of colder air. Warm fronts move slowly, typically 10 to 25 miles per hour. The slope of the advancing front slides over the top of the cooler air and gradually pushes it out of the area. Warm fronts contain warm air that often have very high humidity. As the warm air is lifted, the temperature drops and condensation occurs. Generally, prior to the passage of a warm front, cirriform or stratiform clouds, along with fog, can be expected to form along the frontal boundary. In the summer months, cumulonimbus clouds, thunderstorms, are likely to develop. Light to moderate precipitation is probable, usually in the form of rain, sleet, snow, or drizzle, accentuated by poor visibility. The wind blows from the south-southeast, and the outside temperature is cool or cold, with an increasing dew point. Finally, as the warm front approaches, the barometric pressure continues to fall until the front passes completely. During the passage of a warm front, stratiform clouds are visible and drizzle may be falling. The visibility is generally poor, but improves with variable winds. The temperature rises steadily from the inflow of relatively warmer air. For the most part, the dew point remains steady and the pressure levels off. After the passage of a warm front, stratocumulus clouds predominate and rain showers are possible. The visibility eventually improves, but hazy conditions may exist for a short period after passage. The wind blows from the south-southwest. With warming temperatures, the dew point rises and then levels off. There is generally a slight rise in barometric pressure, followed by a decrease of barometric pressure. Flight toward an approaching warm front. By studying a typical warm front, much can be learned about the general patterns and atmospheric conditions that exist when a warm front is encountered in flight. Figure 11-26 depicts a warm front advancing eastward from St. Louis, Missouri, towards Pittsburgh, Pennsylvania. At the time of departure from Pittsburgh, the weather is good VFR, with a scattered layer of cirrus clouds at 15,000 feet. As the flight progresses westward to Columbus and closer to the oncoming warm front, the clouds deepen and become increasingly stratiform in appearance, with a ceiling of 6,000 feet. The visibility decreases to 6 miles in haze with a falling barometric pressure. Approaching Indianapolis, the weather deteriorates to broken clouds at 2,000 feet with 3 miles visibility and rain. With the temperature and dew point the same, fog is likely. At St. Louis, the sky is overcast with low clouds and drizzle, and the visibility is 1 mile. Beyond Indianapolis, the ceiling and visibility would be too low to continue VFR. Therefore, it would be wise to remain in Indianapolis until the warm front had passed, which might require a day or two. Cold front. A cold front occurs when a mass of cold, dense, and stable air advances and replaces a body of warmer air. Cold fronts move more rapidly than warm fronts, progressing at a rate of 25 to 30 miles per hour. However, extreme cold fronts have been recorded moving at speeds up to 60 miles per hour. A typical cold front moves in a manner opposite that of a warm front. It is so dense it stays close to the ground and acts like a snowplow, sliding under the warmer air and forcing the less dense air aloft. The rapidly ascending air causes the temperature to decrease suddenly, forcing the creation of clouds. The type of clouds that form depend on the stability of the warmer air mass. A cold front in the northern hemisphere is normally oriented in a northeast to southwest manner and can be several hundred miles long, encompassing a large area of land. Prior to the passage of a typical cold front, cirriform or towering cumulus clouds are present, and cumulonimbus clouds are possible. Rain showers and haze are possible due to the rapid development of clouds. The wind from the south-southwest helps to replace the warm temperatures with the relative colder air. A high dew point and falling barometric pressure are indicative of an imminent cold front passage. As the cold front passes, towering cumulus or cumulonimbus clouds continue to dominate the sky. Depending on the intensity of the cold front, heavy rain showers form and might be accompanied by lightning, thunder, and/or hail. More severe cold fronts can also produce tornadoes. During cold front passage, the visibility is poor, with winds variable and gusty, and the temperature and dew point drop rapidly. A quickly falling barometric pressure bottoms out during frontal passage, then begins a gradual increase. After frontal passage, the towering cumulus and cumulonimbus clouds begin to dissipate to cumulus clouds with a corresponding decrease in the precipitation. Good visibility eventually prevails with winds from the west-northwest. Temperatures remain cooler, and the barometric pressure continues to rise. Fast-moving cold front. Fast-moving cold fronts are pushed by intense pressure systems far behind the actual front. The friction between the ground and the cold front retards the movement of the front and creates a steeper frontal surface. This results in a very narrow band of weather, concentrated along the leading edge of the front. If the warm air being overtaken by the cold front is relatively stable, overcast skies and rain may occur for some distance ahead of the front. If the warm air is unstable, scattered thunderstorms and rain showers may form. A continuous line of thunderstorms, or squall line, may form along or ahead of the front. Squall lines present a serious hazard to pilots, as squall-type thunderstorms are intense and move quickly. Behind a fast-moving cold front, the skies usually clear rapidly, and the front leaves behind gusty, turbulent winds and colder temperatures. Flight toward an approaching cold front. Like warm fronts, not all cold fronts are the same. Examining a flight toward an approaching cold front, pilots can get a better understanding of the type of conditions that can be encountered in flight. Figure 11-27 shows a flight from Pittsburgh, Pennsylvania, toward St. Louis, Missouri. At the time of departure from Pittsburgh, the weather is VFR with 3 miles visibility in smoke and a scattered layer of clouds at 3,500 feet. As the flight progresses westward to Columbus and closer to the oncoming cold front, the clouds show signs of vertical development with a broken layer at 2,500 feet. The visibility is 6 miles in haze with a falling barometric pressure. Approaching Indianapolis, the weather has deteriorated to overcast clouds at 1,000 feet and 3 miles visibility with thunderstorms and heavy rain showers. At St. Louis, the weather gets better with scattered clouds at 1,000 feet and a 10-mile visibility. A pilot using sound judgment based on the knowledge of frontal conditions would most likely remain in Indianapolis until the front had passed. Trying to fly below a line of thunderstorms or a squall line is hazardous, and flight over the top of or around the storm is not an option. Thunderstorms can extend up to well over the capability of small airplanes and can extend in a line for 300 to 500 miles. Comparison of cold and warm fronts. Warm fronts and cold fronts are very different in nature, as are the hazards associated with each front. They vary in speed, composition, weather phenomenon, and prediction. Cold fronts, which move at 20 to 35 miles per hour, move very quickly in comparison to warm fronts, which move at only 10 to 25 miles per hour. Cold fronts also possess a steeper frontal slope. Violent weather activity is usually associated with cold fronts, and the weather usually occurs during the frontal boundary, not in advance. However, squall lines can form during the summer months as far as 200 miles in advance of a severe cold front. Whereas warm fronts bring low ceilings, poor visibility, and rain, cold fronts bring sudden storms, gusty winds, turbulence, and sometimes hail or tornadoes. Cold fronts are fast approaching with little or no warning, and they make complete weather change in just a few hours. The weather clears rapidly after passage, and drier air with unlimited visibilities prevail. Warm fronts, on the other hand, provide advance warning of their approach and can take days to pass through a region. Wind shifts. Wind around a high-pressure system rotates in a clockwise fashion, while low-pressure winds rotate in a counterclockwise manner. When two pressure systems are adjacent, the winds are almost in direct opposition to each other at the point of contact. Fronts are the boundaries between two areas of pressure, and therefore wind shifts are continually occurring within a front. Shifting wind direction is most pronounced in conjunction with cold fronts. Stationary front. When the forces of two air masses are relatively equal, the boundary or front that separates them remains stationary and influences the local weather for days. This front is called a stationary front. The weather associated with a stationary front is typically a mixture that can be found in both warm and cold fronts. Occluded front. An occluded front occurs when a fast-moving cold front catches up with a slow-moving warm front. As the occluded front approaches, warm front weather prevails, but is immediately followed by cold front weather. There are two types of occluded fronts that can occur, and the temperature of the colliding frontal systems play a large part in defining the type of front and the resulting weather. A cold front occlusion occurs when a fast-moving cold front is colder than the air ahead of the slow-moving warm front. When this occurs, the cold air replaces the cool air and forces the warm front aloft into the atmosphere. Typically, the cold front occlusion creates a mixture of weather found in both warm and cold fronts, providing the air is relatively stable. A warm front occlusion occurs when the air ahead of the warm front is colder than the air of the cold front. When this is the case, the cold front rides up and over the warm front. If the air forced aloft by the warm front occlusion is unstable, the weather is more severe than the weather found in a cold front occlusion. Embedded thunderstorms, rain, and fog are likely to occur. Figure 11-28 depicts a cross-section of a typical cold front occlusion. The warm front slopes over the prevailing cooler air and produces the warm front type weather. Prior to the passage of the typical occluded front, cirriform and stratiform clouds prevail, light to heavy precipitation is falling, visibility is poor, dew point is steady, and barometric pressure is falling. During the passage of the front, nimbostratus and cumulonimbus clouds predominate, and towering cumulus may also be possible. Light to heavy precipitation is falling, visibility is poor, winds are variable, and the barometric pressure is leveling off. After the passage of the front, nimbostratus and altostratus clouds are visible, precipitation is decreasing and clearing, and visibility is improving. Thunderstorms. For a thunderstorm to form, the air must have sufficient water vapor, an unstable lapse rate, and an initial lifting action to start the storm process. Some storms occur at random in unstable air, last for only an hour or two, and produce only moderate wind gusts and rainfall. These are known as air mass thunderstorms and are generally a result of surface heating. Steady-state thunderstorms are associated with weather systems. Fronts, converging winds, and troughs aloft force upward motion spawning these storms, which often form into squall lines. In the mature stage, updrafts become stronger and last much longer than in air mass storms, hence the name steady state. See Figure 11-29. Knowledge of thunderstorms and the hazards associated with them is critical to the safety of flight. Hazards. Weather can pose serious hazards to flight, and a thunderstorm packs just about every weather hazard known to aviation into one vicious bundle. These hazards occur individually or in combination, and most can be found in a squall line. Squall line. A squall line is a narrow band of active thunderstorms. Often it develops on or ahead of a cold front in moist, unstable air, but it may develop in unstable air far removed from any front. The line may be too long to detour easily and too wide and severe to penetrate. It often contains steady-state thunderstorms and presents the single most intense weather hazard to aircraft. It usually forms rapidly, generally reaching maximum intensity during the late afternoon and the first few hours of darkness. Tornadoes. The most violent thunderstorms draw air into their cloud bases with great vigor. If the incoming air has any initial rotating motion, it often forms an extremely concentrated vortex from the surface well into the cloud. Meteorologists have estimated that wind in such a vortex can exceed 200 knots, with pressure inside the vortex quite low. The strong winds gather dust and debris, and the low pressure generates a funnel-shaped cloud extending downward from the cumulonimbus base. If the cloud does not reach the surface, it is a funnel cloud. If it touches a land surface, it is a tornado. Tornadoes occur with both isolated and squall-line thunderstorms. Reports for forecasts of tornadoes indicate that atmospheric conditions are favorable for violent turbulence. An aircraft entering a tornado vortex is almost certain to suffer structural damage. Since the vortex extends well into the cloud, any pilot inadvertently caught on instruments in a severe thunderstorm could encounter a hidden vortex. Families of tornadoes have been observed as appendages of the main cloud, extending several miles outward from the area of lightning and precipitation. Thus, any cloud connected to a severe thunderstorm carries a threat of violence. Turbulence. Potentially hazardous turbulence is present in all thunderstorms, and a severe thunderstorm can destroy an aircraft. Strongest turbulence within the cloud occurs with shear between updrafts and downdrafts. Outside the cloud, shear turbulence has been encountered at several thousand feet above and 20 miles laterally from a severe storm. A low-level turbulent area is the shear zone associated with the gust front. Often, A roll cloud on the leading edge of the storm marks the top of the eddies in this shear, and it signifies an extremely turbulent zone. Gust fronts often move far ahead, up to 15 miles, of associated precipitation. The gust front causes a rapid and sometimes drastic change in surface wind ahead of an approaching storm. Advisory Circular AC 00-50A, low-level wind shear, explains in detail the hazards associated with gust fronts. Figure 1 in the AC shows a schematic truss section of a thunderstorm with areas outside the cloud where turbulence may be encountered. Icing. Updrafts in a thunderstorm support abundant liquid water with relatively large droplet sizes. When carried above the freezing level, the water becomes supercooled. When the temperature in the upward current cools to about minus 15 degrees centigrade, much of the remaining water vapor sublimates as ice crystals. Above this level, at lower temperatures, the amount of supercooled water decreases. Supercooled water freezes on impact with an aircraft. Clear icing can occur at any altitude above the freezing level, but at high levels, icing from smaller droplets may be rime or mixed rime and clear ice. The abundance of large supercooled water droplets makes clear icing very rapid between 0 degrees centigrade and minus 15 degrees centigrade, and encounters can be frequent in a cluster of cells. Thunderstorm icing can be extremely hazardous. Thunderstorms are not the only area where pilots could encounter icing conditions. Pilots should be alert for icing any time that the temperature approaches 0 degrees Celsius and visible moisture is present. Hail. Hail competes with turbulence as the greatest thunderstorm hazard to aircraft. Supercooled drops above the freezing level begin to freeze. Once a drop has frozen, other drops latch on and freeze to it, so the hailstone grows, sometimes into a huge ice ball. Large hail occurs with severe thunderstorms with strong updrafts that have built to great heights. Eventually the hailstones fall, possibly some distance from the storm core. Hail may be encountered in clear air several miles from thunderstorm clouds. As hailstones fall through air whose temperature is above 0 degrees Celsius, they begin to melt, and precipitation may reach the ground as either hail or rain. Rain at the surface does not mean the absence of hail aloft. Possible hail should be anticipated with any thunderstorm, especially beneath the anvil of a large cumulonimbus. Hailstones larger than 1/2 inch in diameter can significantly damage an aircraft in a few seconds. Ceiling and visibility. Generally, visibility is near 0 within a thunderstorm cloud. Ceiling and visibility also may be restricted in precipitation and dust between the cloud base and the ground. The restrictions create the problem as all ceiling and visibility restrictions, but the hazards are multiplied when associated with the other thunderstorm hazards of turbulence, hail, and lightning. Effect on altimeters. Pressure usually falls rapidly with the approach of a thunderstorm, rises sharply with the onset of the first gust and arrival of the cold downdraft and heavy rain showers, and then falls back to normal as the storm moves on. This cycle of pressure change may occur in 15 minutes. If the pilot does not receive a corrected altimeter setting, the altimeter may be more than 100 feet in error. Lightning. A lightning strike can puncture the skin of an aircraft and damage communications and electronic navigational equipment. Although lightning has been suspected of igniting fuel vapors and causing an explosion, serious accidents due to lightning strikes are rare. Nearby lightning can blind the pilot, rendering him or her momentarily unable to navigate, either by instrument or by visual reference. Nearby lightning can also induce permanent errors in the magnetic compass. Lightning discharges, even distant ones, can disrupt radio communications on low and medium frequencies. Though lightning intensity and frequency have no simple relationship to other storm parameters, severe storms, as a rule, have a higher frequency of lightning. Engine water ingestion. Turbine engines have a limit on the amount of water they can ingest. Updrafts are present in many thunderstorms, particularly those in developing stages. if the updraft velocity in the thunderstorm approaches or exceeds the terminal velocity of the falling raindrops, very high concentrations of water may occur. It is possible that these concentrations can be in excess of the quantity of water turbine engines are designed to ingest. Therefore, severe thunderstorms may contain areas of high water concentration, which could result in a flameout and/or structural failure of one or more engines. Chapter Summary. Knowledge of the atmosphere and the forces acting within it to create weather is essential to understand how weather affects a flight. By understanding basic weather theories, a pilot can make sound decisions during flight planning after receiving weather briefings. For additional information on the topics discussed in this chapter, see AC00-6, Aviation Weather for Pilots and Flight Operations Personnel, AC00-24, Thunderstorms, AC00-45, Aviation Weather Services, AC91-74, Pilot Guide Flight in Icing Conditions, and Chapter 7, Section 2 of the Aeronautical Information Manual, AIM. End of Chapter 11. Recording by April Walters.
Part 1 of Chapter 12 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 12. Aviation Weather Services. Introduction. In aviation, weather service is a combined effort of the National Weather Service, NWS, Federal Aviation Administration, FAA, Department of Defense, DoD, other aviation groups, and individuals. Because of the increasing need for worldwide weather services, foreign weather organizations also provide vital input. While weather forecasts are not 100% accurate, meteorologists, through careful scientific study and computer modeling, have the ability to predict weather patterns, trends, and characteristics with increasing accuracy. Through a complex system of weather services, government agencies and independent weather observers, pilots, and other aviation professionals receive the benefit of this vast knowledge base in the form of up-to-date weather reports and forecasts. These reports and forecasts enable pilots to make informed decisions regarding weather and flight safety before and during a flight. Observations. The data gathered from surface and upper altitude observations form the basis of all weather forecasts, advisories, and briefings. There are 4 types of weather observations: surface, upper air, radar, and satellite. Surface aviation weather observations. Surface aviation weather observations, METAR, METARs, are a compilation of elements of the current weather at individual ground stations across the United States. The network is made up of government and privately contracted facilities that provide continuous, up-to-date weather information. Automated weather sources, such as the Automated Weather Observing Systems, AWOS, Automated Surface Observing Systems, ASOS, Air Route Traffic Control Center, ARTCC, facilities, as well as other automated facilities, also play a major role in the gathering of surface observations. Surface observations provide local weather conditions and other relevant information for a radius of 5 miles of a specific airport. This information includes the type of report, station identifier, date and time, modifier as required, wind, visibility, runway visual range, RVR, weather phenomena, sky condition, temperature/dew point, altimeter reading, and applicable remarks. The information gathered for the surface observation may be from a person, an automated station, or an automated station that is updated or enhanced by a weather observer. In any form, the surface observation provides valuable information about individual airports around the country. Although the reports cover only a small radius, the pilot can generate a good picture of the weather over a wide area when many reporting stations are looked at together. Air Route Traffic Control Center, ARTCC. The ARTCC facilities are responsible for maintaining separation between flights conducted under Instrument Flight Rules, IFR, in the en route structure. Center radars, Air Route Surveillance Radar, ARSR, acquire and track transponder returns using the same basic technology as terminal radars. Earlier center radars displayed weather as an area of slashes, light precipitation, and H's, moderate rainfall. Because the controller could not detect higher levels of precipitation, pilots had to be wary of areas showing moderate rainfall. Newer radar displays show weather as 3 shades of blue. Controllers can select the level of weather to be displayed. Weather displays of higher levels of intensity make it difficult for controllers to see aircraft data blocks, so pilots should not expect air traffic control, ATC, to keep weather displayed continuously. Upper air observations. Observations of upper air weather are more challenging than surface observations. There are only 2 methods by which upper air weather phenomena can be observed: radiosonde observations and pilot weather reports, PIREP, PIREPs. A radiosonde is a small cubic instrumentation package which is suspended below a 6-foot hydrogen or helium-filled balloon. Once released, the balloon rises at a rate of approximately 1,000 feet per minute, FPM. As it ascends, the instrumentation gathers various pieces of data, such as air temperature and pressure, as well as wind speed and direction. Once the information is gathered, it is relayed to ground stations via a 300 milliwatt radio transmitter. The balloon flight can last as long as 2 hours or more and can ascend to altitudes as high as 115,000 feet and drift as far as 125 miles. The temperatures and pressures experienced during the flight can be as low as minus 130 degrees Fahrenheit and pressures as low as a few thousandths of what is experienced at sea level. Since the pressure decreases as the balloon rises in the atmosphere, the balloon expands until it reaches the limits of its elasticity. This point is reached when the diameter has increased to over 20 feet. At this point, the balloon pops and the radiosonde falls back to Earth. The descent is slowed by means of a parachute. The parachute aids in protecting people and objects on the ground. Each year, over 75,000 balloons are launched. Of that number, 20% are recovered and returned for reconditioning. Return instructions are printed on the side of each radiosonde. Pilots also provide vital information regarding upper air weather observations and remain the only real-time source of information regarding turbulence, icing, and cloud heights. This information is gathered and filed by pilots in flight. Together, PIREPs and radiosonde observations provide information on upper air conditions important for flight planning. Many domestic and international airlines have equipped their aircraft with instrumentation that automatically transmits in-flight weather observations through the data link system to the airline dispatcher, who disseminates the data to appropriate weather forecasting authorities. Radar observations. Weather observers use 4 types of radar to provide information about precipitation, wind, and weather systems. 1. The WSR-88D NEXRAD radar, commonly called Doppler radar, provides in-depth observations that inform surrounding communities of impending weather. Doppler radar has 2 operational modes, clear air and precipitation. In clear air mode, the radar is in its most sensitive operational mode because a slow antenna rotation allows the radar to sample the atmosphere longer. Images are updated about every 10 minutes in this mode. Precipitation targets provide stronger return signals. Therefore, the radar is operated in the precipitation mode when precipitation is present. A faster antenna rotation in this mode allows images to update at a faster rate, approximately every 4 to 6 minutes. Intensity values in both modes are measured in dBz, decibels of Z, and depicted in color on the radar image, figure 12-1. Intensities are corrected to intensity terminology, phraseology for air traffic control purposes, figures 12-2 and 12-3. Figure 12-3 text. WSR-88D weather radar precipitation intensity terminology. Reflectivity, dBz ranges, weather radar echo intensity. Less than 30 dBz, light. 30 to 40 dBz, moderate. Greater than 40 to 50 dBz, heavy. 50 plus dBz, extreme. End of figure 12-3 text. 2. FAA Terminal Doppler Weather Radar, TWWR, installed at some major airports around the country, also aids in providing severe weather alerts and warnings to ATC. Terminal radar ensures pilots are aware of wind shear, gust fronts, and heavy precipitation, all of which are dangerous to arriving and departing aircraft. 3. The third type of radar commonly used in the detection of precipitation is the FAA Airport Surveillance Radar. This radar is used primarily to detect aircraft, but it also detects the location and intensity of precipitation, which is used to route aircraft traffic around severe weather in an airport environment. 4. Airborne radar is equipment carried by aircraft to locate weather disturbances. The airborne radars generally operate in the C or X bands, around 6 GHz or around 10 GHz, respectively, permitting both penetration of heavy precipitation, required for determining the extent of thunderstorms, and sufficient reflection from less intense precipitation. Satellite. Advancement in satellite technologies has recently allowed for commercial use to include weather uplinks. Through the use of satellite subscription services, individuals are now able to receive satellite-transmitted signals that provide near real-time weather information for the North American continent. Satellite weather. Recently, private enterprise and satellite technology have expanded the realm of weather services. Pilots now have the capability of receiving continuously updated weather across the entire continent at any altitude. No longer are pilots restricted by radio range or geographic isolations such as mountains or valleys. In addition, pilots no longer have to request specific information from weather briefing personnel directly. When the weather becomes questionable, radio congestion often increases, delaying the timely exchange of valuable in-flight weather updates for a pilot's specific route of flight. Flight Service Station, FSS personnel, can communicate with only one pilot at a time, which leaves other pilots waiting and flying in uncertain weather conditions. Satellite weather provides the pilot with a powerful resource for enhanced situational awareness at any time. Due to continuous satellite broadcasts, pilots can obtain a weather briefing by looking at a display screen. Pilots have a choice between FAA-certified devices or portable receivers as a source of weather data. Satellite weather products. Significant meteorological information, SIGMET. SIGMETs are weather advisories issued concerning weather significant to the safety of all aircraft. SIGMET advisories can cover an area of at least 3,000 square miles and can provide data regarding severe and extreme turbulence, severe icing, and widespread dust or sandstorms that reduce visibility to less than 3 miles. Figure 12-4. Airmen's meteorological information, AirMet. AirMets are weather advisories issued only to amend the area forecast concerning weather phenomena which were of operational interest to all aircraft and potentially hazardous to aircraft having limited capability because of lack of equipment, instrumentation, or pilot qualifications. AirMets concern weather of less severity than that covered by SIGMETs or convective SIGMETs. Airmets cover moderate icing, moderate turbulence, sustained winds of 30 knots or more at the surface, widespread areas of ceilings less than 1,000 feet, and or visibility less than 3 miles, and extensive mountain obscurement. Figure 12-5. Service outlets. Service outlets are government or private facilities that provide aviation weather services. Several different government agencies, including the FAA, National Oceanographic and Atmospheric Administration, NOAA, and the NWS, work in conjunction with private aviation companies to provide different means of accessing weather information. Automated Flight Service Station, AFSS. The AFSS is the primary source for pre-flight weather information. A pre-flight weather briefing from an AFSS can be obtained 24 hours a day by calling 1-800-WX-BRIEF, WX Brief, from almost anywhere in the United States. In areas not served by an AFSS, NWS facilities may provide pilot weather briefings. Telephone numbers for NWS facilities and additional numbers for AFSS can be found in the Airport Facility Directory, A/FD, or in the United States Government section of the telephone book. The AFSS also provides in-flight weather briefing services, as well as scheduled and unscheduled weather broadcasts. An AFSS may also furnish weather advisories to flights within the AFSS region of authority. Transcribed Information Briefing Services, TIBS. The Transcribed Information Briefing Service, TIBS, is a service prepared and disseminated by selected AFSS. It provides continuous telephone recordings of meteorological and aeronautical information. Specifically, TIBS provides area and route briefings, airspace procedures, and special announcements. It is designed to be a preliminary briefing tool and is not intended to replace a standard briefing from a FSS specialist. The TIBS service is available 24 hours a day and is updated when conditions change, but it can only be accessed by a touch-tone phone. The phone numbers for the TIBS service are listed in the A/FD. Direct User Access Terminal Services, DUATS, DUATS. The Direct User Access Terminal Service, DUATS, which is funded by the FAA, allows any pilot with a current medical certificate to access weather information and file a flight plan via computer. Two methods of access are available to connect with DUATS. The first is via the internet at http://www.duats.com. The second method requires a modem and communications program supplied by a DUATS provider. To access the weather information and file a flight plan by this method, pilots use a toll-free number to connect the user's computer directly to the DUATS computer. The current vendors of DUATS service and associated phone numbers are listed in Chapter 7, Safety of Flight, of the Aeronautical Information Manual, AIM. En route Flight Advisory Service, EFAS. A service specifically designed to provide timely en route weather information upon pilot request is known as the En route Flight Advisory Service, EFAS, or Flight Watch. EFAS provides a pilot with weather advisories tailored to the type of flight, route, and cruising altitude. EFAS can be one of the best sources for current weather information along the route of flight. A pilot can usually contact an EFAS specialist from 6 a.m. to 10 p.m. anywhere in the conterminous United States and Puerto Rico. The common EFAS frequency, 122.0 megahertz, is established for pilots of aircraft flying between 5,000 feet above ground level, AGL, and 17,500 feet mean sea level, MSL. Hazardous In-Flight Weather Advisory, HIWAS, HIWAS. Hazardous In-Flight Weather Advisory, HIWAS, is a national program for broadcasting hazardous weather information continuously over selected navigation aids, NavAids. The broadcasts include advisories such as AirMets, SIGMETs, convective SIGMETs, and urgent PIREPs. These broadcasts are only a summary of the information, and pilots should contact a FSS or EFAS for detailed information. NavAids that have HIWAS capability are depicted on sectional charts with an H in the upper right corner of the identification box, Figure 12-6. Transcribed Weather Broadcast, TWEB, Alaska only. Equipment is provided in Alaska by which meteorological and aeronautical data are recorded on tapes and broadcast continuously over selected low or medium frequency, L/MF, and very high frequency, VHF, omnidirectional radio range navigation system, VOR, facilities. Broadcasts are made from a series of individual tape recordings, and changes, as they occur, are transcribed onto the tapes. The information provided varies depending on the type of equipment available. Generally, the broadcast contains a summary of adverse conditions, surface weather observations, PIREPs, and a density altitude statement, if applicable. At the discretion of the broadcast facility, recordings may also include a synopsis, winds aloft forecast, en route and terminal forecast data, and radar reports. At selected locations, telephone access to the TWEB has been provided, TEL-TWEB. Telephone numbers for this service are found in the supplement Alaska, A/FD. These broadcasts are made available primarily for pre-flight and in-flight planning, and as such should not be considered as a substitute for specialist-provided pre-flight briefings. End of Part 1 of Chapter 12. Part 2 of Chapter 12 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Pilot's Handbook of Aeronautical Knowledge by the FAA. Weather briefings. Prior to every flight, pilots should gather all information vital to the nature of the flight. This includes an appropriate weather briefing obtained from a specialist at a FSS, AFSS, or NWS. For weather specialists to provide an appropriate weather briefing, they need to know which of the three types of briefings is needed: standard, abbreviated, or outlook. Other helpful information is whether the flight is visual flight rules, VFR, or IFR, aircraft identification and type, departure point, estimated time of departure, ETD, flight altitude, route of flight, destination, and estimated time en route, ETE. This information is recorded in the flight plan system, and a note is made regarding the type of weather briefing provided. If necessary, it can be referenced later to file or amend a flight plan. It is also used when an aircraft is overdue or is reported missing. Standard briefing. A standard briefing is the most complete report and provides the overall weather picture. This type of briefing should be obtained prior to the departure of any flight and should be used during flight planning. A standard briefing provides the following information in sequential order if it is applicable to the route of flight. 1. Adverse conditions. This includes information about adverse conditions that may influence a decision to cancel or alter the route of flight. Adverse conditions include significant weather, such as thunderstorms or aircraft icing, or other important items such as airport closings. 2. VFR flight not recommended. If the weather for the route of flight is below VFR minimums, or if it is doubtful the flight could be made under VFR conditions due to the forecast weather, the briefer may state that VFR is not recommended. It is the pilot's decision whether or not to continue the flight under VFR, but this advisory should be weighed carefully. 3. Synopsis, an overview of the larger weather picture. Fronts and major weather systems that affect the general area are provided. 4. Current conditions. This portion of the briefing contains the current ceilings, visibility, winds, and temperatures. If the departure time is more than 2 hours away, current conditions are not included in the briefing. 5. En route forecast. A summary of the weather forecast for the proposed route of flight. 6. Destination forecast. A summary of the expected weather for the destination airport at the estimated time of arrival, ETA. 7. Winds and temperatures aloft. A report of the winds at specific altitudes for the route of flight. The temperature information is provided only on request. 8. Notices to airmen. NOTAM. NOTAM. Information pertinent to the route of flight, which has not been published in the NOTAM publication. Published NOTAM information is provided during the briefing only when requested. 9. ATC delays. An advisory of any known ATC delays that may affect the flight. 10. Other information. At the end of the standard briefing, the FSS specialist provides the radio frequencies needed to open a flight plan and to contact EFAS. Any additional information requested is also provided at this time. Abbreviated briefing. An abbreviated briefing is a shortened version of the standard briefing. It should be requested when a departure has been delayed or when weather information is needed to update the previous briefing. When this is the case, the weather specialist needs to know the time and source of the previous briefing, so the necessary weather information will not be omitted inadvertently. It is always a good idea to update weather whenever a pilot has additional time. Outlook briefing. An outlook briefing should be requested when a planned departure is 6 hours or more away. It provides initial forecast information that is limited in scope due to the time frame of the planned flight. This type of briefing is a good source of flight planning information that can influence decisions regarding route of flight, altitude, and ultimately the go, no-go decision. A prudent pilot requests a follow-up briefing prior to departure, since an outlook briefing generally only contains information based on weather trends and existing weather in geographical areas at or near the departure airport. A standard briefing near the time of departure ensures the pilot has the latest information available prior to their flight. Aviation weather reports. Aviation weather reports are designed to give accurate depictions of current weather conditions. Each report provides current information that is updated at different times. Some typical reports are METAR, PIREPs, and Radar Weather Reports, SDs. Aviation Routine Weather Report, METAR. METAR. A METAR is an observation of current service weather reported in a standard international format. While a METAR code has been adopted worldwide, each country is allowed to make modifications to the code. Normally these differences are minor, but necessary to accommodate local procedures or particular units of measure. This discussion of METAR will cover elements used in the United States. METARs are issued hourly unless significant weather changes have occurred. A special METAR, SPECI, can be issued at any interval between routine METAR reports. Example: METAR, METAR, KGGG 161753Z, Auto 14021G26, 3/4SM, plus TSRA, BR, BKN 008, OVC 012CB, 18/17, A2970, RMK, PRESFR. A typical METAR report contains the following information in sequential order. 1. Type of report. There are two types of METAR reports: The first is the routine METAR report that is transmitted every hour. The second is the Aviation Selected SPECI. This is a special report that can be given at any time to update the METAR for rapidly changing weather conditions, aircraft mishaps, or other critical information. 2. The Station Identifier. A 4-letter code is established by the International Civil Aviation Organization, ICAO. In the 48 contiguous states, a unique 3-letter identifier is preceded by the letter K. For example, Gregg County Airport in Longview, Texas is identified by the letters KGGG, K being the country designation and GGG being the airport identifier. In other regions of the world, including Alaska and Hawaii, the first 2 letters of the 4-letter ICAO identifier indicate the region, country, or state. Alaska identifiers always begin with the letters PA. Hawaii identifiers always begin with the letters PH. A list of station identifiers can be found in an FSS or NWS office. 3. Date and time of report. Depicted in a 6-digit group, 161753Z, the first 2 digits are the date. The last 4 digits are the time of the METAR, which is always given in Coordinated Universal Time, UTC. A Z is appended to the end of the time to denote the time is given in Zulu time, UTC, as opposed to local time. 4. Modifier. Denotes that the METAR came from an automated source or that the report was corrected. If the notation AUTO auto is listed in the METAR, the report came from an automated source. It also lists AO1 or AO2 in the remarks section to indicate the type of precipitation sensors employed at the automated station. When the modifier COR is used, it identifies a corrected report sent to replace an earlier report that contained an error. For example, METAR KGGG 161753Z COR. 5. Wind. Reported with 5 digits 14021, unless the speed is greater than 99 knots, in which case the wind is reported with 6 digits. The first 3 digits indicate the direction the true wind is blowing in tens of degrees. If the wind is variable, it is reported as VRB. The last 2 digits indicate the speed of the wind in knots, unless the wind is greater than 99 knots, in which case it is indicated by 3 digits. If the winds are gusting, the letter G follows the wind speed, G26. After the letter G, the peak gust recorded is provided. If the wind varies more than 60 degrees and the wind speed is greater than 6 knots, a separate group of numbers, separated by a V, will indicate the extremes of the wind direction. Figure 12-7 shows how the TDWR/Weather System Processor, WSP, determines the true wind, as well as gust front/wind shear location. 6. Visibility. The prevailing visibility, 3/4 SM, is reported in statute miles, as denoted by the letters SM. It is reported in both miles and fractions of miles. At times, runway visual range, RVR, is reported following the prevailing visibility. RVR is the distance a pilot can see down the runway in a moving aircraft. When RVR is reported, it is shown with an R, then the runway number, followed by a slant, then the visual range in feet. For example, when the RVR is reported as R17L/1400FT, it translates to a visual range of 1,400 feet on runway 17 left. 7. Weather can be broken down into 2 different categories, qualifiers and weather phenomenon, plus TSRA, BR. First, the qualifiers of intensity, proximity, and the descriptor of the weather will be given. The intensity may be light, minus, moderate, no symbol, or heavy, plus. Proximity only depicts weather phenomena that are in the airport vicinity. The notation VC indicates a specific weather phenomenon is in the vicinity of 5 to 10 miles from the airport. Descriptors are used to describe certain types of precipitation and obscurations. Weather phenomena may be reported as being precipitation, obscurations, and other phenomena such as squalls or funnel clouds. Descriptions of weather phenomena as they begin or end and hailstone size are also listed in the remarks section of the report. Figure 12-8, read at the end of this audio section. 8. Sky condition, always reported in the sequence of amount, height, and type or indefinite ceiling / height, vertical visibility, BKN 008, OVC 012 CB. The heights of the cloud bases are reported with a 3-digit number in hundreds of feet AGL. Clouds above 1,200 feet are not detected or reported by an automated station. The types of clouds, specifically towering cumulus, TCU, or cumulonimbus, CB clouds, are reported with their height. Contractions are used to describe the amount of cloud coverage and obscuring phenomena. The amount of sky coverage is reported in eighths of the sky from horizon to horizon. Figure 12-9, read at the end of this audio section. 9. Temperature and dew point. The air temperature and dew point are always given in degrees Celsius, C, or degrees C, 18/17. Temperatures below 0 degrees C are preceded by the letter M to indicate minus. Altimeter setting, reported as inches of mercury, inches HG, in a 4-digit number group, A2970. It is always preceded by the letter A. Rising or falling pressure may also be denoted in the remarks section as PRES-RR or PRES-FR, respectively. 11. Zulu time, a time used in aviation for UTC, which places the entire world on one time standard. 12. Remarks. The remarks section always begins with the letters RMK. Comments may or may not appear in this section of the METAR. The information contained in this section may include wind data, variable visibility, beginning and ending times of particular phenomenon, pressure information, and various other information deemed necessary. An example of a remark regarding weather phenomenon that does not fit in any other category would be OCNL LTGICCG. This translates as occasional lightning in the clouds and from cloud to ground. Automated stations also use the remarks section to indicate equipment needs maintenance. Example, METAR KGGG 161753 Zulu, Auto 14021G26 3/4 SM plus TSRA BR BKN 008 OVC 012 CB 18/17 A2970 RMK PRES-FR. Explanation of example. METAR KGGG 161753Z AUTO Auto. Routine METAR for Gregg County Airport for the 16th day of the month at 1753 Zulu Automated Source. 14021G26. Winds are 140 at 21 knots, gusting to 26. 3/4 SM. Visibility is 3/4 statute mile. plus TSRA. Thunderstorms with heavy rain and mist. BR, BKN 008, OVC 012, CB. Ceiling is broken at 800 feet, overcast at 1,200 feet with cumulonimbus clouds. 18/17. Temperature 18 degrees Celsius and dew point 17 degrees Celsius. A2970, RMK, PRES, FR. Barometric pressure is 29.70 inches mercury and falling rapidly. Pilot weather reports, PIREPs. PIREPs provide valuable information regarding the conditions as they actually exist in the air, which cannot be gathered from any other source. Pilots can confirm the height of bases and the tops of clouds, locations of wind shear and turbulence, and the location of in-flight icing. If the ceiling is below 5,000 feet, or visibility is at or below 5 miles, ATC facilities are required to solicit PIREPs from pilots in the area. When unexpected weather conditions are encountered, pilots are encouraged to make a report to a FSS or ATC. When a pilot weather report is filed, the ATC facility, or FSS, will add it to the distribution system to brief other pilots and provide in-flight advisories. PIREPs are easy to file, and a standard reporting form outlines the manner in which they should be filed. Figure 12-10, read at the end of this audio section, shows the elements of a PIREP form. Item numbers 1 through 5 are required information when making a report, as well as at least one weather phenomenon encountered. A PIREP is normally transmitted as an individual report, but may be appended to a surface report. Pilot reports are easily decoded, and most contractions used in the reports are self-explanatory. Example: UA/OVGGG 090-025 /TM 1450 /FL 060 /TP C182 /SK 080 OVC /WX FV 04R /TA 05 /WV 270030 /TB LGT /RM HVY RAIN. Explanation: UA type routine pilot report /OVGGG 090-025 location 25 nautical miles out on the 90-degree radial, Gray County, VOR /TM 1450 time 1450 Zulu /FL 060 altitude or flight level 6,000 feet /TP C182 aircraft type Cessna 182 /SK 080 OVC sky cover 8,000 overcast /WX FV 04R visibility /weather 4 miles in rain /TA 05 temperature 5 degrees Celsius /WV 270030 wind 270 degrees at 30 knots /TB LGT turbulence light icing none reported /RM HVY RAIN remarks rain is heavy. Radar weather reports RAREP RAREP Areas of precipitation and thunderstorms are observed by radar on a routine basis. Radar weather reports, RAREPs, or storm detections, SDs, are issued by radar stations at 35 minutes past the hour, with special reports issued as needed. RAREPs provide information on the type, intensity, and location of the echo top of the precipitation. Figure 12-11, read at the end of this audio section. These reports may also include direction and speed of the area of precipitation, as well as the height and base of the precipitation in hundreds of feet MSL. RAREPs are especially valuable for pre-flight planning to help avoid areas of severe weather. However, radar only detects objects in the atmosphere that are large enough to be considered precipitation. Cloud bases and tops, ceilings, and visibility are not detected by radar. A typical RAREP will include location identifier and time of radar observation, echo pattern, 1. Line, LN. A line of precipitation echoes at least 30 miles long, at least 4 times as long as it is wide, and at least 25% coverage within the line. 2. Area, AREA, area. A group of echoes of similar type and not classified as a line. 3. Single cell, CELL, cell. A single isolated convective echo, such as a rain shower. Area coverage in tenths. Type and intensity of weather. Azimuth, referenced to true north and range in nautical miles from the radar site of points defining the echo pattern. For lines and areas, there will be 2 azimuth and range sets that define the pattern. For cells, there will be only 1 azimuth and range set. Dimension of echo pattern, given when the azimuth and range define only the center of the pattern. Cell movement. Movement is coded only for cells. It will not be coded for lines or areas. Maximum top of precipitation and location. Maximum tops may be coded with the symbols MT or MTS. If it is coded with MTS, it means that satellite data as well as radar information was used to measure the top of the precipitation. If the contraction AUTO auto appears in the report, it means the report is automated from WSR-88D weather radar data. The last section is primarily used to prepare radar summary charts, but it can be used during pre-flight to determine the maximum precipitation intensity within a specific grid box. The higher the number, the greater the intensity. 2 or more numbers appearing after a grid box reference, such as PM34, indicates precipitation in consecutive grid boxes. Example: TLX 1935 LN 8 TRW ++ 86/40 199/115 20W C2425 MTS 570 AT 159/65 AUTO auto caret M01 NO2 ON3 PM34 QM3 RL2 =. Explanation. The radar report gives the following information. The report is automated from Oklahoma City and was made at 1935 UTC. The echo pattern for this report indicates a line of echoes covering 8/10 of the area. Thunderstorms and very heavy rain showers are indicated. The next set of numbers indicates the azimuth that defines the echo, 86 degrees at 40 nautical miles, and 199 degrees at 115 nautical miles. The dimension of this echo is given as 20 nautical miles wide, 10 nautical miles on either side of the line defined by the azimuth and range. The cells within the line are moving from 240 degrees at 25 knots. The maximum top of the precipitation, as determined by radar and satellite, is 57,000 feet, and it is located on the 159-degree radial, 65 nautical miles out. The last line indicates the intensity of the precipitation. For example, in grid QM, the intensity is 3, or heavy precipitation. 1 is light and 6 is extreme. Figures 12-8 through 12-11 will now be read. Figure 12-8, text. Descriptors and weather phenomena used in a typical METAR. The weather groups are constructed by considering columns 1 through 5 in this table in sequence. Intensity, followed by descriptor, followed by weather phenomena, e.g., heavy rain showers, is coded as plus SHRA. Qualifier, intensity or proximity 1, minus sign, light. No qualifier, moderate, plus sign, heavy. VC, in the vicinity. Descriptor 2, MI, shallow, BC, patches, DR, low drifting, BL, blowing, SH, showers, TS, thunderstorms, FZ, freezing, PR, partial. Weather phenomena. Precipitation, 3. DZ, drizzle, RA, rain, SN, snow, SG, snow grains, IC, ice crystals, diamond dust, PL, ice pellets, GR, hail, GS, small hail or snow pellets, UP, unknown precipitation, from automated stations only. Obscuration, 4. BR, mist, FG, fog, FU, smoke, DU, dust, SA, sand, HZ, haze, PY, spray, VA, volcanic ash. Other, 5. PO, dust/sand whirls, SQ, squalls, FC, funnel cloud, plus FC, tornado or waterspout, SS, sandstorm, DS, dust storm. End of Figure 12-8 text. Figure 12-9 text. Reportable contractions for sky conditions. Sky cover and contraction. Less than 1/8, clear. SKC, CLR, FEW. 1/8 through 2/8, few. Contraction, FEW. 3/8 through 4/8, scattered. Contraction, SCT. 5/8 through 7/8, broken. Contraction, BKN. 8/8 or overcast. Contraction, OVC. End of Figure 12-9 text. Figure 12-10, text. PIREP encoding and decoding. Encoding pilot weather reports, PIREPs. 1. XXX, 3-letter station identifier. Nearest weather reporting location to the reported phenomenon. 2. UA, routine PIREP. UUA, urgent PIREP. 3. /OV, location. Use 3-letter NavAid idents only. A, fix. /OV, ABC, also /OV, ABC 090025. B, fix. /OV, ABC 045020-DEF. Also /OV, ABC-DEF /GHI. 4/TM, time, 4 digits in UTC /TM 0915. 5/FL, altitude /flight level, 3 digits for hundreds of feet. If not known, use UNKN /FL095, also /FL310 /FLUNKN. 6/TP, type aircraft, 4 digits maximum. If not known, use UNKN /TP-L329 /TP-B727 /TP-UNKN. 7/SK, sky cover /cloud layers. Describe as follows. A, height of cloud base in hundreds of feet. If unknown, use UNKN. B, cloud cover symbol. C, height of cloud tops in hundreds of feet. 8/WX, weather. Flight visibility reported first. Use standard weather symbols. Intensity is not reported. /WX, FV02, RH. /WX, FV01, TRW. 9/TA, air temperature in Celsius, C. If below 0, prefix with a hyphen, /TA 15, /TA -06. 10/WV, wind, direction in degrees magnetic north, and speed, in 6 digits, /WV 270045, WV 280110. 11/TB, turbulence. Use standard contractions for intensity and type. Use CAT or CHOP when appropriate. Include altitude only if different from /FL. /TB, EXTREME, extreme. /TB, LGT-MDT, BLO 090. 12/IC, icing. Describe using standard intensity and type contractions. Include altitude only if different than /FL. /IC, LGT-MDT, RIME. /IC, SVR, CLR 028-045. 13/RM, remarks. Use freeform to clarify the report and type hazardous elements first. /RM, LLWS -15 knots, SFC -030, DURC, RNWI 22, JFK. End of Figure 12-10 text. Figure 12-11 text. Radar weather report codes. Symbol and meaning. R, rain. RW, rain shower. S, snow. SW, snow shower. T, thunderstorm. Symbol and intensity. Minus, light. None, moderate. Plus, heavy. Plus, very heavy. X, intense. XX, extreme. Contraction and operational status. PPINE. Radar is operating normally, but there are no echoes being detected. PPINA. Radar observation is not available. PPIOM. Radar is inoperative or out of service. AUTO. Automated Weather Report from WSR-88D. End of Figure 12-11 text. End of Part 2 of Chapter 12.
Part 3 of Chapter 12 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 3 of Chapter 12, Aviation Weather Services. Aviation Forecasts. Observed weather condition reports are often used in the creation of forecasts for the same area. A variety of different forecast products are produced and designed to be used in the pre-flight planning stage. The printed forecasts that pilots need to be familiar with are the Terminal Aerodrome Forecast, TAF, Aviation Area Forecast, FA, In-Flight Weather Advisories, SIGMET, AirMet, and the Winds and Temperature Aloft Forecast, FD. Terminal Aerodrome Forecasts, TAF. A TAF is a report established for the 5 statute-mile radius around an airport. TAF reports are usually given for larger airports. Each TAF is valid for a 30-hour time period and is updated 4 times a day at 0000 Zulu, 0600 Zulu, 1200 Zulu, and 1800 Zulu. The TAF utilizes the same descriptors and abbreviations as used in the METAR report. The TAF includes the following information in sequential order. 1. Type of report. A TAF can be either a routine forecast, TAF, or an amended forecast, TAF-AMD. 2. ICAO Station Identifier. The station identifier is the same as that used in a METAR. 3. Date and time of origin. Time and date of TAF origination is given in the 6-number code, with the first 2 being the date, the last 4 being the time. Time is always given in UTC, as denoted by the Z following the number group. 4. Valid period dates and times, either 24 or 30 hours. The first 2 digits of each 4-digit number indicate the date of the valid period. The final 2 digits indicate the time. 5. Forecast wind. The wind direction and speed forecast are given in a 5-digit number group. The first 3 indicate the direction of the wind in reference to true north. The last 2 digits state the wind speed in knots as denoted by the letters KT. Like the METAR, winds greater than 99 knots are given in 3 digits. 6. Forecast visibility. Given in statute miles and may be in whole numbers or fractions. If the forecast is greater than 6 miles, it will be coded as P6SM. 7. Forecast significant weather. Weather phenomena are coded in the TAF reports in the same format as the METAR. If no significant weather is expected during the forecast time period, the denotation NSW is included in the becoming or temporary weather groups. 8. Forecast sky condition, given in the same manner as the METAR. Only cumulonimbus, CB clouds, are forecast in this portion of the TAF report, as opposed to CBs and towering cumulus in the METAR. 9. Forecast change group. For any significant weather change forecast to occur during the TAF time period, the expected conditions and time period are included in this group. This information may be shown as from, FM, becoming, BECMG, and temporary, TEMPO. FM is used when a rapid and significant change, usually within an hour, is expected. BECMG is used when a gradual change in the weather is expected over a period of no more than 2 hours. Tempo is used for temporary fluctuations of weather expected to last less than 1 hour. 10. Probability forecast. a given percentage that describes the probability of thunderstorms and precipitation occurring in the coming hours. This forecast is not used for the first 6 hours of the 24-hour forecast. Example: TAF, KPIR 111130Z 1112/1212, tempo 1112/1114, FM 1500, 16015G25KT, P6SM, SCT 040, BKN 250, FM 0000, 14012KT, P6SM, BKN 080, OVC 150, PROB 400004, 3SM, TSRA, BKN 030CB, FM 0400, 1408KT, P6SM, SCT 040, OVC 080, tempo 0408, 3SM, TSRA, OVC 030CB, BECMG 0810, 32007KT, =. Explanation: Routine TAF for Pierre, South Dakota, on the 11th day of the month at 11:30 Zulu, valid for 24 hours from 1200 Zulu on the 11th to 1200 Zulu on the 12th. Wind from 150 degrees at 12 knots, visibility greater than 6 miles, broken clouds at 9,000 feet. Temporarily, between 1200 Zulu and 1400 Zulu, visibility 5 statute miles in mist. From 1500 Zulu, winds from 160 degrees at 15 knots, gusting to 25 knots, visibility greater than 6 miles, clouds scattered at 4,000 feet and broken at 25,000 feet. From 0000 Zulu, wind from 140 degrees at 12 knots, visibility greater than 6 miles, clouds broken at 8,000 feet, overcast at 15,000 feet. Between 0100 Zulu and 0400 Zulu, there is a 40% probability of visibility 3 statute miles, thunderstorm with moderate rain showers, clouds broken at 3,000 feet with cumulonimbus clouds. From 0400 Zulu, winds from 140 degrees at 8 knots, visibility greater than 6 miles, clouds at 4,000 scattered and overcast at 8,000. Temporarily, between 0400 Zulu and 0800 Zulu, visibility 3 miles, thunderstorms with moderate rain showers, clouds overcast at 3,000 feet with cumulonimbus clouds. Becoming between 0800 Zulu and 1000 Zulu, wind from 320 at 7 knots, end of report, the =. Area forecasts, FA. The FA gives a picture of clouds, general weather conditions, and visual meteorological conditions, VMC, expected over a large area encompassing several states. There are 6 areas for which area forecasts are published in the contiguous 48 states. Area forecasts are issued 3 times a day and are valid for 18 hours. This type of forecast gives information vital to en route operations, as well as forecast information for smaller airports that do not have terminal forecasts. Area forecasts are typically disseminated in 4 sections and include the following information. 1. Header. Gives the location identifier of the source of the FA, the date and time of issuance, the valid forecast time, and the area of coverage. Example: DFWC FA 120945. Synopsis and VFR CLDS /WX. Synopsis valid until 130400. CLDS/WX valid until 122200. OTLK valid 122200-1304000. OKTX, AR, LA, MS, AL, and CSTL WTRS. Explanation. The area forecast shows information given by Dallas-Fort Worth for the region of Oklahoma, Texas, Arkansas, Louisiana, Mississippi, and Alabama, as well as a portion of the Gulf coastal waters. It was issued on the 12th day of the month at 0945. The synopsis is valid from the time of issuance until 0400 hours on the 13th. VFR clouds and weather information on this area forecast are valid until 2200 hours on the 12th, and the outlook is valid until 0400 hours on the 13th. 2. Precautionary statements. IFR conditions, mountain obscurations, and thunderstorm hazards are described in this section. Statements made here regarding height are given in MSL, and if given otherwise, AGL or ceiling, CIG, will be noted. Example. See AirMet Sierra for IFR CONDS and MTN OBSCN. TS imply SEV or GTR TURB, SEV, ICE, LLWS, and IFR CONDS. Non-MSL HGTS denoted by AGL or CIG. Explanation. The area forecast covers VFR clouds and weather, so the precautionary statement warns that AirMet Sierra should be referenced for IFR conditions and mountain obscuration. The code TS indicates the possibility of thunderstorms and implies that there may be occurrence of severe or greater turbulence, severe icing, low-level wind shear, and IFR conditions. The final line of the precautionary statement alerts the user that heights, for the most part, are MSL. Those that are not MSL will be AGL or CIG. 3. Synopsis. Gives a brief summary identifying the location and movement of pressure systems, fronts, and circulation patterns. Example. Synopsis. Low PRES, TROF, 10Z, OK/TX, PN/HDL, area FCST, MOV, EWD, into CNTRL-SWRN, OK, by 04Z, WRM FNT, 10Z, CNTRL, OK-SRN, AR-NRN MS, FCST, lift NWD, into NERN, OK-NRN, AR, EXTRM, NRN MS, by 04Z. Explanation. As of 1000 Zulu, there is a low-pressure trough over the Oklahoma and Texas Panhandle area, which is forecast to move eastward into central southwestern Oklahoma by 0400 Zulu. A warm front located over central Oklahoma, southern Arkansas, and northern Mississippi at 1000 Zulu is forecast to lift northwestward into northeastern Oklahoma, northern Arkansas, and extreme northern Mississippi by 0400 Zulu. 4. VFR clouds and weather. This section lists expected sky conditions, visibility, and weather for the next 12 hours and an outlook for the following 6 hours. Example. SCNTRL and SERN-TX. AGL SCT-BKN-010. TOPS 030. VIS 3-5SM BR. 14-16Z BECMG AGL SCT 030. 19Z, AGL SCT-050, OTLK, VFR, OK, PND-LAND, NW, AGL SCT-030, SCT-BKN-100, TOPS FL200, 15Z, AGL SCT-040, SCT-100, AFT-20Z, SCT-TSRA, DVLPG, FEW POSS SEV, CB TOPS FL450, OTLK VFR. Explanation. In south central and southeastern Texas, there is a scattered to broken layer of clouds for 1,000 feet AGL with tops at 3,000 feet. Visibility is 3 to 5 statute miles in mist. Between 1400 Zulu and 1600 Zulu, the cloud bases are expected to increase to 3,000 feet AGL. After 1900 Zulu, the cloud bases are expected to continue to increase to 5,000 feet AGL, and the outlook is VFR. In northwestern Oklahoma and Panhandle, the clouds are scattered at 3,000 feet with another scattered to broken layer at 10,000 feet AGL, with tops at 20,000 feet. At 1,500 Zulu, the lowest cloud base is expected to increase to 4,000 feet AGL, with a scattered layer at 10,000 feet AGL. After 2,000 Zulu, the forecast calls for scattered thunderstorms, with rain developing and a few becoming severe. The CB clouds will have tops at flight level 450 or 45,000 feet MSL. It should be noted that when information is given in the area forecast, locations may be given by states, regions, or specific geological features such as mountain ranges. Figure 12-12 shows an area forecast chart with 6 regions of forecast, states, regional areas, and common geographical features. In-flight weather advisories. In-flight weather advisories, which are provided to en route aircraft, are forecasts that detail potentially hazardous weather. These advisories are also available to pilots prior to departure for flight planning purposes. An in-flight weather advisory is issued in the form of either an AirMet, SIGMET, or convective SIGMET. AirMet. AirMets, WAs, are examples of in-flight weather advisories that are issued every 6 hours with intermediate updates issued as needed for a particular area forecast region. The information contained in an AirMet is of operational interest to all aircraft, but the weather section concerns phenomena considered potentially hazardous to light aircraft and aircraft with limited operational capabilities. An AirMet includes forecast of moderate icing, moderate turbulence, sustained surface winds of 30 knots or greater, widespread areas of ceilings less than 1,000 feet, and or visibilities less than 3 miles, and extensive mountain obscurement. Each AirMet bulletin has a fixed alphanumeric designator, numbered sequentially for easy identification, beginning with the first issuance of the day. Sierra is the AirMet code used to denote IFR and mountain obscuration. Tango is used to denote turbulence, strong surface winds, and low-level wind shear, and Zulu is used to denote icing and freezing levels. Example: DFW-TWA 241650, AirMet Tango UPDT-3 for TURBC, STG, SFC, winds, and LLWS, valid until 242000, AirMet TURBC, OK, TX, UPDT, from OKC to DFW to SAT to MAF to CDS to OKC, OCNL, MDT, TURBC, BLO, 60, due to STG, and gusty, low LVL winds. CONDS, CONTG, BYD 2000Z. Explanation. This airmet was issued by Dallas-Fort Worth on the 24th day of the month at 1650 Zulu time. On this third update, the airmet Tango is issued for turbulence, strong surface winds, and low-level wind shear until 2000 Zulu on the same day. The turbulence section of the airmet is an update for Oklahoma and Texas. It defines an area from Oklahoma City to Dallas, Texas, to San Antonio, to Midland, Texas, to Childress, Texas, to Oklahoma City that will experience occasional moderate turbulence below 6,000 feet due to strong and gusty low-level winds. It also notes that these conditions are forecast to continue beyond 2000 Zulu. SIGMET. SIGMETs, WSs, are in-flight advisories concerning non-convective weather that is potentially hazardous to all aircraft. They report weather forecasts that include severe icing not associated with thunderstorms, severe or extreme turbulence or clear air turbulence, CAT, not associated with thunderstorms, dust storms or sandstorms that lower surface or in-flight visibilities to below 3 miles, and volcanic ash. SIGMETs are unscheduled forecasts that are valid for 4 hours, but if the SIGMET relates to hurricanes, it is valid for 6 hours. A SIGMET is issued under an alphabetic identifier from November through Yankee, excluding Sierra and Tango. The first issuance of a SIGMET is designated as an Urgent Weather SIGMET, UWS. Reissued SIGMETs for the same weather phenomena are sequentially numbered until the weather phenomenon ends. Example: SFOR WS 100130. SIGMET Romeo 02, valid until 100530 ORWA. From SEA to PDT to EUG to SEA, OCNL, MOGR, CAT, BTN, 280 and 350, EXPCD, due to JTSTR, CONDS, BGNG, AFT, 0200Z, CONTG, BYD, 0530Z. Explanation. This is SIGMET Romeo 2, the second issuance for this weather phenomenon. It is valid until the 10th day of the month at 0530 Zulu time. This SIGMET is for Oregon and Washington, for a defined area from Seattle to Portland to Eugene to Seattle. It calls for occasional moderate or greater clear air turbulence between 28,000 and 35,000 feet due to the location of the jet stream. These conditions will be beginning after 0200 Zulu and will continue beyond the forecast scope of this segment of 0530 Zulu. Convective SIGMET Meteorological Information, WST. A convective SIGMET, WST, is an in-flight weather advisory issued for hazardous convective weather that affects the safety of every flight. Convective SIGMETs are issued for severe thunderstorms with surface winds greater than 50 knots, hail at the surface greater than or equal to 3/4 inch in diameter, or tornadoes. They are also issued to advise pilots of embedded thunderstorms, lines of thunderstorms, or thunderstorms with heavy or greater precipitation that affect 40% or more of a 3,000 square foot or greater region. Convective SIGMETs are issued for each area of the contiguous 48 states, but not Alaska or Hawaii. Convective SIGMETs are issued for the eastern E, western W, and central C United States. Each report is issued at 55 minutes past the hour, but special reports can be issued during the interim for any reason. Each forecast is valid for 2 hours. They are numbered sequentially each day from 1 to 99, beginning at 00 Zulu time. If no hazardous weather exists, the convective SIGMET is still issued. However, it states, convective SIGMET, none. Example. MKCC WST 221855. Convective Sigmet 21C, valid until 2055. KS OK TX. VCNTY GLD-CDS line. No SGFNT TSTMS RPRTD. Line TSTMS DVLPG by 1955Z will MOV EWD 30-35KT THRU 2055Z. Hail to 2IN PSBL. Explanation. The WST indicates this report is a convective SIGMET. The current date is the 22nd of the month, and it was issued at 1855 Zulu. It is convective SIGMET number 21 Charlie, indicating that it is the 21st consecutive report issued for the Central United States. This report is valid for 2 hours until 2055 Zulu time. The convective SIGMET is for an area from Kansas to Oklahoma to Texas, in the vicinity of a line from Goodland, Kansas to Childress, Texas. No significant thunderstorms are being reported, but a line of thunderstorms will develop by 1955 Zulu time and will move eastward at a rate of 30 to 35 knots through 2055 Zulu. Hail up to 2 inches in size is possible with the developing thunderstorms. Winds and temperature aloft forecasts, FD. Winds and temperature aloft forecasts, FD, provide wind and temperature forecasts for specific locations in the contiguous United States, including network locations in Hawaii and Alaska. The forecasts are made twice a day based on the radiosonde upper air observations taken at 0 Zulu and 1200 Zulu. Through 12,000 feet are true altitudes, and above 18,000 feet are pressure altitudes. Wind direction is always in reference to true north, and wind speed is given in knots. The temperature is given in degrees Celsius. No winds are forecast when a given level is within 1,500 feet of the station elevation. Similarly, temperatures are not forecast for any station within 2,500 feet of the station elevation. If the wind speed is forecast to be greater than 100 knots, but less than 199 knots, the computer adds 50 to the direction and subtracts 100 from the speed. To decode this type of data group, the reverse must be accomplished. For example, when the data appears as 731960, subtract 50 from the 73 and add 100 to the 19, and the wind would be 230 degrees at 119 knots, with a temperature of minus 60 degrees Celsius. If the wind speed is forecast to be 200 knots or greater, the wind group is coded as 99 knots. For example, when the data appears as 7799, subtract 50 from 77 and add 100 to 99, and the wind is 270 degrees at 199 knots or greater. When the forecast wind speed is calm, or less than 5 knots, the data group is coded 9900, which means light and variable. Refer to Figure 12-13. Explanation of Figure 12-13. The heading indicates that this FD was transmitted on the 15th of the month at 1640 Zulu, and is based on the 1200 Zulu radiosonde. The valid time is 1800 Zulu on the same day, and should be used for the period between 1700 Zulu and 2100 Zulu. The heading also indicates that the temperatures above 24,000 feet MSL are negative. Since the temperatures above 24,000 feet are negative, the minus sign is omitted. A 4-digit data group shows the wind direction in reference to true north and the wind speed in knots. The elevation at Amarillo, Texas, AMA, is 3,605 feet, so the lowest reportable altitude is 6,000 feet for the forecast winds. In this case, 2714 means the wind is forecast to be from 270 degrees at a speed of 14 knots. A 6-digit group includes the forecast temperature aloft. The elevation at Denver, DEN, is 5,431 feet, so the lowest reportable altitude is 9,000 feet for the winds and temperature forecast. In this case, 2321-04 indicates the wind is forecast to be from 230 degrees at a speed of 21 knots with a temperature of -4 degrees Celsius. End of Part 3 of Chapter 12. Part 4 of Chapter 12 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 4 of Chapter 12, Aviation Weather Services. Weather charts. Weather charts are graphic charts that depict current or forecast weather. They provide an overall picture of the United States and should be used in the beginning stages of flight planning. Typically, weather charts show the movement of major weather systems and fronts. Surface analysis, weather depiction, and radar summary charts are sources of current weather information. Significant weather prognostic charts provide an overall forecast weather picture. Surface analysis chart. The surface analysis chart depicts an analysis of the current surface weather. Refer to Figure 12-14. This chart is a computer-prepared report that is transmitted every 3 hours and covers the contiguous 48 states and adjacent areas. A surface analysis chart shows the areas of high and low pressure, fronts, temperatures, dew points, wind directions and speeds, local weather, and visual obstructions. Surface weather observations for reporting points across the United States are also depicted on this chart. Each of these reporting points is illustrated by a station model. Refer to Figure 12-15 with errata. A station model includes type of observation. A round model indicates an official weather observer made the observation. A square model indicates the observation is from an automated station. Stations located offshore give data from ships, buoys, or offshore platforms. Sky cover. The station model depicts the total sky cover and is shown as clear, scattered, broken, overcast, or obscured / partially obscured. Clouds. Represented by specific symbols. Low cloud symbols are placed beneath the station model, while middle and high cloud symbols are placed directly above the station model. Typically, only one type of cloud will be depicted with the station model. Sea level pressure. Given in 3 digits to the nearest tenth of a millibar, MB. For 1,000 millibars or greater, prefix a 10 to the 3 digits. For less than 1,000 millibars, prefix a 9 to the 3 digits. Pressure change / tendency. Pressure change in tenths of millibars over the past 3 hours. This is depicted directly below the sea level pressure. Precipitation. A record of the precipitation that has fallen over the last 6 hours to the nearest hundredth of an inch. Dew point, given in degrees Fahrenheit. Present weather. Over 100 different weather symbols are used to describe the current weather. Temperature, given in degrees Fahrenheit. Wind. True direction of wind is given by the wind pointer line, indicating the direction from which the wind is coming. A short barb is equal to 5 knots of wind, a long barb is equal to 10 knots of wind, and a pennant is equal to 50 knots. Weather depiction chart. A weather depiction chart details surface conditions as derived from METAR and other surface observations. The weather depiction chart is prepared and transmitted by computer every 3 hours beginning at 0100 Zulu time and is valid at the time of the plotted data. It is designed to be used for flight planning by giving an overall picture of the weather across the United States. Refer to Figure 12-16. This type of chart typically displays major fronts or areas of high and low pressure. The weather depiction chart also provides a graphic display of IFR, VFR, and MVFR, marginal VFR weather. Areas of IFR conditions, ceilings less than 1,000 feet and visibility less than 3 miles, are shown by a hatched area outlined by a smooth line. Marginal VFR regions, ceilings 1,000 to 3,000 feet, visibility 3 to 5 miles, are shown by a non-hatched area outlined by a smooth line. Areas of VFR, no ceiling or ceiling greater than 3,000 feet, and visibility greater than 5 miles, are not outlined. Weather depiction charts show a modified station model that provides sky conditions in the form of total sky cover, cloud height or ceiling, weather, and obstructions to visibility, but does not include winds or pressure readings like the surface analysis chart. A bracket symbol to the right of the station indicates the observation was made by an automated station. A detailed explanation of a station model is depicted in the previous discussion of surface analysis charts. Radar Summary Chart. A radar summary chart is a graphically depicted collection of radar weather reports, SDs. Refer to Figure 12-17. The chart is published hourly at 35 minutes past the hour. It displays areas of precipitation as well as information regarding the characteristics of the precipitation. Refer to Figure 12-18. A radar summary chart includes no information. If information is not reported, the chart will say NA. If no echoes are detected, the chart will say NE. Precipitation intensity contours. Intensity can be described as one of 6 levels and is shown on the chart by 3 contour intervals. Height of tops. The heights of the echo tops are given in hundreds of feet MSL. Movement of cells. Individual cell movement is indicated by an arrow pointed in the direction of movement. The speed of movement in knots is the number at the top of the arrowhead. LM indicates little movement. Type of precipitation. The type of precipitation is marked on the chart using specific symbols. These symbols are not the same as used on the METAR charts. Echo configuration. Echoes are shown as being areas, cells, or lines. Weather watches. Severe weather watch areas for tornadoes and severe thunderstorms are depicted by boxes outlined with heavy dashed lines. The radar summary chart is a valuable tool for pre-flight planning. It does, however, contain several limitations for the usage of the chart. This chart depicts only areas of precipitation. It will not show areas of clouds and fog with no appreciable precipitation, or the height of tops and bases of the clouds. Radar summary charts are a depiction of current precipitation and should be used in conjunction with current METAR and weather forecasts. Significant weather prognostic charts. Significant weather prognostic charts are available for low-level significant weather from the surface to flight level 240, 24,000 feet, also referred to as the 400 millibar level, and high-level significant weather from flight level 250 to flight level 600, 25,000 to 60,000 feet. The primary concern of this discussion is the low-level significant weather prognostic chart. The low-level chart comes in 2 forms, the 12 and 24-hour forecast chart and the 36 and 48-hour surface forecast chart. The first chart is a 4-panel chart that includes 12 and 24-hour forecasts for significant weather and surface weather. Charts are issued 4 times a day at 0000 Zulu, 0600 Zulu, 1200 Zulu, and 1800 Zulu. The valid time for the chart is printed on the lower left corner of each panel. The upper 2 panels show forecast significant weather, which may include non-convective turbulence, freezing levels, and IFR or marginal VFR weather. Areas of moderate or greater turbulence are enclosed in dashed lines. Numbers within these areas give the height of the turbulence in hundreds of feet MSL. Figures below the line show the anticipated base, while figures above the line show the top of the zone of turbulence. Also shown on this panel are areas of VFR, IFR, and marginal VFR. IFR areas are enclosed by solid lines. Marginal VFR areas are enclosed by scallop lines, and the remaining unenclosed area is designated VFR. Zigzag lines and the letters SFC indicate freezing levels in that area are at the surface. Freezing level height contours for the highest freezing level are drawn at 4,000-foot intervals with dashed lines. The lower two panels show the forecast surface weather and depicts the forecast locations and characteristics of pressure systems, fronts, and precipitation. Standard symbols are used to show fronts and pressure centers. Direction of movement of the pressure center is depicted by an arrow. The speed in knots is shown next to the arrow. In addition, areas of forecast precipitation and thunderstorms are outlined. Areas of precipitation that are shaded indicate at least one-half of the area is being affected by the precipitation. Unique symbols indicate the type of precipitation and the manner in which it occurs. Figure 12-19 depicts a typical significant weather prognostic chart, as well as the symbols typically used to depict precipitation. Prognostic charts are an excellent source of information for pre-flight planning. However, this chart should be viewed in light of current conditions and specific local area forecasts. The 36 and 48-hour significant weather prognostic chart is an extension of the 12 and 24-hour forecast. It provides information regarding surface weather forecasts and includes a discussion of the forecast. This chart is issued twice a day. It typically contains forecast positions and characteristics of pressure patterns, fronts, and precipitation. An example of a 36 and 48-hour surface prognostic chart is shown in Figure 12-20. ATC radar weather displays. Although ATC systems cannot always detect the presence or absence of clouds, they can often determine the intensity of a precipitation area, but the specific character of that area, snow, rain, hail, virga, etc., cannot be determined. For this reason, ATC refers to all weather areas displayed on ATC radar scopes as precipitation. ARTCC facilities normally use a weather and radar processor, WARP, to display a mosaic of data obtained from multiple NEXRAD sites. There is a time delay between actual conditions and those displayed to the controller. The precipitation data on the ARTCC controller's display could be up to 6 minutes old. The WARP processor is only used in ARTCC facilities. All ATC facilities using radar weather processors with the ability to determine precipitation intensity describe the intensity to pilots as light, moderate, heavy, or extreme. When the WARP is not available, a second system, the Narrowband Air Route Surveillance Radar, ARSR, can display two distinct levels of precipitation intensity that will be described to pilots as moderate and heavy to extreme. ATC facilities that cannot display the intensity levels of precipitation due to equipment limitations will describe the location of the precipitation area by geographic position or position relative to the aircraft. Since the intensity level is not available, the controller will state intensity unknown. ATC radar is not able to detect turbulence. Generally, turbulence can be expected to occur as the rate of rainfall or intensity of precipitation increases. Turbulence associated with greater rates of rainfall or precipitation will normally be more severe than any associated with lesser rates of rainfall or precipitation. Turbulence should be expected to occur near convective activity, even in clear air. Thunderstorms are a form of convective activity that implies severe or greater turbulence. Operation within 20 miles of thunderstorms should be approached with great caution, as the severity of turbulence can be much greater than the precipitation intensity might indicate. Weather avoidance assistance. To the extent possible, controllers will issue pertinent information on weather and assist pilots in avoiding such areas when requested. Pilots should respond to a weather advisory by either acknowledging the advisory or by acknowledging the advisory and requesting an alternative course of action as follows. Request to deviate off course by stating the number of miles and the direction of the requested deviation. Request a new route to avoid the affected area. Request a change of altitude. request radar vectors around the affected areas. It should be remembered that the controller's primary function is to provide safe separation between aircraft. Any additional service, such as weather avoidance assistance, can only be provided to the extent that it does not detract from the primary function. It's also worth noting that the separation workload is generally greater than normal when weather disrupts the usual flow of traffic. ATC radar limitations and frequency congestion may also be a factor in limiting the controller's capability to provide additional service. Electronic Flight Displays, EFD, Multifunction Display, MFD weather. Many aircraft manufacturers now include satellite weather services with new Electronic Flight Display, EFD systems. EFDs give a pilot access to many of the satellite weather services available. Products available to a pilot on the display pictured in Figure 12-21 are listed as follows. The letters in parentheses indicate the soft key to press in order to access the data. Graphical NEXRAD data, NEXRAD. Graphical METAR data, METAR. Textual METAR data. Textual Terminal Aerodrome Forecasts, TAF. City Forecast data. Graphical Wind data, WIND. Graphical Echo Tops, EchoTops. Graphical Cloud Tops, CLD Tops. Graphical Lightning Strikes, LTNG. Graphical Storm Cell Movement, Cell MOV. NEXRAD radar coverage, information displayed with the NEXRAD data. SIGMETS/AIRMETS, SIG/AIR. Surface analysis to include city forecasts, SFC. County warnings, county. Freezing levels, FRZ, LVL. Hurricane track, cyclone. Temporary flight restrictions, TFR. Pilots must be familiar with any EFD or MFD used and the satellite weather products available on the display. Weather products age and expiration. The information displayed using a satellite weather link is near real-time but should not be thought of as instantaneous up-to-date information. Each type of weather display is stamped with the age information on the MFD. The time is referenced from Zulu when the information was assembled at the ground station. The age should not be assumed to be the time when the FIS received the information from the satellite. Two types of weather are displayed on the screen: current weather and forecast data. Current information is displayed by an age, while the forecast data has a date stamp in the form of character, character, refer to Figure 12-22. The Next Generation Weather Radar System, NEXRAD. The NEXRAD system is comprised of a series of 159 weather surveillance radar 1988 Doppler, WSR-88 Delta sites situated throughout the United States, as well as selected overseas sites. The NEXRAD system is a joint venture between the United States Department of Commerce, DOC, the United States Department of Defense, DOD, as well as the United States Department of Transportation, DOT. The individual agencies that have control over the system are the NWS, Air Force Weather Agency, AFWA, and the FAA. Refer to Figure 12-23. NEXRAD radar produces two levels of products, Level 2 and Level 3. Level 2 data products. All NEXRAD Level 2 data products are available through the National Climatic Data Center, NCDC. Level 2 data consists of the three meteorological base data quantities: reflectivity, mean radial velocity, and spectrum width. Level 3 data products. There are 41 products routinely available through the NCDC. Level 3 graphic products are available as digital images, color hard copy, grayscale hard copy, or acetate overlay copies. This information is then encoded and disseminated through the satellite weather system as well as other sources. NEXRAD Level 3 data for up to a 2,000-mile range can be displayed. It is important to realize that the radar image is not real-time and can be up to 5 minutes old. At no time should the images be used as storm-penetrating radar, nor to navigate through a line of storms. The images display should only be used as a reference. NEXRAD radar is mutually exclusive of topographic, topo, terrain, and storm scope. When NEXRAD is turned on, topo, terrain, and storm scope are turned off because the colors used to display intensities are very similar. Lightning information is available to assist when NEXRAD is enabled. This presents a more vivid picture of the weather in the surrounding area. In addition to utilizing the soft keys to activate the NEXRAD display, the pilot also has the option of setting the desired range. It is possible to zoom in on a specific area of the display in order to gain a more detailed picture of the radar display. Refer to Figure 12-24. NEXRAD abnormalities. Although NEXRAD is a compilation of stations across the country, there can be abnormalities associated with the system. Some of the abnormalities are listed below. Ground clutter, strobes and spurious radar data, sun strobes when the radar antenna points directly at the sun, interference from buildings or mountains which may cause shadows, military aircraft which deploy metallic dust and may reflect the radar signature. NEXRAD limitations. In addition to the abnormalities listed, the NEXRAD system does have some specific limitations. Base reflectivity. The NEXRAD base reflectivity does not provide adequate information from which to determine cloud layers or type of precipitation with respect to hail versus rain. Therefore, a pilot may mistake rain for hail. In addition, the base reflectivity is sampled at the minimum antenna elevation angle. With this minimum angle, an individual site cannot depict high-altitude storms directly over the station. This will leave an area of null coverage if an adjacent site does not also cover the affected area. Resolution display. The resolution of the displayed data will pose additional concerns when the range is decreased. The minimum resolution for NEXRAD returns is 2 kilometers. This means that when the display range is zoomed in to approximately 10 miles, the individual square return boxes will be more prevalent. Each square will indicate the strongest display return within that 2-kilometer square area. AirMet slant segment display. AirMet slant segment information is available for the displayed viewing range on the MFD. Some displays are capable of displaying weather information for a 2,000-mile range. AirMet slant segments are displayed by dashed lines on the map. Refer to Figure 12-25. The legend box denotes the various colors used to depict the airmets such as icing, turbulence, IFR weather, mountain obscuration, as well as surface winds. Refer to Figure 12-26. The great advantage of the graphically displayed AirMet slant segment boundary box is the pilot can see the extent of the area that the report covers. The pilot does not need to manually plot the points to determine the full extent of the coverage area. Graphical METARs. METARs can be displayed on the multifunction display. Each reporting station that has a METAR slant TAF available is depicted by a flag from the center of the airport symbol. Each flag is color-coded to depict the type of weather that is currently reported at that station. A legend is available to assist users in determining what each flag color represents. Refer to Figure 12-27. The graphical METAR display shows all available reporting stations within the set viewing range. By setting the range knob up to a 2,000-mile range, pilots can pan around the display map to check the current conditions of various airports along the route of flight. By understanding what each colored flag indicates, a pilot can quickly determine where weather patterns display marginal weather, IFR, or areas of VFR. These flags make it easy to determine weather at a specific airport should the need arise to divert from the intended airport of landing. Chapter Summary. While no weather forecast is guaranteed to be 100% accurate, pilots have access to a myriad of weather information on which to base flight decisions. Weather products available for pre-flight planning to en route information received over the radio or via satellite link provide the pilot with the most accurate and up-to-date information available. Each report provides a piece of the weather puzzle. Pilots must use several reports to get an overall picture and gain an understanding of the weather that will affect the safe completion of a flight. End of Part 4 of Chapter 12. Part 1 of Chapter 13 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 1 of Chapter 13, Airport Operations. Introduction. Each time a pilot operates an aircraft, the flight normally begins and ends at an airport. An airport may be a small sod field or a large complex utilized by air carriers. This chapter examines airport operations, identifies features of an airport complex, and provides information on operating on or in the vicinity of an airport. Types of airports. There are two types of airports, towered and non-towered. These types can further be subdivided to civil airports, airports that are open to the general public, military/federal government airports, airports operated by the military, National Aeronautics and Space Administration, NASA, or other agencies of the federal government, private airports, airports designated for private or restricted use only, not open to the general public. Towered airport. A towered airport has an operating control tower. Air traffic control, ATC, is responsible for providing the safe, orderly, and expeditious flow of air traffic at airports where the type of operations and/or volume of traffic requires such a service. Pilots operating from a towered airport are required to maintain two-way radio communication with air traffic controllers and to acknowledge and comply with their instructions. Pilots must advise ATC if they cannot comply with the instructions issued and request amended instructions. A pilot may deviate from an air traffic instruction in an emergency, but must advise ATC of the deviation as soon as possible. Non-towered airport. A non-towered airport does not have an operating control tower. Two-way radio communications are not required, although it is a good operating practice for pilots to transmit their intentions on the specified frequency for the benefit of other traffic in the area. The key to communicating at an airport without an operating control tower is selection of the correct common frequency. The acronym CTAF, which stands for Common Traffic Advisory Frequency, is synonymous with this program. A CTAF is a frequency designated for the purpose of carrying out airport advisory practices while operating to or from an airport without an operating control tower. The CTAF may be a Universal Integrated Community, UNICOM, Multicom, Flight Service Station, FSS, or tower frequency, and is identified in appropriate aeronautical publications. UNICOM is a non-government air-to-ground communications station which may provide airport information at public use airports where there is no tower or flight service station. On pilot request, UNICOM stations may provide pilots with weather information, wind direction, the recommended runway, or other necessary information. If the UNICOM frequency is designated as the CTAF, it will be identified in appropriate aeronautical publications. Figure 13-1 lists recommended communications procedures. More information on radio communications is discussed later in this chapter. Sources for airport data. When a pilot flies into a different airport, it is important to review the current data for that airport. This data provides the pilot with information such as communication frequencies, services available, closed runways, or airport construction. Three common sources of information are aeronautical charts, airport slant facility directory, A/FD, notices to airmen, NOTAMs. Aeronautical charts. Aeronautical charts provide specific information on airports. Chapter 15, Navigation, contains an excerpt from an aeronautical chart and an aeronautical chart legend, which provides guidance on interpreting the information on the chart. Airport Slant Facility Directory, A/FD. The Airport Facility Directory provides the most comprehensive information on a given airport. It contains information on airports, heliports, and seaplane bases that are open to the public. The Airport Facility Directory is published in 7 books, which are organized by regions and are revised every 56 days. The Airport Facility Directory is also available digitally at www.naco.faa.gov. Figure 13-2 contains an excerpt from a directory. For a complete listing of information provided in an airport facility directory and how the information may be decoded, refer to the directory legend sample located in the front of each airport facility directory. In addition to airport information, each airport facility directory contains information such as special notices, Federal Aviation Administration FAA and National Weather Service NWS telephone numbers, preferred instrument flight rules IFR routing, visual flight rules VFR waypoints, a listing of very high frequency VHF omnidirectional range VOR receiver checkpoints, aeronautical chart bulletins, land and hold short operations LAHSO for selected airports, airport diagrams for selected towered airports, en route flight advisory service EFAS outlets, parachute jumping areas, and facility telephone numbers. It would be helpful to review an airport facility directory to become familiar with the information it contains. Notices to Airmen. NOTAMs. NOTAMs provide the most current information available. They provide time-critical information on airports and changes that affect the National Airspace System, NAS, and are of concern to IFR operations. NOTAM information is classified into 4 categories. See Chapter 5 of the Airman's Information Manual for a description of the Notice to Airmen NOTAM system. NOTAM-Ds are attached to hourly weather reports and are available at automated flight service stations, AFSS, or flight service stations. FDC NOTAMs are issued by the National Flight Data Center and contain regulatory information, such as temporary flight restrictions or an amendment to instrument approach procedures. The NOTAM-Ds and FDC NOTAMs are contained in the NOTAM publication, which is issued every 28 days. Prior to any flight, pilots should check for any NOTAMs that could affect their intended flight. NOTAM-D information includes such data as taxiway closures, personnel and equipment near or crossing runways, and airport lighting aids that do not affect instrument approach criteria such as Visual Approach Slope Indicator, VASI. NOTAM-D information is distributed locally only and is not attached to the hourly weather reports. A separate file of local NOTAMs is maintained at each flight service station for facilities in their area only. NOTAM-D information for other flight service station areas must be specifically requested directly from the flight service station that has responsibility for the airport concerned. Airport markings and signs. There are markings and signs used at airports which provide directions and assist pilots in airport operations. Some of the most common markings and signs are discussed. Additional information may be found in Chapter 2, Aeronautical Lighting and Other Airport Visual Aids in the Aeronautical Information Manual, AIM. Runway markings. Runway markings vary depending on the type of operations conducted at the airport. Figure 13-3 shows a runway that is approved as a precision instrument approach runway and some other common runway markings. A basic VFR runway may only have centerline markings and runway numbers. Since aircraft are affected by the wind during takeoffs and landings, runways are laid out according to the local prevailing winds. Runway numbers are in reference to magnetic north. Certain airports have 2 or even 3 runways laid out in the same direction, These are referred to as parallel runways and are distinguished by a letter added to the runway number, e.g., runway 36L for left, 36C center, and 36R right. Another feature of some runways is a displaced threshold. A threshold may be displaced because of an obstruction near the end of the runway. Although this portion of the runway is not to be used for landing, it may be available for taxiing, takeoff, or landing rollout. Some airports may have a blast pad slant stopway area. The blast pad is an area where a propeller or jet blast can dissipate without creating a hazard. The stopway area is paved in order to provide space for an aircraft to decelerate and stop in the event of an aborted takeoff. These areas cannot be used for takeoff or landing. Taxiway markings. Aircraft use taxiways to transition from parking areas to the runway. Taxiways are identified by a continuous yellow centerline stripe and may include edge markings to define the edge of the taxiway. This is usually done when the taxiway edge does not correspond with the edge of the pavement. If an edge marking is a continuous line, the paved shoulder is not intended to be used by an aircraft. If it is a dashed marking, an aircraft may use that portion of the pavement. Where a taxiway approaches a runway, there may be a holding position marker. These consist of 4 yellow lines, 2 solid and 2 dashed. The solid lines are where the aircraft is to hold. At some towered airports, holding position markings may be found on a runway. They are used when there are intersecting runways and ATC issues instructions such as cleared to land, hold short of runway 30. Other markings. Some other markings found on the airport include vehicle roadway markings, VOR receiver checkpoint markings, and non-movement area boundary markings. Vehicle roadway markings are used when necessary to define a pathway for vehicle crossing areas that are also intended for aircraft. These markings usually consist of a solid white line to delineate each edge of the roadway and a dashed line to separate lanes within the edges of the roadway. In lieu of the solid lines, zipper markings may be used to delineate the edges of the vehicle roadway. Refer to Figure 13-4. A VOR receiver checkpoint marking consists of a painted circle with an arrow in the middle. The arrow is aligned in the direction of the checkpoint azimuth. This allows pilots to check aircraft instruments with navigational aid signals. A non-movement area boundary marking delineates a movement area under ATC. These markings are yellow and located on the boundary between the movement and non-movement area. They normally consist of 2 yellow lines, 1 solid and 1 dashed. Airport signs. There are 6 types of signs that may be found at airports. The more complex the layout of an airport, the more important the signs become to pilots. Figure 13-5 shows examples of signs, their purpose, and appropriate pilot action. The 6 types of signs are mandatory instruction signs. Red background with white inscription. These signs denote an entrance to a runway, critical area, or prohibited area. Location signs. Black with yellow inscription and a yellow border, no arrows. They are used to identify a taxiway or runway location, to identify the boundary of the runway, or identify an instrument landing system, ILS critical area. Direction signs. Yellow background with black inscription. The inscription identifies the designation of the intersecting taxiway or taxiways leading out of an intersection. Destination signs. Yellow background with black inscription and also contains arrows. These signs provide information on locating things such as runways, terminals, cargo areas, and civil aviation areas. Information signs. Yellow background with black inscription. These signs are used to provide the pilot with information on such things as areas that cannot be seen from the control tower, applicable radio frequencies, and noise abatement procedures. The airport operator determines the need, size, and location of these signs. Runway distance remaining signs. black background with white numbers. The numbers indicate the distance of the remaining runway in thousands of feet. End of Part 1 of Chapter 13. Part 2 of Chapter 13 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 2 of Chapter 13, Airport Operations. Airport Lighting. The majority of airports have some type of lighting for night operations. The variety and type of lighting systems depends on the volume and complexity of operations at a given airport. Airport lighting is standardized so that airports use the same light colors for runways and taxiways. Airport Beacon. Airport beacons help a pilot identify an airport at night. The beacons are operated from dusk till dawn. Sometimes they are turned on if the ceiling is less than 1,000 feet and or the ground visibility is less than 3 statute miles, VFR minimums. However, there is no requirement for this, so a pilot has the responsibility of determining if the weather meets VFR requirements. The beacon has a vertical light distribution to make it most effective from 1 to 10 degrees above the horizon, although it can be seen well above or below this spread. The beacon may be an omnidirectional capacitor discharge device, or it may rotate at a constant speed, which produces the visual effect of flashes at regular intervals. The combination of light colors from an airport beacon indicates the type of airport. Refer to Figure 13-6. Some of the most common beacons are flashing white and green for civilian land airports, flashing white and yellow for a water airport, flashing white, yellow, and green for a heliport, and 2 quick white flashes alternating with a green flash identifying a military airport. Approach light systems. Approach light systems are primarily intended to provide a means to transition from instrument flight to visual flight for landing. The system configuration depends on whether the runway is a precision or a non-precision instrument runway. Some systems include sequenced flashing lights, which appear to the pilot as a ball of light traveling toward the runway at high speed. Approach lights can also aid pilots operating under VFR at night. Visual glide slope indicators. Visual glide slope indicators provide the pilot with glide path information that can be used for day or night approaches. By maintaining the proper glide path as provided by the system, a pilot should have adequate obstacle clearance and should touch down within a specified portion of the runway. Visual Approach Slope Indicator, VASI. VASI installations are the most common visual glide path systems in use. The VASI provides obstruction clearance within 10 degrees of the runway extended runway centerline and to 4 nautical miles from the runway threshold. The VASI consists of light units arranged in bars. There are 2-bar and 3-bar VASIs. The 2-bar VASI has near and far light bars, and the 3-bar VASI has near, middle, and far light bars. 2-bar VASI installations provide one visual glide path, which is normally set at 3 degrees. The 3-bar system provides 2 glide paths. The lower glide path normally is set at 3 degrees, and the upper glide path 1/4 degree above the lower glide path. The basic principle of the VASI is that of color differentiation between red and white. Each light unit projects a beam of light, a white segment in the upper part of the beam, and a red segment in the lower part of the beam. The lights are arranged so the pilot sees the combination of lights shown in Figure 13-7 to indicate below, on, or above the glide path. Other glide path systems. A Precision Approach Path Indicator, PAPI, uses lights similar to the VASI system except they are installed in a single row, normally on the left side of the runway. Refer to Figure 13-8. A tricolor system consists of a single light unit projecting a 3-color visual approach path. Below the glide path is indicated by red, on the glide path is indicated by green, and above the glide path is indicated by amber. When descending below the glide path, there is a small area of dark amber. Pilots should not mistake this area for an above the glide path indication. Refer to Figure 13-9. Pulsating visual approach slope indicators normally consist of a single light unit projecting a two-color visual approach path into the final approach area of the runway upon which the indicator is installed. The on-glide path indication is a steady white light. The slightly below glide path indication is a steady red light. If the aircraft descends further below the glide path, the red light starts to pulsate. The above glide path indication is a pulsating white light. The pulsating rate increases as the aircraft gets further above or below the desired glide slope. The useful range of the system is about 4 miles during the day and up to 10 miles at night. Refer to Figure 13-10 with errata. Runway lighting. There are various lights that identify parts of the runway complex. These assist a pilot in safely making a takeoff or landing during night operations. Runway End Identifier Lights, REIL. Runway End Identifier Lights, REIL, are installed at many airfields to provide rapid and positive identification of the approach end of a particular runway. The system consists of a pair of synchronized flashing lights located laterally on each side of the runway threshold. REILs may be either omnidirectional or unidirectional facing the approach area. Runway Edge Lights. Runway edge lights are used to outline the edges of runways at night or during low visibility conditions. These lights are classified according to the intensity they are capable of producing. High-intensity runway lights, HIRL, medium-intensity runway lights, MIRL, and low-intensity runway lights, LIRL. The HIRL and MIRL have variable intensity settings. These lights are white except on instrument runways, where amber lights are used in the last 2,000 feet or half the length of the runway, whichever is less. The lights marking the end of the runway are red. In-runway lighting. Runway Centerline Lighting System, RCLS, installed on some precision approach runways to facilitate landing under adverse visibility conditions. They are located along the runway centerline and are spaced at 50-foot intervals. When viewed from the landing threshold, the runway centerline lights are white until the last 3,000 feet of the runway. The white lights begin to alternate with red for the next 2,000 feet. For the remaining 1,000 feet of the runway, all centerline lights are red. Touchdown Zone Lights, TDZL, installed on some precision approach runways to indicate the touchdown zone when landing under adverse visibility conditions. They consist of 2 rows of transverse light bars disposed symmetrically about the runway centerline. The system consists of steady burning white lights which start 100 feet beyond the landing threshold and extend to 3,000 feet beyond the landing threshold or to the midpoint of the runway, whichever is less. Taxiway centerline lead-off lights provide visual guidance to persons exiting the runway. They are color-coded to warn pilots and vehicle drivers that they are within the runway environment or ILS/MLS critical area, whichever is more restrictive. Alternate green and yellow lights are installed, beginning with green from the runway centerline to one centerline light position beyond the runway holding position of the ILS/MLS critical area holding position. Taxiway centerline lead-on lights provide visual guidance to persons entering the runway. These lead-on lights are also color-coded with the same color pattern as lead-off lights to warn pilots and vehicle drivers that they are within the runway environment or instrument landing system/microwave landing system, ILS/MLS critical area, whichever is more conservative. The fixtures used for lead-on lights are bidirectional, i.e., one side emits light for the lead-on function while the other side emits light for the lead-off function. Any fixture that emits yellow light for the lead-off function also emits yellow light for the lead-on function. Land and hold short lights, used to indicate the hold short point on certain runways which are approved for LAHSO. Land and hold short lights consist of a row of pulsating white lights installed across the runway at the hold short point. Where installed, the lights are on any time LAHSO is in effect. These lights are off when LAHSO is not in effect. Control of airport lighting. Airport lighting is controlled by air traffic controllers at towered airports. At non-towered airports, the lights may be on a timer, or where an FSS is located at an airport, the flight service station personnel may control the lighting. A pilot may request various light systems be turned on or off, and also request a specified intensity, if available, from ATC or flight service station personnel. At selected non-towered airports, the pilot may control the lighting by using the radio. This is done by selecting a specified frequency and clicking the radio microphone. For information on pilot-controlled lighting at various airports, refer to the Airport Facility Directory. Refer to Figure 13-11. Taxiway lights. Omnidirectional taxiway lights outline the edges of the taxiway and are blue in color. At many airports, these edge lights may have variable intensity settings that may be adjusted by an air traffic controller when deemed necessary or when requested by the pilot. Some airports also have taxiway centerline lights that are green in color. Obstruction lights. Obstructions are marked or lighted to warn pilots of their presence during daytime and nighttime conditions. Obstruction lighting can be found both on and off an airport to identify obstructions. They may be marked or lighted in any of the following conditions. Red obstruction lights. Flash or emit a steady red color during nighttime operations, and the obstructions are painted orange and white for daytime operations. High-intensity white obstruction lights. Flash high-intensity white lights during the daytime with the intensity reduced for nighttime. Dual lighting. A combination of flashing red beacons and steady red lights for nighttime operation and high-intensity white lights for daytime operations. Wind direction indicators. It is important for a pilot to know the direction of the wind. At facilities with an operating control tower, this information is provided by ATC. Information may also be provided by flight service station personnel located at a particular airport or by requesting information on a CTAF at airports that have the capacity to receive and broadcast on this frequency. When none of these services is available, it is possible to determine wind direction and runway in use by visual wind indicators. A pilot should check these wind indicators even when information is provided on the CTAF at a given airport, because there is no assurance that the information provided is accurate. The wind direction indicator can be a wind cone, wind sock, tetrahedron, or wind tee. These are usually located in a central location near the runway and may be placed in the center of a segmented circle, which identifies the traffic pattern direction if it is other than the standard left-hand pattern. Refer to Figures 13-12 and 13-13. The windsock is a good source of information since it not only indicates wind direction, but allows the pilot to estimate the wind velocity and gusts or factor. The windsock extends out straighter in strong winds and tends to move back and forth when the wind is gusty. Wind tees and tetrahedrons can swing freely and align themselves with the wind direction. The wind tee and tetrahedron can also be manually set to align with the runway in use. Therefore, a pilot should also look at the windsock if available. Traffic patterns. At those airports without an operating control tower, a segmented circle visual indicator system, refer to Figure 13-13, if installed, is designed to provide traffic pattern information. Usually located in a position affording maximum visibility to pilots in the air and on the ground, and providing a centralized location for other elements of the system, the segmented circle consists of the following components: wind direction indicators, landing direction indicators, landing strip indicators, and traffic pattern indicators. A tetrahedron is installed to indicate the direction of landings and takeoffs when conditions at the airport warrant its use. It may be located at the center of a segmented circle and may be lighted for night operations. The small end of the tetrahedron points in the direction of landing. Pilots are cautioned against using a tetrahedron for any purpose other than as an indicator of landing direction. At airports with control towers, the tetrahedron should only be referenced when the control tower is not in operation. Tower instructions supersede tetrahedron indications. Landing strip indicators are installed in pairs as shown in Figure 13-13 and are used to show the alignment of landing strips. Traffic pattern indicators are arranged in pairs in conjunction with landing strip indicators and used to indicate the direction of turns when there is a variation from the normal left traffic pattern. If there is no segmented circle installed at the airport, traffic pattern indicators may be installed on or near the end of the runway. At most airports and military air bases, traffic pattern altitudes for propeller-driven aircraft generally extend from 600 feet to as high as 1,500 feet above ground level, AGL. Pilots can obtain the traffic pattern altitude for an airport from the Airport Facility Directory. Also, traffic pattern altitudes for military turbojet aircraft sometimes extend up to 2,500 feet AGL. Therefore, pilots of en route aircraft should be constantly on the alert for other aircraft and traffic patterns and avoid these areas whenever possible. When operating at an airport, traffic pattern altitude should be maintained unless otherwise required by the applicable distance from cloud criteria in Title 14 of the Code of Federal Regulations, 14 CFR, Section 91.155. Additional information on airport traffic pattern operations can be found in Chapter 4, Air Traffic Control, of the Airman's Information Manual. Pilots can find traffic pattern information and restrictions such as noise abatement in the Airport Facility Directory. Example: Key to traffic pattern operations, single runway. 1. Enter pattern in level flight, abeam the midpoint of the runway, at pattern altitude, 1,000 feet AGL, is recommended pattern altitude unless established otherwise. 2. Maintain pattern altitude until abeam approach end of the landing runway on downwind leg. 3. Complete turn to final at least 1/4 mile from the runway. 4. Continue straight ahead until beyond departure end of runway. 5. If remaining in the traffic pattern, commence turn to crosswind leg beyond the departure end of the runway within 300 feet of pattern altitude. 6. If departing the traffic pattern, continue straight out or exit with a 45-degree turn. To the left when in a left-hand traffic pattern, to the right when in a right-hand traffic pattern, beyond the departure end of the runway, after reaching pattern altitude. Refer to Figure 13-14. Example: Key to traffic pattern operations, parallel runways. 1. Enter pattern in level flight, abeam the midpoint of the runway, at pattern altitude. 1,000 feet AGL is recommended pattern altitude unless established otherwise. 2. Maintain pattern altitude until abeam approach end of the landing runway on downwind leg. 3. Complete turn to final at least 1/4 mile from the runway. 4. Continue straight ahead until beyond departure end of runway. 5. If remaining in the traffic pattern, commence turn to crosswind leg beyond the departure end of the runway within 300 feet of pattern altitude. 6. If departing the traffic pattern, continue straight out or exit with a 45-degree turn, to the left when in a left-hand traffic pattern, to the right when in a right-hand traffic pattern, beyond the departure end of the runway, after reaching pattern altitude. 7. Do not overshoot final or continue on a track which penetrates the final approach of the parallel runway. 8. Do not continue on a track which penetrates the departure path of the parallel runway. Refer to Figure 13-15. Radio communications. Operating in and out of a towered airport, as well as in a good portion of the airspace system, requires that an aircraft have two-way radio communication capability. For this reason, a pilot should be knowledgeable of radio station license requirements and radio communications equipment and procedures. Radio license. There is no license requirement for a pilot operating in the United States. However, a pilot who operates internationally is required to hold a restricted radio telephone permit issued by the Federal Communications Commission, FCC. There is also no station license requirement for most general aviation aircraft operating in the United States. A station license is required, however, for an aircraft which is operating internationally, which uses other than a VHF radio and which meets other criteria. Radio equipment. In general aviation, the most common types of radios are VHF. A VHF radio operates on frequencies between 118.0 and 136.975 and is classified as 720 or 760 depending on the number of channels it can accommodate. The 720 and 760 use .025 spacing, 118.025, 118.050, with the 720 having a frequency range up to 135.975 and the 760 going up to 136.975. VHF radios are limited to line-of-sight transmissions. Therefore, aircraft at higher altitudes are able to transmit and receive at greater distances. In March of 1997, the International Civil Aviation Organization, ICAO, amended its international standards and recommended practices to incorporate a channel plan specifying 8.33 kHz channel spacings in the aeronautical mobile service. The 8.33 kHz channel plan was adopted to alleviate the shortage of VHF ATC channels experienced in Western Europe and in the United Kingdom. 7 Western European countries and the United Kingdom implemented the 8.33 kHz channel plan on January 1, 1999. Accordingly, aircraft operating in the airspace of these countries must have the capability of transmitting and receiving on the 8.33 kHz space channels. Using proper radio phraseology and procedures contribute to a pilot's ability to operate safely and efficiently in the airspace system. A review of the Pilot Slant Controller Glossary contained in the Airman's Information Manual assists a pilot in the use and understanding of standard terminology. The Airman's Information Manual also contains many examples of radio communications. ICAO has adopted a phonetic alphabet which should be used in radio communications. When communicating with ATC, pilots should use this alphabet to identify their aircraft. Refer to Figure 13-16. Lost communication procedures. It is possible that a pilot might experience a malfunction of the radio. This might cause the transmitter, receiver, or both to become inoperative. If a receiver becomes inoperative and a pilot needs to land at a towered airport, it is advisable to remain outside or above Class D airspace until the direction and flow of traffic is determined. A pilot should then advise the tower of the aircraft type, position, altitude, and intention to land. The pilot should continue, enter the pattern, report a position as appropriate, and watch for light signals from the tower. Light signal colors and their meanings are contained in Figure 13-17. If the transmitter becomes inoperative, a pilot should follow the previously stated procedures and also monitor the appropriate ATC frequency. During daylight hours, ATC transmissions may be acknowledged by rocking the wings, and at night by blinking the landing light. When both receiver and transmitter are inoperative, the pilot should remain outside of Class D airspace until the flow of traffic has been determined, and then enter the pattern and watch for light signals. If a radio malfunctions prior to departure, it is advisable to have it repaired if possible. If this is not possible, a call should be made to ATC, and the pilot should request authorization to depart without two-way radio communications. If authorization is given to depart, the pilot is advised to monitor the appropriate frequency and/or watch for light signals as appropriate. End of Part 2 of Chapter 13. Part 3 of Chapter 13 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 3 of Chapter 13, Airport Operations. Air Traffic Control, ATC, Services. Besides the services provided by an FSS as discussed in Chapter 12, Aviation Weather Services, numerous other services are provided by ATC. In many instances, a pilot is required to have contact with ATC, but even when not required, a pilot finds it helpful to request their services. Primary radar. Radar is a device which provides information on range, azimuth, and/or elevation of objects in the path of the transmitted pulses. It measures the time interval between transmission and reception of radio pulses and correlates the angular orientation of the radiated antenna beam or beams in azimuth and/or elevation. Range is determined by measuring the time it takes for the radio wave to go out to the object and then return to the receiving antenna. The direction of a detected object from a radar site is determined by the position of the rotating antenna when the reflected portion of the radio wave is received. Modern radar is very reliable, and there are seldom outages. This is due to reliable maintenance and improved equipment. There are, however, some limitations which may affect ATC services and prevent a controller from issuing advisories concerning aircraft which are not under his or her control and cannot be seen on radar. The characteristics of radio waves are such that they normally travel in a continuous straight line unless they are bent by atmospheric phenomena such as temperature inversions, reflected or attenuated by dense objects such as heavy clouds and precipitation, or screened by high terrain features. ATC Radar Beacon System, ATC-RBS. The ATC Radar Beacon System, ATC-RBS, is often referred to as secondary surveillance radar. This system consists of 3 components and helps in alleviating some of the limitations associated with primary radar. The 3 components are an interrogator, transponder, and radar scope. The advantages of ATC-RBS are the reinforcement of radar targets, rapid target identification, and a unique display of selected codes. Transponder. The transponder is the airborne portion of the secondary surveillance radar system and a system with which a pilot should be familiar. The ATC-RBS cannot display the secondary information unless an aircraft is equipped with a transponder. A transponder is also required to operate in certain controlled airspace as discussed in Chapter 14, Airspace. A transponder code consists of 4 numbers from 0 to 7, 4,096 possible codes. There are some standard codes, or ATC may issue a 4-digit code to an aircraft. When a controller requests a code or function on the transponder, the word squawk may be used. Figure 13-18 lists some standard transponder phraseology. Additional information concerning transponder operation can be found in the Airman's Information Manual, Chapter 4. Radar Traffic Advisories. Radar-equipped ATC facilities provide radar assistance to aircraft on instrument flight plans, and VFR aircraft provided the aircraft can communicate with the facility and are within radar coverage. This basic service includes safety alerts, traffic advisories, limited vectoring when requested, and sequencing at locations where this procedure has been established. ATC issues traffic advisories based on observed radar targets. The traffic is referenced by azimuth from the aircraft in terms of the 12-hour clock. Also, distance in nautical miles, direction in which the target is moving, and type and altitude of the aircraft, if known, are given. An example would be traffic 10 o'clock, 5 miles eastbound, Cessna 152, 3,000 feet. The pilot should note that traffic position is based on the aircraft track and that wind correction can affect the clock position at which a pilot locates traffic. This service is not intended to relieve the pilot of the responsibility to see and avoid other aircraft. Refer to Figure 13-19. In addition to basic radar service, Terminal Radar Service Area, TRSA, has been implemented at certain terminal locations. TRSAs are depicted on sectional aeronautical charts and listed in the Airport Facility Directory. The purpose of this service is to provide separation between all participating VFR aircraft and all IFR aircraft operating within the TRSA. Class C service provides approved separation between IFR and VFR aircraft and sequencing of VFR aircraft to the primary airport. Class B service provides approved separation of aircraft based on IFR, VFR, and/or weight, and sequencing of VFR arrivals to the primary airport or airports. Wake turbulence. All aircraft generate wake turbulence while in flight. This disturbance is caused by a pair of counter-rotating vortices trailing from the wingtips. The vortices from larger aircraft pose problems to encountering aircraft. The wake of these aircraft can impose rolling moments exceeding the roll control authority of the encountering aircraft. Also, the turbulence generated within the vortices can damage aircraft components and equipment if encountered at close range. For this reason, a pilot must envision the location of the vortex wake and adjust the flight path accordingly. During ground operations and during takeoff, jet engine blast, thrust stream turbulence, can cause damage and upset smaller aircraft at close range. For this reason, pilots of small aircraft should consider the effects of jet engine blast and maintain adequate separation. Also, pilots of larger aircraft should consider the effects of their aircraft's jet engine blast on other aircraft and equipment on the ground. Vortex generation. Lift is generated by the creation of a pressure differential over the wing surface. The lowest pressure occurs over the upper wing surface and the highest pressure under the wing. This pressure differential triggers the roll-up of the airflow aft of the wing, resulting in swirling air masses trailing downstream of the wingtips. After the roll-up is completed, the wake consists of two counter-rotating cylindrical vortices. Most of the energy is within a few feet of the center of each vortex, but pilots should avoid a region within about 100 feet of the vortex core. Refer to Figure 13-20. Vortex strength. The strength of the vortex is governed by the weight, speed, and shape of the wing of the generating aircraft. The vortex characteristics of any given aircraft can also be changed by the extension of flaps or other wing configuration devices, as well as by a change in speed. The greatest vortex strength occurs when the generating aircraft is heavy, clean, and slow. Vortex behavior. Trailing vortices have certain behavioral characteristics that can help a pilot visualize the wake location and take avoidance precautions. Vortices are generated from the moment an aircraft leaves the ground until it touches down, since trailing vortices are the byproduct of wing lift. Refer to Figure 13-21. The vortex circulation is outward, upward, and around the wingtips when viewed from either ahead or behind the aircraft. Tests have shown that vortices remain spaced a bit less than a wingspan apart, drifting with the wind at altitudes greater than a wingspan from the ground. Tests have also shown that the vortices sink at a rate of several hundred feet per minute, slowing their descent and diminishing in strength with time and distance behind the generating aircraft. When the vortices of larger aircraft sink close to the ground, within 100 to 200 feet, they tend to move laterally over the ground at a speed of 2 to 3 knots. A crosswind decreases the lateral movement of the upwind vortex and increases the movement of the downwind vortex. A tailwind condition can move the vortices of the preceding aircraft forward into the touchdown zone. Vortex avoidance procedures. Landing behind a larger aircraft on the same runway. Stay at or above the larger aircraft's approach flight path and land beyond its touchdown point. Landing behind a larger aircraft on a parallel runway closer than 2,500 feet. Consider the possibility of drift and stay at or above the larger aircraft's final approach flight path and note its touchdown point. landing behind a larger aircraft on a crossing runway, cross above the larger aircraft's flight path, landing behind a departing aircraft on the same runway, land prior to the departing aircraft's rotating point, landing behind a larger aircraft on a crossing runway. Note the aircraft's rotation point, and if that point is past the intersection, continue and land prior to the intersection. If the larger aircraft rotates prior to the intersection, avoid flight below its flight path. Abandon the approach unless a landing is ensured well before reaching the intersection. Departing behind a large aircraft. Rotate prior to the large aircraft's rotation point and climb above its climb path until turning clear of the wake. For intersection takeoffs on the same runway, be alert to adjacent larger aircraft operations, particularly upwind of the runway of intended use. If an intersection takeoff clearance is received, avoid headings that cross below the larger aircraft's path. If departing or landing after a large aircraft executing a low approach, missed approach, or touch-and-go landing, since vortices settle and move laterally near the ground, the vortex hazard may exist along the runway and in the flight path, particularly in a quartering tailwind. It is prudent to wait at least 2 minutes prior to a takeoff or landing. En route, it is advisable to avoid a path below and behind a large aircraft, and if a large aircraft is observed above on the same track, change the aircraft position laterally and preferably upwind. Collision avoidance. 14 CFR 91 has established right-of-way rules, minimum safe altitudes, and VFR cruising altitudes to enhance flight safety. The pilot can contribute to collision avoidance by being alert and scanning for other aircraft. This is particularly important in the vicinity of an airport. Effective scanning is accomplished with a series of short, regularly spaced eye movements that bring successive areas of the sky into the central visual field. Each movement should not exceed 10 degrees, and each should be observed for at least 1 second to enable detection. Although back and forth eye movements seem preferred by most pilots, each pilot should develop a scanning pattern that is most comfortable and then adhere to it to assure optimum scanning. Even if entitled to the right-of-way, a pilot should yield if another aircraft seems too close. Clearing procedures. The following procedures and considerations should assist a pilot in collision avoidance under various situations. Before takeoff. Prior to taxiing onto a runway or landing area in preparation for takeoff, pilots should scan the approach area for possible landing traffic, executing appropriate maneuvers to provide a clear view of the approach areas. Climbs and descents. During climbs and descents in flight conditions which permit visual detection of other traffic, pilots should execute gentle banks left and right at a frequency which permits continuous visual scanning of the airspace. Straight and level. During sustained periods of straight and level flight, a pilot should execute appropriate clearing procedures at periodic intervals. Traffic patterns. Entries into traffic patterns while descending should be avoided. Traffic at VOR sites. Due to converging traffic, sustained vigilance should be maintained in the vicinity of VORs and intersections. Training operations. Vigilance should be maintained and clearing turns should be made prior to a practice maneuver. During instruction, the pilot should be asked to verbalize the clearing procedures. Call out clear left, right, above, and below. High-wing and low-wing aircraft had their respective blind spots. The pilot of a high-wing aircraft should momentarily raise the wing in the direction of the intended turn and look for traffic prior to commencing the turn. The pilot of a low-wing aircraft should momentarily lower the wing and look for traffic prior to commencing the turn. Runway incursion avoidance. A runway incursion is any occurrence in the airport runway environment involving an aircraft, vehicle, person, or object on the ground that creates a collision hazard or results in a loss of required separation with an aircraft taking off, intending to take off, landing, or intending to land. It is important to give the same attention to operating on the surface as in other phases of flight. Proper planning can prevent runway incursions and the possibility of a ground collision. A pilot should be aware of the aircraft's position on the surface at all times and be aware of other aircraft and vehicle operations on the airport. At times, towered airports can be busy and taxi instructions complex. In this situation, it may be advisable to write down taxi instructions. The following are some practices to help prevent a runway incursion. Read back all runway crossing and/or hold instructions. Review airport layouts as part of pre-flight planning, before descending to land and while taxiing as needed. Know airport signage. Review NOTAM for information on runway, slant taxiway closures, and construction areas. Request progressive taxi instructions from ATC when unsure of the taxi route. Check for traffic before crossing any runway hold line and before entering a taxiway. Turn on aircraft lights and the rotating beacon or strobe lights while taxiing. When landing, clear the active runway as soon as possible, then wait for taxi instructions before further movement. Study and use proper phraseology in order to understand and respond to ground control instructions. Write down complex taxi instructions at unfamiliar airports. For more detailed information, contact the FAA's Office of Runway Safety and Operational Services website at http://www.faa.gov/runway-safety/ or visit http://aopa.org/asf/accident_data/incursions.html to access a learning tool developed by the FAA and the Aircraft Owners and Pilots Association, AOPA, to help pilots and maintenance technicians avoid runway incursions involving taxiing aircraft. Additional information can also be found in Advisory Circular AC 91-73, Part 91, Pilot and Flight Crew Procedures During Taxi Operations, and Part 135, Single Pilot Procedures During Taxi Operations. Chapter Summary. This chapter focused on airport operations both in the air and on the surface. For specific information about an unfamiliar airport, consult the Airport Facility Directory and NOTAMs before flying. For further information regarding procedures discussed in this chapter, refer to 14 CFR Part 91 and the Airman's Information Manual. By adhering to established procedures, both airport operations and safety are enhanced. End of Part 3 of Chapter 13.
Part 1 of Chapter 14 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 1 of Chapter 14. Airspace. Introduction. The two categories of airspace are regulatory and non-regulatory. Within these two categories, there are four types: controlled, uncontrolled, special use, and other airspace. Figure 14-1 presents a profile view of the dimensions of various classes of airspace. Also, there are excerpts from sectional charts which are discussed in Chapter 15, Navigation, that are used to illustrate how airspace is depicted. Controlled airspace. Controlled airspace is a generic term that covers the different classifications of airspace and defined dimensions within which air traffic control, ATC, service is provided in accordance with the airspace classification. Controlled airspace consists of Class A, Class B, Class C, Class D, Class E. Class A airspace. Class A airspace is generally the airspace from 18,000 feet mean sea level, MSL, up to and including flight level, FL 600, including the airspace overlaying the waters within 12 nautical miles, nm of the coast of the 48 contiguous states and Alaska. Unless otherwise authorized, all operation in Class A airspace is conducted under Instrument Flight Rules, IFR. Class B airspace. Class B airspace is generally airspace from the surface to 10,000 feet MSL, surrounding the nation's busiest airports in terms of airport operations or passenger enplanements. The configuration of each Class B airspace area is individually tailored, consists of a surface area and 2 or more layers. Some Class B airspace areas resemble upside-down wedding cakes and is designed to contain all published instrument procedures once an aircraft enters the airspace. An ATC clearance is required for all aircraft to operate in the area, and all aircraft that are so cleared receive separation services within the airspace. Class C airspace. Class C airspace is generally airspace from the surface to 4,000 feet above the airport elevation, charted in MSL, surrounding those airports that have an operational control tower, are serviced by a radar approach control, and have a certain number of IFR operations or passenger enplanements. Although the configuration of each Class C area is individually tailored, the airspace usually consists of a surface area with a 5 nautical mile radius, an outer circle with a 10 nautical mile radius that extends from 1,200 feet to 4,000 feet above the airport elevation, and an outer area. Each aircraft must establish 2-way radio communications with the ATC facility providing air traffic services prior to entering the airspace and thereafter maintain those communications while within the airspace. Class D airspace. Class D airspace is generally airspace from the surface to 2,500 feet above the airport elevation, charted in MSL, surrounding those airports that have an operational control tower. The configuration of each Class D airspace area is individually tailored, and when instrument procedures are published, the airspace is normally designed to contain the procedures. Arrival extensions for instrument approach procedures, IAPs, may be Class D or Class E airspace. Unless otherwise authorized, each aircraft must establish 2-way radio communications with the ATC facility providing air traffic services prior to entering the airspace and thereafter maintain those communications while in the airspace. Class E airspace. If the airspace is not Class A, B, C, or D and is controlled airspace, then it is Class E airspace. Class E airspace extends upward from either the surface or a designated altitude to the overlying or adjacent controlled airspace. When designated as a surface area, the airspace is configured to contain all instrument procedures. Also in this class are federal airways, airspace beginning at either 700 or 1,200 feet above ground level, AGL, used to transition to and from the terminal or en route environment, and en route domestic and offshore airspace areas designated below 18,000 feet MSL. Unless designated at a lower altitude, Class E airspace begins at 14,500 MSL over the United States, including that airspace overlying the waters within 12 nautical miles of the coast of the 48 contiguous states and Alaska, up to but not including 18,000 feet MSL, and the airspace above FL 600. Uncontrolled airspace. Class G airspace. Uncontrolled airspace, or Class G airspace, is the portion of the airspace that has not been designated as Class A, B, C, D, or E. It is therefore designated uncontrolled airspace. Class G airspace extends from the surface to the base of the overlying Class E airspace. Although ATC has no authority or responsibility to control air traffic, pilots should remember there are visual flight rules, VFR, minimums which apply to Class G airspace. Special use airspace. Special Use Airspace, or Special Area of Operation, SAO, is the designation for airspace in which certain activities must be confined, or where limitations may be imposed on aircraft operations that are not part of those activities. Certain special use airspace areas can create limitations on the mixed use of airspace. The special use airspace depicted on instrument charts includes the area name or number, effective altitude, time and weather conditions of operation, the controlling agency, and the chart panel location. On National Aeronautical Charting Group (NACG) and route charts, this information is available on one of the N panels. Special use airspace usually consists of prohibited areas, restricted areas, warning areas, military operation areas, MOAs, alert areas, controlled firing areas, CFAs. Prohibited areas. Prohibited areas contain airspace of defined dimensions within which the flight of aircraft is prohibited. Such areas are established for security or other reasons associated with the national welfare. These areas are published in the Federal Register and are depicted on aeronautical charts. The area is charted as a P followed by a number, for example, P-49. Examples of prohibited areas include Camp David and the National Mall in Washington, D.C., where the White House and the congressional buildings are located. See Figure 14-2. Restricted areas. Restricted areas are areas where operations are hazardous to non-participating aircraft and contain airspace within which the flight of aircraft, while not wholly prohibited, is subject to restrictions. Activities within these areas must be confined because of their nature, or limitations may be imposed upon aircraft operations that are not a part of those activities, or both. Restricted areas denote the existence of unusual, often invisible, hazards to aircraft. For example, artillery firing, aerial gunnery, or guided missiles. IFR flights may be authorized to transit the airspace and are routed accordingly. Penetration of restricted areas without authorization from the using or controlling agency may be extremely hazardous to the aircraft and its occupants. ATC facilities apply the following procedures when aircraft are operating on an IFR clearance, including those cleared by ATC to maintain VFR on top, via a route which lies within joint use restricted airspace. 1. If the restricted area is not active and has been released to the Federal Aviation Administration, FAA, the ATC facility allows the aircraft to operate in the restricted airspace without issuing specific clearance for it to do so. 2. If the restricted area is active and has not been released to the FAA, the ATC facility issues a clearance which ensures the aircraft avoids the restricted airspace. Restricted areas are charted with an R followed by a number, for example, R-4401, and are depicted on the en route chart appropriate for use at the altitude or FL being flown. See Figure 14-3. Restricted area information can be obtained on the back of the chart. Warning areas. Warning areas are similar in nature to restricted areas. However, the United States government does not have sole jurisdiction over the airspace. A warning area is airspace of defined dimensions, extending from 12 nautical miles outward from the coast of the United States, containing activity that may be hazardous to non-participating aircraft. The purpose of such areas is to warn non-participating pilots of the potential danger. A warning area may be located over domestic or international waters or both. The airspace is designated with a W, followed by a number. For example, W-237. See Figure 14-4. Military Operation Areas, MOAs. MOAs consist of airspace with defined vertical and lateral limits established for the purpose of separating certain military training activities from IFR traffic. Whenever an MOA is being used, non-participating IFR traffic may be cleared through an MOA if IFR separation can be provided by ATC. Otherwise, ATC reroutes or restricts non-participating IFR traffic. MOAs are depicted on sectional, VFR terminal area, and en route low-altitude charts and are not numbered. For example, Camden Ridge MOA, see Figure 14-5. However, the MOA is also further defined on the back of the sectional charts with times of operation, altitudes affected, and the controlling agency. Alert areas. Alert areas are depicted on aeronautical charts with an A, followed by a number, for example, A-211, to inform non-participating pilots of areas that may contain a high volume of pilot training or an unusual type of aerial activity. Pilots should exercise caution in alert areas. All activity within an alert area shall be conducted in accordance with regulations without waiver, and pilots of participating aircraft, as well as pilots transiting the area, shall be equally responsible for collision avoidance. See Figure 14-6. Controlled Firing Areas, CFAs. CFAs contain activities which, if not conducted in a controlled environment, could be hazardous to non-participating aircraft. The difference between CFAs and other special use airspace is that activities must be suspended when a spotter aircraft, radar, or ground lookout position indicates an aircraft might be approaching the area. There is no need to chart CFAs since they do not cause a non-participating aircraft to change its flight path. End of Part 1, Chapter 14.
Part 2 of Chapter 14 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Robert Sherman, Jr. Pilot's Handbook of Aeronautical Knowledge, Chapter 14, Part 2, Other Airspace Areas. Other Airspace Areas. Other airspace areas is a general term referring to the majority of the remaining airspace. It includes local airport advisory, military training route or MTR, temporary flight restriction or TFR, parachute jump aircraft operations, published VFR routes, Terminal Radar Service Area, TRSA, National Security Area, or NSA. Local Airport Advisory, LAA. A service provided by facilities which are located on the landing airport, have a discrete ground-to-air communication frequency or the tower frequency when the tower is closed, automated weather reporting with voice broadcasting, and a continuous ASOS/AWOS data display, other continuous direct reading instruments, or manual observations available to the specialist. Military Training Routes, MTRs. MTRs are routes used by military aircraft to maintain proficiency in tactical flying. These routes are usually established below 10,000 feet MSL for operations at speeds in excess of 250 knots. Some route segments may be defined at higher altitudes for purposes of route continuity. Routes are identified as IFR or IR and VFR or VR, followed by a number. See Figure 14-7. MTRs with no segment above 1,500 feet AGL are identified by 4 number characters, e.g. IR1206, VR1207. MTRs that include one or more segments above 1,500 feet AGL are identified by 3 number characters, e.g. IR206 or VR207. IFR low-altitude en-route charts depict all IR routes and all VR routes that accommodate operations above 1,500 feet AGL. IR routes are conducted in accordance with IFR regardless of weather conditions. VFR sectional charts depict military training activities such as IR, VR, MOA, restricted area, warning area, and alert area information. Temporary flight restrictions, or TFR. A Flight Data Center, FDC, Notice to Airman, NOTAM, is issued to designate a TFR. The NOTAM begins with the phrase, flight restrictions, followed by the location of the temporary restriction, effective time period, area defined in statute miles, and altitudes affected. The NOTAM also contains the FAA Coordination Facility and telephone number, the reason for the restriction, and any other information deemed appropriate. The pilot should check the NOTAMs as part of flight planning. Some of the purposes for establishing a TFR are: protect persons and property in the air or on the surface from an existing or imminent hazard, provide a safe environment for the operation of disaster relief aircraft, prevent an unsafe congestion of sightseeing aircraft above an incident or event which may generate a high degree of public interest, protect declared national disasters for humanitarian reasons in the state of Hawaii, protect the President, Vice President, or other public figures, provide a safe environment for space agency operations. Since the events of September 11, 2001, the use of TFRs has become much more common. There have been a number of incidents of aircraft incursions into TFRs, which have resulted in pilots undergoing security investigations and certificate suspensions. It is the pilot's responsibility to be aware of TFRs in their proposed area of flight. One way to check is to visit the FAA website, www.tfr.faa.gov, and verify that there is not a TFR in the area. Parachute jump aircraft operations. Parachute jump aircraft operations are published in the Airport Facility Directory, AFD. Sites that are used frequently are depicted on sectional charts. Published VFR routes. Published VFR routes are for transitioning around, under, or through some complex airspace. Terms such as VFR flyway, VFR corridor, Class B airspace VFR transition route, and terminal area VFR route have been applied to such routes. These routes are generally found on VFR terminal area planning charts. Terminal Radar Service Areas, TRSAs. TRSAs are areas where participating pilots can receive additional radar services. The purpose of the service is to provide separation between all IFR operations and participating VFR aircraft. The primary airport within the TRSA becomes Class D airspace. The remaining portion of the TRSA overlies other controlled airspace, which is normally Class E airspace beginning at 700 or 1,200 feet and established to transition to or from the en route or terminal environment. TRSAs are depicted on VFR sectional charts and terminal area charts with a solid black line and altitudes for each segment. The Class D portion is charted with a blue segmented line. Participation in TRSA services is voluntary. However, pilots operating under VFR are encouraged to contact the Radar Approach Control and take advantage of TRSA service. National Security Areas, NSAs. NSAs consist of airspace of defined vertical and lateral dimensions established at locations where there is a requirement for increased security and safety of ground facilities. Flight in NSAs may be temporarily prohibited by regulation under the provisions of Title 14 of the Code of Federal Regulations, 14 CFR, Part 99, and prohibitions are disseminated via NOTAM. Pilots are requested to voluntarily avoid flying through these depicted areas. Air Traffic Control and the National Airspace System. The primary purpose of the ATC system is to prevent a collision between aircraft operating in the system and to organize and expedite the flow of traffic. In addition to its primary function, the ATC system has the capability to provide, with certain limitations, additional services. The ability to provide additional services is limited by many factors, such as the volume of traffic, frequency congestion, quality of radar, controller workload, higher priority duties, and the pure physical inability to scan and detect those situations that fall in this category. It is recognized that these services cannot be provided in cases in which the provision of services is precluded by the above factors. Consistent with the aforementioned conditions, controllers shall provide additional service procedures to the extent permitted by higher priority duties and other circumstances. The provision of additional services is not optional on the part of the controller, but rather is required when the work situation permits. Provide ATC service in accordance with the procedures and minima in this order except when 1. A deviation is necessary to conform with ICAO documents, national rules of the air, or special agreements where the United States provides ATC service in airspace outside the country and its possessions, or 2. Other procedures minima are prescribed in a letter of agreement, FAA directive, or a military document, or 3. A deviation is necessary to assist an aircraft when an emergency has been declared. Coordinating the use of airspace. ATC is responsible for ensuring that the necessary coordination has been accomplished before allowing an aircraft under their control to enter another controller's area of jurisdiction. Before issuing control instructions directly or relaying through another source to an aircraft which is within another controller's area of jurisdiction that will change that aircraft's heading, route, speed, or altitude, ATC ensures that coordination has been accomplished with each of the controllers listed below whose area of jurisdiction is affected by those instructions unless otherwise specified by a letter of agreement or a facility directive. 1. The controller within whose area of jurisdiction the control instructions are issued. 2. The controller receiving the transfer of control. 3. Any intervening controllers through whose area of jurisdiction the aircraft will pass. If ATC issues control instructions to an aircraft through a source other than another controller, e.g. Aeronautical Radio Incorporated, ARINC, Automated Flight Service Station, AFSS, FSS, or another pilot, they ensure that the necessary coordination has been accomplished with any controllers listed above, whose area of jurisdiction is affected by those instructions, unless otherwise specified by a letter of agreement or a facility directive. Operating in the various types of airspace. It is important that pilots be familiar with the operational requirements for each of the various types or classes of airspace. Subsequent sections cover each class in sufficient detail to facilitate understanding with regard to weather, type of pilot certificate held, as well as equipment required. Basic VFR weather minimums. No pilot may operate an aircraft under basic VFR when the flight visibility is less or at a distance from clouds that is less than that prescribed for the corresponding altitude and class of airspace. See Figure 14-9. Except as provided in 14 CFR Section 91.157, Special VFR Weather Minimums, no person may operate an aircraft beneath the ceiling under VFR within the lateral boundaries of controlled airspace designated to the surface for an airport when the ceiling is less than 1,000 feet. Additional information can be found in 14 CFR Section 91.155C. Operating rules and pilot equipment requirements. The safety of flight is a top priority of all pilots, and the responsibilities associated with operating an aircraft should always be taken seriously. The air traffic system maintains a high degree of safety and efficiency with strict regulatory oversight of the FAA. Pilots fly in accordance with regulations that have served the United States well, as evidenced by the fact that the country has the safest aviation system in the world. All aircraft operating in today's National Airspace System, NAS, has complied with the CFR governing its certification and maintenance. All pilots operating today have completed rigorous pilot certification training and testing. Of equal importance is the proper execution of pre-flight planning, Aeronautical Decision-Making, ADM, and risk management. ADM involves a systematic approach to risk assessment and stress management in aviation, illustrates how personal attitudes can influence decision-making, and how those attitudes can be modified to enhance safety in the flight deck. More detailed information regarding ADM and risk mitigation can be found in Chapter 17, Aeronautical Decision-Making. Pilots also comply with very strict FAA general operating and flight rules as outlined in the CFR, including the FAA's important See and Avoid mandate. These regulations provide the historical foundation of the FAA regulations governing the aviation system and the individual classes of airspace. Figure 14-10 lists the operational and equipment requirements for these various classes of airspace. It will be helpful to refer to this figure as the specific classes are discussed in greater detail. Class A. Pilots operating an aircraft in Class A airspace must conduct that operation under IFR and only under an ATC clearance received prior to entering the airspace. Unless otherwise authorized by ATC, each aircraft operating in Class A airspace must be equipped with a two-way radio capable of communicating with ATC on a frequency assigned by ATC. Unless otherwise authorized by ATC, all aircraft within Class A airspace must be equipped with the appropriate transponder equipment, meeting all applicable specifications found in 14 CFR Section 91.215. Class B. All pilots operating an aircraft within a Class B airspace area must receive an ATC clearance from the ATC facility having jurisdiction for that area. The pilot in command, PIC, may not take off or land an aircraft at an airport within a Class B airspace unless he or she has met one of the following requirements. 1. A private pilot certificate. 2. A recreational pilot certificate and all requirements contained within 14 CFR Section 61.101D, or the requirements for a student pilot seeking a recreational pilot certificate in 14 CFR Section 61.94. 3. A sport pilot certificate and all requirements contained within 14 CFR Section 61.325, or the requirements for a student pilot seeking a recreational pilot certificate in 14 CFR Section 61.94, or the aircraft is operated by a student pilot who has met the requirements of 14 CFR Sections 61.94 and 61.95 as applicable. Unless otherwise authorized by ATC, all aircraft within Class B airspace must be equipped with the applicable operating transponder and automatic altitude reporting equipment specified in 14 CFR Section 91.215A, and an operable two-way radio capable of communications with ATC on appropriate frequencies for that Class B airspace area. Class C. For the purpose of this section, the primary airport is the airport for which the Class C airspace area is designated. A satellite airport is any other airport within the Class C airspace area. No pilot may take off or land an aircraft at a satellite airport within a Class C airspace area except in compliance with FAA arrival and departure traffic patterns. Two-way radio communications must be established and maintained with the ATC facility providing air traffic services prior to entering the airspace and thereafter maintained while within the airspace. A pilot departing from the primary airport or satellite airport with an operating control tower must establish and maintain two-way radio communications with the control tower, and thereafter as instructed by ATC while operating in the Class C airspace area. If departing from a satellite airport without an operating control tower, the pilot must establish and maintain two-way radio communications with the ATC facility having jurisdiction over the Class C airspace area as soon as practicable after departing. Unless otherwise authorized by the ATC having jurisdiction over the Class C airspace area, all aircraft within Class C airspace must be equipped with the appropriate transponder equipment meeting all applicable specifications found in 14 CFR Section 91.215. Class D. No pilot may take off or land an aircraft at a satellite airport within a Class D airspace area except in compliance with FAA arrival and departure traffic patterns. A pilot departing from the primary airport or satellite airport with an operating control tower must establish and maintain two-way radio communications with the control tower, and thereafter as instructed by ATC while operating in the Class D airspace area. If departing from a satellite airport without an operating control tower, the pilot must establish and maintain two-way radio communications with the ATC facility having jurisdiction over the Class D airspace area as soon as practicable after departing. Two-way radio communications must be established and maintained with the ATC facility providing air traffic services prior to entering the airspace and thereafter maintained while within the airspace. If the aircraft radio fails in flight under IFR, the pilot should continue the flight by the route assigned in the last ATC clearance received, or if being radar vectored, by the direct route from the point of radio failure to the fix, route, or airway specified in the vector clearance. In the absence of an assigned route, the pilot should continue by the route that ATC advised may be expected in a further clearance, or if a route had not been advised, by the route filed in the flight plan. If the aircraft radio fails in flight under VFR, the PIC may operate that aircraft and land if weather conditions are at or above basic VFR weather minimums, visual contact with the tower is maintained, and a clearance to land is received. Class E. unless otherwise required by 14 CFR Part 93, or unless otherwise authorized or required by the ATC facility having jurisdiction over the Class E airspace area. Each pilot operating an aircraft on or in the vicinity of an airport in a Class E airspace area must comply with the requirements of Class G airspace. Each pilot must also comply with any traffic patterns established for that airport in 14 CFR Part 93. Unless otherwise authorized or required by ATC, no person may operate an aircraft to, from, through, or on an airport having an operational control tower unless two-way radio communications are maintained between that aircraft and the control tower. Communications must be established prior to 4 nautical miles from the airport, up to and including 2,500 feet AGL. However, if the aircraft radio fails in flight, the PIC may operate that aircraft and land if weather conditions are at or above basic VFR weather minimums, visual contact with the tower is maintained, and a clearance to land is received. If the aircraft radio fails in flight under IFR, the pilot should continue the flight by the route assigned in the last ATC clearance received, or if being radar vectored, by the direct route from the point of radio failure to the fix, route, or airway specified in the vector clearance. In the absence of an assigned route, the pilot should continue by the route that ATC advised may be expected in a further clearance, or if a route had not been advised, by the route filed in the flight plan. Class G. When approaching to land at an airport without an operating control tower in Class G airspace. 1. Each pilot of an airplane must make all turns of that airplane to the left unless the airport displays approved light signals or visual markings indicating that turns should be made to the right, in which case the pilot must make all turns to the right. 2. Each pilot of a helicopter or a powered parachute must avoid the flow of fixed-wing aircraft. Unless otherwise authorized or required by ATC, no person may operate an aircraft to, from, through, or on an airport having an operational control tower unless two-way radio communications are maintained between that aircraft and the control tower. Communications must be established prior to 4 nautical miles from the airport, up to and including 2,500 feet AGL. However, if the aircraft radio fails in flight, the pilot in command may operate that aircraft and land if weather conditions are at or above basic VFR weather minimums, visual contact with the tower is maintained, and a clearance to land is received. If the aircraft radio fails in flight under IFR, the pilot should continue the flight by the route assigned in the last ATC clearance received, or if being radar vectored, by the direct route from the point of radio failure to the fix, route, or airway specified in the vector clearance. In the absence of an assigned route, the pilot should continue by the route that ATC advised may be expected in a further clearance, or, if a route had not been advised, by the route filed in the flight plan. Ultralight vehicles. No person may operate an ultralight vehicle within Class A, Class B, Class C, or Class D airspace, or within the lateral boundaries of the surface area of Class C airspace designated for an airport, unless that person has prior authorization from the ATC facility having jurisdiction over that airspace. See 14 CFR Part 103. Unmanned free balloons. Unless otherwise authorized by ATC, no person may operate an unmanned free balloon below 2,000 feet above the surface within the lateral boundaries of Class B, Class C, Class D, or Class E airspace designated for an airport. See 14 CFR Part 101. Parachute jumps. No person may make a parachute jump, and no PIC may allow a parachute jump to be made from that aircraft in or into Class A, Class B, Class C, or Class D airspace without, or in violation of, the terms of an ATC authorization issued by the ATC facility having jurisdiction over the airspace. See 14 CFR Part 105. Chapter Summary. This chapter introduces the various classifications of airspace and provides information on the requirements to operate in such airspace. For further information, consult the AIM and 14 CFR Part 71, 73, and 91. End of Part 2 of Chapter 14. Recording by Robert Sherman, Jr., Washington, D.C., www.nyckidd.com.
Part 1 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Sammy. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 15, Navigation. Introduction. This chapter provides an introduction to cross-country flying under Visual Flight Rules, VFR. It contains practical information for planning and executing cross-country flights for the beginning pilot. Air navigation is the process of piloting an aircraft from one geographic position to another, while monitoring one's position as the flight progresses. It introduces the need for planning, which includes plotting the course on an aeronautical chart, selecting checkpoints, measuring distances, obtaining pertinent weather information, and computing flight time, headings, and fuel requirements. The methods used in this chapter include pilotage, navigating by reference to visible landmarks, dead reckoning, computations of direction and distance from a known position, and radio navigation, by use of radio aids. Aeronautical charts. An aeronautical chart is a roadmap for a pilot flying under VFR. The chart provides information which allows pilots to track their position and provides available information which enhances safety. The three aeronautical charts used by VFR pilots are Sectional, VFR Terminal Area, World Aeronautical. A free catalog listing aeronautical charts and related publications, including prices and instructions for ordering, is available at the National Aeronautical Charting Group NACG website, www.naco.faa.gov. Sectional charts. Sectional charts are the most common charts used by pilots today. The charts have a scale of 1 to 500,000, 1 inch equals 6.86 nautical miles, NM, or approximately 8 statute miles, SM, which allows for more detailed information to be included on the chart. The charts provide an abundance of information, including airport data, navigational aids, airspace, and topography. Figure 15-1 is an excerpt from the legend of a sectional chart. By referring to the chart legend, a pilot can interpret most of the information on the chart. A pilot should also check the chart for other legend information, which includes air traffic control, ATC frequencies, and information on airspace. These charts are revised semi-annually, except for some areas outside the conterminous United States where they are revised annually. VFR Terminal Area Charts. VFR Terminal Area Charts are helpful when flying in or near Class B airspace. They have a scale of 1 to 250,000. 1 inch equals 3.43 nautical miles, or approximately 4 statute miles. These charts provide a more detailed display of topographical information and are revised semi-annually, except for several Alaskan and Caribbean charts. See Figure 15-2. World Aeronautical Charts. World Aeronautical Charts are designed to provide a standard series of aeronautical charts covering land areas of the world at a size and scale convenient for navigation by moderate-speed aircraft. They are produced at a scale of 1 to 1 million. 1 inch equals 13.7 nautical miles, or approximately 16 statute miles. These charts are similar to sectional charts, and the symbols are the same, except there's less detail due to the smaller scale. See Figure 15-3. These charts are revised annually, except several Alaskan charts and the Mexican Caribbean charts, which are revised every 2 years. Latitude and longitude. Parallels and meridians. The equator is an imaginary circle, equidistant from the poles of the Earth. Circles parallel to the equator, lines running east and west, are parallels of latitude. They are used to measure degrees of latitude north, N, or south, S, of the equator. The angular distance from the equator to the pole is 1/4 of a circle, or 90 degrees. The 48 conterminous states of the United States are located between 25 degrees and 49 degrees north latitude. The arrows in figure 15-4 labeled latitude point to lines of latitude. Meridians of longitude are drawn from the North Pole to the South Pole and are at right angles to the equator. The prime meridian, which passes through Greenwich, England, is used as the zero line from which measurements are made in degrees east, E, and west, W, to 180 degrees. The 48 conterminous states of the United States are between 67 degrees and 125 degrees west longitude. The arrows in figure 15-4 labeled longitude point to lines of longitude. Any specific geographical point can be located by reference to its longitude and latitude. Washington, D.C., for example, is approximately 39 degrees north latitude, 77 degrees west longitude. Chicago is approximately 42 degrees north latitude, 88 degrees west longitude. Time zones. The meridians are also useful for designating time zones. A day is defined as the time required for the Earth to make one complete rotation of 360 degrees. Since the day is divided into 24 hours, the Earth revolves at the rate of 15 degrees an hour. Noon is the time when the sun is directly above a meridian. To the west of that meridian is morning, to the east is afternoon. The standard practice is to establish a time zone for each 15 degrees of longitude. This makes a difference of exactly 1 hour between each zone. In the United States, there are 4 time zones. The time zones are Eastern, 75 degrees, Central, 90 degrees, Mountain, 105 degrees, and Pacific, 120 degrees. The dividing lines are somewhat irregular because communities near the boundaries often find it more convenient to use time designations of neighboring communities or trade centers. Figure 15-5 and errata shows the time zones in the United States. When the sun is directly above the 90th meridian, it is noon Central Standard Time. At the same time, it is 1 p.m. Eastern Standard Time, 11 a.m. Mountain Standard Time, and 10 a.m. Pacific Standard Time. When daylight saving time is in effect, generally between the second Sunday in March and the first Sunday in November, the sun is directly above the 75th meridian at noon Central Daylight Time. These time zone differences must be taken into account during long flights eastward, especially if the flight must be completed before dark. Remember, an hour is lost when flying eastward from one time zone to another, or perhaps even when flying from the western edge to the eastern edge of the same time zone. Determine the time of sunset at the destination by consulting the flight service stations, AFSS/FSS, or National Weather Service, NWS, and take this into account when planning an eastbound flight. In most aviation operations, time is expressed in terms of the 24-hour clock. ATC instructions, weather reports and broadcasts, and estimated times of arrival are all based on this system. For example, 9 a.m. is expressed as 0900, 1 p.m. is 1300, and 10 p.m. is 2200. Because a pilot may cross several time zones during a flight, a standard time system has been adopted. It is called Universal Coordinated Time, UTC, and is often referred to as Zulu time. UTC is the time at the 0-degree line of longitude, which passes through Greenwich, England. All of the time zones around the world are based on this reference. To convert to this time, a pilot should do the following. Eastern Standard Time, add 5 hours. Central Standard Time, add 6 hours. Mountain Standard Time, add 7 hours. Pacific Standard Time, add 8 hours. For daylight saving time, 1 hour should be subtracted from the calculated times. Measurement of direction. By using the meridians, direction from one point to another can be measured in degrees, in a clockwise direction from true north. To indicate a course to be followed in flight, draw a line on the chart from the point of departure to the destination, and measure the angle which this line forms with a meridian. Direction is expressed in degrees, as shown by the compass rose in Figure 15-6 and errata. Because meridians converge toward the poles, course measurement should be taken at a meridian near the midpoint of the course, rather than at the point of departure. The course measured on the chart is known as the true course, TC. This is the direction measured by reference to a meridian, or true north. It is the direction of intended flight, as measured in degrees clockwise from true north. As shown in Figure 15-7, the direction from A to B would be a true course of 065 degrees, whereas the return trip, called the reciprocal, would be a true course of 245 degrees. The true heading, TH, is the direction in which the nose of the aircraft points during a flight, when measured in degrees clockwise from true north. Usually, it is necessary to head the aircraft in a direction slightly different from the true course to offset the effect of wind. Consequently, numerical value of the true heading may not correspond with that of the true course. This is discussed more fully in subsequent sections in this chapter. For the purpose of this discussion, assume a no-wind condition exists, under which heading and course would coincide. Thus, for a true course of 065 degrees, the true heading would be 065 degrees. To use the compass accurately, however, corrections must be made for magnetic variation and compass deviation. End of Part 1 of Chapter 15.
Part 2 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 15, Navigation. Variation. Variation is the angle between true north and magnetic north. It is expressed as east variation or west variation depending upon whether magnetic north, MN, is to the east or west of true north, TN. The north magnetic pole is located close to 71 degrees north latitude, 96 degrees west longitude, and is about 1,300 miles from the geographic or true north pole as indicated in Figure 15-8. If the Earth were uniformly magnetized, the compass needle would point toward the magnetic pole, in which case the variation between true north, as shown by the geographical meridians, and magnetic north, as shown by the magnetic meridians, could be measured at any intersection of the meridians. Actually, the Earth is not uniformly magnetized. In the United States, the needle usually points in the general direction of the magnetic pole, but it may vary in certain geographical localities by many degrees. Consequently, the exact amount of variation at thousands of selected locations in the United States has been carefully determined. The amount and direction of variation, which change slightly from time to time, are shown on most aeronautical charts as broken magenta lines, called isogonic lines, which connect points of equal magnetic variation. The line connecting points at which there is no variation between true north and magnetic north is the agonic line. An isogonic chart is shown in Figure 15-9. Minor bends and turns in the isogonic and agonic lines are caused by unusual geological conditions affecting magnetic forces in these areas. On the west coast of the United States, the compass needle points to the east of true north. On the east coast, the compass needle points to the west of true north. 0-degree variation exists on the agonic line, where magnetic north and true north coincide. This line runs roughly west of the Great Lakes, south through Wisconsin, Illinois, western Tennessee, and along the border of Mississippi and Alabama. Compare Figures 15-9 and 15-10. Because courses are measured in reference to geographical meridians which point toward true north, and these courses are maintained by reference to the compass, which points along a magnetic meridian in the general direction of magnetic north, the true direction must be converted into magnetic direction for the purpose of flight. This conversion is made by adding or subtracting the variation which is indicated by the nearest isogonic line on the chart. For example, a line drawn between 2 points on a chart is called a true course, as it is measured from true north. However, flying this course off the magnetic compass would not provide an accurate course between the 2 points due to 3 elements that must be considered. The first is magnetic variation, the second is compass deviation, and the third is wind correction. All 3 must be considered for accurate navigation. Magnetic variation. As mentioned in the paragraph discussing variation, the appropriate variation for the geographical location of the flight must be considered and added or subtracted as appropriate. If flying across an area where the variation changes, then the values must be applied along the route of flight appropriately. Once applied, this new course is called the magnetic course. Magnetic deviation. Because each aircraft has its own internal effect upon the onboard compass systems from its own localized magnetic influencers, the pilot must add or subtract these influencers based upon the direction he or she is flying. The application of deviation, taken from a compass deviation card, compensates the magnetic course unique to that aircraft's compass system, as affected by localized magnetic influencers, and it now becomes the compass course. Therefore, the compass course, when followed in a no-wind condition, takes the aircraft from point A to point B, even though the aircraft heading may not match the original course line drawn on the chart. If the variation is shown as 9 degrees east, this means that magnetic north is 9 degrees east of true north. If a true course of 360 degrees is to be flown, 9 degrees must be subtracted from 360 degrees, which results in a magnetic heading of 351 degrees. To fly east, a magnetic course of 081 degrees, 090 degrees minus 9 degrees, would be flown. To fly south, the magnetic course would be 171 degrees, 180 degrees minus 9 degrees. To fly west, it would be 261 degrees, 270 degrees minus 9 degrees. To fly a true heading of 060 degrees, a magnetic course of 051 degrees, 060 degrees minus 9 degrees would be flown. Remember, if variation is west, add. If east, subtract. One method for remembering whether to add or subtract variation is the phrase, east is least, subtract, and west is best, add. Deviation. Determining the magnetic heading is an intermediate step necessary to obtain the correct compass heading for the flight. To determine compass heading, a correction for deviation must be made. Because of magnetic influences within an aircraft, such as electrical circuits, radio, lights, tools, engine, and magnetized metal parts, the compass needle is frequently deflected from its normal reading. This deflection is deviation. The deviation is different for each aircraft, and it also may vary for different headings in the same aircraft. For instance, if magnetism in the engine attracts the north end of the compass, there would be no effect when the plane is on a heading of magnetic north. On easterly and westerly headings, however, the compass indications would be in error, as shown in Figure 15-11. Magnetic attraction can come from many other parts of the aircraft. The assumption of attraction in the engine is merely used for the purpose of illustration. Some adjustment of the compass, referred to as compensation, can be made to reduce this error, but the remaining correction must be applied by the pilot. Proper compensation of the compass is best performed by a competent technician. Since the magnetic forces within the aircraft change because of landing shocks, vibration, mechanical work, or changes in equipment, the pilot should occasionally have the deviation of the compass checked. The procedure used to check the deviation, called swinging the compass, is briefly outlined. The aircraft is placed on a magnetic compass rose, the engine started, and the electrical devices normally used, such as radio, are turned on. Tailwheel type aircraft should be jacked up into flying position. The aircraft is aligned with magnetic north indicated on the compass rose, and the reading shown on the compass is recorded on a deviation card. The aircraft is then aligned at 30-degree intervals, and each reading is recorded. If the aircraft is to be flown at night, the lights are turned on and any significant changes in the readings are noted. If so, additional entries are made for use at night. The accuracy of the compass can also be checked by comparing the compass reading with the known runway headings. A deviation card similar to Figure 15-12 is mounted near the compass, showing the addition or subtraction required to correct for deviation on various headings, usually at intervals of 30 degrees. For intermediate readings, the pilot should be able to interpolate mentally with sufficient accuracy. For example, if the pilot needed the correction for 195 degrees and noted the correction for 180 degrees to be 0 degrees and for 210 degrees to be plus 2 degrees, it could be assumed that the correction for 195 degrees would be plus 1 degree. The magnetic heading, when corrected for deviation, is known as compass heading. Effective wind. The preceding discussion explained how to measure a true course on the aeronautical chart and how to make corrections for variation and deviation. But one important factor has not been considered: wind. As discussed in the study of the atmosphere, wind is a mass of air moving over the surface of the earth in a definite direction. When the wind is blowing from the north at 25 knots, it simply means that air is moving southward over the Earth's surface at the rate of 25 nautical miles in 1 hour. Under these conditions, any inert object free from contact with the Earth is carried 25 nautical miles southward in 1 hour. This effect becomes apparent when such things as clouds, dust, and toy balloons are observed being blown along by the wind. Obviously, an aircraft flying within the moving mass of air is similarly affected. Even though the aircraft does not float freely with the wind, it moves through the air at the same time the air is moving over the ground, thus is affected by wind. Consequently, at the end of 1 hour of flight, the aircraft is in a position which results from a combination of the following two motions: movement of the air mass in reference to the ground, forward movement of the aircraft through the air mass. Actually, these two motions are independent. It makes no difference whether the mass of air through which the aircraft is flying is moving or is stationary. A pilot flying in a 70-knot gale would be totally unaware of any wind, except for possible turbulence, unless the ground were observed. In reference to the ground, however, the aircraft would appear to fly faster with a tailwind or slower with a headwind, or to drift right or left with a crosswind. As shown in Figure 15-13, an aircraft flying eastward at an airspeed of 120 knots in still air has a ground speed, GS, exactly the same, 120 knots. If the mass of air is moving eastward at 20 knots, the airspeed of the aircraft is not affected. But the progress of the aircraft over the ground is 120 plus 20, or a GS of 140 knots. On the other hand, if the mass of air is moving westward at 20 knots, the airspeed of the aircraft remains the same, but GS becomes 120 minus 20, or 100 knots. Assuming no correction is made for wind effect, if an aircraft is heading eastward at 120 knots and the air mass moving southward at 20 knots, the aircraft at the end of 1 hour is almost 120 miles east of its point of departure because of its progress through the air. It is 20 miles south because of the motion of the air. Under these circumstances, the airspeed remains 120 knots, but the GS is determined by combining the movement of the aircraft with that of the air mass. GS can be measured as the distance from the point of departure to the position of the aircraft at the end of 1 hour. The GS can be computed by the time required to fly between 2 points a known distance apart. It can also be determined before flight by constructing a wind triangle, which is explained later in this chapter. Refer to Figure 15-14. The direction in which the aircraft is pointing as it flies is heading. Its actual path over the ground, which is a combination of the motion of the aircraft and the motion of the air, is its track. The angle between the heading and the track is drift angle. If the aircraft heading coincides with the true course and the wind is blowing from the left, the track does not coincide with the true course. The wind causes the aircraft to drift to the right, so the track falls to the right of the desired course or true course. Refer to Figure 15-15. The following method is used by many pilots to determine compass heading. After the TC is measured and the wind correction applied resulting in a TH, the sequence TH plus or minus variation, V, equals magnetic heading, MH, plus or minus deviation, D, equals compass heading, CH, is followed to arrive at compass heading. Refer to Figure 15-16. By determining the amount of drift, the pilot can counteract the effect of the wind and make the track of the aircraft coincide with the desired course. If the mass of air is moving across the course from the left, the aircraft drifts to the right, and a correction must be made by heading the aircraft sufficiently to the left to offset this drift. To state in another way, if the wind is from the left, the correction is made by pointing the aircraft to the left a certain number of degrees, therefore correcting for wind drift. This is the wind correction angle, WCA, and is expressed in terms of degrees right or left of the true course. Refer to Figure 15-17. To summarize, course, intended path of an aircraft over the ground, or the direction of a line drawn on a chart representing the intended aircraft path, expressed as the angle measured from a specific reference datum clockwise from 0 degrees through 360 degrees to the line. Heading, direction in which the nose of the aircraft points during flight. Track, actual path made over the ground in flight. If proper correction has been made for the wind, track and course are identical. Drift angle, angle between heading and track. WCA, correction applied to the course to establish a heading so that track coincides with course. Airspeed, rate of the aircraft's progress through the air. GS, rate of the aircraft's in-flight progress over the ground. Basic calculations. Before a cross-country flight, a pilot should make common calculations for time, speed, and distance, and the amount of fuel required. Converting minutes to equivalent hours. Frequently, it is necessary to convert minutes into equivalent hours when solving speed, time, and distance problems. To convert minutes to hours, divide by 60. 60 minutes equal 1 hour. Thus, 30 minutes is 30 divided by 60 equals 0.5 hours. To convert hours to minutes, multiply by 60. Thus, 0.75 hour equals 0.75 times 60 equals 45 minutes. Time. T equals D divided by GS. To find the time, T, in flight, divide the distance, D, by the GS. The time to fly 210 nautical miles at a GS of 140 knots is 210 divided by 140, or 1.5 hours. The 0.5 hour multiplied by 60 minutes equals 30 minutes. Answer, 1 hour, 30 minutes. Distance. D equals GS times T. To find the distance flown in a given time, multiply ground speed by time. The distance flown in 1 hour 45 minutes at a ground speed of 120 knots is 120 times 1.75, or 210 nautical miles. GS. GS equals D divided by T. To find the ground speed, divide the distance flown by the time required. If an aircraft flies 270 nautical miles in 3 hours, the ground speed is 270 divided by 3 equals 90 knots. Converting knots to miles per hour. Another conversion is that of changing knots to miles per hour, mph. The aviation industry is using knots more frequently than mph, but it might be well to discuss the conversion for those that use mph when working with speed problems. The National Weather Service reports both surface winds and winds aloft in knots. However, airspeed indicators in some aircraft are calibrated in mph, although many are now calibrated in both miles per hour and knots. Pilots therefore should learn to convert wind speeds that are reported in knots to miles per hour. A knot is 1 nautical mile per hour, nmph. Because there are 6,076.1 feet in 1 nautical mile and 5,280 feet in 1 statute mile, the conversion factor is 1.15. To convert knots to miles per hour, multiply speed in knots by 1.15. For example, a wind speed of 20 knots is equivalent to 23 miles per hour. Most flight computers or electronic calculators have a means of making this conversion. Another quick method of conversion is to use the scales of nautical miles and statute miles at the bottom of aeronautical charts. Fuel consumption. Aircraft fuel consumption is frequently computed in gallons per hour. Consequently, to determine the fuel required for a given flight, the time required for the flight must be known. Time in flight multiplied by rate of consumption gives the quantity of fuel required. For example, a flight of 400 nautical miles at a ground speed of 100 knots requires 4 hours. If an aircraft consumes 5 gallons an hour, the total consumption is 4 times 5, or 20 gallons. The rate of fuel consumption depends on many factors: condition of the engine, propeller or rotor pitch, propeller or rotor revolutions per minute, RPM, richness of the mixture, and particularly the percentage of horsepower used for flight at cruising speed. The pilot should know the approximate consumption rate from cruise performance charts or from experience. In addition to the amount of fuel required for the flight, there should be sufficient fuel for reserve. Flight computers. Up to this point, only mathematical formulas have been used to determine such items as time, distance, speed, and fuel consumption. In reality, most pilots use a mechanical or electronic flight computer. These devices can compute numerous problems associated with flight planning and navigation. The mechanical or electronic computer has an instruction book that probably includes sample problems so the pilot can become familiar with its functions and operation. Refer to Figure 15-18. Plotter. Another aid in flight planning is a plotter, which is a protractor and ruler. The pilot can use this when determining true course and measuring distance. Most plotters have a ruler which measures in both nautical miles and statute miles and has a scale for a sectional chart on one side and a world aeronautical chart on the other. Refer to Figure 15-18. End of Part 2 of Chapter 15.
Part 3 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Chris Hawkins, Gaithersburg. Pilot's Handbook of Aeronautical Knowledge by the FAA. Navigation. Pilotage. Pilotage is navigation by reference to landmarks or checkpoints. It is a method of navigation that can be used on any course that has adequate checkpoints, but is more commonly used in conjunction with dead reckoning and VFR radio navigation. The checkpoints selected should be prominent features common to the area of the flight. Choose checkpoints that can be readily identified by other features such as roads, rivers, railroad tracks, lakes, and power lines. If possible, select features that make useful boundaries or brackets on each side of the course, such as highways, rivers, railroads, and mountains. A pilot can keep from drifting too far off course by referring to and not crossing the selected brackets. Never place complete reliance on a single checkpoint. Choose ample checkpoints. If one is missed, look for the next one while maintaining the heading. When determining position from checkpoints, remember that the scale of a sectional chart is 1 inch equals 8 square miles, or 6.86 nautical miles. For example, if a checkpoint selected was approximately 1/2 inch from the course line on the chart, it is 4 square miles, or 3.43 nautical miles, from the course on the ground. In the more congested areas, some of the smaller features are not included on the chart. If confused, hold the heading. If a turn is made away from the heading, it is easy to become lost. Roads shown on the chart are primarily the well-traveled roads or those most apparent when viewed from the air. New roads and structures are constantly being built and may not be shown in the chart until the next chart is issued. Some structures, such as antennas, may be difficult to see. Sometimes TV antennas are grouped together in an area near a town. They are supported by almost invisible guy wires. Never approach an area of an antenna less than 500 feet above the tallest one. Most of the taller structures are marked with strobe lights to make them more visible to a pilot. However, some weather conditions or background lighting may make them difficult to see. Aeronautical charts display the best information available at the time of printing, but a pilot should be cautious for new structures or changes that have occurred since the chart was printed. Dead reckoning. Dead reckoning is navigation solely by means of computation based on time, airspeed, distance, and direction. The products derived from these variables, when adjusted by wind speed and velocity, are the heading and ground speed. The predicted heading takes the aircraft along the intended path, and the ground speed establishes the time to arrive at each checkpoint and the destination. Except for flights over water, dead reckoning is usually used with pilotage for cross-country flying. The heading and ground speed as calculated is constantly monitored and corrected by pilotage as observed from checkpoints. The wind triangle or vector analysis. If there is no wind, the aircraft's ground track is the same as the heading and the ground speed is the same as the true airspeed. This condition rarely exists. A wind triangle, the pilot's version of a vector analysis, is the basis of dead reckoning. The wind triangle is a graphic explanation of the effect of a wind upon flight. Ground speed, heading, and time for any flight can be determined by using the wind triangle. It can be applied to the simplest kind of cross-country flight as well as the most complicated instrument flight. The experienced pilot becomes so familiar with the fundamental principles that estimates can be made which are adequate for visual flight without actually drawing the diagrams. The beginning student pilot, however, needs to develop skill in constructing these diagrams as an aid to the complete understanding of wind effect. Either consciously or unconsciously, every good pilot thinks of the flight in terms of wind triangle. If flight is to be made on a course to the east, with a wind blowing from the northeast, the aircraft must be headed somewhat to the north of east to counteract the drift. This can be represented by a diagram as shown in Figure 15 TAC 19. Each line represents direction and speed. The long blue and white hashed line shows the direction the aircraft is heading, and its length represents the distance the airspeed for 1 hour. The short blue arrow at the right shows the wind direction, and the length represents the wind velocity for 1 hour. The solid yellow line shows the direction of the track or the path of the aircraft as measured over the earth, and its length represents the distance traveled in 1 hour, or the ground speed. In actual practice, the triangle illustrated in Figure 15 TAC 19 is not drawn. Instead, construct a similar triangle as shown by the blue, yellow, and black lines in Figure 15 TAC 20, which is explained in the following example. Suppose a flight is to be flown from E to P. Draw a line on the aeronautical chart connecting these 2 points. Measure the direction with a protractor or plotter in reference to a meridian. This is the true course, which in this example is assumed to be 90 degrees east. From the nautical wind speed it is learned that the wind at the altitude of the intended flight is 40 knots from the northeast, 45 degrees. Since the nautical wind speed reports the wind speed in knots, if the true airspeed of the aircraft is 120 knots, there is no need to convert speeds from knots to miles per hour or vice versa. Now, on a plain piece of paper, draw a vertical line representing north to south. The various steps are shown in Figure 15 TAC 21. Step 1. Place the protractor with the base resting on the vertical line and the curved edge facing east. At the center point of the base, make a dot labeled E, point of departure, and at the curved edge, make a dot at 90 degrees, indicating the direction of the true course, and another at 45 degrees, indicating wind direction. Step 2. With a ruler, draw the true course line from E, extending it somewhat beyond the dot by 90 degrees and labeling it TC 90 degrees. Step 3. Next align the ruler with E and the dot at 45 degrees, and draw the wind arrow from east, not toward 45 degrees, but downwind in the direction of the wind is blowing, making it 40 units long to correspond with a wind velocity of 40 knots. Identify this line as the wind line by placing the letter W at the end to show the wind direction. Step 4. Finally, measure 120 units on the ruler to represent the airspeed, making a dot on the ruler at this point. The units used may be any convenient scale or value, such as 1/4 inch equals 10 knots. But once selected, the same scale must be used for each of the linear movements involved. Then place the ruler so that the end of it is on the arrowhead, west, and the 120 knot dot intercepts the true course line. Draw the line and label it airspeed 120. The point P placed at the intersection represents the position of the aircraft at the end of 1 hour. The diagram is now complete. The distance flown in 1 hour, ground speed, is measured as the number of units on the true course line, 88 nautical miles per hour, or 88 knots. The true heading necessary to offset drift is indicated by the direction of the airspeed line, which can be determined in one of two ways. By placing the straight side of the protractor along the north-south line with its center point at the intersection of the airspeed line and the north-south line. Read the true heading directly in degrees, 76 degrees, figure 15 TAC 22. By placing the straight side of the protractor along the true course line with its center at P, read the angle between the true course and the airspeed line. This is the wind correction angle, which must be applied to the true course to obtain the true heading. If the wind blows from the right of the true course, the angle is added. If from the left, it is subtracted. In the example given, the wind correction angle is 14 degrees, and the wind is from the left. Therefore, subtract 14 degrees from the true course of 90 degrees, making the true heading 76 degrees. Figure 15 TAC 23. After obtaining the true heading, apply the correction for magnetic variation to obtain magnetic heading, and the correction for compass deviation to obtain a compass heading. The compass heading can be used to fly to the destination by dead reckoning. To determine the time and fuel required for the flight, first find the distance to destination by measuring the length of the course line drawn on the aeronautical chart using the appropriate scale at the bottom of the chart. If the distance measures 220 nautical miles, divide the ground speed of 88 knots, which gives 2.5 hours, or 2 hours and 30 minutes, as the time required. If fuel consumption is 8 gallons an hour, 8 times 2.5, or about 20 gallons is used. Briefly summarized, the steps in obtaining flight information are as follows. TC, direction of the line connecting two desired points, drawn on the chart and measured clockwise in degrees from true north on the mid-meridian. WCA, determined from the wind triangle, added to TC if the wind is from the right, subtracted if the wind is from the left. TH, direction measured in degrees clockwise from true north, in which the nose of the plane should point to make good the desired course. Variation, obtained from the isogonic line on the chart, added to TH if west, subtracted if east. MH, an intermediate step in the conversion, obtained by applying variation to true heading. Deviation, obtained from the deviation card on the aircraft, added to MH or subtracted from as indicated. Compass heading, reading on the compass found by applying deviation to MH, which is followed to make good the desired course. Total distance, obtained by measuring the length of the TC line on the chart, using the scale at the bottom of the chart. GS, obtained by measuring the length of the TC line on the wind triangle, using the scale employed for drawing the diagram. Estimated time en route, ETE, total distance divided by GS. Fuel rate, predetermined gallons per hour used at cruising speed. Note, additional fuel for adequate reserve should be added as a safety measure. End of Part 3 of Chapter 15.
Part 4 of Chapter 15, Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michael Early, Brisbane, Australia. Pilot's Handbook of Aeronautical Knowledge, Part 4 of Chapter 15 by the FAA. Flight Planning. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 states, in part, that before beginning a flight, the pilot in command, PIC, of an aircraft shall become familiar with all available information concerning that flight. For flights not in the vicinity of an airport, this must include information on available current weather reports and forecasts, fuel requirements, alternatives available if the planned flight cannot be completed, and any known traffic delays of which the pilot in command has been advised by ATC. Assembling necessary material. The pilot should collect the necessary material well before the flight. An appropriate current sectional chart and charts for areas adjoining the flight route should be among this material if the route of flight is near the border of a chart. Additional equipment should include a flight computer or electronic calculator, plotter, and any other item appropriate to the particular flight. For example, if a night flight is to be undertaken, carry a flashlight. If a flight is over desert country, carry a supply of water and other necessities. Weather check. It is wise to check the weather before continuing with other aspects of flight planning to see, first of all, if the flight is feasible, and, if it is, which route is best. Chapter 12, Aviation Weather Services, discusses obtaining a weather briefing. Use of Airport or Facility Directory, AFD. Study available information about each airport at which a landing is intended. This should include a study of the notices to airmen, NOTAMs, and the AFD, Figure 15-24. This includes location, elevation, runway and lighting facilities, available services, availability of Aeronautical Advisory Station Frequency, UNICOM, types of fuel available, used to decide on refueling stops, AFSS, FSS, located on the airport, control tower, and ground control frequencies, traffic information, remarks, and other pertinent information. The NOTAMs, issued every 28 days, should be checked for additional information on hazardous condition or changes that have been made since issuance of the AFD. The sectional chart bulletin subsection should be checked for major changes that have occurred since the last publication date of each sectional chart being used. Remember, the chart may be up to 6 months old. The effective date of the chart appears at the top of the front of the chart. The AFD generally has the latest information pertaining to such matters and should be used in preference to the information on the back of the chart if there are differences. Airplane Flight Manual or Pilot's Operating Handbook, AFM-POH. The Aircraft Flight Manual or Pilot's Operating Handbook, AFM-POH, should be checked to determine the proper loading of the aircraft, weight and balance data. The weight of the usable fuel and drainable oil aboard must be known. Also, check the weight of the passengers, the weight of all baggage to be carried, and the empty weight of the aircraft, to be sure that the total weight does not exceed the maximum allowable. The distribution of the load must be known to tell if the resulting center of gravity, CG, is within limits. Be sure to use the latest weight and balance information in the FAA-approved AFM or other permanent aircraft records, as appropriate, to obtain empty weight and empty weight CG information. Determine the takeoff and landing distances from the appropriate charts based on the calculated load, elevation of the airport, and temperature. Then compare these distances with the amount of runway available. Remember The heavier the load and higher the elevation, temperature, or humidity, the longer the takeoff roll and landing roll, and the lower the rate of climb. Check the fuel consumption charts to determine the rate of fuel consumption at the estimated flight altitude and power settings. Calculate the rate of fuel consumption, and then compare it with the estimated time for the flight so that refueling points along the route can be included in the plan. Charting the course. Once the weather has been checked and some preliminary planning done, it is time to chart the course and determine the data needed to accomplish the flight. The following sections provide a logical sequence to follow in charting the course, filling out a flight log, and filing a flight plan. In the following example, a trip is planned based on the following data and the sectional chart excerpt in Figure 15-25. Route of flight: Chickasha Airport, direct to Guthrie Airport. True airspeed, TAS, 115 knots. Winds aloft, 360 degrees at 10 knots. Usable fuel, 38 gallons. Fuel rate, 8 gallons per hour. Deviation, +2 degrees. Steps in charting the course. The following is a suggested sequence for arriving at the pertinent information for the trip. As information is determined, it may be noted as illustrated in the example of a flight log in Figure 15-26. Errata. Figure 15-26, Pilot's Planning Sheet. Change the column label above 7 degrees east from WCA R plus L minus to mag var W plus E minus. Errata. Figure 15-26. Show an additional column labeled altitude on both the pilot's planning sheet and the visual flight log. Where calculations are required, the pilot may use a mathematical formula or a manual or electronic flight computer. If unfamiliar with the use of a manual or electronic computer, it would be advantageous to read the operation manual and work several practice problems at this point. First, draw a line from Chickasha Airport, point A, directly to Guthrie Airport, point F. The course line should begin at the center of the airport of departure and end at the center of the destination airport. If the route is direct, the course line consists of a single straight line. If the route is not direct, it consists of two or more straight line segments. For example, a VOR station which is off the direct route, but which makes navigating easier, may be chosen. Radio navigation is discussed later in this chapter. Appropriate checkpoints should be selected along the route and noted in some way. These should be easy to locate points such as large towns, large lakes and rivers, or combinations of recognizable points such as towns with an airport, towns with a network of highways, and railroads entering and departing. Normally, choose only towns indicated by splashes of yellow on the chart. Do not choose towns represented by a small circle. These may turn out to be only a half dozen houses. In isolated areas, however, towns represented by a small circle can be prominent checkpoints. For this trip, 4 checkpoints have been selected. Checkpoint 1 consists of a tower located east of the course and can be further identified by the highway and railroad track, which almost parallels the course at this point. Checkpoint 2 is the obstruction just to the west of the course and can be further identified by Will Rogers World Airport, which is directly to the east. Checkpoint 3 is Wiley Post Airport, which the aircraft should fly directly over. Checkpoint 4 is a private, non-surfaced airport to the west of the course and can be further identified by the railroad track and highway to the east of the course. The course and areas on either side of the planned route should be checked to determine if there is any type of airspace with which the pilot should be concerned or which has special operational requirements. For this trip, it should be noted that the course passes through a segment of the Class C airspace surrounding Will Rogers World Airport, where the floor of the airspace is 2,500 feet mean sea level, MSL, and the ceiling is 5,300 feet, MSL, point B. Also, there is Class D airspace from the surface to 3,800 feet MSL surrounding Wiley Post Airport, point C, during the time the control tower is in operation. Study the terrain and obstructions along the route. This is necessary to determine the highest and lowest elevations, as well as the highest obstruction to be encountered, so that an appropriate altitude which conforms to 14 CFR Part 91 regulations can be selected. If the flight is to be flown at an altitude more than 3,000 feet above the terrain, conformance to the cruising altitude appropriate to the direction of flight is required. Check the route for particularly rugged terrain so it can be avoided. Areas where a takeoff or landing is made should be carefully checked for tall obstructions. Television transmitting towers may extend to altitudes over 1,500 feet above the surrounding terrain. It is essential that pilots be aware of their presence and location. For this trip, it should be noted that the tallest obstruction is part of a series of antennas with a height of 2,749 feet MSL, point D. The highest elevation should be located in the northeast quadrant and is 2,900 feet MSL, point E. Since the wind is no factor, and it is desirable and within the aircraft's capability to fly above the Class C and D airspace to be encountered, an altitude of 5,500 feet MSL is chosen. This altitude also gives adequate clearance of all obstructions, as well as conforms to the 14 CFR Part 91 requirement to fly at an altitude of odd 1,000 plus 500 feet when on a magnetic course between 0 and 179 degrees. Next, the pilot should measure the total distance of the course as well as the distance between checkpoints. The total distance is 53 nautical miles, and the distance between checkpoints is as noted on the flight log in Figure 15-26. After determining the distance, the true course should be measured. If using a plotter, follow the directions on the plotter. The true course is 031 degrees. Once the true heading is established, the pilot can determine the compass heading. This is done by the following formula given earlier in this chapter. The formula is TC plus or minus WCA equals TH plus or minus V equals MH plus or minus D equals CH. The WCA can be determined by using a manual or electronic flight computer. Using a wind of 360 degrees at 10 knots, it is determined that the WCA is 3 degrees left. This is subtracted from the TC, making the TH 28 degrees. Next, the pilot should locate the isogonic line closest to the route of the flight to determine variation. Figure 15-25 shows the variation to be 6.30 degrees east, rounded to 7 degrees east, which means it should be subtracted from the TH, giving an MH of 21 degrees. Next, add 2 degrees to the MH for the deviation correction. This gives the pilot the compass heading, which is 23 degrees. Now, the GS can be determined. This is done using a manual or electronic calculator. The GS is determined to be 106 knots. Based on this information, the total trip time, as well as time between checkpoints, and the fuel burned can be determined. These calculations can be done mathematically or by using a manual or electronic calculator. For this trip, the GS is 106 knots and the total time is 35 minutes. 30 minutes plus 5 minutes for climb, with a fuel burn of 4.7 gallons. Refer to the flight log in Figure 15-26 for the time between checkpoints. As the trip progresses, the pilot can note headings and time and make adjustments in headings, GS, and time. Filing a VFR flight plan. Filing a flight plan is not required by regulations. However, It is a good operating practice since the information contained in the flight plan can be used in search and rescue in the event of an emergency. Flight plans can be filed in the air by radio, but it is best to file a flight plan by phone just before departing. After takeoff, contact the AFSS by radio and give them the takeoff time so the flight plan can be activated. When a VFR flight plan is filed, it is held by the AFSS until 1 hour after the proposed departure time, and then cancelled unless the actual departure time is received, a revised proposed departure time is received, or at the time of filing the AFSS is informed that the proposed departure time is met, but actual time cannot be given because of inadequate communication. The FSS specialist who accepts the flight plan does not inform the pilot of this procedure, however. Figure 15-27 shows the flight plan form a pilot files with the AFSS. When filing a flight plan by telephone or radio, give the information in the order of the numbered spaces. This enables the AFSS specialist to copy the information more efficiently. Most of the fields are either self-explanatory or non-applicable to the VFR flight plan, such as item 13. However, some fields may need explanation. Item 3 is the aircraft type and special equipment. An example would be C-150X, which means the aircraft has no transponder. A listing of special equipment codes is found in the Aeronautical Information Manual, AIM. Item 6 is the proposed departure time in UTC, indicated by the Z. Item 7 is the cruising altitude. Normally, VFR can be entered in this block, since the pilot chooses a cruising altitude to conform to FAA regulations. Item 8 is the route of flight. If the flight is to be direct, enter the word direct. If not, enter the actual route to be followed, such as via certain towns or navigation aids. Item 10 is the estimated time en route. In the sample flight plan, 5 minutes was added to the total time to allow for the climb. Item 12 is the fuel on board in hours and minutes. This is determined by dividing the total usable fuel aboard in gallons by the estimated rate of fuel consumption in gallons. Remember, there is every advantage in filing a flight plan, but do not forget to close the flight plan on arrival. Do this by telephone to avoid radio congestion. End of Part 4 of Chapter 15. Recording by Michael Early, Brisbane, Australia.
Part 5 of Chapter 15 of the Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Nathan Heck. The Pilot's Handbook of Aeronautical Knowledge by the FAA. Radio navigation. Advances in navigational radio receivers installed in aircraft, the development of aeronautical charts which show the exact location of ground transmitting stations and their frequencies, along with refined flight deck instrumentation, make it possible for pilots to navigate with precision to almost any point desired. Although precision in navigation is obtainable through the proper use of this equipment, beginning pilots should use this equipment to supplement navigation by visual reference to the ground, pilotage. This method provides the pilot with an effective safeguard against disorientation in the event of a radio malfunction. There are 4 radio navigation systems available for use in VFR navigation. These are VHF Omnidirectional Range, VOR, Non-Directional Radio Beacon, NDB, Long Range Navigation, LORAN-C, Global Positioning System, GPS, Very High Frequency, VHF, Omnidirectional Range, VOR. The VOR system is present in 3 slightly different navigation aids, NavAids, VOR, VOR-DME, and VORTAC. By itself it is known as a VOR, and it provides magnetic bearing information to and from the station. When DME is also installed with a VOR, the NavAid is referred to as a VOR-DME. When military tactical air navigation, TACAN, equipment is installed with a VOR, the nav aid is known as a VORTAC. DME is always an integral part of the VORTAC. Regardless of the type of nav aid utilized, VOR, VOR-DME, or VORTAC, the VOR indicator behaves the same. Unless otherwise noted in this section, VOR, VOR-DME, and VORTAC nav aids are all referred to hereafter as VORs. The prefix omni means all, and an omnidirectional range is a VHF radio transmitting ground station that projects straight-line courses, radials, from the station in all directions. From a top view, it can be visualized as being similar to the spokes from the hub of a wheel. The distance VOR radials are projected depends upon the power output of the transmitter. The course or radials projected from the station are referenced to magnetic north. Therefore, a radial is defined as a line of magnetic bearing extending outward from the VOR station. Radials are identified by numbers beginning with 001, which is 1 degree east of magnetic north, and progress in sequence through all the degrees of a circle until reaching 360. To aid in orientation, a compass rose reference to magnetic north is superimposed on aeronautical charts at the station location. VOR ground stations transmit within a VHF frequency band of 108.0 to 117.95 MHz. Because the equipment is VHF, the signals transmitted are subject to line-of-sight restrictions. Therefore, its range varies in direct proportion to the altitude of receiving equipment. Generally, the reception range of the signals at an altitude of 1,000 feet above ground level, AGL, is about 40 to 45 miles. This distance increases with altitude. See Figure 1528. VORs and VORTACs are classed according to operational use. There are 3 classes: T, terminal; L, low altitude; H, high altitude. The normal useful range for the various classes is shown in the following table. VOR, VORTAC nav aids. Normal usable altitudes and radius distances. Class, terminal. Altitudes, 12,000 feet and below. Distance in miles, 25. Class, low altitude. Altitude, below 18,000 feet. Distance in miles, 40. Class, high altitude. Altitudes, below 14,500 feet. Distance in miles, 40. Class, high altitude. Altitudes, within the conterminous 48 states only, between 14,500 feet and 17,999 feet. Distance in miles, 100. Class, high altitude. Altitudes, 18,000 feet, flight level 450. Distance in miles, 130. Class, high altitude. Altitudes, 60,000 feet, flight level 450. Distance in miles, 100. The useful range of certain facilities may be less than 50 miles. For further information concerning these restrictions, refer to the Communication Nav Aid remarks in the AFD. The accuracy of course alignment of VOR radials is considered to be excellent. It is generally within plus or minus 1 degree. However, certain parts of the VOR receiver equipment deteriorate, and this affects its accuracy. It is particularly true at great distances from the VOR station. The best assurance of maintaining an accurate VOR receiver is periodic checks and calibrations. VOR accuracy checks are not a regulatory requirement for VFR flight. However, to assure accuracy of the equipment, these checks should be accomplished quite frequently and a complete calibration each year. The following means are provided for pilots to check VOR accuracy. FAA VOR Test Facility, VOT, Certified Airborne Checkpoints, Certified Ground Checkpoints located on airport surfaces. If an aircraft has 2 VOR receivers installed, a dual VOR receiver check can be made. To accomplish the dual receiver check, a pilot tunes both VOR receivers to the same VOR ground facility. The maximum permissible variation between the two indicated bearings is 4 degrees. A list of the airborne and ground checkpoints is published in the AFD. Basically, these checks consist of verifying that the VOR radials the aircraft equipment receives are aligned with the radials the station transmits. There are not specific tolerances in VOR checks required for VFR flight, but as a guide to assure acceptable accuracy, the required IFR tolerances can be used, plus or minus 4 degrees for ground checks and plus or minus 6 degrees for airborne checks. These checks can be performed by the pilot. The VOR transmitting station can be positively identified by its Morse code identification or by a recorded voice identification which states the name of the station followed by a VOR. Many FSS transmit voice messages on the same frequency that the VOR operates. Voice transmissions should not be relied upon to identify stations because many FSS remotely transmit over several omni ranges which have names different from that of the transmitting FSS. If the VOR is out of service for maintenance, the coded identification is removed and not transmitted. This serves to alert pilots that this station should not be used for navigation. VOR receivers are designed with an alarm flag to indicate when signal strength is inadequate to operate this navigational equipment. This happens if the aircraft is too far from the VOR, or the aircraft is too low and therefore is out of the line of sight of the transmitting signals. Using the VOR. In review, for VOR radio navigation, there are 2 components required: ground transmitter and aircraft receiving equipment. The ground transmitter is located at a specific position on the ground and transmits on an assigned frequency. The aircraft equipment includes a receiver with a tuning device and a VOR or omni-navigation instrument. The navigation instrument could be a course deviation indicator, CDI, horizontal situation indicator, HSI, or a radiomagnetic indicator, RMI. Each of these instruments indicates the course to the tuned VOR. Course deviation indicator, CDI. The CDI is found in most training aircraft. It consists of 1. An omni-bearing selector, OBS, sometimes referred to as the course selector, 2. A CDI needle, left-right needle, and 3. A to-from indicator. The course selector is an azimuth dial that can be rotated to select a desired radial or to determine the radial over which the aircraft is flying. In addition, the magnetic course to or from the station can be determined. When the course selector is rotated, it moves the CDI or needle to indicate the position of the radial relative to the aircraft. If the course selector is rotated until the deviation needle is centered, the radial, magnetic course from the station, or its reciprocal, magnetic course to the station, can be determined. The course deviation needle also moves to the right or left if the aircraft is flown or drifting away from the radial which is set in the course selector. By centering the needle, the course selector indicates either the course from the station or the course to the station. If the flag displays a to, the course shown on the course selector must be flown to the station. See Figure 1529. If from is displayed and the course shown is followed, the aircraft is flown away from the station. Horizontal situation indicator. The HSI is a direction indicator that uses the output from a flux valve to drive the compass card. The HSI, see Figure 1530, combines the magnetic compass with navigation signals and a glide slope. The HSI gives the pilot an indication of the location of the aircraft with relationship to the chosen course or radial. In Figure 1530, the aircraft's magnetic heading displayed on the compass card under the lubber line is 184 degrees. The course select pointer shown is set to 295 degrees. The tail of the pointer indicates the reciprocal, 115 degrees. The course deviation bar operates with the VOR localizer, VOR LOC, or GPS navigation receiver to indicate left or right deviations from the course selected with the course select pointer. Operating in the same manner, the angular movement of a conventional VOR LOC needle indicates deviation from course. The desired course is selected by rotating the course select pointer in relation to the compass card by means of course select knob. The HSI has a fixed aircraft symbol, and the course deviation bar displays the aircraft's position relative to the selected course. The to from indicator is a triangular pointer. When the indicator points to the head of the course select pointer, the arrow shows the course selected. If properly intercepted and flown, the course will take the aircraft to the chosen facility. When the indicator points to the tail of the course, the arrow shows that the course selected, if properly intercepted and flown, will take the aircraft directly away from the chosen facility. When the nav warning flag appears, it indicates no reliable signal is being received. The appearance of the HDG flag indicates the compass card is not functioning properly. The glide slope pointer indicates the relation of the aircraft to the glide slope. When the pointer is below the center position, the aircraft is above the glide slope, and an increased rate of descent is required. In some installations, the azimuth card is a remote indicating compass. However, in others, the heading must be checked occasionally against the magnetic compass and reset. Radio Magnetic Indicator, RMI. The RMI, figure 1531, is a navigational aid providing aircraft magnetic or directional gyro heading and very high frequency omnidirectional range, VOR, GPS, and automatic direction finder, ADF, bearing information. Remote indicating compasses were developed to compensate for errors in and limitations of older types of heading indicators. The remote compass transmitter is a separate unit usually mounted in a wingtip to eliminate the possibility of magnetic interference. The RMI consists of a compass card, a heading index, 2 bearing pointers, and pointer function switches. The 2 pointers are driven by any 2 combinations of a GPS, an ADF, and/or a VOR. The pilot has the ability to select the navigation aid to be indicated. The pointer indicates course to selected nav aid or waypoint. In figure 1531, the green pointer is indicating the station tuned on the ADF. The yellow pointer is indicating the course to a VOR of GPS waypoint. Note that there is no requirement for a pilot to select course with the RMI, but only the nav aid is to be indicated. Tracking with VOR. The following describes a step-by-step procedure to use when tracking to and from VOR station using a CDI. Figure 1532 and errata illustrates the procedure. First, tune the VOR receiver to the frequency of the selected VOR station. For example, 115.0 to receive Bravo VOR. Next, check the identifiers to verify that the desired VOR is being received. As soon as the VOR is properly tuned, the course deviation needle deflects either left or right. Then, rotate the azimuth dial to the course selector until the course deviation needle centers and the to from indicator indicates to. If the needle centers with a from indication, the azimuth should be rotated 180 degrees because in this case it is desired to fly to the station. Now, turn the aircraft to the heading indicated on the VOR azimuth dial or course selector 350 degrees in this example. If a heading of 350 is maintained with the wind from the right as shown, the aircraft drifts to the left of the intended track. As the aircraft drifts off course, the VOR course deviation needle gradually moves to the right of the center or indicates the direction of the desired radial or track. To return to the desired radial, the aircraft heading must be altered to the right. As the aircraft returns to the desired track, the deviation needle slowly returns to center. When centered, the aircraft is on the desired radial and a left turn must be made toward, but not to the original heading of 350, because a wind drift correction must be established. The amount of correction depends upon the strength of the wind. If the wind velocity is unknown, a trial and error method can be used to find the correct heading. Assume, for example, a 10-degree correction for a heading of 360 is maintained. While maintaining a heading of 360, assume that the course deviation begins to move to the left. This means that the wind correction of 10 degrees is too great and the aircraft is flying to the right of the course. A slight turn to the left should be made to permit the aircraft to return to the desired radial. When the deviation needle centers, a small wind drift correction of 5 degrees or a heading correction of 355 degrees should be flown. If this correction is adequate, the aircraft remains on the radial. If not, small variations in heading should be made to keep the needle centered, and consequently keep the aircraft on the radial. As the VOR station is passed, the course deviation needle fluctuates, then settles down, and the to indication changes to from. If the aircraft passes to one side of the station, the needle deflects in the direction of the station as the indicator changes to from. Generally, the same techniques apply when tracking outbound as those used for tracking inbound. If the intent is to fly over the station and track outbound on the reciprocal of the inbound radial, the course selector should not be changed. Corrections are made in the same manner to keep the needle centered. The only difference is that the omnidirectional range indicator indicates from. If tracking outbound on a course other than the reciprocal of the inbound radial, this new course or radial must be set in the course selector and a turn made to intercept this course. After this course is reached, tracking procedures are the same as previously discussed. Tips on using the VOR. Positively identify the station by its code or voice identification. Keep in mind that VOR signals are line of sight. A weak signal or no signal at all is received if the aircraft is too low or too far from the station. When navigating to a station, determine the inbound radial and use this radial. Fly a heading that will maintain the course. If the aircraft drifts, fly a heading to re-intercept the course, then apply a correction to compensate for wind drift. If minor needle fluctuations occur, avoid changing headings immediately. Wait momentarily to see if the needle recenters. If it does not, then correct. When flying to a station, always fly the selected course with a to indication. When flying from a station, always fly the selected course with a from indication. If this is not done, the action of the course deviation needle is reversed. To further explain this reverse action, if the aircraft is flown toward a station with a from indication, or away from a station with a to indication, the course deviation needle indicates in a direction opposite to that which it should indicate. For example, if the aircraft drifts to the right of the radial being flown, the needle moves to the right or points away from the radial. If the aircraft drifts to the left of the radial being flown, the needle moves left or in the direction opposite to the radial. When navigating using the VOR, it is important to fly headings that maintain or re-intercept the course. Just turning toward the needle will cause overshooting the radial and flying an S-turn to the left and right of the course. End of Part 5 of Chapter 15. Recording by Nathan Heck.
Part 6 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 15, Part 6. Time and distance check from a station. To compute time and distance from a station, first turn the aircraft to place the bearing pointer on the nearest 90-degree index. Note time and maintain heading. When the bearing pointer has moved 10 degrees, note the elapsed time in seconds and apply the formulas in the following example to determine time and distance. See Figure 15-33. The time from station may also be calculated by using a short method based on the above formula, if a 10-degree bearing change is flown. If the elapsed time for the bearing change is noted in seconds, and a 10-degree bearing change is made, the time from the station in minutes is determined by counting off 1 decimal point. Thus, if 75 seconds are required to fly a 10-degree bearing change, the aircraft is 7.5 minutes from the station. When the bearing pointer is moving rapidly, or when several corrections are required to place the pointer on the wingtip position, the aircraft is at the station passage. The distance from the station is computed by multiplying TAS or GS in miles per minute by the previously determined time in minutes. For example, if the aircraft is 7.5 minutes from station, flying at a TAS of 120 knots or 2 nm per minute, the distance from station is 15 nm. 7.5 times 2 equals 15. The preceding are methods of computing approximate time and distance. The accuracy of time and distance checks is governed by existing wind, degree of bearing change, and accuracy of timing. The number of variables involved causes the result to be only an approximation. However, by flying an accurate heading and checking the time and bearing closely, the pilot can make a reasonable estimate of time and distance from the station. Course intercept. Course interceptions are performed in most phases of instrument navigation. The equipment used varies, but an intercept heading must be flown that results in an angle or rate of intercept sufficient to solve a particular problem. Rate of intercept. Rate of intercept, seen by the aviator as bearing pointer or HSI movement, is a result of the following factors: the angle at which the aircraft is flown toward a desired course, angle of intercept, true airspeed and wind, GS, distance from the station, angle of intercept. The angle of intercept is the angle between the heading of the aircraft, intercept heading, and desired course. Controlling this angle by selection/adjustment of the intercept heading is the easiest and most effective way to control course interceptions. Angle of intercept must be greater than the degrees from course, but should not exceed 90 degrees. Within this limit, adjust to achieve the most desirable rate of intercept. When selecting an intercept heading, the key factor is the relationship between distance from the station and degrees from the course. Each degree, or radial, is 1 nm wide at a distance of 60 nm from the station. Width increases or decreases in proportion to the 60 nm distance. For example, 1 degree is 2 nm wide at 120 nm, and 1/2 nm wide at 30 nm. For a given GS and angle of intercept, the resultant rate of intercept varies according to the distance from the station. When selecting an intercept heading to form an angle of intercept, consider the following factors: degrees from course, distance from the station, true airspeed and wind, GS. Distance measuring equipment, DME. Distance measuring equipment, DME, consists of an ultra-high frequency, UHF, navigational aid with VOR/DMEs and VOR-TACs. It measures, in nm, the slant range distance of an aircraft from a VOR/DME or VOR-TAC, both hereafter referred to as a VOR-TAC. Although DME equipment is very popular, not all aircraft are DME equipped. To utilize DME, the pilot should select, tune, and identify a VOR-TAC, as previously described. The DME receiver, utilizing what is called a paired frequency concept, automatically selects and tunes the UHF DME frequency associated with the VHF VOR TAC frequency selected by the pilot. This process is entirely transparent to the pilot. After a brief pause, the DME display shows the slant range distance to or from the VOR TAC. Slant range distance is the direct distance between the aircraft and the VOR TAC, and is therefore affected by aircraft altitude. Station passage directly over a VOR TAC from an altitude of 6,076 feet above ground level, AGL, would show approximately 1.0 nm on the DME. DME is a very useful adjunct to VOR navigation. A VOR radial alone merely gives line of position information. With DME, a pilot may precisely locate the aircraft on that line, radial. Most DME receivers also provide GS and time-to-station modes of operation. The GS is displayed in knots, NMPH. The time-to-station mode displays the minutes remaining to VOR TAC station passage, predicated upon the present GS. GS and time-to-station information is only accurate when tracking directly to or from a VOR TAC. DME receivers typically need a minute or two of stabilized flight directly to or from a VOR TAC before displaying accurate GS or time-to-station information. Some DME installations have a hold feature that permits a DME signal to be retained from one VOR TAC, while the course indicator displays course deviation information from an ILS or another VOR TAC. VOR/DME RNAV. Area Navigation RNAV permits electronic course guidance on any direct route between points established by the pilot. While RNAV is a generic term that applies to a variety of navigational aids, such as LORAN-C, GPS, and others, this section deals with VOR/DME based RNAV. VOR/DME RNAV is not a separate ground-based NAV-AID, but a method of navigation using VOR/DME and VOR-TAC signals specially processed by the aircraft's RNAV computer. See Figure 15-34. Note: in this section, the term VOR-TAC also includes VOR/DME NAV-AIDs. In its simplest form, VOR/DME RNAV allows the pilot to electronically move VOR TACs around to more convenient locations. Once electronically located, they are referred to as waypoints. These waypoints are described as a combination of a selected radial and distance within the service volume of the VOR TAC to be used. These waypoints allow a straight course to be flown between almost any origin and destination, without regard to the orientation of VOR TACs, or the existence of airways. While the capabilities and methods of operation of VOR/DME RNAV units differ, They are basic principles of operation that are common to all. Pilots are urged to study the manufacturer's operating guide and receive instruction prior to the use of VOR/DME, RNAV, or any unfamiliar navigational system. Operation information and limitations should also be sought from placards and the supplement section of the AFM/POH. VOR/DME based RNAV units operate in at least 3 modes: VOR, en route, and approach. A 4th mode, VOR parallel, may also be found on some models. The units need both VOR and DME signals to operate in any RNAV mode. If the NAV AID selected is a VOR without DME, RNAV mode will not function. In the VOR or non-RNAV mode, the unit simply functions as a VOR receiver with DME capability. See Figure 15-35. The unit's display on the VOR indicator is conventional in all respects. For operation on established airways or any other ordinary VOR navigation, the VOR mode is used. To utilize the unit's RNAV capability, the pilot selects and establishes a waypoint or a series of waypoints to define a course. To operate in any RNAV mode, the unit needs both radial and distance signals. Therefore, a VOR TAC or VOR/DME needs to be selected as a NAV AID. To establish a waypoint, a point somewhere within the service range of a VOR TAC is defined on the basis of radial and distance. Once the waypoint is entered into the unit and the RNAV en route mode is selected, the CDI displays course guidance to the waypoint, not the original VOR TAC. DME also displays distance to the waypoint. Many units have the capability to store several waypoints, allowing them to be programmed prior to flight, if desired, and called up in flight. RNAV waypoints are entered into the unit in magnetic bearings, radials of degrees and tenths. For example, 275.5 degrees, and distances in nm and tenths. For example, 25.2 nm. When plotting RNAV waypoints on an aeronautical chart, pilots find it difficult to measure to that level of accuracy, and in practical application, it is rarely necessary. A number of flight planning publications publish airport coordinates and waypoints with this precision, and the unit accepts those figures. There is a subtle but important difference in CDI operation and display in the RNAV modes. In the RNAV modes, course deviation is displayed in terms of linear deviation. In the RNAV en route mode, maximum deflection of the CDI typically represents 5 nm on either side of the selected course, without regard to distance from the waypoint. In the RNAV approach mode, maximum deflection of the CDI typically represents 1 1/4 nm on either side of the selected course. There is no increase in CDI sensitivity as the aircraft approaches a waypoint in RNAV mode. The RNAV approach mode is used for instrument approaches. Its narrow scale width, 1/4 of the en route mode, permits very precise tracking to or from the selected waypoint. In visual flight rules, VFR, cross-country navigation, tracking a course in the approach mode is not desirable because it requires a great deal of attention and soon becomes tedious. A fourth, lesser used mode on some units is the VOR parallel mode. This permits the CDI to display linear, not angular, deviation as the aircraft tracks to and from VOR TACs. It derives its name from permitting the pilot to offset or parallel a selected course or airway at a fixed distance of the pilot's choosing, if desired. The VOR parallel mode has the same effect as placing a waypoint directly over an existing VOR TAC. Some pilots select the VOR parallel mode when utilizing the navigation, NAV, tracking function of their autopilot for smoother course following near the VOR TAC. Confusion is possible when navigating an aircraft with VOR/DME based RNAV, and it is essential that the pilot become familiar with the equipment installed. It is not unknown for pilots to operate inadvertently in one of the RNAV modes when the operation was not intended by overlooking switch positions or annunciators. The reverse has also occurred with the pilot neglecting to place the unit into one of the RNAV modes by overlooking switch positions or annunciators. As always, the prudent pilot is not only familiar with the equipment used, but never places complete reliance in just one method of navigation when others are available for cross-check. Automatic Direction Finder, ADF. Many general aviation type aircraft are equipped with ADF radio receiving equipment. To navigate using the ADF, the pilot tunes the receiving equipment to a ground station known as a non-directional radio beacon, NDB. The NDB stations normally operate in a low or medium frequency band of 200 to 415 kHz. The frequencies are readily available on aeronautical charts or in the A/FD. All radio beacons except compass locators transmit a continuous 3-letter identification in code, except during voice transmissions. A compass locator, which is associated with an instrument landing system, transmits a 2-letter identification. Standard broadcast stations can also be used in conjunction with ADF. Positive identification of all radio stations is extremely important, and this is particularly true when using standard broadcast stations for navigation. NDBs have one advantage over the VOR. This advantage is that low or medium frequencies are not affected by line of sight. The signals follow the curvatures of the Earth. Therefore, if the aircraft is within the range of the station, the signals can be received regardless of altitude. The following table gives the class of NDB stations, their power, and usable range. Non-directional radio beacon, NDB. Usable radius distances for all altitudes. Class, power in watts, distance in miles. Compass locator. Under 25, 15. MH. Under 50, 25. H. 50 to 1999, 50. HH. 2000 or more, 75. Service range of individual facilities may be less than 50 miles. One of the disadvantages that should be considered when using low-frequency, LF for navigation, is that low-frequency signals are very susceptible to electrical disturbances, such as lightning. These disturbances create excessive static, needle deviations, and signal fades. There may be interference from distant stations. Pilots should know the conditions under which these disturbances can occur, so that they can be more alert to possible interference when using the ADF. Basically, the ADF aircraft equipment consists of a tuner, which is used to set the desired station frequency, and the navigational display. The navigational display consists of a dial upon which the azimuth is printed, and a needle which rotates around the dial and points to the station to which the receiver is tuned. Some of the ADF dials can be rotated to align the azimuth with the aircraft heading. Others are fixed with the 0 degrees representing the nose of the aircraft, and 180 degrees representing the tail. Only the fixed azimuth dial is discussed in this handbook. See Figure 15-36. Figure 15-37 illustrates terms that are used with the ADF and should be understood by the pilot. To determine the magnetic bearing from the station, 180 degrees is added to or subtracted from the magnetic bearing to the station. This is the reciprocal bearing and is used when plotting position fixes. Keep in mind that the needle of fixed azimuth points to the station in relation to the nose of the aircraft. If the needle is deflected 30 degrees to the left for a relative bearing of 330 degrees, this means that the station is located 30 degrees left. If the aircraft is turned left 30 degrees, the needle moves to the right 30 degrees and indicates a relative bearing of 0 degrees, or the aircraft is pointing toward the station. If the pilot continues flight toward the station, keeping the needle on 0 degrees, the procedure is called homing to the station. If a crosswind exists, the ADF needle continues to drift away from 0. To keep the needle on 0, the aircraft must be turned slightly, resulting in a curved flight path to the station. Homing to the station is a common procedure, but results in drifting downwind, thus lengthening the distance to the station. Tracking to the station requires correcting for wind drift and results in maintaining flight along a straight path or bearing to the station. When the wind drift correction is established, the ADF needle indicates the amount of correction to the right or left. For instance, if the magnetic bearing to the station is 340 degrees, a correction for a left crosswind would result in a magnetic heading of 330 degrees, and the ADF needle would indicate 10 degrees to the right, or a relative bearing of 010 degrees. See Figure 15-38. When tracking away from the station, wind corrections are made similar to tracking to the station, but the ADF needle points toward the tail of the aircraft or the 180-degree position on the azimuth dial. Attempting to keep the ADF needle on the 180-degree position during winds results in the aircraft flying a curved flight, leading further and further from the desired track. To correct for wind when tracking outbound, correction should be made in the direction opposite of that in which the needle is pointing. Although the ADF is not as popular as the VOR for radio navigation, with proper precautions and intelligent use, the ADF can be a valuable aid to navigation. End of Part 6 of Chapter 15. Part 7 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 15, Part 7. Global Positioning System. The GPS is a satellite-based radio navigation system. Its RNAV guidance is worldwide in scope. There are no symbols for GPS on aeronautical charts, as it is a space-based system with global coverage. Development of the system is underway so that GPS is capable of providing the primary means of electronic navigation. Portable and yoke-mounted units are proving to be very popular in addition to those permanently installed in the aircraft. Extensive navigation databases are common features in aircraft GPS receivers. The GPS is a satellite radio navigation and time dissemination system, developed and operated by the U.S. Department of Defense, DoD. Civilian interface and GPS system status is available from the U.S. Coast Guard. It is not necessary to understand the technical aspects of GPS operation to use it in VFR/Instrument Flight Rules, IFR, navigation. It does differ significantly from conventional ground-based electronic navigation, and awareness of those differences is important. Awareness of equipment approvals and limitations is critical to the safety of flight. The GPS navigation system broadcasts a signal that is used by receivers to determine precise position anywhere in the world. The receiver tracks multiple satellites and determines a pseudo-range measurement to determine the user location. A minimum of 4 satellites is necessary to establish an accurate 3-dimensional position. The Department of Defense, DoD, is responsible for operating the GPS satellite constellation and monitors the GPS satellites to ensure proper operation. The status of a GPS satellite is broadcast as part of the data message transmitted by the satellite. GPS status information is also available by means of the U.S. Coast Guard Navigation Information Service at 703-313-5907 or online at http://www.navcen.uscg.gov/. Additionally, satellite status is available through the Notice to Airmen (NOTAM) system. The GPS receiver verifies the integrity, usability of the signals received from the GPS constellation through Receiver Autonomous Integrity Monitoring, RAIM, to determine if a satellite is providing corrupted information. At least one satellite, in addition to those required for navigation, must be in view for the receiver to perform the RAIM function. Thus, RAIM needs a minimum of 5 satellites in view, or 4 satellites and a barometric altimeter, baro aiding, to detect an integrity anomaly. For receivers capable of doing so, RAIM needs 6 satellites in view, or 5 satellites with baro aiding, to isolate the corrupt satellite signal and remove it from the navigation solution. Baro aiding is a method of augmenting the GPS integrity solution by using a non-satellite input source. GPS-derived altitude should not be relied upon to determine aircraft altitude, since the vertical error can be quite large and no integrity is provided. To ensure that baro aiding is available, the current altimeter setting must be entered into the receiver as described in the operating manual. RAIM messages vary somewhat between receivers. However, generally there are 2 types. One type indicates that there are not enough satellites available to provide RAIM integrity monitoring, and another type indicates that the RAIM integrity monitor has detected a potential error that exceeds the limit for the current phase of flight. Without RAIM capability, the pilot has no assurance of the accuracy of the GPS position. Selective availability. Selective availability, SA, is a method by which the accuracy of GPS is intentionally degraded. This feature is designed to deny hostile use of precise GPS positioning data. SA was discontinued on May 1, 2000, but many GPS receivers are designed to assume that SA is still active. The GPS constellation of 24 satellites is designed so that a minimum of 5 satellites are always observable by a user anywhere on Earth. The receiver uses data from a minimum of 4 satellites above the mask angle, the lowest angle above the horizon at which a receiver can use a satellite. VFR use of GPS. GPS navigation has become a great asset to VFR pilots, providing increased navigation capability and enhanced situational awareness, while reducing operating costs due to greater ease in flying direct routes. While GPS has many benefits to the VFR pilot, care must be exercised to ensure that system capabilities are not exceeded. Types of receivers used for GPS navigation under VFR are varied, from a full IFR installation being used to support a VFR flight, to a VFR-only installation, in either a VFR or IFR capable aircraft, to a handheld receiver. The limitations of each type of receiver installation, or use, must be understood by the pilot to avoid misusing navigational information. In all cases, VFR pilots should never rely solely on one system of navigation. GPS navigation must be integrated with other forms of electronic navigation, as well as pilotage and dead reckoning. Only through the integration of these techniques can the VFR pilot ensure accuracy in navigation. Some critical concerns in VFR use of GPS include RAIM capability, database currency, and antenna location. RAIM capability. Many VFR GPS receivers and all handheld units have no RAIM alerting capability. Loss of the required number of satellites in view, or the detection of a position error, cannot be displayed to the pilot by such receivers. In receivers with no RAIM capability, no alert would be provided to the pilot that the navigation solution had deteriorated, and an undetected navigation error could occur. A systematic cross-check with other navigation techniques would identify this failure and prevent a serious deviation. In many receivers, an updatable database is used for navigation fixes, airports, and instrument procedures. These databases must be maintained to the current update for IFR operation, but no such requirement exists for VFR use. However, in many cases, the database drives a moving map display, which indicates special use airspace, and the various classes of airspace, in addition to other operational information. Without a current database, the moving map display may be outdated and offer erroneous information to VFR pilots wishing to fly around critical airspace areas, such as a restricted area or a Class B airspace segment. Numerous pilots have ventured into airspace they were trying to avoid by using an outdated database. If there is not a current database in the receiver, disregard the moving map display when making critical navigation decisions. In addition, waypoints are added, removed, relocated, or renamed as required to meet operational needs. When using GPS to navigate relative to a named fix, a current database must be used to properly locate a named waypoint. Without the update, it is the pilot's responsibility to verify the waypoint location referencing to an official current source, such as the A/FD, sectional chart, or en route chart. In many VFR installations of GPS receivers, antenna location is more a matter of convenience than performance. In IFR installations, care is exercised to ensure that an adequate clear view is provided for the antenna to see satellites. If an alternate location is used, some portion of the aircraft may block the view of the antenna, causing a greater opportunity to lose navigation signal. This is especially true in the case of handhelds. The use of handheld receivers for VFR operations is a growing trend, especially among rental pilots. Typically, suction cups are used to place the GPS antennas on the inside of aircraft windows. While this method has great utility, the antenna location is limited by aircraft structure for optimal reception of available satellites. Consequently, signal losses may occur in certain situations of aircraft satellite geometry, causing a loss of navigation signal. These losses, coupled with a lack of RAIM capability, could present erroneous position and navigation information with no warning to the pilot. While the use of a handheld GPS for VFR operations is not limited by regulation, modification of the aircraft, such as installing a panel or yoke-mounted holder, is governed by 14 CFR Part 43. Pilots should consult with a mechanic to ensure compliance with the regulation and a safe installation. Tips for using GPS for VFR operations. Always check to see if the unit has RAIM capability. If no RAIM capability exists, be suspicious of a GPS displayed position when any disagreement exists with the position derived from other radio navigation systems, pilotage, or dead reckoning. Check the currency of the database, if any. If expired, update the database using the current revision. If an update of an expired database is not possible, disregard any moving map display of airspace for critical navigation decisions. Be aware that named waypoints may no longer exist or may have been relocated since the database expired. At a minimum, the waypoints planned to be used should be checked against a current official source, such as the A/FD or a sectional aeronautical chart. While a handheld GPS receiver can provide excellent navigation capability to VFR pilots, be prepared for intermittent loss of navigation signal, possibly with no RAIM warning to the pilot. If mounting the receiver in the aircraft, be sure to comply with 14 CFR Part 43. Plan flights carefully before taking off. If navigating to user-defined waypoints, enter them before flight, not on the fly. Verify the planned flight against the current source, such as the current sectional chart. There have been cases in which one pilot used waypoints created by another pilot that were not where the pilot flying was expecting. This generally resulted in a navigation error. Minimize head-down time in the aircraft and keep a sharp lookout for traffic, terrain, and obstacles. Just a few minutes of preparation and planning on the ground makes a great difference in the air. Another way to minimize head-down time is to become very familiar with the receiver's operation. Most receivers are not intuitive. The pilot must take the time to learn the various keystrokes, knob functions, and displays that are used in the operation of the receiver. Some manufacturers provide computer-based tutorials or simulations of the receivers. Take the time to learn about the particular unit before using it in flight. In summary, be careful not to rely on GPS to solve all VFR navigational problems. Unless an IFR receiver is installed in accordance with IFR requirements, no standard of accuracy or integrity has been assured. While the practicality of GPS is compelling, the fact remains that only the pilot can navigate the aircraft, and GPS is one of the pilot's tools to do the job. VFR waypoints. VFR waypoints provide VFR pilots with a supplementary tool to assist with position awareness while navigating visually in aircraft equipped with area navigation receivers. VFR waypoints should be used as a tool to supplement current navigation procedures. The uses of VFR waypoints include providing navigational aids for pilots unfamiliar with an area, waypoint definition of existing reporting points, enhanced navigation in and around Class B and Class C airspace, and enhanced navigation around special use airspace. VFR pilots should rely on appropriate and current aeronautical charts, published specifically for visual navigation. If operating in a terminal area, pilots should take advantage of the terminal area chart available for the area, if published. The use of VFR waypoints does not relieve the pilot of any responsibility to comply with the operational requirements of 14 CFR Part 91. VFR waypoint names for computer entry and flight plans consists of 5 letters beginning with the letters VP and are retrievable from navigation databases. The VFR waypoint names are not intended to be pronounceable, and they are not for use in ATC communications. On VFR charts, a standalone VFR waypoint is portrayed using the same 4-point star symbol used for IFR waypoints. VFR waypoint co-located with a visual checkpoint on the chart is identified by a small magenta flag symbol. A VFR waypoint co-located with a visual checkpoint is pronounceable based on the name of the visual checkpoint and may be used for ACT communications. Each VFR waypoint name appears in parentheses adjacent to the geographic location on the chart. Latitude/longitude data for all established VFR waypoints may be found in the appropriate regional A/FD. When filing VFR flight plans, use the 5-letter identifier as a waypoint in the route of flight section if there is an intended course change at that point, or if used to describe the planned route of flight. This VFR filing would be similar to VOR use in the route of flight. Pilots must use the VFR waypoints only when operating under VFR conditions. Any VFR waypoints intended for use during a flight should be loaded into the receiver while on the ground and prior to departure. Once airborne, pilots should avoid programming routes or VFR waypoint chains into their receivers. Pilots should be especially vigilant for other traffic while operating near VFR waypoints. The same effort to see and avoid other aircraft near VFR waypoints is necessary, as is the case when operating near VORs and NDBs. In fact, the increased accuracy of navigation through the use of GPS demands even greater vigilance, as off-course deviations among different pilots and receivers is less. When operating near a VFR waypoint, use whatever ATC services are available, even if outside a class of airspace where communications are required. Regardless of the class of airspace, monitor the available ATC frequency closely for information on other aircraft operating in the vicinity. It is also a good idea to turn on landing lights when operating near a VFR waypoint to make the aircraft more conspicuous to other pilots, especially when visibility is reduced. Lost procedures. Getting lost in an aircraft is a potentially dangerous situation, especially when low on fuel. If a pilot becomes lost, there are some good common sense procedures to follow. If a town or city cannot be seen, the first thing to do is climb, being mindful of traffic and weather conditions. An increase in altitude increases radio and navigation reception range, and also increases radar coverage. If flying near a town or city, it might be possible to read the name of the town on a water tower. If the aircraft has a navigational radio, such as a VOR or ADF receiver, it can be possible to determine position by plotting an azimuth from 2 or more navigational facilities. If GPS is installed, or a pilot has a portable aviation GPS on board, it can be used to determine the position and the location of the nearest airport. Communicate with any available facility using frequencies shown on the sectional chart. If contact is made with the controller, Radar vectors may be offered. Other facilities may offer direct finding, DF assistance. To use this procedure, the controller requests the pilot to hold down the transmit button for a few seconds and then release it. The controller may ask the pilot to change directions a few times and repeat the transmit procedure. This gives the controller enough information to plot the aircraft position and then give vectors to a suitable landing site. If the situation becomes threatening, transmit the situation on the emergency frequency 121.5 MHz and set the transponder to 7,700. Most facilities, and even airliners, monitor the emergency frequency. Flight diversion. There probably comes a time when the pilot is not able to make it to the planned destination. This can be the result of unpredicted weather conditions, a system malfunction, or poor pre-flight planning. In any case, the pilot needs to be able to safely and efficiently divert to an alternate destination. Before any cross-country flight, check the charts for airports or suitable landing areas along or near the route of flight. Also check for navigational aids that can be used during a diversion. Computing course, time, speed, and distance information in flight requires the same computations used during pre-flight planning. However, because of the limited flight deck space, and because attention must be divided between flying the aircraft, making calculations, and scanning for other aircraft, take advantage of all possible shortcuts and rule-of-thumb computations. When in flight, it is rarely practical to actually plot a course on a sectional chart and mark checkpoints and distances. Furthermore, because an alternate airport is usually not very far from your original course, actual plotting is seldom necessary. A course to an alternate can be measured accurately with a protractor or plotter, but can be measured with reasonable accuracy using a straight edge and the compass rose depicted around VOR stations. This approximation can be made on the basis of a radial from a nearby VOR, or an airway that closely parallels the course to your alternate. However, remember that the magnetic heading associated with a VOR radial or printed airway is outbound from the station. To find the course to the station, it may be necessary to determine the reciprocal of that heading. It is typically easier to navigate to an alternate airport that has a VOR or NDB facility on the field. After selecting the most appropriate alternate, approximate the magnetic course to the alternate using a compass rose or airway on the sectional chart. If time permits, try to start the diversion over a prominent ground feature. However, in an emergency, divert promptly toward your alternate. Attempting to complete all plotting, measuring, and computations involved before diverting to the alternate may only aggravate an actual emergency. Once established on course, note the time, and then use the winds aloft nearest to your diversion point to calculate a heading and GS. Once the GS has been calculated, determine a new arrival time and fuel consumption. Give priority to flying the aircraft while dividing attention between navigation and planning. When determining an altitude to use while diverting, consider cloud heights, winds, terrain, and radio reception. Chapter Summary. This chapter has discussed the fundamentals of VFR navigation, beginning with an introduction to the charts that can be used for navigation, to the more technically advanced concept of GPS. There's one aspect of navigation that remains the same. The pilot is responsible for proper planning and the execution of that planning to ensure a safe flight. End of Part 7 of Chapter 15.
Part 1 of Chapter 16 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 16. Aeromedical Factors. Introduction. It is important for a pilot to be aware of the mental and physical standards required for the type of flying done. This chapter provides information on medical certification and on a variety of aeromedical factors related to flight activities. Obtaining a medical certificate. Most pilots must have a valid medical certificate to exercise the privileges of their airman certificates. Glider and free balloon pilots are not required to hold a medical certificate. Sports pilots may hold either a medical certificate or a valid state driver's license. Acquisition of a medical certificate requires an examination by an aviation medical examiner, AME, a physician with training in aviation medicine designated by the Civil Aerospace Medical Institute, CAMI. There are 3 classes of medical certificates. The class of certificate needed depends on the type of flying the pilot plans to do. The requirements for a third-class medical certificate for a private or recreational pilot certificate are currently under review. For the latest information and requirements regarding third-class medical certificates, reference the updated Regulation 14 CFR Part 61, Section 61.23, particularly the table in paragraph D. See errata for a hyperlink. A commercial pilot requires at least a second-class medical certificate, which is valid for 1 year. First-class medical certificates are required for airline transport pilots and are valid for 6 months. The standards are more rigorous with the higher classes of certificates. A pilot with a higher class medical certificate has met the requirements for the lower classes as well. Since the required medical class applies only when exercising the privileges of the pilot certificate for which it is required, a first-class medical certificate would be valid for 1 year if exercising the privileges of a commercial certificate and 2 or 3 years as appropriate for exercising the privileges of a private or recreational certificate. The same applies for a second-class medical certificate. The standards for medical certification are contained in Title 14 of the Code of Federal Regulations, 14 CFR, Part 67, and the requirements for obtaining medical certificates can be found in 14 CFR Part 61. Students who have physical limitations, such as impaired vision, loss of a limb, or hearing impairment, may be issued a medical certificate valid for student pilot privileges only while learning to fly. Pilots with disabilities may require special equipment installed in the aircraft, such as hand controls for pilots with paraplegia. Some disabilities necessitate a limitation on the individual certificate. For example, impaired hearing would require the limitation not valid for flight requiring the use of radio. When all the knowledge, experience, and proficiency requirements have been met, and a student can demonstrate the ability to operate the aircraft with the normal level of safety, a Statement of Demonstrated Ability, SODA, can be issued. This waiver, or SODA, is valid as long as the physical impairment does not worsen. Contact the local Flight Standards District Office, FSDO, for more information on this subject. Health and physiological factors affecting pilot performance. A number of health factors and physiological effects can be linked to flying. Some are minor, while others are important enough to require special attention to ensure safety of flight. In some cases, physiological factors can lead to in-flight emergencies. Some important medical factors that a pilot should be aware of include hypoxia, hyperventilation, middle ear and sinus problems, spatial disorientation, motion sickness, carbon monoxide, CO, poisoning, stress and fatigue, dehydration, and heat stroke. Other subjects include the effects of alcohol and drugs, anxiety, and excess nitrogen in the blood after scuba diving. Hypoxia. Hypoxia means reduced oxygen, or not enough oxygen. Although any tissue will die if deprived of oxygen long enough, usually the most concern is with getting enough oxygen to the brain, since it is particularly vulnerable to oxygen deprivation. Any reduction in mental function while flying can result in life-threatening errors. Hypoxia can be caused by several factors, including an insufficient supply of oxygen, inadequate transportation of oxygen, or the inability of the body tissues to use oxygen. The forms of hypoxia are based on their cause: hypoxic hypoxia, hypemic hypoxia, stagnant hypoxia, and histotoxic hypoxia. Hypoxic hypoxia. Hypoxic hypoxia is a result of insufficient oxygen available to the body as a whole. A blocked airway and drowning are obvious examples of how the lungs can be deprived of oxygen, but the reduction in partial pressure of oxygen at high altitude is an appropriate example for pilots. Although the percentage of oxygen in the atmosphere is constant, its partial pressure decreases proportionately as atmospheric pressure decreases. As the airplane ascends during flight, the percentage of each gas in the atmosphere remains the same, but there are fewer molecules available at the pressure required for them to pass between the membranes in the respiratory system. This decrease in the number of oxygen molecules at sufficient pressure can lead to hypoxic hypoxia. Hypemic hypoxia. Hypemic hypoxia occurs when the blood is not able to take up and transport a sufficient amount of oxygen to the cells in the body. Hypemic means not enough blood. This type of hypoxia is a result of oxygen deficiency in the blood rather than a lack of inhaled oxygen and can be caused by a variety of factors. It may be due to reduced blood volume due to severe bleeding, or it may result from certain blood diseases such as anemia. More often, hypemic hypoxia occurs because hemoglobin, the actual blood molecule that transports oxygen, is chemically unable to bind oxygen molecules. The most common form of hypemic hypoxia is CO poisoning. This is explained in greater detail on page 16-11. Hypemic hypoxia can also be caused by the loss of blood due to blood donation. Blood can require several weeks to return to normal following a donation. Although the effects of the blood loss are slight at ground level, there are risks when flying during this time. Stagnant hypoxia. Stagnant means not flowing. And stagnant hypoxia, or ischemia, results when the oxygen-rich blood in the lungs is not moving, for one reason or another, to the tissues that need it. An arm or leg going to sleep because the blood flow has accidentally been shut off is one form of stagnant hypoxia. This kind of hypoxia can also result from shock, the heart failing to pump blood effectively, or a constricted artery. During flight, stagnant hypoxia can occur with excessive acceleration of gravity, Gs. Cold temperatures can also reduce circulation and decrease the blood supplied to extremities. Histotoxic hypoxia. The inability of the cells to effectively use oxygen is defined as histotoxic hypoxia. Histo refers to tissues or cells, and toxic means poisonous. In this case, enough oxygen is being transported to the cells that need it, but they are unable to make use of it. This impairment of cellular respiration can be caused by alcohol and other drugs, such as narcotics and poisons. Research has shown that drinking 1 ounce of alcohol can equate to about an additional 2,000 feet of physiological altitude. Symptoms of hypoxia. High-altitude flying can place a pilot in danger of becoming hypoxic. Oxygen starvation causes the brain and other vital organs to become impaired. One noteworthy attribute of the onset of hypoxia is that the first symptoms are euphoria and a carefree feeling. With increased oxygen starvation, the extremities become less responsive and flying becomes less coordinated. The symptoms of hypoxia vary with the individual, but common symptoms include cyanosis, blue fingernails and lips, headache, decreased response to stimuli and increased reaction time, impaired judgment, euphoria, visual impairment, drowsiness, lightheaded or dizzy sensation, tingling in fingers and toes, numbness. As hypoxia worsens, the field of vision begins to narrow and instrument interpretation can become difficult. Even with all these symptoms, the effects of hypoxia can cause a pilot to have a false sense of security and be deceived into believing everything is normal. The treatment for hypoxia includes flying at lower altitudes and/or using supplemental oxygen. All pilots are susceptible to the effects of oxygen starvation, regardless of physical endurance or acclimatization. When flying at high altitudes, it is paramount that oxygen be used to avoid the effects of hypoxia. The term time of useful consciousness describes the maximum time the pilot has to make rational, life-saving decisions and carry them out at a given altitude without supplemental oxygen. As altitude increases above 10,000 feet, the symptoms of hypoxia increase in severity, and the time of useful consciousness rapidly decreases. See Figure 16-1, Time of Useful Consciousness. Altitude, 45,000 feet MSL. Time of Useful Consciousness, 9 to 15 seconds. 40,000 feet MSL. Time of Useful Consciousness, 15 to 20 seconds. 35,000 feet MSL. Time of Useful Consciousness, 30 to 60 seconds. 30,000 feet MSL. Time of Useful Consciousness, 1 to 2 minutes. 28,000 feet MSL. Time of Useful Consciousness, 2½ to 3 minutes. 25,000 feet MSL. Time of Useful Consciousness, 3 to 5 minutes. 22,000 feet MSL. Time of Useful Consciousness, 5 to 10 minutes. 20,000 feet MSL. Time of Useful Consciousness, 30 minutes or more. Since symptoms of hypoxia can be different for each individual, the ability to recognize hypoxia can be greatly improved by experiencing and witnessing the effects of it during an altitude chamber flight. The Federal Aviation Administration, FAA, provides this opportunity through aviation physiology training, which is conducted at the FAA-CMI and at many military facilities across the United States. For information about the FAA's one-day physiological training course with altitude chamber and vertigo demonstrations, visit the FAA website, www.faa.gov/pilots/airman_aerospace_physiology/index.cfm. Hyperventilation. Hyperventilation is the excessive rate and depth of respiration leading to abnormal loss of carbon dioxide from the blood. This condition occurs more often among pilots than is generally recognized. It seldom incapacitates completely, but it causes disturbing symptoms that can alarm the uninformed pilot. In such cases, increased breathing rate and anxiety further aggravate the problem. Hyperventilation can lead to unconsciousness due to the respiratory system's overriding mechanism to regain control of breathing. Pilots encountering an unexpected stressful situation may subconsciously increase their breathing rate. If flying at higher altitudes, either with or without oxygen, a pilot may have a tendency to breathe more rapidly than normal, which often leads to hyperventilation. Since many of the symptoms of hyperventilation are similar to those of hypoxia, it is important to correctly diagnose and treat the proper condition. If using supplemental oxygen, check the equipment and flow rate to ensure the symptoms are not hypoxia-related. Common symptoms of hyperventilation include visual impairment, unconsciousness, lightheaded or dizzy sensations, tingling sensations, hot and cold sensations, muscle spasms. The treatment for hyperventilation involves restoring the proper carbon dioxide level in the body. Breathing normally is both the best prevention and the best cure for hyperventilation. In addition to slowing the breathing rate, breathing into a paper bag or talking aloud helps to overcome hyperventilation. Recovery is usually rapid once the breathing rate is returned to normal. Middle ear and sinus problems. During climbs and descents, the free gas formerly present in various body cavities expands due to a difference between the pressure of the air outside the body and that of the air inside the body. If the escape of the expanded gas is impeded, pressure builds up within the cavity and pain is experienced. Trapped gas expansion accounts for ear pain and sinus pain, as well as a temporary reduction in the ability to hear. The middle ear is a small cavity located in the bone of the skull. It is closed off from the external ear canal by the eardrum. Normally, pressure differences between the middle ear and the outside world are equalized by a tube leading from the inside each ear to the back of the throat on each side, called the eustachian tube. These tubes are usually closed, but open during chewing, yawning, or swallowing to equalize pressure. Even a slight difference between external pressure and middle ear pressure can cause discomfort. See Figure 16-2. During a climb, middle ear air pressure may exceed the pressure of the air in the external ear canal, causing the eardrum to bulge outward. Pilots become aware of this pressure change when they experience alternate sensations of fullness and clearing. During descent, the reverse happens. When the pressure of the air in the external ear canal increases, the middle ear cavity, which equalized with the lower pressure at altitude, is at lower pressure than the external ear canal. And this results in a higher outside pressure, causing the eardrum to bulge inward. This condition can be more difficult to relieve due to the fact that the partial vacuum tends to constrict the walls of the eustachian tube. To remedy this often painful condition, which also causes a temporary reduction in hearing sensitivity, pinch the nostrils shut, close the mouth and lips,
and blow slowly and gently in the mouth and nose.
This procedure forces air through the eustachian tube into the middle ear. It may not be possible to equalize the pressure in the ears if a pilot has a cold, an ear infection, or a sore throat. A flight in this condition can be extremely painful, as well as damaging to the eardrums. If experiencing minor congestion, nose drops or nasal sprays may reduce the risk of a painful ear blockage. Before using any medication, check with an AME to ensure that it will not affect the ability to fly. In a similar way, air pressure in the sinuses equalizes with the pressure in the flight deck through small openings that connect the sinuses to the nasal passages. An upper respiratory infection, such as a cold or sinusitis, or a nasal allergic condition can produce enough congestion around an opening to slow equalization. As the difference in pressure between the sinuses and the flight deck increases, congestion may plug the opening. This sinus block occurs most frequently during descent. Slow descent rates can reduce the associated pain. A sinus block can occur in the frontal sinuses, located above each eyebrow, or in the maxillary sinuses, located in each upper cheek. It will usually produce excruciating pain over the sinus area. A maxillary sinus block can also make the upper teeth ache. Bloody mucus may discharge from the nasal passages. Sinus block can be avoided by not flying with an upper respiratory infection or nasal allergic condition. Adequate protection is usually not provided by decongestant sprays or drops to reduce congestion around the sinus openings. Oral decongestants have side effects that can impair pilot performance. If a sinus block does not clear shortly after landing, a physician should be consulted. End of Part 1 of Chapter 16. Recording by April Walters.
Part 2 of Chapter 16 of the Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Nathan Heck. The Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 16. Spatial Disorientations and Illusions. Spatial disorientation specifically refers to the lack of orientation with regard to the position, altitude, or movement of the airplane in space. The body uses three integrated systems working together to ascertain orientation and movement in space. The vestibular system, organs found in the inner ear that sense position by the way we are balanced. The somatosensory system, nerves in the skin, muscles, and joints, which, along with hearing, sense position based on gravity, feeling, and sound. The visual system, eyes, which sense position based on what is seen. All this information comes together in the brain and, most of the time, the three streams of information agree, giving a clear idea of where and how the body is moving. Flying can sometimes cause these systems to supply conflicting information to the brain, which can lead to disorientation. During flight, in visual meteorological conditions, VMC, the eyes are the major orientation source and usually prevail over false sensations from other sensory systems. When these visual cues are removed, as they are in instrument meteorological conditions, IMC, false sensations can cause a pilot to quickly become disoriented. The vestibular system in the inner ear allows the pilot to sense movement and determine orientation in the surrounding environment. In both the left and right inner ear, 3 semicircular canals are positioned at approximate right angles to one another. See Figure 16.3. Each canal is filled with fluid and has a section full of fine hairs. Acceleration of the inner ear in any direction causes the tiny hairs to deflect, which in turn stimulates nerve impulses, sending messages to the brain. The vestibular nerve transmits the impulses from the utricle, saccule, and semicircular canals to the brain to interpret motion. The somatosensory system sends signals from the skin, joints, and muscles to the brain that are interpreted in relation to the Earth's gravitational pull. These signals determine posture. Inputs from each movement update the body's position to the brain on a constant basis. Seat of the pants flying is largely dependent upon these signals. Used in conjunction with visual and vestibular clues, these senses can be fairly reliable. However, the body cannot distinguish between acceleration forces due to gravity and those resulting from maneuvering the aircraft, which can lead to sensory illusions and false impressions of an aircraft's orientation and movement. Under normal flight conditions, when there is a visual reference to the horizon and ground, the sensory system in the inner ear helps to identify the pitch, roll, and yaw movements of the aircraft. When visual contact with the horizon is lost, the vestibular system becomes unreliable. Without visual references outside the aircraft, there are many situations in which combinations of normal motions and forces create convincing illusions that are difficult to overcome. Prevention is usually the best remedy for spatial disorientation. Unless a pilot has many hours of training in instrument flight, flight should be avoided in reduced visibility or at night when the horizon is not visible. A pilot can reduce susceptibility to disorienting illusions through training and awareness and learning to rely totally on flight instruments. Vestibular illusions, the leans. A condition called the leans can result when a banked altitude to the left, for example, may be entered too slowly to set in motion the fluid in the roll semicircular tubes. See Figure 16.4. An abrupt correction of this altitude sets the fluid in motion, creating the illusion of a banked altitude to the right. The disoriented pilot may make the error of rolling the aircraft into the original left banked altitude, or, if level flight is maintained, will feel compelled to lean in the perceived vertical plane until this illusion subsides. Coriolis illusion. The Coriolis illusion occurs when a pilot has been in a turn long enough for the fluid in the ear canal to move at the same speed as the canal. A movement of the head in a different plane, such as looking at something in a different part of the flight deck, may set the fluid moving and create the illusion of turning or accelerating on an entirely different axis. This action causes the pilot to think the aircraft is doing a maneuver that it is not. The disoriented pilot may maneuver the aircraft into a dangerous altitude in an attempt to correct the aircraft's perceived altitude. For this reason, it is important that pilots develop an instrument cross-check or scan that involves minimal head movement. Take care when retrieving charts and other objects in the flight deck. If something is dropped, retrieve it with minimal head movement and be alert for the Coriolis illusion. Graveyard spiral. As in other illusions, a pilot in a prolonged, coordinated, constant rate turn will have the illusion of not turning. During the recovery to level flight, the pilot will experience the sensation of turning in the opposite direction. The disoriented pilot may return the aircraft to its original turn. Because an aircraft tends to lose altitude in turns unless the pilot compensates for the loss in lift, the pilot may notice a loss of altitude. The absence of any sensation of turning creates the illusion of being in a level descent. The pilot may pull back on the controls in an attempt to climb or stop the descent. This action tightens the spiral and increases the loss of altitude. This illusion is referred to as a graveyard spiral. See Figure 16.5. At some point, this could lead to a loss of aircraft control. Somatographic illusion. A rapid acceleration, such as experienced during takeoff, stimulates the otolith organs in the same way as tilting the head backwards. This action creates the somatographic illusion of being in a nose-up altitude, especially in situations without good visual references. The disoriented pilot may push the aircraft into a nose-low or dive attitude. A rapid deceleration by quick reduction of the throttle can have the opposite effect, with the disoriented pilot pulling the aircraft into a nose-up or stall attitude. Inversion illusion. An abrupt change from climb to straight and level flight can stimulate the otolith organs enough to create the illusion of tumbling backwards, or inversion illusion. The disoriented pilot may push the aircraft abruptly into a nose-low attitude, possibly intensifying this illusion. Elevator illusion. An abrupt upward vertical acceleration, as can occur in an updraft, can stimulate the otolith organs to create the illusion of being in a climb. This is called elevator illusion. The disoriented pilot may push the aircraft into a nose-low attitude. An abrupt downward vertical acceleration, usually in a downdraft, has the opposite effect, with the disoriented pilot pulling the aircraft into a nose-up attitude. Visual illusions. Visual illusions are especially hazardous because pilots rely on their eyes for correct information. Two illusions that lead to spatial disorientation, false horizon and autokinesis, are concerned with only the visual system. False horizon. A sloping cloud formation, an obscured horizon, an aurora borealis, a dark scene spread with ground lights and stars, and certain geometric patterns of ground lights can provide inaccurate visual information, or false horizon, for aligning the aircraft correctly with the actual horizon. The disoriented pilot may place the aircraft in a dangerous attitude. Autokinesis. In the dark, a stationary light will appear to move about when stared at for many seconds. The disoriented pilot could lose control of the aircraft in attempting to align it with the false movements of this light, called autokinesis. Postural considerations. The postural system sends signals from the skin, joints, and muscles to the brain that are interpreted in relation to Earth's gravitational pull. These signals determine posture. Inputs from each movement update the body's position to the brain on a constant basis. Seat of the pants flying is largely dependent upon these signals. Used in conjunction with visual and vestibular clues, these sensations can be fairly reliable. However, because of the forces acting upon the body in certain flight situations, many false sensations can occur due to acceleration forces overpowering gravity. See Figure 16.6. These situations include uncoordinated turns, climbing turns, and turbulence. Demonstration of spatial disorientation. There are a number of controlled aircraft maneuvers a pilot can perform to experiment with spatial disorientation. While each maneuver will normally create a specific illusion, any false sensation is an effective demonstration of disorientation. Thus, even if there is no sensation during any of these maneuvers, the absence of sensation is still an effective demonstration because it illustrates the inability to detect bank or roll. There are several objectives in demonstrating these various maneuvers. 1. They teach pilots to understand the susceptibility of the human system to spatial disorientation. 2. They demonstrate that judgments of aircraft attitude based on bodily sensations are frequently false. 3. They help decrease the occurrence and degree of disorientation through a better understanding of the relationships between aircraft motion, head movements, and resulting disorientation. 4. They help instill a greater confidence in relying on flight instruments for assessing true aircraft attitude. A pilot should not attempt any of these maneuvers at low altitudes, or in the absence of an instructor pilot or an appropriate safety pilot. Climbing while accelerating. With the pilot's eyes closed, the instructor pilot maintains approach airspeed and a straight and level attitude for several seconds, then accelerates while maintaining straight and level attitude. The usual illusion during this maneuver without visual references is that the aircraft is climbing. Climbing while turning. With the pilot's eyes still closed and the aircraft in a straight and level attitude, the instructor pilot now executes, with a relatively slow entry, a well-coordinated turn of about 1.5 positive G, approximately 50% bank, for 90%. While in the turn, without outside visual references and under the effect of the slight positive G, the usual illusion produced is that of a climb. Upon sensing the climb, the pilot should immediately open the eyes to see that a slowly established coordinated turn produces the same sensation as a climb. Diving while turning. Repeating the previous procedure, except the pilot's eyes should be kept closed until recovery from the turn is approximately one-half completed, can create the illusion of diving while turning. Tilting to right or left. While in a straight and level attitude, with the pilot's eyes closed, the instructor pilot executes a moderate or slight skid to the left with wings level. This creates the illusion of the body being tilted to the right. Reversal of motion. This illusion can be demonstrated in any of the three planes of motion. While straight and level, with the pilot's eyes closed, the instructor pilot smoothly and positively rolls the aircraft to approximately 45-degree bank altitude while maintaining heading and pitch attitude. This creates the illusion of a strong sense of rotation in the opposite direction. After this illusion is noted, the pilot should open his or her eyes and observe that the aircraft is in a banked attitude. Diving or rolling beyond the vertical plane. This maneuver may produce extreme disorientation. While in straight and level flight, the pilot should sit normally, either with eyes closed or gaze lowered to the floor. The instructor starts a positive coordinated roll toward a 30 or 40-degree angle of bank. As this is in progress, the pilot tilts his or her head forward, looks to the right or left, then immediately returns his or her head to an upright position. The instructor pilot should time the maneuver so the roll is stopped as the pilot returns his or her head upright. An intense disorientation is usually produced by this maneuver, and the pilot experiences the sensation of falling downward into the direction of the roll. In the descriptions of these maneuvers, the instructor pilot is doing the flying, but having the pilot do the flying can also be a very effective demonstration. The pilot should close his or her eyes and tilt the head to one side. The instructor pilot tells the pilot what control inputs to perform. The pilot then attempts to establish the correct attitude or control input with eyes closed and head tilted. While it is clear that the pilot has no idea of the actual attitude, he or she will react to what the senses are saying. After a short time, the pilot will become disoriented, and the instructor pilot then tells the pilot to look up and recover. The benefit of this exercise is that the pilot experiences the disorientation while flying the aircraft. Coping with spatial disorientation. To prevent illusions and their potentially disastrous consequences, pilots can 1. Understand the causes of these illusions and remain constantly alert for them. Take the opportunity to experience spatial disorientation illusions in a device such as a Barony chair, a Vertigon, or a virtual reality spatial disorientation demonstrator. 2. Always obtain and understand pre-flight weather briefings. 3. Before flying in marginal visibility, less than 3 miles, or where a visible horizon is not evident, such as flight over open water during the night, obtain training and maintain proficiency in airplane control by reference to instruments. 4. Do not continue flight into adverse weather conditions or into dusk or darkness unless proficient in the use of flight instruments. If intending to fly at night, maintain night flight currency and proficiency. Include cross-country and local operations at various airfields. 5. Ensure that when outside visual references are used, they are reliable fixed points on the Earth's surface. 6. Avoid sudden head movement, particularly during takeoffs, turns, and approaches to landing. 7. Be physically tuned for flight into reduced visibility. That is, ensure proper rest, adequate diet, and, if flying at night, allow for night adaptation. Remember that illness, medication, alcohol, fatigue, sleep loss, and mild hypoxia are likely to increase susceptibility to spatial disorientation. 8. Most importantly, become proficient in the use of flight instruments and rely upon them. Trust the instruments and disregard your sensory perceptions. The sensations that lead to illusions during instrument flight conditions are normal perceptions experienced by pilots. These undesirable sensations cannot be completely prevented, but through training and awareness, pilots can ignore or suppress them by developing absolute reliance on the flight instruments. As pilots gain proficiency in instrument flying, they become less susceptible to these illusions and their effects. Optical illusions. Of the senses, vision is the most important for safe flight. However, various terrain features and atmospheric conditions can create optical illusions. These illusions are primarily associated with landing. Since pilots must transition from reliance on instruments to visual cues outside the flight deck for landing at the end of an instrument approach, it is imperative that they be aware of the potential problems associated with these illusions and take appropriate corrective action. The major illusions leading to landing errors are described below. Runway width illusion. A narrower than usual runway can create an illusion the aircraft is at a higher altitude than it actually is, especially when runway length to width relationships are comparable. See Figure 16.7. The pilot who does not recognize this illusion will fly a lower approach, with the risk of striking objects along the approach path or landing short. A wider than usual runway can have the opposite effect, with the risk of the pilot leveling out on the aircraft high and landing hard, or overshooting the runway. Runway and terrain slopes illusion. An upsloping runway, upsloping terrain, or both, can create an illusion that the aircraft is at a higher altitude than it actually is. See Figure 16.7. The pilot who does not recognize this illusion will fly a lower approach. Downsloping runways and downsloping approach terrain can have the opposite effect. Featureless terrain illusion. An absence of surrounding ground features, as in an overwater approach over darkened areas or terrain made featureless by snow, can create an illusion that the aircraft is at a higher altitude than it actually is. This illusion, sometimes referred to as the black hole approach, causes pilots to fly at a lower approach than is desired. Water refraction. Rain on the windscreen can create an illusion of being at a higher altitude due to the horizon appearing lower than it is. This can result in the pilot flying a lower approach. Haze. Atmospheric haze can create an illusion of being at a greater distance and height from the runway. As a result, the pilot will have a tendency to be low on the approach. Conversely, extremely clear air, clear bright conditions of a high-altitude airport, can give the pilot the illusion of being closer than he or she actually is, resulting in a high approach, which may result in an overshoot or go-around. The diffusion of light due to water particles on the windshield can adversely affect depth perception. The lights and terrain features normally used to gauge height during landing become less effective for the pilot. Fog. Flying into fog can create an illusion of pitching up. Pilots who do not recognize this illusion will often steepen the approach quite abruptly. Ground lighting illusions. Lights along a straight path, such as a road or lights along moving trains, can be mistaken for runway and approach lights. Bright runway and approach lighting systems, especially where few lights illuminate the surrounding terrain, may create the illusion of less distance to the runway. The pilot who does not recognize this illusion will often fly a higher approach. How to prevent landing errors due to optical illusions. To prevent these illusions and their potentially disastrous consequences, pilots can 1. Anticipate the possibility of visual illusions during approaches to unfamiliar airports, particularly at night or in adverse weather conditions. Consult airport diagrams and the Airport Facility Directory, AFD, for information on runway slope, terrain, and lighting. 2. Make frequent reference to the altimeter, especially during all approaches, day and night. 3. If possible, conduct aerial visual inspection of unfamiliar airports before landing. 4. Use Visual Approach Slope Indicator, VASI, or Precision Approach Path Indicator, PAPI systems for a visual reference, or an electronic glide slope whenever they are available. 5. Utilize the Visual Descent Point, VDP, found on many non-precision instrument approach procedure charts. 6. Recognize that the chances of being involved in an approach accident increase when some emergency or other activity distracts from usual procedures. 7. Maintain optimum proficiency and landing procedures. In addition to the sensory illusions due to misleading inputs to the vestibular system, a pilot may also encounter various visual illusions during flight. Illusions rank among the most common factors cited as contributing to fatal aviation accidents. Sloping cloud formations, an obscured horizon, a dark scene spread with ground lights and stars, and certain geometric patterns of ground light can create illusions of not being aligned correctly with the actual horizon. Various surface features and atmospheric conditions encountered in landing can create illusions of being on the wrong approach path. Landing errors due to these illusions can be prevented by anticipating them during approaches, inspecting unfamiliar airports before landing, using electronic glide slope or VASI systems when available, and maintaining proficiency in landing procedures. End of Part 2 of Chapter 16. Recording by Nathan Heck.